Hello and welcome to Pre-Algebra Lesson 1. In this video, we're going to learn about place value. So the lesson objectives for today, we want to learn basic definitions of terms relating to place value. We want to gain a basic understanding of how our number system works. And additionally, we want to learn how to construct and use a place value chart. All right, let's start out by talking about the whole numbers. So the whole numbers start with 0. So that's your smallest whole number, and then increase in increments of 1 indefinitely. So I've written here the whole numbers, and look how we've listed 0, the smallest whole number, first or in the leftmost position. And then you're going to put a comma. You're going to add 1 to 0 to get to 1. So you put your next largest whole number there, and then you can just keep adding 1. So then you would go to 2, then 3, then 4, then 5. There's not a largest whole number. You can keep just adding 1 to get to the next largest whole number. So what you'd want to do at some point is stop and put your final comma, and then these 3 dots here. And that's just going to tell you that the pattern continues forever. So after 5 comes 6, then 7, then 8, then 9, and so on and so forth. All right, so now let's talk about what we call the digits. These are the first 10 whole numbers, and they are used to build numbers. So I have here the whole numbers, 0 through 9, so the first 10 whole numbers are referred to as digits. So I've listed them out here, so 0 through 9. The whole key is that as we change a digit's position in a number, its value is going to change. So I have here that our number system relies on the digits. So again, that's the first 10 whole numbers, and a place value to build each number. So it doesn't matter how large of a number you have or how small of a number you have, you're only going to use the digits to build that number. The key, again, is just as you change the position or the placement of a digit in a number, its value is going to change. That's why we call our number system a place value system. So to show this, let's take a look at 4 numbers, each containing the digit 9. All right, so what we're going to do is look at the 4 numbers we have here. So 49, 192, 3,945, and then 9,687. There are some things that we're going to do here that we haven't talked about yet. So just take everything as a given, and then I'm going to fully explain as we move forward. So the first thing is I'm going to write each number in what we call expanded notation, and that is going to be covered in the next lesson. It's just a way that we can write a number such that the value of each digit is fully shown. So for example, something like 49, I could write that as 40 plus 9. Or something like 192, I would say that's 100 plus 90 plus 2. Then something like 3,945, that's going to be 3,000 plus 900 plus 40 plus 5. And then 9,687, that's going to be 9,000 plus 600 plus 80 plus 7. So we'll learn how to do this in the next lesson. But right now, let's just take it as a given and use it to understand what's going on. We have a 9 in each number, so that digit 9. So here, 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 and here. Now look at it in the expanded form of each number. So it's going to be here, 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 and then here. Notice that in the first number, 49, it's just a 9. And that's coming from the fact that the 9 is in the ones place there, so its value comes from 9 times 1, which is 9. Then in the next number, you have 192. Well, this 9 is in what we call the tens place, so it's 9 times 10, or 90. Then when we get to 3,945, the 9 is in the hundreds place, so it's 9 times 100, or 900. Then finally, when we get to 9,687, the 9 is in the thousands place, so it's 9 times 1,000, or 9,000. The main thing here is to understand that as we change the position of that 9, that digit in a number, it's getting a different value. So it's getting its value based on where it is in the number, its position, or its placement. Now, as a final example, let's just think about, instead of 49, let's write 94. And let's think about the 9 here. Let me write this out and say that this is 90 plus 4. Well, now this 9 is a 90. It's in the tens place, it's 9 times 10, or 90. Here, the 9 is just a 9. 9 times 1, which is 9. But notice that these numbers are built with the same 2 digits, a 4 and a 9. But this one is 49, which is 40 plus 9, and this is 94, which is 90 plus 4. We know that $94 would be more than $49, so obviously these two numbers are not the same, even though they contain the same 2 digits only. So the position of a digit in a number is going to determine its value. Okay, let's look at what we call a place value chart. So this is a good way to understand how to find the place value for a given digit in a number. So to start off, I'm just going to pick a number a smaller number, let's say something like 1052. And you're just going to feed this into the place value chart. So provided you're working with a whole number, you can just make your own example. If you're working with a decimal, then you're going to need an expanded place value chart. We'll cover that later on in the course. For right now, the rightmost digit of your whole number, in this case it's a 2, and that's going to be in what we call the ones place. I'll talk more about this in a moment, but basically for right now, let's just feed this in to the rightmost position on that place value chart. So that 2 is going to go right there, again, where it says ones. Okay, let me get rid of this highlighting so nobody's lost. As I move to the left in my number, I'm going to match that movement to the left on my place value chart. So this 5 is now going to go here where it says tens. I go to the left. This 0 is now going to go in this position that says hundreds. I'm just going to the left. Then I'm going to go to the left one more time. This 1 is going to go into the thousands. So what does it mean to have ones, tens, hundreds, thousands, all these things? Where does that come from and what does it mean? Well, the first thing is this is all based on 10. Once you understand that, it becomes very easy to come up with these names. So I'm just going to start. You see that this says ones here. I'm just going to write a 1. Then as I move to the left, let me just write a 10, let me write 100, and let me write 1000, and I'm just going to stop there, and I'm going to show you the pattern. So basically what's happening is, as I move to the left, I'm just multiplying by 10. So 1 times 10 gives me 10. Then as I move to the left, I'm multiplying by 10. 10 times 10 gives me 100. As I move to the left, I'm just multiplying by 10. So 100 times 10 gives me 1000. This would continue forever and ever and ever as you move to the left. Now, it's also true as you move to the right, you're dividing by 10. We can show that real quick too. So if I took 1000 and I divide by 10, I get 100. If I take 100 and I divide by 10, I get 10. If I take 10 and I divide by 10, I'm going to get 1. So we see the pattern. As we move to the left, we multiply by 10. As we go to the right, we divide by 10. So we can use that to come up with these names. Just remember that the rightmost position here is the ones place. You can just think about that as a 1. That's all you have to remember. Then as you move to the left, well, hey, I multiply by 10, so I have a 10. Well, now I say tens. Move to the left, multiply by 10, I get 100, so we say hundreds, and this just continues. So then you'd have thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, 100 billions, trillions. You just keep multiplying by 10. So you'd have 10 trillions, 100 trillions, so on and so forth. Now you can't possibly list everything, so at some point you just stop. Okay, so I've stopped here, but you can stop wherever you want. So now that we understand where these names are coming from and how this pattern works, let's think a little bit about this expanded notation that I showed you earlier. Essentially, we'll get to this in the next lesson in more detail, but for right now, just think about the digit multiplied by its corresponding place value. So you have a 1 in the thousands place. So basically that's 1 times 1,000 or just 1,000. So I'm just going to write that. Then I'm going to put plus. You have a 0 in the hundreds place. Now the 0 there is really a placeholder. It's telling me I don't have any hundreds in this particular number, but I need that 0 there to keep these other numbers in their correct positions. Otherwise, the number would collapse down and you'd have 152. Well, I don't have 152, I have 1052, so I need that 0 there as a placeholder. With expanded notation, if you have a 0 somewhere, you could just skip it over. Then I have 5 tens. So that's 5 times 10, which is 50. And then plus I have 2 ones, so that's 2 times 1, which is 2. So this is the basic idea behind expanded notation that we saw in the last part of the lesson. All right, so let's just get a little practice writing a number inside of a place value chart. It's a very easy exercise. So 673,452. Let me grab this, come down here and paste this in. I would advise you to get a piece of paper and a pencil and try this on your own. Just make a place value chart. You don't have to go out to the trillions. This number is only going to go to the 100,000s, so you can just cut your paper off there. So I'm just going to take the rightmost digit of this whole number here, this 2, put that in the ones place. That's the rightmost position in this place value chart. So I'd put a 2 here. Again, as I work my way to the left in the number, I'm working my way to the left on the place value chart. So I'm just matching my movement. So this 5 would go into the tens, this 4 would go into the hundreds, this 3 would go into the thousands, this 7 would go into the 10,000s, and this 6 would go into the 100,000s. Okay, let's look at a bigger one. So now we have 7,853,922,673. So 7,853,922,673. You can grab this real quick. Come down here and paste this in. All right, so I'm going to take my 3, which is the rightmost position of this whole number, and I'm going to put it in the rightmost position on this place value chart. So again, that's going into the ones place. So I'm going to put a 3 there, and I'm going to work my way to the left in the number, and I'm going to match that movement on my place value chart. So I'm going to the left and getting that 7. That's going to be in the tens place. Go to the left, I have a 6 that's in the hundreds place. Go to the left, I have this 2 here, which would be in the thousands place. And then go to the left, I have this 2, which is going to be in the 10,000s place. And then go to the left, I have a 9 that's in the 100,000s place. Now, as I go to the left, I have a 3 that's in the millions place. Go to the left, I have a 5 in the 10 millions place. Go to the left, I have an 8 in the 100 millions place. And then lastly, I go to the left and have a 7 in the billions place. All right, let's look at some standard questions now. So a typical place value test consists of questions that ask for the place value of a specified digit. So we're going to try a few examples. We want to find the place value for each underlined digit. So I went ahead and underlined them, and also I wrote them in a different color. And I'm going to come down here and paste this in. We'll do some with the place value chart, and then we'll do some without it. It's a really easy thing. Once you do a few examples, you sort of start to memorize the pattern, and then it's really, really easy to figure this out. So once again, I'm going to start with the rightmost digit of this whole number. I'm going to put it in the rightmost position in this place value chart. So the 1 would go here in the ones place. The 8 here, I'm going to the left, so I'm mashing that movement on my place value chart. The 8 here would go in the tens place. The 5 here would go in the hundredths place. The 3 here would go in the thousands place. The 7 would go in the 10,000s place. And then lastly, the 6 would go in the 100,000s place. So to answer our question, let me put a little border here. We would say for the 3, that's going to be where? That's going to be in the thousands place. So this is in the thousands. And you could put place if you want. I'm just going to put thousands. And then the 8 here, well, that's going to be in the tens place. So let's put the 8 is going to be in the tens place. All right, let's take a look at another example. So here we have 6,358,791. So let me just paste this in here. I'm going to start with the rightmost digit of the number. I'm going to put that into the rightmost position in our place value chart. So this 1 would go in the ones place, and then I'm going to work my way to the left in the number and then match that in my place value chart. So I'm going to have a 9 that's going to be in the tens place, a 7 in the hundreds place, an 8 in the thousands place, a 5 in the 10,000s place, a 3 in the 100,000s place, and then lastly a 6 in the millions place. Now we want to find the place value for the underlined digits. Let me put a little border here. So we have this 3, and that's going to be in the 100,000s place. So let's just write 100,000s here. And again, you can put place if you want. That's up to you. And then for the other one, it's going to be the 7, which is going to be right here. So that's going to be in the hundreds place. So let's put that the 7 is in the hundreds place. All right, let's look at one that's really big. So we have 9,551,072,636,010. So let me paste that in, and we're going to be looking for the place value of this guy, this 9, this 7, and this 3. So again, I'm just going to feed this into the place value chart. So the 0, the rightmost digit of that number, it's going to go into the rightmost position of the place value chart. So that 0 is in the ones place. Just going to work my way to the left here and match that in my place value chart. So I'd have a 1 in the tens place, a 0 in the hundreds place, a 6 in the thousands place, a 3 in the 10,000s place. Let me go ahead and highlight that since we have so much going on here. And then we're going to have a 6 in the 100,000s place, a 2 in the millions place, a 7 in the 10 millions place. So again, that's one of the ones that's underlined. So let me highlight that real quick. And then as we work our way to the left, we have a 0 in the 100 millions place, a 1 in the billions place, a 5 in the 10 billions place, and then also a 5 in the 100 billions place. And then lastly, we have a 9 in the trillions place. So let me highlight that and that, again, because it's underlined. Okay, so really not that bad. Let me put a little border here, and I'll slide down just a little bit. And let me put this around the number. Hopefully I can fit everything on the right of this border, but maybe I can't. We'll see. So for the 9, that is going to be in the trillions place. So I'm just going to write trillions. Again, if you want to write place, that is up to you. Then for the 7, that is going to be in the 10 millions place. So 10 millions. Again, you can put place there. And then for the 3, we are going to say that's in the 10,000s place. So let's put 10 thousands. And again, you could put place. All right, let's try a few without the place value chart. So I'm going to start with 7,036. So remember, the rightmost position of your whole number, that's in the ones place. You could just write ones like this. And if you're lost, again, as you move to the left, you're just multiplying by 10. So 1 times 10 is 10. So this next position to the left that's in the tens place. And we can keep going even though we have our answer. Multiply 10 by 10, that's 100. So this position right here, this is in the hundreds place. And then I probably can't fit this here. Maybe I can just arrow down here like that. So going to the left one more time, 100 times 10 is 1,000. So this would be in the thousands place. So the answer we want is actually the tens place. Let me put the 3 over here. That's what's underlined. And we'll say this is in the tens place. All right, the next example, we have 64,114. I think we probably don't need to write things out at this point. So the rightmost digit of that whole number, again, that's in the ones place. As you move to the left, just multiply by 10. So you'd have the tens, the hundreds, the thousands. So that's what we're looking for. That digit 4 that's underlined here is going to be in the thousands. So the thousands place. Again, not this 4. This 4 right here would be in the ones place. We're talking about this 4 specifically that's underlined. That's going to be in the thousands place. All right, let's just look at one more. So a pretty big number. This is 1,998,004,557. So the guy that's underlined here is the 9. Now, one thing that you could do is by reading the number, you immediately say, okay, well, this is 1 billion. Well, what comes to the right of 1 billion? Again, you could just divide by 10. That's going to be 100 million. So immediately you know that 9 that's underlined is in the 100 millions place. But again, you could start here and say, okay, well, this is the ones. And every time I go to the left, that's going to be times 10. So tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, again, 100 millions. So however you figure that out, this digit here, this 9, is going to be in the 100. So the 100 millions place. And again, there's 2 9s here. So specifically, I'm talking about this one right here that's underlined. If you look at the one to the right of it, that would be in the 10 millions place, but we're not talking about that one because it's not underlined. So this one specifically, this 9, is in the 100 millions place. Hello and welcome to Pre-Algebra Lesson 2. And in this video, we're going to be learning about expanded notation. So our lesson objectives for today would be to learn how to write a number in expanded notation. And we also want to learn the difference between standard and expanded notation. So in our first lesson, we learned all about place value. I taught you how to use this place value chart to find the place value for all the digits in a given number. Now, when we think about expanded notation, all we're simply doing is we're writing a number in a way that it emphasizes the place value for each digit in that number. So this is kind of just a continuation of the last lesson. And in fact, in the first lesson, I gave you a couple of examples where we wrote a number in expanded notation. Now, let's say I took a number like 1,035. And we want to write this in expanded notation. Well, the first thing is we need the place value for each digit in the number. So let's feed this into the place value chart. So we start with the rightmost digit, and we put it in the rightmost column of the place value chart. So the 5 goes into the ones place. And as we move left on the place value chart. So the 3 goes in the tens place, the 0 goes in the hundreds place, and the 1 goes in the thousands place. So now that we know the place value for each digit in the number, we can write the number in expanded notation. All we need to do is form the sum of each digit multiplied by its corresponding place value. So starting with this 1 on the left, it's in the thousands place. So each digit, that 1, multiplied by its corresponding place value. If it's in the thousands place, we multiply it by 1,000. Then plus. Next, we have a 0 in the hundreds place. Now that 0, as I've previously explained to you, is just a placeholder. But to illustrate expanded notation, I'm going to go ahead and include it for now, although you don't have to. So the 0 here is multiplied by 100. Then plus, we have a 3 in the tens place. So that digit 3 is multiplied by 10. And lastly, we have a 5 in the ones place. So we'll have plus 5, that's the digit, times 1, the place value. Okay, let's do a little multiplication now. So 1 times 1,000 is 1,000. Plus 0 times 100 is 0. Plus 3 times 10 is 30. And then plus 5 times 1, that's 5. So let's just write this as 1,000 plus 30 plus 5, right? We don't need to include that 0. So essentially, when we write a number in expanded notation, you can see that it's emphasizing the place value of each digit. This 1 has a value of 1,000. This 3 has a value of 30. This 5 is still a 5. The reason this is still a 5 is because it's in the ones place. 5 times 1 is just 5. The reason this is a 30 is because it's in the tens place. 3 times 10 is 30. And the reason this 1 is 1,000 is because it's in the thousands place. 1 times 1,000 is 1,000. So it's a pretty simple concept overall. And remember, when we talk about this 0 here, it's a placeholder, right? It's a placeholder. We don't have any hundreds in this case, right? We don't have any hundreds in this case. But our number system will allow us to write 1,035 with this 0 saying, hey, I don't have anything there, but hold that space. Otherwise, what would you have? This 1 would collapse down and you wouldn't be able to tell the difference between 135 and 1,035. So you get all kinds of problems. So let's take a look at another one. Let's say we want to write the number 22,359 in expanded notation. Well, let's get the place value first. So I'm just going to feed this into the place value chart. The 9 goes in the ones place. The 5 goes in the tens place. The 3 goes in the hundreds place. The 2 goes in the thousands place. And then this 2 here is going to go in the 10,000s place. So to write the number in expanded notation, again, we form the sum of each digit multiplied by its corresponding place value. So there's a 2 for the digit times its corresponding place value. It's in the 10,000s place. So just 2 times 10,000. Plus, now we have a 2 in the thousands place, so 2 times 1,000. Plus, now we have a 3 in the hundreds place, so 3 times 100. Plus, we have a 5 in the tens place, so 5 times 10. And then lastly, plus, we have a 9 in the ones place, so 9 times 1. Let's do some multiplication. 2 times 10,000 is 20,000. Plus 2 times 1,000 is 2,000. Plus 3 times 100 is 300. Plus 5 times 10 is 50. And then plus 9 times 1, that's 9. So again, by writing this number in expanded notation, we can see the true value of each digit in the number. This 2 has a value of 20,000. This 2, let me do it in a different color because they're both 2's and are side by side. This 2 has a value of 2,000, right? It's in the thousands place. This 3 has a value of 300. This 5 has a value of 50. And then this 9 has a value of just 9. So each digit gets its value, again, based on where it is in the number, and that's why we call it a place value system. Let's look at another one. Okay, let's say we had 759,275. So let's feed this into the place value chart. So the 5 goes in the ones place, the 7 goes in the tens place, the 2 goes in the hundreds place, the 9 goes in the thousands place, the 5 goes in the 10,000s place, and the 7 goes in the 100,000s place. So to write this in expanded notation, again, we form the sum of each digit multiplied by its corresponding place value. So this digit is a 7. Its place value is the 100,000s place, so 7 times 100,000. 7 times 100,000. Then plus. Next we have a 5 in the 10,000s place. So 5 times 10,000. Then plus, we have a 9 in the thousands place. So 9 times 1,000. And plus, we have a 2 in the hundreds place. So 2 times 100. And plus, we have a 7 in the tens place. So 7 times 10. Then lastly, we have plus 5 times 1. Right? We have a 5 in the ones place. 5 times 1. So we do a little multiplication. 7 times 100,000 is 700,000. Plus 5 times 10,000, that's 50,000. Plus 9 times 1,000, that's 9,000. Plus 2 times 100, that's 200. Plus 7 times 10, that's 70. And then lastly, plus 5 times 1, that's 5. So by taking this number from standard notation and putting it in expanded notation, we can see the true value of each digit in the number. The 7 is 700,000, right? Because it's in the 100,000s place. The 5 is 50,000 because it's in the 10,000s place. 5 groups of 10,000, 50,000. The 9 is 9,000, right? It's in the thousands place. The 2 is 200. It's in the hundreds place. The 7 is 70. It's in the tens place. And lastly, the 5 is still a 5 because it's in the ones place. Let's look at another one. All right, for the next one, let's write 36,255,927 in expanded notation. Now, some of you might be going, well, where's the place value chart? At some point, you have to be able to do this without a place value chart. You have to simply memorize the place values. So if that's something you can't do yet, pull out a place value chart, write this number into the place value chart so that you can get the place value for each digit in the number, and then continue with me. But otherwise, remember that there's a trick you can use. And in case you didn't watch the first video where we talked about place value, I'll explain it for you. So the rightmost place you should be able to remember is the ones place. As you move to the left, you're just multiplying by 10. So in other words, if you think about this as just 1. As I move left, I multiply by 10. This would be 10, right? It's the tens place. It's the tens place. Then as I move left, again, I multiply by 10. This just keeps going forever and ever and ever. You just keep multiplying by 10. So 10 times 10 is 100. So this is the hundreds place. Okay, then this would be the thousands. And let me make that apostrophe a little better. And then this would be the 10,000s. And this would be the 100,000s. This would be the millions. And this would be the 10 millions. And again, the way you figure this out is the rightmost column is always the ones place. So you just think about it as just a 1. As you move to the left, you multiply by 10. So 1 times 10 is 10. So this is the tens place. Now I have a 10. Multiply by 10 again, you get to 100. So now this is the hundreds place. Multiply by 10 again, you get to 1,000. That's the thousands. Then 10,000, then 100,000, then a million, then 10 million, so on and so forth. That continues forever and ever and ever. So you could have a number as large as you want, and provided you had enough time, you could sit there and write out the place values for each digit in that number. Now, let's take this number and write it in expanded notation. So it's kind of a big number, so it's going to take a little time. We have a 3 that's in the 10 millions place. So we would have 3 times 10 million. Then plus, we have a 6 in the millions place. So 6 times 1 million. And plus, we have a 2 in the 100,000s place. So 2 times 100,000. And plus, we have a 5 in the 10,000s place. So 5 times 10,000. And plus, we have another 5, and that's in the thousands place. So 5 times 1,000. And plus, we have a 9 in the hundreds place, so 9 times 100. And plus, we have a 2 in the tens place, so 2 times 10. And lastly, we have plus 7 times 1, right? We have a 7 in the ones place. So we do a little multiplication. 3 times 10 million is 30 million. 30 million. And again, that's telling me that the value of this 3 here is 30 million. Then plus, we have 6 times 1 million, which is 6 million. 6 million. So the value for this 6 is 6 million. Then plus, we have 2 times 100,000, or 200,000. The 2 is worth what? 200,000. Then next we have 5 times 10,000, so plus 50,000. 50,000. So this 5 is 50,000. Then plus, we have 5 times 1,000, which is 5,000, so 5,000. So this 5 is a 5,000. And then we have plus 9 times 100, or 900. So this 9 is worth 900. And then plus, we have a 2 in the tens place, so 2 times 10, or 20. So this 2 is a 20. And then lastly, we just have plus 7. right? 7 times 1 is 7. This is just a 7. So your number, 36,255,927, written in expanded notation, looks like this. 30 million plus 6 million plus 200,000 plus 50,000 plus 5,000 plus 900 plus 20 plus 7. So again, just breaking it down and showing you the true value of each digit in that number. Okay, for the last example, let's look at one that's really big. So we have 10 billion, 5,327,005. Now the good thing about this number is I included a lot of zeros. And when you have zeros and you write a number in expanded notation, you can skip them. So in other words, I'll have this 1 here. This is in the 10 billions place. Because essentially this is the ones, the tens, the hundreds. This is the thousands, the 10,000s, the 100,000s. This is the millions, the 10 millions, the 100 millions. Then this is the billions and the 10 billions. Okay? So this 1 is in the 10 billions place. So I'd have 1 times 10 billion. Then plus. Now all these zeros are basically just placeholders. So when we write the number in expanded notation, we don't have to put them. So I can kind of just skip down to the next non-zero number. So that's a 5, and that's going to be in the millions place. So 5 times 1 million. Then plus. Next I have a 3 in the 100,000s place. So 3 times 100,000. And plus, I have a 2 in the 10,000s place, so 2 times 10,000. Then plus, I have a 7 in the thousands place, so 7 times 1,000. Then plus, I have a 5 in the ones place, so 5 times 1. Let's do a little bit of multiplication here. 1 times 10 billion is just 10 billion. Okay, then we have plus 5 times 1 million is 5 million. Then plus 3 times 100,000 is 300,000. And plus 2 times 10,000, that's 20,000. And plus 7 times 1,000 is 7,000. And plus 5 times 1, which is 5. So again, all we're doing is we're breaking the number down to see the value for each digit in this number. So this 1 is a 10 billion. This 5 is a 5 million. This 3 is a 300,000. This 2 is a 20,000. This 7 is a 7,000. And then lastly, the 5 is just a 5 because, again, it's in the ones place. 5 times 1 is just 5. Hello and welcome to Pre-Algebra Lesson 3. In this video, we're going to learn about inequalities and the number line. All right, so the lesson objectives for today, we want to learn how to create and work with a number line for the whole numbers. And then also we want to learn about inequalities and a few symbols we're going to work with. So previously in our course, during the lesson on place value, we introduced the whole numbers. So the whole numbers start with 0. So that is the smallest whole number. And then they increase in increments of 1 out indefinitely. So after 0 comes 1, then 2, then 3, then 4, then 5. You just pick a spot because you can't list all of them. And you're going to stop. And you can put the 3 dots there just to show that the pattern continues forever. So after 5 comes 6, then 7, then 8, so on and so forth. Now we can visually represent our whole numbers using a horizontal number line. And so the leftmost notch here is going to correspond to the smallest whole number, which is 0. So see, this guy would correspond to this guy here. And then as we move to the right on the number line, each additional notch is corresponding to the next largest whole number. So this, going to the right by 1 unit, this would be 1. The next largest whole number is 1. Then this notch going to the right would be 2. The next largest whole number is 2, so on and so forth. You're just increasing by 1 each time. So you go to 3, then 4, then 5, then 6, so on and so forth. Now, in a similar way to this guy right here where we put the 3 dots, we need to show that the whole numbers continue going out to infinity. So basically they continue forever. So what we're going to do here is draw this little arrow and say that, hey, after 10 comes 11, then 12, then 13, so on and so forth. Now, there's a few things we want to think about when we look at the number line. First off, numbers increase from left to right. So you can pick any two numbers you want and just think about them for a moment. Let's say I start with something easy like 1 and 2. Well, I know that 2 is a larger number than 1, and notice how 2 is to the right of 1 on the number line. Let's just pick two other ones. So let's say we look at 6 and 7. Well, 7 is a larger number than 6, and notice that 7 is to the right of 6 on the number line. So as we move to the right, numbers are increasing in value. So what you can say is that if a number is to the right of another number on the number line, it is a larger number. Then additionally, we can say that numbers decrease from right to left. So if I'm going this way, numbers are decreasing in value. Let's take 4 and 5. Well, 4 is to the left of 5 on the number line, and 4 is a smaller number. So what you can say here is that if a number is to the left of another number on the number line, it is a smaller number. All right, before we move on with the lesson, we need to introduce a few new symbols. So the first symbol I'm going to talk about is the equality symbol. A lot of people just call this the equal sign or equals. So let me put that up there. I'm sure you've seen that before. So this means is equal to. So whatever's on the left is equal to whatever's on the right. You could also think about this as saying whatever's on the left is the same as whatever's on the right. Now, it's not always going to be very straightforward. So let's say I start with something very easy to identify as being equal or the same. So I'm going to put a 5 here and a 5 here. So obviously 5 is equal to 5, or 5 is the same as 5. If I have $5 in my wallet and my friend has $5 in his wallet, well, we have an equal amount of money or the same amount of money. We can each go to the store and buy $5 worth of stuff. Now, let's say we change up the way this looks a little bit. And to give you an example, let's say I keep my $5 bill in my pocket, but my friend goes to a bill changer and he exchanges his $5 bill for 5 singles, or you could say 5 $1 bills. One way you could write this is by showing this as 1 plus 1 plus 1 plus 1 plus 1. So now it doesn't look as straightforward as this, but these two sides represent the same value in the end. If he goes through and adds up his singles, he still has $5, right? This is 1 plus 1, which is 2, plus 1, which is 3, plus 1, which is 4, plus 1, which is 5. So each of us can go to the store and spend $5 on stuff. We have the same amount of money or an equal amount of money. So 5 is equal to or the same as 1 plus 1 plus 1 plus 1 plus 1. At the end of the day, the value on each side is 5. So another symbol we're going to use is the not equal to symbol. So here we're going to draw the equal symbol and we're going to put a little slash through it. So this means is not equal to. So whatever's on the left is not equal to whatever's on the right. Now it doesn't matter what's on the left and what's on the right as long as they're not equal. So you could have a smaller number on the left and the larger number on the right, or you could put the larger number on the left and the smaller number on the right. It does not matter. So what I'm going to do is say something like, let's say 5 is not equal to 7. So let's say my friend got $2 additional, and so now he has $2 more than me to spend. He can spend $7, but I can only spend $5. So the amount of money we have is not the same. It's not equal. Again, this can also be more complicated. So let's say that I have a 5 here, and let's say over here, keeping with what we did a moment ago, let's say we have 1 plus 1 plus 1 plus 1 plus 1. So that's my 5 ones. And let's add an additional 2 here. So here we have 1 plus 1, which is 2, plus 1, which is 3, plus 1, which is 4, plus 1, which is 5, plus 1, which is 6, plus 1, which is 7. So 5 is not equal to, at the end of the day, 7. So it doesn't matter if it's straightforward like this. You're going to see a lot of stuff that's not straightforward, and you need to go through and think about, well, what is the value of this once I perform this operation? Well, this would be 7, and this is 5, and 5 is not the same as 7. So here we can show that with the not equal to symbol. All right, now the next two symbols we'll use for the rest of this lesson. These are called the strict inequalities. We'll talk about non-strict inequalities later on, but for right now, when you talk about a strict inequality, you're talking about a less than symbol or a greater than symbol. So let's start with a less than symbol. So this right here means is less than. So whatever's on the left is less than whatever's on the right. So the way you remember this, when you're looking at these symbols, this guy right here is always pointing to the smaller number. So if I grab two numbers from the number line, let's say 2 and 3, again, 2 is smaller than 3 because 2 is to the left of 3 on the number line. In order to make this a true statement, I need to put that smaller number on the left and the larger number on the right. So it's very important that you do it this way. If you put here that 3 is less than 2, that's a false statement, okay? So with this one, you want to make sure that the smaller number is on the left and the larger number is on the right. So you can say that, in this case, 2, or whatever that smaller number is less than the 3, or whatever that larger number is. Then the other guy is going to be the greater than symbol. So this means is greater than. So now the number on the left is larger than the number on the right. So here the number on the right needs to be smaller. The symbol always points to the smaller number. Here it points to 2 because 2 is smaller than 3. Here it's going to point to, let's just pick two numbers. Let's say we go with 8 and 9. So here it would point to 8 because 8's a smaller number. It's to the left of 9 on the number line. 9 needs to go over here because it's the larger number. So we would say 9 is greater than 8. So whatever the bigger number is goes on the left, and that's greater than whatever the smaller number is, that's going to go on the right. All right, let's go through some examples. I think you're going to find this very, very easy, but something you'll definitely see in your textbook. So we want to replace each question mark with the inequality symbol less than or greater than. All right, for the first example, we have 5 question mark 2. So let me write this over here. 5. And then we have a question mark, and then a 2. So first, let's circle 5, and then let's circle 2. So 5 is to the right of 2 on the number line, so 5 is a larger number than 2. So here I would want to use a greater than symbol. Again, if you can't remember, the symbol always points to the smaller number. 2 is a smaller number than 5, so just point the symbol to the smaller number. So here you would say 5 is greater than 2. Now, if we flip this around, and let's say the problem was 2, question mark 5, then now we want to use a less than symbol. Always point the symbol to the smaller number. So this guy right here would point towards 2. 2 is less than 5. Here, 5 is greater than 2. With a greater than, the larger number's on the left. With a less than, the smaller number's on the left. All right, for the next problem, we'll look at 3 question mark 0. Here's 3. Here's 0. So 3 is to the right of 0 on the number line, so 3 is going to be a larger number. So we would say that 3 is greater than 0. Again, that symbol is going to point, let me use a different color here, is going to point to that smaller number. 0 is the smaller number. If you flip this around, and let's say you got 0 and then question mark 3, well now I want to use a less than. 0, which is the smaller number, is less than 3. The symbol always points to the smaller number. What about the next one? We have 4 question mark 8. So 4 question mark 8. Here's 4. Here's 8. So 4 lies to the left of 8 on the number line, so it's a smaller number. So here we would want to use the less than symbol. Again, the symbol is going to point to the smaller number. If we had gotten 8 question mark 4, well now we want to use the greater than symbol. 8's a bigger number. It lies to the right of 4 on the number line, so we would want to say 8 is greater than 4. What about 7 question mark 3? So 7 question mark 3. Here's 7, here's 3. 7 lies to the right of 3 on the number line, so it's a bigger number, so you want to use a greater than there. Again, the symbol always points to the smaller number, so the symbol would point to 3. If you had gotten 3 question mark 7, well now you want to use your less than symbol to say 3 is less than 7. Symbol always points to the smaller number. What about 1 question mark 2? Here's 1, here's 2. So 1 is to the left of 2 on the number line, so you would say 1 is less than 2. Symbol always points to the smaller number. If you got 2 question mark 1, well then you want to use the greater than symbol. 2 is a larger number than 1. The symbol always points to the smaller number. The smaller number here is 1. Hello, and welcome to Pre-Algebra Lesson 4. And in this video, we're going to learn about rounding whole numbers. So our lesson objective for today is simply to learn how to round whole numbers. So before we get into the procedure that we use to round a whole number, let's talk a little bit about why we would round whole numbers. So in many situations, an exact value is not needed. In these cases, an approximation is easier to use and remember. And when we talk about approximations, we're talking about a value that is close to the original value, but not exactly there. All right, so rounding a whole number. The first thing you want to do is locate the digit in the round off place. So for example, if we are rounding to the nearest 10, you would start by locating the digit in the tens place. When you first start out, I would circle that digit or highlight it or do something to say, hey, this is my round off place. So kind of step 2 is to look at the digit to the right of the round off place. So if the digit to the right of the round off place is, and you have two different scenarios. The first one is 4 or less. You want to leave the digit in the round off place unchanged. Then the second scenario that could occur is that it's 5 or larger. In this case, we increase the digit in the round off place by 1. Okay, increase the digit in the round off place by 1. And then your third and final step is pretty easy. You just replace each digit to the right of the round off place with a 0. Okay, here we want to round 631 to the nearest 10. So again, I'm looking for the tens place, and that's going to be this 3 here. And then in step 2, what I want to do is I want to look at the digit to the right, and that's going to be this 1. Now, does this 1 fall in the category of 4 or less, or does it fall in the category of 5 or larger? Well, it's clearly in the category of 4 or less. So when that happens, I want to leave the digit in the round off place, which is the 3, right? It's in the tens place, unchanged. So I would have 6, and then the 3 is going to be unchanged. And then in step 3, I'm going to replace each digit to the right of the round off place with a 0. So the 1 is to the right of the round off place. I'm going to replace that with a 0. And so 631 rounded to the nearest 10 is 630. Okay, next we want to round 7,952 to the nearest 1,000. So 7,952. And we're looking for the digit in the thousands place. So that's going to be this 7 here. And then we look for the digit immediately to the right of that. So that's this 9. And obviously the 9 falls in the category of 5 or larger. So when this occurs, we increase the digit in the round off place by 1. So I'm going to increase that 7 by 1. 7 plus 1 is 8. And then I replace each digit to the right of the round off place with a 0. So I'm going to replace the 9 with a 0, the 5 with a 0, and the 2 with a 0. And so 7,952 rounded to the nearest 1,000 is 8,000. Okay, next we want to round 813,275 to the nearest 10,000. All right, so we have 813,275, and the 10,000th place is right here. So I'm looking at the digit that follows that, and that's this 3 here. 3 falls in the category of 4 or less. So when this occurs, we're going to leave this digit in the round off place unchanged. Unchanged. So the 8 and the 1 are going to stay unchanged. I don't need to do anything to those. But I'm going to replace each digit to the right of the round off place with a 0. So the 3 is to the right of the 1, so I'm going to replace that with a 0. And then I'm going to replace the 2, the 7, and the 5. And so 813,275 rounded to the nearest 10,000 is 810,000. Okay, for the last problem, we want to round 61,005,387 to the nearest million. So 61,005,387 to the nearest million. So the millions place is right here. That's the 1. And we want to look at the digit to the right of the 1. So I'm looking at this digit here, which is a 0. 0 is obviously in the category of 4 or less. So we're going to leave the digit in the round off place unchanged. Unchanged. So basically the 6 and the 1 will be unchanged. And then everything that follows the 1, which is the digit in the round off place, will just be a 0. So I'll have 0, 0, 0, comma, 0, 0, 0. So 61,005,387 rounded to the nearest million is 61 million. Hello and welcome to Pre-Algebra Lesson 5. And in this video, we're going to learn about the properties of addition. Okay, so for the lesson objectives, we want to learn about the identity property of 0. We want to learn about the commutative property of addition, We want to learn about the associative property of addition, and then also we want to learn to identify the parts of an addition problem. Okay, so let's begin the lesson by thinking about what addition actually is. So addition is the operation that allows us to group items together. So if we think about this in a very simple way, kind of the way that you would think about it if you're in grammar school, we have this picture here, and we have 3 boxes, and we're adding to that 2 more boxes. So we can just go through and count how many boxes we have. We can just say, okay, I have 1, 2, 3 boxes, right, from up here. And then I added to that 2 more. So then 4 and then 5. And at this point, we all know that 3 plus 2 is 5. But this just visually represents what's going on when we add. We're trying to get a total for all the amounts that we've combined together, right? I've combined this group of 3 boxes with this group of 2 boxes, and it gave me a total of 5 boxes. Okay, so let's talk about a little bit of vocabulary. So in an addition problem, the numbers being added together are called addends. Okay, addends. And then the result of an addition operation is known as the sum. Okay, the sum. So let's look at a quick problem. We want to identify each part of the addition problems below. Okay, so we're going to start with 5 plus 6 equals 11. And all we're going to do is just label. So we know that the numbers being combined together or added together are called addends. So 5 and 6 would be addends. And then 11, which is the result of the addition, would be called the sum. Okay, let's look at the next one. We have 12 plus 8 equals 20. So 12 and 8 are the numbers being added together. Those are called addends. So these are the addends. And again, the result of the addition is called the sum. So 20 is the result of 12 plus 8. So this is the sum. Okay, so the first property we're going to learn about today is called the identity property of 0. And it's really pretty simple. It just tells us that adding 0 to any number leaves the number unchanged. Okay, so I can add 0 to any number and it will remain unchanged. So let's take a look at some examples here. So 5 plus 0 equals what? Well, adding 0 to 5 leaves 5 unchanged, so 5 plus 0 equals 5. 7 plus 0 equals what? Adding 0 to 7 leaves 7 unchanged, so 7 plus 0 equals 7. And then 1,365,371 plus 0. Again, adding 0 to anything leaves it unchanged, so it would just be 1,365,371 as the answer. Okay, the next property is also very simple. It's called the commutative property of addition. And the commutative property of addition tells us we can add numbers in any order without changing the sum. So the order that you add does not matter whatsoever. And kind of to prove this, I have some examples. So we have 6 plus 3 equals 3 plus 6. Basically, the order is changed. So 6 is on the left here. 6 is on the right over here. It doesn't matter. You're going to get 9 either way, right? If I say 6 plus 3, what does that equal? It equals 9. If I say 3 plus 6, what does that equal? It equals 9. So changing the order of the addends does not change the sum. Again, as another example, 7 plus 9 equals 9 plus 7. So changing the order here of the addends does not change the sum. 7 plus 9 is 16, and 9 plus 7 is 16 as well. And as a final example, we have 12 plus 5 equals 5 plus 12. Again, switching the order or changing the order of the addends does not affect the sum. 12 plus 5 is equal to 17. 5 plus 12 is also equal to 17. Okay, so the last property we're going to talk about today is another easy one. It's known as the associative property of addition. And the associative property of addition tells us that the addition of 3 or more numbers can be grouped in any order without changing the sum. So the way that we group numbers when we're adding does not change the sum. So let's look at some examples of this. We have 3 plus 6 here on the left, and that's inside of parentheses. And then we're adding to that 2. And we're saying that's equal to 3 plus, and here we have 6 plus 2 inside of parentheses on the right. Now the associative property is telling us that since we're adding the same three numbers, 3 plus 6 plus 2, it doesn't matter what we put parentheses around. We're going to get the same result. We haven't done a lesson on the order of operations yet, but the order of operations tells us that if you have operations inside of parentheses, you have to do them first. So if we were to follow that rule, we would say 3 plus 6 is 9. We would do that operation first, and then we would add 2 to that. So 9 plus 2 gives me 11. So kind of the left side here gives me a result of 11. On the right, I would do 6 plus 2 first because that's inside of parentheses. 6 plus 2 is 8, so we would have 3 plus 8, and that equals 11 as well. So it didn't matter that we had parentheses here on the left around 3 plus 6 and parentheses on the right around 6 plus 2. We got the same result either way. And that's exactly what the associative property of addition is telling us. Okay, for another example, we have 7 plus 5 plus 2, and 5 plus 2 is inside of parentheses. And this is equal to 7 plus 5. Now 7 plus 5 is inside of parentheses plus 2. So 7 plus, and a lot of times you'll hear that people say the quantity when something's inside of parentheses. So 7 plus the quantity 5 plus 2. 5 plus 2 is done first. 5 plus 2 is 7. So we get 7 plus 7, and that gives us 14. So the left side here is 14. What's the right side going to be? It's going to be 14 as well. The quantity 7 plus 5 is 12. Again, we're doing that first because it's inside of parentheses, and then plus 2 gives us 14. So again, we group this different in each case. We have 5 plus 2 inside of parentheses on the left. We have 7 plus 5 inside of parentheses on the right, but it didn't matter, right? Because we got 14 either way. Okay, as our last example, we have 15 plus 9 inside of parentheses. So the quantity 15 plus 9 plus 2, and this is equal to 15 plus, now we have parentheses around 9 plus 2, so 15 plus the quantity 9 plus 2. So on the left here, we start with 15 plus 9 because that's in parentheses. So the quantity 15 plus 9 is 24. 24. Then plus 2 would give me 26. On the right, I'm going to do 9 plus 2 first. So the quantity 9 plus 2 is 11. So we'd have 15 plus 11. And of course, that gives us 26 as well. So again, that's what the associative property of addition is telling us. We have the same three numbers being added, 15, 9, and 2. We're going to get 26 no matter how we group the addition. We can put parentheses around 15 plus 9. We can put parentheses around 9 plus 2. It doesn't matter. We get 26 as a result either way. Hello and welcome to Pre-Algebra Lesson 6. And in this video, we're going to be learning about adding whole numbers using a number line. So the lesson objective for today will be to just learn how to add whole numbers, again, using a number line. So during a previous lesson, we talked about using a number line to visually represent a group of numbers. So let's look at a number line that shows the whole numbers. And again, I've talked about the whole numbers in previous lessons. The whole numbers are a group of numbers that start with 0. So 0 is your smallest whole number. And then they increase in increments of 1. So after 0, you get 1, then 2, then 3, then 4. Again, just increasing in increments of 1. And this continues forever. And that's why we have the 3 dots here. When you see the 3 dots in this case, it means that the pattern, which we're increasing in increments of 1, is going to continue forever. So after 4 comes 5, then 6, then 7, so on and so forth. So if we look at the whole numbers using a number line, again, this is a number line. This is a visual representation of the whole numbers. So you'll see the leftmost whole number is 0. That's your smallest whole number. And you see you have a little notch here. Now, every time you have another notch as you move to the right, you're going to the next largest whole number. So you go to 1, then you're going to 2, then you're going to 3, then you're going to 4, so on and so forth. So it's impossible to list all the whole numbers. So basically what we do is at some point we just stop, and it can be basically anywhere. I could have stopped this at 5. You just draw an arrow to say, hey, this is going to continue forever. Okay, so we can use the number line to visually show the addition of whole numbers. So this may seem like a trivial exercise, but it will help us a lot when we start working with integers. So this is going to seem kind of like it's a waste of time to you at first, but when you start working with integers, especially for the first few times that you work with integers. With addition and subtraction, it's a lot easier to start out doing it on a number line. And if you've already had that experience doing it with whole numbers, it'll make it a little bit easier for you when you do it with integers. So how do we add whole numbers on a number line? Well, we start at the leftmost number. So for example, if you had 3 plus 7, you would start out at 3 on the number line, and then you move to the right by the number of units being added. So we're adding 7 to 3, so we would just move to the right by 7 units. It's actually very, very, very simple. So let's take a look at some examples now. We want to add 2 plus 6 using the number line. So the leftmost number, the 2, is where we're going to start on the number line. So we're just going to start right here. And then we're adding 6. Okay, we're adding 6. So I'm just going to go 6 units to the right, and I'll be at my answer. So I'm going to go 1, 2, 3, 4, 5, 6 units to the right. I'm at 8. So that is my answer. And all of us know at this point that 2 plus 6 is 8. So 2 plus 6 equals 8. It's just to get the practice of doing it on the number line. Okay, now we want to add 4 plus 7 using a number line. And so I have a number line that's a little bit larger. It's a little bit more crowded. But we can still find everything. We're adding 4 plus 7. So we're going to start at the leftmost number, or the 4. And that's going to be right here. This is your 4. And then you're adding 7. So we're just going to move 7 places to the right. So each notch is a place or increased by 1. So 1, 2, 3, 4, 5, 6, 7. So that's going to put us right here at 11. Okay, at 11. And again, we all know that 4 plus 7 is 11. Again, it's just to get the practice of doing it on the number line. So 4 plus 7 equals 11. Okay, now we want to add 6 plus 5 plus 1 using a number line. Although we're adding 3 numbers, the process is basically the same. We're starting at this leftmost number, so we're starting at 6. So that's going to be right here. And then we're going to go 5 places to the right because we're adding 5. So 1, 2, 3, 4, 5. So that puts us at 11. And we all know that 6 plus 5 is 11. Now we're adding 1 more, so we just go 1 more place to the right. So 1 more place to the right. That puts us at 12. And so our answer for 6 plus 5 plus 1 is, of course, equal to 12. Okay, now we want to add 3 plus 2 plus 1 plus 7, again, using a number line. So let's find 3. That's where we're going to start, the leftmost number. And that's right here. That's this guy. And we're going to move 2 places to the right because we're adding 2. So that's going to go 1, 2 places to the right. And now we're adding 1. So we're going to go 1 more place to the right. And then we're adding 7. So we're going to go 7 places to the right. 1, 2, 3, 4, 5, 6, 7. So we end up here at 13. So 3 plus 2 plus 1 plus 7 equals 13. And I kind of checked this since we can all do addition. 3 plus 2 is 5. 5 plus 1 is 6. 6 plus 7 is in fact 13. Essentially, you're just starting at the leftmost number of the addition problem. Every time you add something, you just move that number of places to the right on the number line. So we started at 3. We moved 2 places to the right to get to 5. Then we moved another place to the right to get to 6. And then we moved 7 places to the right to get to our final answer of 13. Okay, let's look at the final one. We want to add 2 plus 3 plus 5 plus 4 plus 7 plus 1 using a number line. So again, we're going to start at the leftmost number. So that's 2. So we'll start out here on the number line. And every time I add something, I just move that number of places to the right. So I'm adding 3. So I just want to go 3 places to the right. So 1, 2, 3 places to the right. So that put me at 5. Then I'm adding 5. So I'm going 5 places to the right. Let me just change colors. So 1, 2, 3, 4, 5 places to the right. So that would put me at 10. Then I'm adding 4. So now I'm going to go 4 places to the right. So 1, 2, 3, 4 places to the right. That's going to put me at 14. I'm adding 7 to that. So that's going to put me 7 places to the right. 1, 2, 3, 4, 5, 6, 7 places to the right. That's going to put me at 21. And then lastly, I'm going to add 1 more to that. So that is going to put me at 22. So that's my final answer here. It's 22. So we have 2 plus 3 plus 5 plus 4 plus 7 plus 1. And the answer is 22. And to check that, just go through and do your addition. 2 plus 3 is 5. 5 plus 5 is 10. 10 plus 4 is 14. 14 plus 7 is 21. 21 plus 1 is 22. So again, adding whole numbers on a number line seems pretty trivial. It's actually very, very easy, but it's going to help us when we get to adding integers. And again, what we do is we start at the leftmost number of the addition problem on the number line, and then every time we add a number, we move to the right on the number line by that number of units. Hello and welcome to Pre-Algebra Lesson 7, and in this video we're going to learn about vertical addition. So the lesson objectives for today would be to learn how to properly set up and perform vertical addition, and also to learn the process of carrying. Okay, so when are we going to use vertical addition? Well, vertical addition is a process we use when we're adding multi-digit numbers together. And a multi-digit number is any number that is larger than one digit. So to perform the vertical addition, the first step is to arrange the numbers to be added vertically, and by place value. So when I say vertically, I mean we're going to stack the numbers on top of each other. Let me just show you real quick with an example. Let's say we're adding 13 to 24. So 13 plus 24 is the problem. In this first step, we're just going to put the numbers on top of each other. Doesn't matter which number's on top or which number's on bottom. So 13 and 24, we're going to write like this. And there's more to it, but we'll get to those in the next steps. Now, notice how when I stack these numbers on top of each other, the digits in the ones place for each number line up, and the digits in the tens place for each number line up. This is your ones, and this is your tens. Let me just make this a little cleaner. This is the ones. Okay, so that is the first step. Stack the numbers on top of each other and by place value. So don't do something like this where you have 13 and 24 over there. That won't work. Again, vertically and then by place value. All right, so let's take a look at the second step. So let me just rewrite this. We have 13 and we have 24 written like this at this point. And for step 2, we want to draw a horizontal line underneath the bottom number. So let's do that. And place a plus symbol, okay, this is the plus symbol, to the left of the bottom number. So to the left of this bottom number, I'm just going to put a plus symbol. And now we have our addition problem set up. And in step 3, we're going to learn how to actually perform the addition. Okay, so for step 3, let me just rewrite this. We have 13 plus 24. We want to add the numbers in each column, starting with the ones column and moving left. So that means we're going to start in this column. You always work right to left when you're doing vertical addition. Now, we want to place the result directly below the horizontal line. So I'm going to start with the numbers in this column here. We're starting in the ones column. So what is 3 plus 4? 3 plus 4 is 7. So all I'm going to do is I'm going to put that directly below this horizontal line, and I got to stay in line. Basically, this 7 is going to be in the ones place for the answer. And then I just move left. So next I'm going to do the addition in the tens column. So I'm doing the addition here. So now I'm doing 1 plus 2, and that gives me 3. So when we add 13 and 24 together, we get 37. Okay, so let's take a look at some examples here. We're going to start with some very easy problems, and then we'll progress to some that are a little bit more challenging. So we have 27 plus 12. Again, we're going to begin by stacking the numbers on top of each other. So 27 can go on top, 12 can go on the bottom. And again, you can reverse that order. You could put 12 on the top and 27 on the bottom. It really doesn't matter. Now we're going to draw a horizontal line beneath the bottom number, and we're going to put a plus symbol off to the left of that bottom number. Now, we start by adding the numbers in the ones column. So we have 7 plus 2, and that gives us 9. Put your answer down in the ones column. Just keep following straight down. Then we move to the left. So now we're going to look at adding the numbers in the tens column. So 2 plus 1 is 3. So 27 plus 12 is 39. Let's kind of break this addition problem down a little bit further. If we think about 27 plus 12, again, we did it like this. 27 plus 12. We added in the ones column. 7 plus 2 is 9. We add in the tens column. 2 plus 1 is 3. We got an answer of 39. But if we think about 27, it's what? It's 2 tens or 20 plus 7 ones or 7. If we think about 12, it's 1 10 or just 10 plus 2 ones or 2. So we think about adding these numbers together, just looking at them like this, it makes sense to have, okay, we want 7 ones plus 2 ones to know the amount of ones that we're going to have in our answer. So that's why those are lined up. So 7 plus 2 is 9. You get 9 ones. And it makes sense to think about the tens together as well. We have 2 tens plus 1 10, or we have basically 20 plus 10 or 30. So we have 3 tens. And when we think about this, this is basically 30 plus 9 or 39. So very important to translate this longer process into this shorter process here. This is just a shorthand for this over there. Now, what if you didn't stack the numbers up by place value? You'd run into a mess. You'd never get the right answer. If we think about 27 plus 12, let's say I did it like this. Let's say I put 27 here, and I don't know, let's say I put 12 over here. Would I get the right answer? Well, no, because now I think I only have 7 ones. So this would just come straight down. And now I think I have 2 tens plus another 2 tens, or 4 tens, or 40. And this would come down. So I get an answer of 147, which is completely incorrect, right? Completely incorrect. So that's why it's important to line up your numbers by place value. It's going to tell you how much of each you're going to have. How many ones, how many tens, how many hundreds that you're going to have in your answer. Okay, let's look at the next one. We have 405 plus 314. So again, we're going to line these up vertically and by place value. So everything is lined up. We got the ones, the tens, and now the hundreds. So we work right to left. So we're going to start by adding the numbers in the ones column. What is 5 plus 4? That is 9. So you're going to write your 9 in the ones column for the answer. 5 ones plus 4 ones is going to give me 9 ones. Then we're just working our way to the left. So now we're going into the tens column. 0 plus 1 is going to give me 1. And we worked our way to the left again. Now we're in the hundreds column. 4 plus 3 is going to give me 7. And so my answer is 719. And again, just thinking about this, we had 5 ones plus 4 ones. That gave us 9 ones. We had 0 tens plus 1 10, which gave us 1 10. Then we had 4 hundreds plus 3 hundreds, which gave us 7 hundreds. So essentially we have 700 plus 10 plus 9, or the number 719 as our result. Okay, now we have 2,057 plus 14,112. So again, we're going to stack these numbers on top of each other and by place value. But one thing you're going to notice here is that one of the numbers has fewer digits than the other. Typically when this happens, you put the number with more digits on top. So typically you're going to see 14,112 on top and 2,057 on the bottom. But I'm going to do this addition problem twice and show you that it doesn't actually matter. This is just a little bit easier. So we're going to start in the ones column. 2 plus 7 is 9. Then we're going to the tens column. 1 plus 5 is 6. Then we're going to the hundreds column. 1 plus 0 is 1. And then I'm going to put a comma there. And now I'm going into the thousands column. So 4 plus 2 is 6. And then I'm going to the 10,000s column. And you'll notice how there's nothing here to add with 1. Typically, we'll teach this as, okay, just bring the number down, and you'll put a 1 there. So your answer is 16,169. Let's say I change what's on top. Let's put 2,057 on top, and let's put 14,112 on the bottom. Let's kind of move that over a little bit. And it's the same thing. We start in the ones column. 7 plus 2 is 9. Then we move to the left. 5 plus 1 is 6. 0 plus 1 is 1. 2 plus 4 is 6. And then bring down the 1. We get 16,169 either way. Just typically, you're going to see this setup because the number with more digits is generally going to be on top. Okay, now we want to look at a problem that's going to involve something known as carrying. So I'm going to work through this problem, and then I'm going to go back and explain how it works. So 27 plus 35 is what we're going to work on. So 27 plus 35. So what happens is when we try to add the numbers in the ones column, 7 plus 5, you get 12. I can't fit a 12 in this space right here. I can only fit numbers 0 through 9. I can only fit a digit in this space. So 12 is too big. So what I'm going to do, I'm going to break 12 apart. I'm going to think about the left number, and I'm going to think about the right number. So the right number is going to stay. It's going to stay right here in the answer column, just like you normally would do. And then the left number is going to get carried into the next column. Okay, so we're going to carry the 1 into the next column. And now I'm just going to include it with the addition of that column. So 1 plus 2 plus 3. 1 plus 2 is 3. 3 plus 3 is 6. So we end up with 62. But let's think about what we actually did here. Let me just erase this real quick and think about what we actually did. When we look at 27 and we break it down, we have 2 10s plus 7 1s. Okay, so this is 20 plus 7. And when we think about 35, we have what? We have 3 10s, or we have 30, plus we have 5 1s, or just 5. So when we add the numbers in the ones column, we have 7 1s and we have 5 1s. 7 plus 5 is 12, so we would have 12 1s. Basically, all we're doing is rewriting 12 1s as 1 10 plus 2 1s. Okay? 1 10 plus 2 1s. So when we think about the result here, if I give you a $10 bill and 2 1s, that's the same as if I handed you 12 1s. It's the same. So all I'm doing here is I'm just going to scratch this out, and instead of putting 12 1s, I'm going to put 2 1s, and then I'm going to go into the next column, into the tens column, and say, hey, I have another 10. I have another 10. So now the result of the addition, we have 10, 20, and 30 that we're adding. 10 plus 20 is 30. 30 plus 30 is 60. So we end up with 6 10s, or 60, plus 2 1s, which is 62. That's what we got. So this is essentially what we're doing when we're using the carrying process. It's just a shorthand way to kind of go through and do all this and evaluate place values. Let's take a look at another one. Okay, next we have 242 plus 977. So 242 plus 977. So again, we're going to start by adding the digits in the ones column. So 2 plus 7 is 9. And then we work our way to the left. So next we're looking at the tens column. So we have 4 plus 7, but that's 11, and I cannot fit an 11 right there. You cannot fit anything larger than a 9 in this space. So what we need to do is evaluate the place values and figure out what we need to do. So we use carrying to do that. So if I have 11, I take the rightmost digit of 11, and that's a 1, and I put that in the answer column. So that goes there. Then I carry the leftmost digit, which is also a 1, into the next column. So that's going to go right here. And I'm just going to add that when I add this column together. So 1 plus 2 is 3, and then 3 plus 9 is 12. Now, when you don't have any more numbers to the left here, I can just simply write a multi-digit number into the answer. And the reason for that is because I'm still maintaining place value. I'm still having a 2 in the hundreds column, and this 1 is just pushed out into the thousands column. Because essentially, if there were more numbers over here, the 1 would have got carried over. But there are none, so it just comes straight down. So we end up with our answer of 1,219. And to think about this carrying action just a little bit more, when we look at the result of this column here, which was 4 10s, 4 tens plus 7 tens. Really, we got 11 tens, right? We got 11 tens, which essentially all we did was we broke it down into 100 plus 110. If I gave you 11 $10 bills, you would have $110. If I gave you a $100 bill and a $10 bill, you'd still have $110. So it's the same either way. So this is exactly what we did. We put 110 right here, and then we carried 100 into the next column to be added with the hundreds. Okay, for the next one we have 6,099 plus 15,763. And as I told you earlier, typically you're going to take the number with more digits and put that on top. So we'll take 15,763 and put that on top. We'll take 6,099 and we'll put that on the bottom. And let me just make this a little cleaner. So again, we're going to start with the digits in the ones column. 3 plus 9 is 12. 12 is too big to fit in the answer column. So I keep the rightmost digit, which is a 2, right? We think about 12. The rightmost digit is a 2. And then I carry the leftmost digit, which is a 1, into the next column. Now I add. 1 plus 6 is 7. 7 plus 9 is 16. So again, I have to carry. So I'm going to put a 6 down, right? Think about 16. The rightmost digit is a 6. And again, I'm going to be carrying a 1. And now I'm going to add. 1 plus 7 is 8. 8 plus 0 is still 8. And just keep moving on to the left. Now we have 5 plus 6, that's 11. So you think about 11, you have a 1 that's going to go into the answer column, the rightmost digit. And then you have a 1 that's going to get carried over into the next column. So now we add this column. 1 plus 1 is 2. And we just bring that down. So we get 21,862 as our answer. Hello and welcome to Pre-Algebra Lesson 8. And in this video, we're going to learn about subtracting whole numbers using a number line. So for the lesson objectives, we want to learn how to identify the parts of a subtraction problem. And we also want to learn how to subtract whole numbers using a number line. So what is subtraction? Well, subtraction is the mathematical operation that allows us to take away. The main idea behind subtraction is to find out how much is left over. So suppose you have 3 $1 bills and you go to a fast food chain and you spend $2 of your $3 on a hamburger. How much would you have left? So you can kind of picture these 3 $1 bills with 2 crossed out now because you've spent those. Well, you just have 1 left. And this is basically the subtraction problem. 3, which is what the amount you start with, minus 2, which is the amount you're going to spend or the amount that's going to be taken away. And that's going to be equal to 1, which is the amount that you're going to have left over after you've spent the money. So again, subtraction is the operation that allows us to take away. In the example, 2 was taken away from a starting amount of 3. Again, we started with $3. We spent 2. That's what's taken away. And then the result was 1. That's what we had left over. We just had a buck left. Okay, so to be more formal, let's give names to the parts of a subtraction problem. So we're going to start out with this called the menu end. Okay, the menu end. And this is the whole amount or starting value. So in the problem, 3 minus 2 equals 1. The whole amount or starting value is 3 because I started out with $3. So this is the menu end. This is the menu end. Then the next part of the subtraction problem is called the subtrahend. Okay, the subtrahend. So this is the amount being taken or subtracted away. So in the problem, 3 minus 2 equals 1. 2 is the subtrahend. This is the subtrahend. Okay, that's the amount that we took away to buy the hamburger. And then finally, we have the difference. Okay, the difference. This is the result of the subtraction operation, basically what we have left over. So 3 minus 2 equals 1. The 1 here, the result or what we have left over, is the difference. Okay, so let's just label these parts too. Again, this is the subtrahend. And this is the menu end. Okay, let's look at a few examples. We want to name the parts of the following subtraction problems. So we have 13 minus 7 equals 6. So 13 is your minuend. Okay, this is the number from which another is subtracted from, or your starting amount, or the whole amount that you have, however you want to think about this. This number 13 is your minuend. Then we're subtracting away 7 from 13. 7 is what we're taking away, so this is the subtrahend. And then finally, 6 is the result of the subtraction operation here, and so it's going to be the difference. Okay, so 6 is the difference. And again, you can also think about the difference as just being the amount left over when you're finished performing the subtraction. I started with 13, that's my minuend. I took away 7, that's my subtrahend, and I have 6 left over after that operation, that's my difference. Okay, now we'll look at 8 minus 3 equals 5. The amount we're starting with, or your whole amount from which another is subtracted, is 8. That's the minuend. Then we have 3. That's what we're subtracting away. So 8 minus 3. Okay, we're taking away 3. That's the subtrahend. And then lastly, we have this 5 here. That's the result of our subtraction operation. We start with 8. We take away 3. The result is 5. So 5 is the difference. Okay, the next thing we want to talk about, if you remember in addition, we have something called the commutative property. And the commutative property tells us that we can add in any order that we'd like, and we don't change the sum. So in other words, 3 plus 9 is equal to 9 plus 3. Right? 3 plus 9 equals 12, 9 plus 3 equals 12. Changing the order around doesn't affect what's going on with my answer. Now, what I want to draw your attention to is that it's very important to note that the commutative property that is associated with addition does not work with subtraction. Does not work with subtraction. So in most cases, if you change the order of your subtraction, you're not going to get the same answer. So I have some examples of this. And I started out with the addition one, just to show you that it does work for addition. 3 plus 6 equals 9. 6 plus 3 equals 9. This works out. 6 minus 3 is 3. 3 minus 6 is negative 3. And we haven't covered negative numbers yet, or integers or anything. Just take my word for it, it's negative 3. So these two values are not the same. So the way that we subtract here made a difference. If I change the order, meaning I go from having 3 last to 3 first, I don't get the same result. Same thing over here. 9 minus 2 is 7. 2 minus 9 is negative 7. So changing the order did change the result. Then lastly, we have 7 minus 5 is not equal to 5 minus 7. 7 minus 5 is 2. 5 minus 7 is negative 2. So again, changing the order does change the result when you're subtracting in almost all the cases. There are some special cases where it's not, but we want to have things as a general rule. So as a general rule, when you're adding, you can change the order around as much as you want. As a general rule, when you're subtracting, you cannot do that. Okay, so now let's talk a little bit about subtracting whole numbers on the number line. This exercise will help us greatly when we start working with integers. So we already practiced adding whole numbers on a number line. Yeah, it was a trivial thing, but it's going to help us when we get to integers, and it's going to be the same thing for subtracting. We need to get a foundation going so that when we get to integers, things flow more smoothly. Okay, so now we want to subtract each using a number line. And to perform subtraction on a number line, it's essentially the same as performing addition on a number line. It's just a little bit of a change on the second step. So let's just learn through an example. We have 7 minus 4. The first thing you're going to do is you're going to start at the leftmost number on the number line. So if you recall from adding on a number line, that step is the same. You always start at the leftmost number. So that's going to be right here. That's 7 on the number line. Now, when we add, so in other words, if we're adding 4, we move to the right by 4 units on the number line. But now since we're subtracting 4, okay, since we're doing subtraction, we're just going to the left by 4 units. So the only thing that's changing is instead of going to the right, we're going to the left. Other than that, the procedure is the same. So we're subtracting 4. We're just going to go 1, 2, 3, 4 units to the left. So that's going to put us at 3. And obviously we know 7 minus 4 is 3. But it's just cool to do it on a number line. So this is our result. So we have 7 minus 4 equals 3. Okay, now we have 12 minus 5. So we're going to start out at the leftmost number. So we're starting out at 12 on the number line. That's right here. And then we're subtracting away 5. So we're going to move 5 units to the left. So I'm going to go 1, 2, 3, 4, 5 units to the left, and I end up at 7. And of course, we all know 12 minus 5 is 7, but we just did it on a number line. So 12 minus 5 equals 7. Okay, now we have 8 minus 7. So again, we're starting out at the leftmost number on the number line. So we're starting out at 8. That guy's right here. And we're subtracting away 7. So we're moving 7 units to the left. So we're going to go 1, 2, 3, 4, 5, 6, and then finally 7 units to the left. And we end up at 1. All right, we end up at 1. And of course, we know that 8 minus 7 is equal to 1. Okay, we'll look at one last problem. Overall, this is pretty simple, right? If you're adding on a number line, you start out at the leftmost number. You go to the right by the number of units you're adding. If you're subtracting on a number line, start at the leftmost number. You go to the left now by the number of units that you're subtracting away. So we have 5 minus 5. 5 minus 5. So that means I'm going to start out at 5 on the number line. That's right here. And then if I'm taking away 5, we know that we're going to end up at 0, right? Because a number minus itself is 0. So let's go 5 units to the left. 1, 2, 3, 4, and 5. Okay, so we end up at 0 right here. And 5 minus 5 equals 0. Hello and welcome to Pre-Algebra Lesson 9. And in this lesson, we're going to learn about vertical subtraction. So our lesson objectives for today would be to learn how to subtract multi-digit numbers. And also, we want to learn the borrowing procedure. So in a previous lesson, I taught you how to do vertical addition. And vertical addition is a convenient way to add multi-digit numbers together. And again, when I say multi-digit numbers, I mean numbers that are larger than 1 digit. So vertical subtraction is essentially the same thing. It's a convenient way to subtract multi-digit numbers. But there's some differences that we need to cover. So let's explain through an example here. The first step for vertical subtraction, we want to line up the subtraction problem vertically and by place value. So you'll recall with vertical addition, it's the same first step. So let's say that we have, I don't know, 47 plus 13 for the addition problem. And let's say that we have 47 minus 13 for the subtraction problem. So here's the main thing that you need to understand. When we do addition, addition is commutative. So the order that we add in does not matter. So in other words, when I go through and I stack these numbers on top of each other, it doesn't matter what I put on the bottom and what I put on the top. So I can do 47 plus 13 like this, or I could do 13 plus 47 like this. Either way, I'm going to get the same answer. So we can go through and add. 7 plus 3 is 10, and we know we need to carry here. So the 1 goes into the next column. 1 plus 4 is 5. 5 plus 1 is 6. So I get 60. If I come over here, I'm going to get the same thing. 3 plus 7 is 10. Carry the 1. 1 plus 1 is 2. 2 plus 4 is 6. I get 60. Now with subtraction, we don't have the commutative property. So what goes on top and what goes on the bottom is going to matter. So you want to take the leftmost number for your subtraction problem. And remember, this is called the minuend. The minuend. And you want to put that on top. So when we're stacking these numbers, that guy has to go on top. And then you want to take your subtrahend. That's 13 in this case. Your subtrahend. And that's the value that's being taken away or subtracted away. And you want to put that guy on the bottom. And again, notice how we're stacking the numbers. They have to be lined up by place value. So all the numbers in the ones place have to line up. All the values or the numbers in the tens place, okay, they have to line up as well. And if we had hundreds and thousands and so on and so forth, those would have to be lined up. So that's your first step. And again, you have to make sure that the correct number is on top and the correct number is on bottom. That way you get the right answer. Okay, for the second step, we want to draw a horizontal line directly underneath the bottom number, just like we did with vertical addition, and then place a minus symbol, okay, the minus symbol, to the left of the bottom number. So essentially, it's the same thing as when you're doing vertical addition. You're just putting a minus symbol in instead of a plus symbol. So we had 47 and we had 13 stacked on top of each other. So again, draw a horizontal line underneath the bottom number and put a minus symbol or a subtraction symbol to the left of the bottom number. And we're ready to move to the next step. So we have 47 minus 13 like that. And for step 3, we subtract in the ones column and place the result directly below the line, just like we did with vertical addition. So if I do 7 minus 3, that gives me 4, and I just put that directly below in the ones column. You just think about this as a ones column that just goes all the way down. Now, in the next step, we're just going to move to the left, just like we did in vertical addition. So in the next step, I would just move to the left, and I would say, okay, what is 4 minus 1? Well, that's 3. And then I've finished the problem. You just keep working right to left. So you start all the way in the rightmost column, and you just keep going to the left. So we end up with 34 as our answer for 47 minus 13. Okay, let's look at some examples now. So we're going to start out with 96 minus 35. So stack the numbers on top of each other. 96, 35. And remember, this 96 here, this is your minuend that's got to go on top. And then 35, that's your subtrahend that's got to go on the bottom. We'll throw our subtraction symbol out there and put our horizontal line underneath. And we're ready to subtract. Remember, we're going to start in the ones column, the rightmost column, and work our way to the left. So 6 minus 5 is 1. And then we go to the next column, the tens column, and we have 9 minus 3, and that's 6. So 96 minus 35 is 61. Let's look at 87 minus 23. Okay, we're going to stack these numbers on top of each other and make sure they're lined up by place value. So remember, 87, your minuend, has to go on top. 23, the subtrahend, has to go on the bottom. So we're going to subtract beginning in the ones column. So we have 7 minus 3, that's 4. And then we work our way to the left. Now we're in the tens column. 8 minus 2, that's 6. So our answer here is 64. Okay, now we have 25,375 minus 10,164. Again, we're going to stack these numbers on top of each other. This number, the leftmost number, the 25,375, the minuend has to go on top. The subtrahend, 10,164, has to go on the bottom. Okay, so we're going to start on the ones column. And we're going to do 5 minus 4, that's 1. We're just going to work our way to the left. Now we're in the tens column. 7 minus 6, that's 1. Now we're in the hundreds column. 3 minus 1, that's 2. Now we're in the thousands column. 5 minus 0, that's 5. And now we're in the 10,000s column. 2 minus 1 is 1. So we end up with 15,211. So the examples that we've looked at so far are not very challenging at all. They're actually very, very simple. But in the next few examples, we're going to see some things that are going to kind of challenge us a little bit at first. So in many cases, the lower digit of a column is larger than the upper digit. When this occurs, we use a procedure called borrowing. And it's best for me to explain this through an example. So let's look at 43 minus 17. So we start the problem off just like we would any other. So we'd have 43 on top minus 17 on the bottom. And what happens is when we try to subtract in the ones column, we see that 3 is smaller than 7. So what happens when I try to do 3 minus 7? We haven't gotten to integers yet, so we don't know how to do this. Essentially, we only know how to subtract when the left number is bigger than the right number, right? When the minuend, or the amount that you're starting with, is larger than the subtrahend, or the amount you're trying to take away. So what we're going to do in this case is we're going to use this procedure called borrowing. Okay, we're going to borrow. And how this works is I go to the next digit to the left, and I'm going to borrow 1. Okay, so I'm going to cross this 4 out, and I'm going to subtract away 1, and that would give me 3. So now this 4 is now a 3. And I'm borrowing it, and I'm sending it over to the column to the right, and I just put a 1 in front of the digit in that column. So now this 3 is a 13, and I'm able to subtract. So I can say 13 minus 7 is 6, and then I just move to the column to the left, and I say 3 minus 1 is 2. So I end up with 26. Now, let me explain a little bit further as far as why this works. If we think about the numbers in terms of the place value of the digits involved, 43 is what? It's 40 plus 3. And 17 is 10 plus 7. So if we think about what we just did, when I crossed out this 4 and made it a 3, you think about this, I crossed this 4 out, and making it a 3, I basically made it a 30. Right? I made it a 30. And then I put a 1 in front of that 3. So if I put a 1 in front of that 3, it's a 13. So 30 plus 13 is still 43. I just changed the way it looked, right? I didn't change the value of the number, so I didn't do anything illegal here. So now when you kind of look through the columns, you can see that, okay, I have 13 minus 7, that gives me 6, and I have 30 minus 10, that gives me 20, or a 2 basically because it's in the tens place, right? 2 groups of 10 is 20. So that's essentially what we're doing when we're borrowing. We're not changing the value of the number. We're just changing the way it looks temporarily so that we can perform the subtraction in that column. Okay, let's take a look at another one. So we have 512 minus 395. So 512 goes on top minus 395, which is on the bottom. And when we try to do our subtraction in the ones column, we have 2 minus 5. We know that 2 is the smaller number, so we need to borrow. So I'm going to go to the next column over to the left, and I'm going to take 1 away. So 1 minus 1 is 0. So now that's 0. And then I'm going to put a 1 in front of this digit 2. Okay, so I'm putting a 1 in front of that. I end up with a 12. So 12 minus 5 is 7. Now I have another problem because when I get to this column, I have a 0, and I'm trying to subtract away a 9. So I need to borrow again. So I'm going to the next column over, and I'm going to take 1 away from this. So 5 minus 1 is 4. And I'm going to put a 1 in front of this. So now this 0 becomes a 10. So then 10 minus 9 is 1. Okay, 10 minus 9 is 1. And then 4 minus 3 is 1. So we end up with 117. So again, let's look at these two numbers in expanded notation and see if we can figure out what we just did. So 512 is 500 plus 10 plus 2. 395 is 300 plus 90 plus 5. So basically when we started out, we rewrote the number by taking this 10 and sending it over here. So this became 0 and this became 12. Right? Just think about adding 10 to 2. So now I have 500 plus 12. That's still 512. Haven't changed the value of the number. So we did our subtraction. We did 12 minus 5. We got 7. But now when I went to the tens, I had a 0 here, and I was trying to take away 90. So what I did was I went over to the hundreds place, and I borrowed 100. So I took this and made it 400. Right? I subtracted away 100. And I sent it over here, and I made this 100. So then 100 minus 90 gave me 10. Okay, gave me 10. And now I was just left with 400 minus 300, and that gave me 100. And so now if I look at this number, this is exactly what we got. 100 plus 10 plus 7, which is 117. So again, that's what borrowing is doing. It's just temporarily changing what these columns look like so that you can do your subtraction. But in order to really understand it, just go through as you're doing it for the first few times. Write the numbers in expanded notation and look at what you're actually doing. Okay, for the final problem, we have 190,005 minus 79,877. So we'll start out, again, stack the numbers on top of each other. 190,005 goes on top. 79,877 goes on the bottom. And of course, when you start trying to subtract here, you notice that there's a problem. 5 minus 7, we need to borrow. But we'll notice when we look at our neighbor to the left, you have a 0 there. You can't borrow from that 0. So basically when this happens, you have to go to the left until you find a non-zero number. So we have to go all the way to this guy over here, to this 9, and borrow from that. But it's not as straightforward as you think. take 1 away from the 9, you get 8. I have to send it to this guy here. Okay, I can't just send it express to the 5. So we got to go through this long, tedious process. So this 0 becomes a 10, and then I'm going to borrow from that. So this 10 will become a 9, and then this 0 will become a 10. Then this 10 will become a 9, and this 0 will become a 10. Then this 10 will become a 9, and this 5 will become a 15. So all that work just so I could subtract here. So now I can finally subtract in the ones column. 15 minus 7 is 8. We move to the left. This is now a 9. 9 minus 7 is 2. Move to the left. 9 minus 8 is 1. Move to the left. 9 minus 9 is 0. Move to the left. 8 minus 7 is 1. And then we have this 1 here. We're not subtracting anything away from it, so it just comes down. And we end up with 110,128 as our answer. So for one final time, let's write these numbers in expanded notation and see if we can figure out what happened. Scroll down a little bit and get a little room. So 190,005 is what? It's 100,000 plus 90,000 plus 5. And then our other number is 79,877, and that's going to be 70,000 plus 9,000 plus 800 plus 70 plus 7. Okay. Now this isn't really lined up, so let me try to line this up for you. So 100,000 plus 90,000 plus, you'd have a blank spot here for the thousands place. You'd have a blank spot here for the hundreds place. You'd have a blank spot here for the tens place. And then finally you'd have a 5 in the ones place. Okay, for this number you'd put 70,000 here, plus 9,000, plus 800, plus 70, plus 7. So when we start our subtraction problem, we immediately see that 5 is smaller than 7. So we need to borrow. But when we look at our neighbors here to the left, they don't have anything that we can take. So we got to go all the way to the 10,000s place. So in the problem, if we go back up here, you remember we crossed this out and we subtracted away 1, we got 8. But that 8 is in the 10,000s place, so it's really 80,000. So if I cross this out, I'm subtracting away 10,000. I'm going to write this as 80,000 now. That's the new value. And I'm going to send 10,000 to my neighbor to the right. So now he has 10,000 there. And I haven't changed the value of the number because 100,000 plus 80,000 plus 10,000 plus 5 is still 190,005. Now I need to keep going until I get to that 5 there. So I'm going to keep borrowing. So I'm going to cross this out. And basically, since I'm in the thousands place now, I'm going to take 1,000 away. So this is going to become 9,000. So now I have 9,000. And I'm going to send that 1,000 that I took away over here. So now this is 1,000. And I need to keep doing this. So I'm going to take, now I'm in the hundreds place, I'm going to take 100 away. So this is going to become 900. And I'm going to throw 100 over here in the tens place. Now I'm going to do it one last time so that I can reach this 5 over here. So I'm in the tens place, so I'm going to take 10 away. So this will become 90. And this will become 5 plus 10 or 15. Okay, think about that as 15. Now when we do our subtraction, 15 minus 7 is 8. 90 minus 70 is 20. 900 minus 800 is 100. 9,000 minus 9,000 is 0. And 80,000 minus 70,000 is 10,000. And this, I'm not subtracting anything away from it, so 100,000 is going to stay there. So when we look at this right here, this is 100,000 plus 10,000 plus 100 plus 20 plus 8, or 110,128, which is exactly what we got right here. Hello and welcome to Pre-Algebra Lesson 10. And in this video, we're going to learn about the properties of multiplication. So for the lesson objectives, we want to learn the basic parts of a multiplication problem. We want to learn the commutative and associative property of multiplication. We want to learn about the identity property of 1, the multiplication property of 0, and the distributive property of multiplication. Okay, so I want to start out the lesson by just briefly thinking about what's going on when we're multiplying whole numbers together. So back in elementary school, when you first started thinking about multiplying whole numbers, you probably started out with learning the times table, and your teacher probably at the same time put something like this up on the board. So here we have 7 plus 7 plus 7 plus 7 is the same as 4 times 7. And essentially, if we look at an addition problem where the same whole number is being added, so in this case, that whole number is 7, right? We have 7 plus 7 plus 7 plus 7. We can use multiplication as a shortcut. So instead of writing this out each time and going through and saying, okay, well, 7 plus 7 is 14. 14 plus 7 is 21. 21 plus 7 is 28. We can do it more quickly with this multiplication. We have 4 groups, right? We have 1, 2, 3, 4. 4 groups of 7. So we use that fact to say that, okay, this is 4 times 7, or 28. So it's a more quick way to perform a repeated addition. If we look at this example here, we have 9 plus 9 plus 9 is the same as 3 times 9, right? Because I have 1, 2, 3 groups of 9. So we know that 3 times 9 is 27. And if we went back and did the addition, we get the same result. 9 plus 9 is 18. 18 plus 9 is 27. Okay, let's look at 2 quick problems. We want to rewrite each as a multiplication problem and solve. So what I have here is I have 2 plus 2 plus 2 plus 2 plus 2. So essentially I have what? I have 1, 2, 3, 4, 5 groups of 2. So this would represent 5 times 2 if we do it using multiplication. And we know that 5 times 2 is 10. And if we go back and verify through addition, 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8, and finally 8 plus 2 is in fact 10. Okay, now we have 4 plus 4 plus 4 plus 4 plus 4 plus 4. So if I count these out, I have 1, 2, 3, 4, 5, 6 groups of 4. So this represents 6 times 4, and we know that that's equal to 24. And again, we can go through and verify this through addition. 4 plus 4 is 8, 8 plus 4 is 12, 12 plus 4 is 16, 16 plus 4 is 20, and then lastly 20 plus 4 is 24. Okay, now let's talk about a little bit of basic terminology. So numbers being multiplied together are called factors. Okay, they're called factors. Then the result of the multiplication is called the product. So if we look at 6 times 5 equals 30, 6 and 5 here are being multiplied together. So those are going to be the factors. And then 30 is the result of the multiplication process. So this is the product. Okay, the product. And a lot of times you'll hear people say 30 is the product of 6 and 5. Okay, now we have 9 times 7 times 2 equals 126. So these three numbers here are the factors for this problem. 9, 7, and 2, that's what we're multiplying together. And then 126 is the result of the multiplication. So this is the product, okay? The product. Okay, now let's talk about some properties of multiplication. And a lot of these are extremely straightforward. Some of them you've used before, you just might not have known the official name for them. So we're going to start out with the commutative property of multiplication. And essentially this just tells us that we can multiply in any order and not change the product. And we've already seen the commutative property of addition. Remember, we could add in any order and it didn't change the sum. Here, again, we can multiply in any order. We can multiply in any order and not change the product. So if you have 3 times 6, which 3 in this case is first, 6 in this case is, you can think of as last, we put this as equal to or the same as 6 going first and 3 going last. It doesn't matter how you multiply. You're going to get the same answer either way. 3 times 6 is 18, and 6 times 3 is 18 as well. Okay, as another example of the commutative property, we have 12 times 9 equals 9 times 12. And again, you can prove this to yourself. If you multiply 12 times 9, you get 108. If you multiply 9 times 12, again, you get 108. So changing the order does not affect your product. Okay, let's look at an example real quick where 3 factors are involved. So we have 7 times 5 times 4 is equal to 5 times 7 times 4, and that's also equal to 4 times 7 times 5. So the same 3 numbers are being multiplied, 7, 5, and 4. We're just changing the order around. And no matter how you do this, you'll get the same answer. 7 times 5 times 4, 7 times 5 is 35, 35 times 4 is 140. Now if I do it this way, 5 times 7 times 4, well, we already know that 5 times 7 and 7 times 5 are the same, so we know we would get 5 times 7 is 35, and then 35 times 4 is 140. And then if I do it this way, 4 times 7 times 5, well, I could do 4 times 7, that's 28, and then multiply times 5, that's also 140. So again, it's very important for you to understand that when you're doing multiplication, and there's only multiplication involved, you can do it however you want. The order is never going to matter. It's never going to change your end result. Okay, now let's talk about the associative property of multiplication. So with this property, we can group the multiplication of 3 or more numbers in any order without changing the product. Notice that where we have 6 times 3 times 1, we have parentheses here around 6 times 3. And we're saying this is equal to or the same as 6 times, and now I have parentheses around 3 times 1. So when we say grouping, we're talking about putting parentheses around different numbers. So if you just have multiplication involved, you can put parentheses around different numbers or take the parentheses away. It's not going to matter at all. You will get the same answer. So if I look at 6 times 3 times 1, where 6 times 3 is inside of parentheses, we would do this first. And I know we haven't gone through order of operations yet, but whenever you have operations inside of parentheses, you start with that. So we would do this first. 6 times 3 is 18. Then 18 times 1 is 18. And just thinking about this over here, now we have 3 times 1 inside of parentheses. So we'd start with that first. So you would have 6 times the result of this, which is 3, right? 3 times 1 is 3. And 6 times 3 is 18 as well. So either way you do it, you end up with 18 as the answer. All right, let's take a look at a few examples here. We have 4 times 2 inside of parentheses, then times 8. And we're saying this is equal to 4 times, and then we have 2 times 8 inside of parentheses. So again, you want to start out with what's inside of parentheses first. So on the left here, we have 4 times 2 inside of parentheses. That gives us 8. So we would have 8 times 8, and that equals 64. Over here on the right, I have 2 times 8 inside of parentheses. So I'd do that first. So we would have 4 times 2 times 8 is 16, and 4 times 16 is also 64. So again, changing what we had parentheses around, or changing our grouping, did not change the product. It didn't matter that we switched what we had parentheses around. We got 64 either way. All right, let's look at one last problem. We have 9 times, and then we have 7 times 5 inside of parentheses. And we're saying this is equal to, here we have 9 times 7 inside of parentheses, then times 5. So again, start with the parentheses. On the left, I have 7 times 5 inside of parentheses. So we would have 9 times 35. And 9 times 35 is 315. On the right, I have 9 times 7 inside of parentheses, so I would do that first. 9 times 7 is 63. And then times 5 is 315 as well. So again, just to kind of wrap this up, I know this is a very easy topic, but essentially, when you think about the associative property of multiplication, it's really just telling you that you can put parentheses around whatever numbers you want when you're multiplying 3 or more numbers. It will not, in any case, change the product or the result that you get from your multiplication. Okay, now we're going to talk about 2 very simple properties. The first one is going to be called the identity property of 1, and then we're going to talk about the multiplication property of 0. So the identity property of 1 states that any number multiplied by 1 remains unchanged. And I think we all know this fact, because when you think about the times tables, it's always about, okay, 1 times 1 is 1, 2 times 1 is 2, 3 times 1 is 3, 4 times 1 is 4, 5 times 1 is 5. So you kind of learn that fact immediately, because that's the easiest one to do. So when we look at 15 times 1, we know we just get 15. Or if we look at kind of some bigger numbers, what's 97 times 1? Well, it's just 97. What's 3,866,151 times 1? Well, it's just 3,866,151. So a very easy property, and a lot of times, kind of in a pre-algebra test when you're first starting out, they'll throw this in there just to kind of trip you up. Oh, hey, this is a big number. How am I going to do this multiplication without a calculator? Well, you use the simple fact that a number times 1 is just itself. Okay, so probably just as easy, the multiplication property of 0 tells us that any number multiplied by 0 gives us a result of 0. So when we start out with 30 times 0, what's the result? It's 0. When we think about 25 times 0, well, the result is 0. When we think about 2,577,313 times 0, well, the result is 0. And a lot of times they'll put this question on a test, but they won't put it straightforward like that. They'll give you these numbers that are being multiplied together. So let's say something like 14 times 10 times 5 times 0 times 30. And a lot of students will see this and they'll go, oh, how am I going to do that without a calculator? Many of them could do it, but it would just take a long time. Well, you use the fact that 0 times any number is always 0. It doesn't matter what the result of the multiplication is through here. Because whatever number that you get as a result, when you multiply it by 0, you get 0. Then when you multiply 0 times 30, you get 0. So when you see something like this where you have a lot of numbers being multiplied together, and there's only multiplication involved, and you have 0 as a factor, you know that the result of that problem is going to be 0. Okay, now let's talk about a very important property. The distributive property of multiplication tells us that multiplication is distributive over addition or subtraction. And I have as a side note here that we use this property constantly in algebra. So now is a great time to learn and understand this property, because when you get to algebra, you're literally going to use it all the time. Okay, so I'm going to explain the distributive property by looking at a few examples. So we're going to start out with 4 times, and then we have 3 plus 6 inside of a set of parentheses, or we can think about this as 4 times the quantity, okay, the quantity 3 plus 6. One of the things I'm going to draw your attention to, and this is kind of a side note, is that up to this point, most of you have only used this to imply multiplication. So if I said, what is 4 times 3? You'd probably write that problem out like this, and you'd solve it and say, okay, 4 times 3 is 12. As we move higher in math, this symbol is going to go away in terms of multiplication. You won't use that anymore. And there's a variety of different ways that we can imply multiplication, and we'll kind of get to those as we move on. But for right now, I just need you to know that when we put a number outside of parentheses, it implies multiplication. So I could write 4 times 3 like this. Okay, I have 4, and it's directly next to a 3 that's inside of parentheses. So that's why I say 4 times this quantity 3 plus 6, because 4 is next to that set of parentheses. Okay, now let's talk a little bit about the distributive property. And before I even get into that, let's think about solving this problem without using distributive property. So I know we haven't done the order of operations yet, but that tells us before we do anything else to perform operations inside of parentheses. So we have 3 plus 6 inside of parentheses. 3 plus 6 is 9. So this would be 4 times 9, or 36. Now when we use the distributive property, we have an alternative way to get this answer. So 4 times this quantity 3 plus 6. Essentially what we're going to do is we're going to take this 4 and we're going to distribute it to each number inside of the parentheses. So we would say 4 times 3 plus, okay, plus 4 times 6. 4 times 6. So you have to remember to multiply by each number inside of the parentheses, and everywhere there's a plus symbol, or in some cases it's going to be a minus symbol because this works with subtraction too, you have to write that. Okay, you can't skip that over. Now, if we go through and we solve this, we're going to do the multiplication first because that's what the order of operations tells us. So we're going to treat these as separate problems before we add. So 4 times 3 is 12. Then plus 4 times 6, which is 24. So 12 plus 24 is also 36. So either way, we're getting the same result. Okay, 36 either way. Now I'm going to erase all of this real quick. And we're just going to rewrite this. And then I'm going to kind of do this a long way. So 4 times 3 plus 4 times 6. And you can leave it like this, or you can put parentheses around this like this. It won't change your answer if you know the order of operations. I just put the parentheses around it so that you know to do 4 times 3 separately from 4 times 6. I don't want you to get confused at this point. Now, if I think about the addition problem that we did earlier, 9 plus 9 plus 9. This is 3 groups of 9, so we said this is 3 times 9. If I apply that same logic here, I have 4 groups. I have 4 groups of 3 plus 6. So what does this translate to? 3 plus 6 plus 3 plus 6 plus 3 plus 6 plus 3 plus 6. Now, I know that the associative property and the commutative property allow me to reorder and regroup this addition however I want. So what I'm going to do is I'm going to write inside of parentheses 3 plus 3 plus 3 plus 3. I have 1, 2, 3, 4 of those. Then plus, inside of another set of parentheses, I'm going to put the 6's. So I have 1, 2, 3, 4 of those. So 6 plus 6 plus 6 plus 6. Now, if I look at it this way, it is clear to me how I arrived at this result. I have 1, 2, 3, 4 groups of 3, which is known as 4 times 3. I have 1, 2, 3, 4 groups of 6, which is 4 times 6. So you can see that this directly matches this. Using the distributive property was just a shorter way to get there, right? Because I know in the end I'm going to have 4 groups of 3, and I'm going to add to that 4 groups of 6. All right, let's look at another one, and we won't go through that long, tedious process again. We have 7 times the quantity 9 plus 2. So we're going to do this 2 different ways. We're going to do it the first way where we do 9 plus 2 first, because that's what's inside of parentheses. So this is 7 times 11, and that's 77. And then let's do it using the distributive property. So remember, I have 7 groups of 9, or 7 times 9, plus I have 7 groups of 2, or 7 times 2. And I'm going to put parentheses around each here so we know to do that first before we add. And again, you won't need that, but we haven't done the order of operations yet, so I don't want to confuse you. So 7 times 9 is 63. And then plus 7 times 2, that's 14. And so 63 plus 14 is 77. So either way, using distributive property or adding what's inside of parentheses first, we get 77. Okay, now let's look at one that involves subtraction, because this does also work with subtraction. So we have 8 times the quantity 4 minus 3. So working inside of parentheses first, I'd get 1. 4 minus 3 is 1. So we'd have 8 times 1, and that just equals 8. If I use the distributive property, again, I want to distribute this. So 8 times 4, 8 times 4, and then we're subtracting 8 times 3. 8 times 3. So again, I'm going to put parentheses around the multiplication problem so that you don't get confused. All right, so 8 times 4 is 32. And then we're subtracting away 8 times 3, which is 24. And 32 minus 24 is 8. So again, either way, we get the same result. Okay, let's take a look at one last problem. So we have 5 times the quantity 9 minus 4. Again, doing this where we do 9 minus 4 first. 9 minus 4 is 5. You'd have 5 times 5. That is 25. Using the distributive property, we're going to distribute the 5. So 5 times 9. 5 times 9. Then subtract away 5 times 4. 5 times 4. And again, I am going to put these multiplication operations inside of parentheses just so that you don't get confused. And when we get to the order of operations, which will be a few lessons from now, you'll learn that you need to perform multiplication before subtraction. But for right now, we know that we got to perform operations inside of parentheses first. So let's just put the parentheses around it and work with that rule. So 5 times 9 is 45. Then minus 5 times 4, that's 20. And then we do this subtraction, 45 minus 20 is 25. So again, either way, we get the same result, either by doing what's inside of the parentheses first, or by using our distributive property, where we distribute our multiplication to each number inside of the parentheses. Hello and welcome to Pre-Algebra Lesson 11. And in this video, we're going to learn about vertical multiplication. So for the lesson objective, we want to learn how to multiply multi-digit numbers together. Okay, so up to this lesson, we have reviewed how to do addition of whole numbers and how to do subtraction of whole numbers. And we saw that when we needed to add multi-digit numbers or when we needed to subtract multi-digit numbers, we did it in a vertical format. Now, the same is going to be true when we think about multiplying whole numbers. Now, before we dig into that, I just want to make you aware that in order to be successful with vertical multiplication, you have to, at minimum, know your times tables. And those are the tables that you learned back in elementary school, where you memorized, 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3, so on and so forth. You need to at least know up through 9 times 9. So if you haven't memorized that, you probably need to go back, make some flashcards, and memorize that so that you can be successful with vertical multiplication. So essentially, you can think about it this way. What do we do when we want to multiply large numbers together? Are we really expected to memorize the multiplication for every number that we may come across? Well, no, of course not. When we multiply multi-digit numbers together, we use a process called vertical multiplication. All right, so I prefer to teach through examples, so let's start out by just looking at 26 times 6. Now, with vertical multiplication, it's going to be the same as vertical addition or vertical subtraction, where we want to stack the numbers on top of each other and line them up by place value. Now, you recall with addition, it didn't matter what went on the top and what went on the bottom, but it was easier, or I would say more common also, to put the number with more digits on top and the number with fewer digits on the bottom. That's going to be the same thing with multiplication. Multiplication is commutative. I can do 26 times 6, or I can do 6 times 26. I get the same answer. It will make your life easier if you take the number with more digits, which in this case is 26, and you put it on top. So I'm going to put 26 on top, and I'm going to put 6 on the bottom. Okay. Now, just like with vertical addition, we want to draw a horizontal line underneath the bottom number, and we want to put an operator symbol, which in this case is the multiplication symbol, out to the left of the bottom number. So performing this operation is very, very simple, and once you've practiced it enough, it'll be very, very easy for you. Okay, so to begin our vertical multiplication, we're going to start with the rightmost digit of the bottom number, and we're going to multiply by the rightmost digit of the top number, and we're going to continue working right to left. So we would begin by doing 6 times 6, and we know that equals 36, but 36 is too big to put in the ones place for the answer, so we're going to do a thing called carrying, which is similar to what we did with addition, but with a slight twist. So this part is the same. You take the rightmost digit, which is a 6, and you write it into the answer column. So I'm going to write a 6 right there. I'm going to then take the left digit, which is a 3, and I'm going to write that in the next column to the left. Okay, so it's going in the tens column. If you think about 36, again, thinking about place value, this is 30 plus 6. So all I've done is said that, hey, we have 6 ones, and I take 3 tens and I put it into the tens column. So that's why that's a 3 there. Again, that's 3 tens. Now, it's important to understand that that's 3 tens. This is 30, because that 30 is going to be added to the result of the next multiplication that we do. It's not going to be multiplied. We will simply add it on to the answer that we get. So now we're going to move to the left, and we're going to do 6 times 2. So 6 times 2, And once we have our result, we're going to tack that 3 on. So plus 3. Okay, so 6 times 2 plus 3. So 6 times 2 is 12. And then if we add 3 to that, we get 15. We get 15. So we're going to write that into our answer. We would write a 5. And normally we carry a 1, but there's nothing else over here. So that 1 can just be written right there. So we get an answer of 156. And really, it's just that simple. So if I think about 6 times, I'm going to break 26 up into 20 plus 6. So if I think about this using the distributive property, I'd have 6 times 20, 6 times 20, then plus, I'd have 6 times 6, 6 times 6. This right here is exactly what we did here. And I'm going to show you that in a second. So I'm going to use some parentheses here to separate my multiplication operations from this addition. And you normally do not have to do that, but we at this point have not studied the order of operations. So I want it to be clear that we're going to do 6 times 20, and then 6 times 6, and then add the results. I don't want you to get confused on what operations we're doing. So 6 times 20 is 120, plus 6 times 6, that's 36. And when we add here, we get 156, which is the same thing that we got there. So looking at this, we can basically see that this over here, this vertical multiplication, is just a condensed version of the distributive property. That's all it is. I started out by doing 6 times 6. That's right here. 6 times 6 gave me 36. Then I did 6 times 20. It looks like 6 times 2, but that 2 is in the tens place, so it's really a 20. So I did 6 times 20, and that gave me 120. Now, I added 120 and 36, and I got 156. The only thing that's a little different here is we had to carry a 3 because we couldn't fit the 3 in the ones place. But essentially all I did was I said 6 times 20 is 120, plus this 3 here, which was really a 30, plus the 6, which was the number from the ones place when we did 6 times 6, right? That 36 right there. So plus 6, and that still gives us 156. So just letting you see this in a different light. Essentially, the vertical multiplication process that we use is just a condensed version of the distributive property. That's all it is. Okay, let's look at another one. So we're going to look at 613 times 5. So again, I'm going to take 613, and I'm going to put that on top because it has more digits. And then I'm going to put 5 on the bottom. And we multiply from right to left. So I start out with this digit on the right, and soon you'll have digits over here too. So you start out on the right, and you multiply by the rightmost digit of that top number. So we're doing 3 times 5. So 3 times 5 equals 15. So I'm going to take the 5 and put it down, and then I'm going to carry this 1. Now remember, I'm not going to multiply the 1. I'm going to only use that 1 once I'm done with the multiplication. So now I'm going to multiply 5 times the 1 there. So 5 times 1. And then when I'm done with that, I'm going to add this 1. I'm going to add that 1. So 5 times 1 is 5. Then plus 1 is 6. Okay. And again, think about what you're saying here. This 5 has a value of 5. This 1 has a value of 10 because it's in the tens place. So 5 times 10 is 50. And then I'm adding another 10. That's a 1 in the tens place. Then I'm adding another 10 to get to 60. So I have a 6. That's in the tens place. That's a 60. So that's what we just did. Now the last thing I'm going to do is I'm going to multiply 5 times 6. And that gives me 30. 5 times 6 equals 30. Now normally I'd have to put the 0 down and carry the 3. But there's nothing else over here. So I can just write that 3 there. I end up with 3065 as my answer. All right, for the next problem, we have 1,752 times 8. Again, I'm going to take this number here, this 1,752, and I'm going to put that on top, and I'm going to put 8 on the bottom. Again, you could reverse that if you chose to. I just find this to be a little easier. So we're going to begin by taking the rightmost digit of the bottom number, which in this case it's just an 8, so that's all there is, and multiplying that by the rightmost digit of the top number. So we're going to do 2 times 8 to begin, and that is 16. So for 16, we're going to need a carry. So I put a 6 down, and I carry a 1 into the next column. And remember, that's not going to be multiplied. That's going to be added after we do our multiplication. So we're working our way left. Now we're multiplying 8 times 5. So 8 times 5, And then once we're done with that, we're going to add this 1 in. We're going to add this 1 in. We're basically saying, hey, whatever you get, add 10 to that, because that 1's in the tens place. Add 10 to that. All right, so 8 times 5 is 40. Then plus 1 is 41. So I need to carry again. I'm going to take the 1, the rightmost digit, and I'm going to write that there. And I'm going to carry the 4, the leftmost digit, into the next column. Now we're ready to multiply in the next column. 8 times 7 is what we're doing next. So we'd have 8 times 7, then plus what we carried over. That 4 is in the hundreds place, so I'm saying, hey, whatever you get for the result here, I want you to add 400 to it. Okay? So I'm just writing this as a 4 because it's in the hundreds place. So 8 times 7 is 56, plus 4 is 60. Again, we need to carry. So I'm going to take this 0, I'm going to put that in the answer column, and I'm going to carry the 6 into the next column to the left. And we have one more multiplication left to do. Okay, so now we want to do 8 times 1. So 8 times 1. And we're going to add to that the 6 that we carried over. So again, whatever we get for this, we're adding 6 more. And that 6 is in the thousands place, so we're basically tacking on another 6,000 to that answer. So 8 times 1 is 8, then plus 6, it's 14. Now, because there's no more numbers to the left, I can just write 14 into my answer. So we get 14,016 as our result. All right, let's take a look at another easy one. So we have 15,319 times 7. And again, I put the number with more digits on top, the number with fewer digits on the bottom. And let's just crank this out. We're going to start at the rightmost digit. In this case, it's just a 7 of the bottom number. We're going to multiply it by the rightmost digit of the top number, and we're working our way to the left. So 7 times 9 is 63. So I would put a 3 down, and I would carry a 6 into the next column. Next, I would do 7 times 1. 7 times 1 is 7, then plus 6 is 13. So I'd put a 3 down, and I'd carry a 1. Then I'd have 7 times 3, that's 21. Then plus 1, that's 22. So I'd put a 2 down and carry a 2. Now I have 7 times 5, that's 35. Then plus 2, that's 37. So I'd put a 7 down and I'd carry a 3. And lastly, I have 7 times 1, that's 7. Then plus 3, that's 10. So I just write a 10 here. And we end up with 107,233. Okay, so up to this point, it's been pretty easy. And the reason for that is the number on the bottom has been a single-digit number. When we start multiplying a multi-digit number by another multi-digit number, the work gets more tedious. So let's start out by thinking about 315 times 12. So again, I'm going to write the number with more digits on top and the number with fewer digits on the bottom. And again, I want to start out at the rightmost digit of the bottom number and multiply it by the rightmost digit of the top number. So 2 times 5 would give me 10. Now, I'm going to put a 0 down, and I'm going to carry a 1. Next, I'm moving to the left. So I'm doing 2 times 1. So 2 times 1 is 2, then add 1, so that's 3. Okay, working my way to the left. Now I have 2 times 3. 2 times 3 is 6. So the result here is 630. But I'm not done. Okay, I'm not done. I still have this other number over here to the left. And there's something that you have to do when that occurs. If you move to the left to multiply, you have to move to the left when you start your answer. So we're going on a whole nother row here, a whole nother row, and we're starting right here, okay, right here. And the reason we're doing that is because this 1 is not a 1. It's actually a 10, because again, it's in the tens place. So what I'm doing is I'm multiplying 10 times 5, and I'm getting 50. So I would write 50 by putting a 5 in the tens place, okay, by putting a 5 in the tens place. If I was to just multiply 1 times 5 and put 5 here, I didn't get the right answer, because this isn't a 1, it's a 10. So I really need to do 10 times 5. So to correct for that, we just move 1 place to the left, and we start our answer in the tens place. So let's begin there. So we're going to do 1 times 5. 1 times 5, as I just said, is 5. Now we move to the left. I'm going to do 1 times 1, and that's 1. And we move to the left one final time. We're going to do 1 times 3, and 1 times 3 is 3. Now you might say, what are we going to do now? Well, essentially, this 630 and this, what looks like 315, it's really 3,150 because of where it's positioned. Those are called partial products, okay? Partial products. What we actually have to do is we have to find the sum of these two rows to get the product for 315 times 12. This 0 here can either come down or you can write a 0 in. It doesn't really matter. So 0 plus 0 is 0. Then 3 plus 5 is 8. Then 6 plus 1 is 7. And then you can just bring that 3 down to get 3,780. So again, if we want to just think about this a little further, again, use the distributive property. Take this number 315 and multiply it by 10 plus 2, that quantity. Again, this is 12. I just broke it up. So doing this, we'd have 315 times 10, 315 times 10, plus 315 times 2. 315 times 2. And that's exactly what we just did here. We did the rightmost digit of this bottom number, 2 times 315. The result of that was 630. So if I think about this, I would have plus 630 over here. And we also did 315 times 10. Because this 1 is in the tens place, I multiplied 10 times 315, and that gave us 3,150. 3,150. So then we did some addition, just like we did over here. 3,150 plus 630, which gives us 3,780. Okay, let's try another one. So we have 765 times 23. So 765, I'm going to put that on top, times 23. I'm going to put that on the bottom. So again, we start out at the rightmost digit of the bottom number, and we multiply it by the rightmost digit of the top number, and we're just going to work left. So 3 times 5 is 15. Put a 5 down, carry a 1. 3 times 6 is 18, plus the 1 that we carried is 19. I'm going to put a 9 down and carry the 1. 3 times 7 is 21, plus the 1 that we carried is 22. And again, I can just write 22 because there's no more numbers out here. Now, we're going to the left in the bottom number. We have to remember to start our answer to the left right here. Because again, this isn't a 2 times 5, this is a 20 times 5. So I've got to start my answer right there. So then 2 times 5 is 10. So I'm going to put a 0 down, and I'm going to carry a 1. 2 times 6 is 12, plus the 1 I carried is 13. Put a 3 down, carry a 1. 2 times 7 is 14, plus 1 is 15. And because I don't have any more numbers out here, I can just write 15. Now, really, because of where this 0 starts, this number is 15,300. I can put a 0 in there if I want, or I can leave it out. It doesn't really matter. We're going to do some addition. So we add these two partial products up. Again, 2,295 is the result of doing 3 times 765. And then 15,300 is a result of doing 20. Again, that 2 is in the tens place, so it's a 20 times 765. So we find the sum here. 5 plus 0 is 5. 9 plus 0 is 9. 2 plus 3 is 5. 2 plus 5 is 7. And then this 1 can just come down. And we end up with 17,595. Okay, let's look at one final problem. And as your numbers get larger, your work doesn't get harder, it gets more tedious. And you have to pay very close attention to what you're doing because it becomes very easy to make a mistake, especially if you're on like your 11th or 12th problem and you're just exhausted. You'll start making these mental mistakes. So you have to pay close attention to what you're doing. Okay, so 212,050 times 1,075. I'm going to take this number, 212,050, and I'm going to put that on top. And I'm going to take 1,075 and I'm going to put that on the bottom. Okay, so again, we start out the rightmost digit of the bottom number times the rightmost digit of the top number, and we're just working our way to the left. So we're going to have 5 times 0. So 5 times 0 is 0. Then we're going to have 5 times 5. 5 times 5 is 25. So I'm putting a 5 down, and I am carrying a 2 into the next column. Now I have 5 times 0. That is 0, plus 2 is 2. Now I have 5 times 2. That is 10. So I'm going to put a 0 down, and I'm going to carry a 1. Now I have 5 times 1. That's 5, plus 1 is 6. Lastly, I have 5 times 2. That's 10. No more numbers out here, so I can just write that in. I'll go through and put some commas. So that's 1,060,250. And that's basically the result of 5 times 212,050. Okay, now we're moving to the left. So what happens when I move to the left? I've got to move to the left where I start my answer. Again, this is not a 7, it's a 70. Okay, it's a 70. So we're going to start out with 7 times 0. 7 times 0 is 0. 7 times 5 is 35. So I put a 5 down, I carry a 3. 7 times 0 is 0, plus 3 is 3. Then 7 times 2 is 14. So I'm going to put a 4 down, and I'm going to carry a 1. Now I have 7 times 1, that's 7, plus 1 is 8. And then lastly, I have 7 times 2, and that is 14. Okay, put in the commas. So I get 14,843,500. You might be saying, well, there's no 0 over here. Well, because I started this over here, there's really a 0 here. There's really a 0 there. But when we add, we don't have to put the 0 in because this can come just straight down and you're going to get the same answer. So I'm going to go ahead and just write a 0 there just so it's not confusing for you. Okay, so now we're going to continue, and we're moving left again. So I'm moving left, and when I do that, I've got to move left. So I'm not going to start in the tens anymore. I'm going to have to start in the hundreds. I'm going to have to start in the hundreds. And the reason for that is I'm starting in the hundreds here. So a lot of people like to just put the zeros in. You can do that and start your answer there. Or again, just as I told you, you can leave it blank. Let's go ahead and put the zeros in so that you're not confused. All right, so we're going to start with 0 times 0. That is 0. 0 times 5. That is 0. 0 times 0. That is 0. So you're starting to notice something. If you have a 0 and you're doing your multiplication, this whole row here will be 0. So essentially, I'm just going to include 1 0 there just so I can maintain my place. I don't really need to write anything else because if I add 0 when I'm doing the addition, it's not going to change the value of the number. So I'm just going to move to the left, and look at this 1 here. So now I've got to start my answer here in the thousands place. Okay, I've moved all the way to the thousands place. Notice how this 1 is in the thousands place. Okay, let's start. So we have 1 times 0, that's 0. We have 1 times 5, that's 5. We have 1 times 0, that's 0. We have 1 times 2, that's 2. We have 1 times 1, that's 1. And we have 1 times 2, that's 2. And another cool trick you can think about is if you're multiplying 1 times this, it's just going to be itself. Remember, 1 times anything leaves it unchanged. So I could have just wrote 212,050 and been done with it. As long as I know where to start, that's the important part. So if I want to, I can go ahead and write 3 zeros here, just so that we don't get confused. Okay, so we're going to go ahead and add. Let me make these zeros a little better so that they line up. So I'm going to come straight down. I have a 0 everywhere, and I can put zeros in here if I want. It doesn't matter. This is just 0 in the end. So coming straight down, I have a 0. Then I have 5 plus 0 plus 0 plus 0, that's 5. Then I have 2 plus 5, that's 7. Then plus 0, that's 7. Then I have 0 plus 3 plus 0 plus 0, that's 3. Then I have 6 plus 4, that's 10. Plus 0 is still 10. Plus 5 is 15. So put a 5 down, carry the 1. Now we have 1 plus 0, which is 1, plus 8, which is 9, plus 0, which is still 9. Then I have 1 plus 4, which is 5, plus 0, which is still 5, plus 2, which is 7. Then I have 1 plus 0, which is 1, plus 1, which is 2, and then I can just bring this 2 down. and I end up with 227,953,750. Hello and welcome to Pre-Algebra Lesson 12. And in this video, we're going to learn about multiplication with trailing zeros. So our lesson objective is just to learn how to multiply numbers with trailing zeros. And you might be asking yourself, what in the world is a trailing zero? Well, a trailing zero is just a zero at the end of the number, or you might say trailing zeros if there's multiple zeros at the end of a number. So let's take the number 600. 600 has two zeros at the very end of it, so this number has two trailing zeros. Or you could look at the number 17,000. This number has three zeros at the end of it, so it has three trailing zeros. Where people get confused is you might have a number like, I don't know, let's say 104,030. This number has three zeros in it, but they're not all trailing zeros. You're only looking at zeros at the end of the number. It can't be interrupted by something that's not zero. So this one right here at the very end, that's a trailing zero. But because there's a 3 here, you can't say that this is a trailing zero also. Yeah, it's close to the end of the number, but it's not at the end. It's interrupted by this 3 here. So this number would have one trailing zero. Let's think a little bit about a simple multiplication fact that you might not have ever thought of. When you multiply, let's say something like 5 times 10, we know that this is 50. But another way to attain this result is to multiply the non-zero parts, so 5 times 1, that would give you 5, and then just attach the trailing zero to the end of the result. So in other words, I can do 5 times 1, and then I can attach a 0 to the end. That would give me 50, and I would have the result for 5 times 10. And this works no matter how large your numbers are. Let's say I would have said, what is 5 times 100? Well, now I would do 5 times 1, that's 5, and then I would attach 2 zeros to the end. 2 zeros to the end to get 500. Let's say I did 5 times 10,000. I'd do 5 times 1, that's 5, and I'd attach 1, 2, 3, 4 zeros to the end. 1, 2, 3, 4 zeros, and I'd get 50,000. Okay? So it's a simple multiplication fact, but once we learn it and understand how to use it, it can greatly speed up our multiplication. You'll come across a lot of problems with trailing zeros, and you might not have a calculator to use. So this is a trick that can speed you up significantly. So just to look at the official procedure, essentially you just want to leave off any trailing zeros and multiply the numbers that result. And then next you want to attach the total number of trailing zeros, and this is between all factors, to the right of your product. So again, super easy to do. Let's just look at some examples. All right, so let's start out with 3 times 60. So we want to multiply and leave off the trailing 0 in this case. What would 3 times 6 be? That's 18. And then all we need to do is attach the total number of trailing zeros between all factors, in this case just 1, to the end of that number. So we end up with 180, and of course that's correct. 3 times 60 is 180. What about 17 times 1,000? Well, we'd multiply 17 times 1, right? You would leave this part off. These are the trailing zeros. 17 times 1 is 17. And then you would just attach them to the end of the number. I have 1, 2, 3 trailing zeros. So I write 1, 2, 3 zeros there. And so 17 times 1,000 is 17,000. All right, let's look at an example where both numbers have trailing zeros. Here we have 70 times 300. So 70 has one trailing zero. 300 has two trailing zeros. And essentially just leave those off. Leave those off. And you would do 7 times 3. 7 times 3 is 21. And then I'm going to attach 1, 2, 3 zeros to the end, because that's how many trailing zeros there are between all the factors. So 1, 2, 3 trailing zeros are attached. And so 70 times 300 is 21,000. Okay, what about 153 times 9,000? So a lot of us cannot do 153 times 9 in our head. I'm going to do 153 times 9 in vertical multiplication format. And then when I'm done, I'm going to take this result, bring it up here, and attach 3 zeros to it. All right, so 9 times 3 is 27. Put a 7 down, carry the 2. 9 times 5 is 45. Plus 2 is 47. put a 7 down, carry the 4. 9 times 1 is 9, plus 4 is 13. So I get 1,377. So 1,377. And I'm just going to attach 3 zeros to the end of that. 1, 2, 3, comma, comma. And so our result is 1,377,000. Okay, let's look at another one. We have 216,000 times 108,000. So we have 3 trailing zeros here, and we have 3 trailing zeros here. So I'm just going to multiply 216 times 108. 216 times 108. And when I'm done, I'm going to attach 1, 2, 3, 4, 5, 6 zeros to the end of whatever the result is from that. So 8 times 6 is 48. Put an 8 down, carry a 4. 8 times 1 is 8, plus 4 is 12. Put a 2 down, carry a 1. 8 times 2 is 16, plus 1 is 17. 0 times 216 is 0. So I can put a 0 here, or I can leave it off. Doesn't really matter. I'm just going to leave it off. And next we move to this 1 here. I have 1 times 216. Remember, the 1 is in the hundreds place, so I have to start my answer in the hundreds place. And 1 times anything is just itself. So 1 times 6 is 6, 1 times 1 is 1, and then 1 times 2 is 2. So we find our sum, bring down the 8, bring down the 2, 7 plus 6 is 13, put a 3 down and carry the 1, 1 plus 1 is 2, 2 plus 1 is 3, and then bring down this 2, and we get 23,328. Now, I'm going to bring this guy up here, 23,328. And I'm going to attach 6 zeros to it. So let me actually write it a little bit lower. 23,328. 1, 2, 3, 4, 5, 6. So this is our answer for 216,000 times 108,000. We get the result of 23,328,000,000. For the final problem, we have 5,300,000 times 1,615,000. So I just need to do 53 times 1,615. Right? These trailing zeros I'm going to cut off, and I'm going to cut these off as well. We have a total of 1, 2, 3, 4, 5, 6, 7, 8 between the factors. So 8 zeros. So I want to do 1,615 times 53. 3 times 5 is 15. Put a 5 down, carry the 1. 3 times 1 is 3, plus 1 is 4. 3 times 6 is 18. Put an 8 down, carry the 1. 3 times 1 is 3, plus 1 is 4. Okay, now we're moving left to the 5. Remember, the 5 is in the tens place, so we start our answer here. 5 times 5 is 25. Put a 5 down, carry the 2. 5 times 1 is 5, plus 2 is 7. 5 times 6 is 30. Put a 0 down, carry the 3. 5 times 1 is 5, plus 3 is 8. And now we add. Bring down the 5. 4 plus 5 is 9. 8 plus 7 is 15. Put a 5 down, carry the 1. 1 plus 4 is 5. Bring down the 8. We get 85,595. So now we're going to take this result here, 85,595, and we're going to attach to the end of that 8 trailing zeros, right? Because that's what we had between the factors. So 1, 2, 3, 4, 5, 6, 7, 8, comma, 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 comma. So we end up with 8,559,500,000,000 as the answer. Hello and welcome to Pre-Algebra Lesson 13. And in this video, we're going to talk about the properties of division. Okay, so for our lesson objectives, we want to learn how to identify the parts of a division problem. We want to learn the properties of division. And also we want to learn how to solve division problems with remainders. Okay, so let's begin our lesson by thinking a little bit about what happens when we divide one whole number by another. And I'm going to start by just taking a look at 6 divided by 3. And you'll see I have an illustration that I drew. And it's a very simple illustration, but it'll get the point across. Basically, I have 6 boxes here. Let's label them 1, 2, 3, 4, 5, and then 6. And if you look at the division problem, 6 divided by 3, this amount on the left, 6, is what we start with, We have this 6, and that's what I have in the illustration. I have 6 items, 6 boxes, however you want to think about it. Then we're dividing by 3, okay? What does it mean when you say the word divide? It means you're cutting something up or you're splitting it up. So to divide by 3 means I'm going to ask the question, how many equal groups of 3 can I make out of this number 6? That's all 6 divided by 3 is saying. If I just look at the illustration, it's very easy to see that I'd have 1, 2, 3. So this would be one group. And then you could say 4, 5, 6. We know that's 3. I could erase this and make it more clear by saying, okay, this is another group of 1, 2, and then 3. So we would end up with 2 equal groups of 3 that can be made out of the number 6. So then 6 divided by 3 is equal to 2. Now, another way you can think about this is by using subtraction. So I could take and count how many times we can subtract 3 away from 6 until the result is 0. Okay? So if I started with 6 and I said, okay, I'm going to subtract away 3, what's the result? Well, it's going to be 3. Okay, so now I'm going to take 3 and subtract away another group of 3, and now the result is 0. So I was able to do this twice. So again, that tells me that 6 divided by 3 is 2. Now, I want you to look at how closely division and multiplication are related to each other. Forget about the fact that we have a problem 6 divided by 3. So let's just look at this and think back to multiplication. When we saw this, we had 1, 2 groups of 3. So what is that? That's basically 3 plus 3, or 2 times 3. And we know this equals 6. Well, if I kind of look at 2 times 3 equals 6, and 6 divided by 3 equals 2, I kind of see a little pattern that's going on here. And I'm going to show you that pattern real quick. So if I have 6 divided by 3 equals 2, then that means that this number right here, the result, which we're going to learn later on is called the quotient, times this right here, the 3, which we're going to learn later on is called the divisor, should give me this back, this 6, which we're going to learn later on is called the dividend. So if 6 divided by 3 equals 2, then that means that 2 times 3 equals 6. You can kind of think about this as going backwards. Right? I take this number and I go this way. So we'd have 2 times 3 now, and that should equal 6. And you can use this to solve a lot of basic division problems. If I have something like, I don't know, let's say 15 divided by 3. What does that equal? Or how would I figure that out? Well, I could say, well, what number times 3 equals 15? Right? What number times 3 equals 15? Well, we know our times tables pretty well at this point. We know that 5 times 3 equals 15. So the answer to 15 divided by 3 would be 5. And you can check this by using the subtraction method that I just did, or you could draw out 15 boxes and you could split them up into equal groups of 3. You're going to see either way that you get 5 as a result. Okay, let's take a look at another one. So here we have 8 divided by 2. And I'm just going to do the same thing basically. I have made another illustration here, and we have 1, 2, 3, 4, 5, 6, 7, 8. What are we asking for when we say 8 divided by 2? Again, it's how many equal groups of 2 can be made from the number 8. Well, and I'm just going to go ahead and relabel this. And I know I keep doing that, but I'm just trying to make things clear. So here's 1, 2. That's one group. Here's 1, 2. That's another group. Here's 1, 2. That's a third group. Here's 1, 2. That's a fourth and final group. So we have one group of 2, second group of 2, third group of 2, and a fourth and final group of 2. So that tells me that 8 divided by 2 is equal to 4. And again, if I want to use subtraction, I can do it that way as well. So I can say, okay, how many times can I subtract 2 away from 8 before the result is 0? So 8 minus 2 would give me 6. Then 6 minus 2 would give me 4. Then 4 minus 2 would give me 2. And then 2 minus 2 would give me 0. So you can see I did 1, 2, 3, 4 operations to get that. So the answer would be 4. And then lastly, probably the method you're going to use most often until you have everything memorized, you would say, okay, 8 divided by 2 equals what? Okay, equals what? Well, remember, I can go backwards. I can say, what times 2 equals 8, right? Go backwards. What times 2 equals 8? Again, we know our times tables by heart at this point, so we know that this answer would be 4, right? We know this answer would be 4. 4 times 2 gives us 8. Okay, so now that we've talked a little bit about the basics for dividing whole numbers, let's talk a little bit about some terminology. So there are 3 parts to a division problem. The first part, the leftmost number, the number that we're going to split up or cut up, is called the dividend. Okay? Again, that's the left number. This is the number that is being divided or split into equal groups. So when we looked at 6 divided by 3 equals 2, 6 was the dividend. Okay, 6 was the dividend. Okay, the next part of a division problem is called the divisor. And this is the number we are dividing by. So where 6 divided by 3 equals 2, this 3 is the divisor. This is the divisor. And then lastly, you have a quotient. So this is the result of the division operation. So in this case, it would be 2, right? Because 6 divided by 3 gives us a result of 2. So that is the quotient. Okay, so let's do a real quick exercise. We want to label the parts of each division problem. So we have 10 divided by 5 equals 2. So 10, the number on the left, the number or the amount that we start with, is called the dividend. This is the dividend. 5, the amount that we're dividing by, is called the divisor. And then 2, the result of the division operation, again, is called the quotient. This is the quotient. Okay, here we have 20 divided by 10 equals 2. Again, this number on the left, this 20, the amount we start with, is the dividend. Then we're dividing by 10, so that's your divisor. And then lastly, the result from this division is 2, so that is your quotient. Okay, let's talk about a few important properties of division. The first thing is that division is not commutative, meaning the order is important when you divide. And we've seen this before with subtraction. We saw that when we subtracted, when we did 6 minus 3, it was not equal to 3 minus 6, right? Those did not produce the same result. So with division, if I do 6 divided by 3, I will not get the same result if I flip this and put 3 divided by 6. The order does matter when you divide. Okay, the next fact is that 0 divided by any non-zero number is always 0. We're going to cover why I said non-zero in a second. But if I have 0 divided by whatever it is, as long as it's not 0, I'm going to get 0 as a result. So let's say it's 17. And think about why that's the case. Remember, if I go this way and make a related multiplication statement, 0 times 17 equals what? It equals 0, because 0 times any number is always 0. Okay, so this is a very important rule that you need to remember. We can never divide by 0, ever. When we see a problem and 0 is the divisor, we write the answer as undefined. Undefined. So, for example, if I were to write a problem like 6 divided by 0, you don't try to solve that. You just say it's undefined. Undefined. That's all you need to put next to it. And you might think a little bit about why this is the case, and I don't want to get into algebra or anything like that, but just think about the fact that if you have 6 divided by 0, it equals what? Just try to come up with a solution there. Well, do the related multiplication. So something times 0 equals 6. Well, you come across a bit of a conundrum there because we know that when we multiply by 0, we get 0. So what number can you think of that when you multiply by 0 produces 6? You can't find any. So this is why we just say that it's undefined. We just stop because we end up with sort of nonsensical statements like this. All right, the next thing is when we divide a number by itself, the result is 1. And I put except 0. Okay, you can't divide 0 by itself because you can't divide by 0. So if I have something like, I don't know, let's do an easy one. Let's say 4 divided by 4, this is 1. And think about why that's the case. How many equal groups of 4 can I make out of 4? Well, only 1, right? If I were to draw 1, 2, 3, 4 boxes, well, I can only make one group of 4. And it's the same no matter what you do. If I was to say 132 divided by 132, I'd still get 1. Because if I drew out 132 boxes, and I said, well, how many equal groups of 132 can I get out of that? Well, just 1. Right? So that works for any number as long as it's not 0. Okay, so another important rule. When we divide a number by 1, okay, by 1, the result is itself. So, for example, let's say you have 5 divided by 1, you get 5. Okay, 5 divided by 1, you get 5. And think about that in terms of the related multiplication statement. If you think about the 5 there, just say question mark, what times 1 equals 5? Okay, what times 1 equals 5? Well, we know the answer to that is 5. And another way to think about it is, again, using your groups. So if I have 5 of something, let's say they're boxes, and I split it up into equal groups of 1, well, I'm always going to get that number back. So 1, 2, 3, 4, 5, right? And that works with any number. And you can even use that one with 0 because you can divide 0 by a number. I could divide 0 by 1. There's no problem there. 0 divided by 1 just equals 0. I just can't divide by 0. Okay, now let's talk a little bit about division problems where you have a remainder. So this basically means that you're going to have some amount left over. And the way we talk about remainders when we're in grammar school is different from how we're going to talk about it when we kind of move forward in math and we're using, calculators and we've learned how to work with fractions and decimals and so on and so forth. So what is 7 divided by 3? Well, I have an illustration here with 7 boxes. And think about splitting up the 7 boxes into equal groups of 3. What do you get? Well, I can see clearly this is 1, 2, 3 here. Here's 1, 2, 3. So those are 2 groups. But I have this 1 over here, and I have nothing else to kind of pair with it to make another group. So that's a leftover amount. I can't do anything with it. That's considered a remainder. So the answer for 7 divided by 3 would be 2 with a remainder of 1. Okay? 2 with a remainder of 1. And when we check our division and you have a remainder, you have to do it a little bit differently. So now I'm going to multiply this part right here, which is still called the quotient. Okay? Still called their quotient. But then when I'm done, so I'll do 2 times 3, 2 times 3. And once I'm done with that operation, I add my remainder to get back to the original number, the dividend. Okay? So 2 times 3 plus 1 would give me 7. So a little bit different to check when you have a remainder involved. So another way, again, to think about this would be to use subtraction. And if we wanted to subtract, we would do 7 minus 3. This would kind of be the first time. That would give us 4. Then the second time we would do 4 minus 3, and that would leave us at 1. Now I can't subtract another 3 away. In other words, if I do 1 minus 3, I'm going to end up with a negative value, which I know we haven't talked about yet, but basically I'm going to pass 0. So I don't want to do that. I wanted to stop when I got to 0. So we're going to have to stop here at 1. So that's my remainder. That's my remainder. Okay, so before I move on, I want to talk a little bit real quick about the difference you might see when you do this on a calculator. So all of us have done division on a calculator. So you punch in 7 divided by 3, and you get something that says something like 2.3333. And basically this 3 is going to repeat forever. So I'm just going to stop right there. I'm going to put 1, 2, 3 dots. This repeats forever. when we did our division, we said that the answer was 2 with a remainder of 1. So what gives? Why is there a discrepancy in the answer? Well, we haven't gotten to fractions yet. We haven't gotten to decimals yet. But essentially, your calculator is taking this 1, the remainder, and it's dividing it by 3. And this part right here that comes after that decimal point is the result. And again, we're going to cover that later. So for right now, until we feel comfortable with that, until we've covered that, we're going to write this as 7 divided by 3 is equal to 2 with a remainder of 1. Okay, let's look at another example. And again, we're going to have a remainder here. So we have 19 divided by 8. So how would we figure that out? Well, again, we could use subtraction. We could count out how many times we can subtract away 8 from 19 until we get to 0. So let's do it that way. So kind of the first time, 19 minus 8 would give us 11. And then the second time, 11 minus 8 would give us 3. And kind of when we go to do a third time, we have 3 minus 8. And you think about this as we're going to pass 0 in the wrong direction. I don't have enough to subtract away 8. So we're not going to be able to make a third group of 8 with the number 19. So we've made 2 full groups, and then we're going to have 3 left over. Okay? 2 full groups, so the answer is 2 with 3 left over. And does that make sense? Just think about what that means. 2 groups of 8, 2 groups of 8, 2 times 8, that's 16. Then plus 3 left over, plus 3 left over. That's 19. That's what we started with. So 19 split up into equal groups of 8 would give me 2 equal groups of 8 with 3 kind of left over that I can't make into another group. Now, if you didn't do this with subtraction, if you wanted to start this out kind of with multiplication, you would start out by just kind of guessing. And I know you kind of think about that. What do you mean you were guessing? Well, we'd have to say, well, what number times 8 would give us 19? And you kind of go through your times tables and say, well, I don't know of any whole numbers that multiply with 8 and give us 19. So you try to get as close as you could. You'd say, okay, well, 1 times 8 equals 8. 2 times 8 gives me 16. 3 times 8 gives me 24. And when you get to this point, this number's too big. So you'd stop. You'd say, okay, it's not that number. So we'd use 2 because that's as close as we can get. So if we think about 2 times 8 gives me 16, 2 times 8, again, gives us 16. To get to 19, I need 3 more. So that means I have a remainder of 3. And I know a lot of this, when you first start hearing it, if you've never heard it before, can seem a little bit complex, but really it's not. Let's look at another one, make it a little bit more clear. Okay, so we have 21 divided by 4. So if we have 21 divided by 4, again, we can use the subtraction method. So kind of the first time we do this, 21 minus 4 is equal to 17. The second time we do this, 17 minus 4 is equal to 13. The third time we do this, 13 minus 4 is equal to 9. The fourth time we do this, 9 minus 4 is equal to 5. And the fifth time we do this, 5 minus 4 is equal to 1. Now, when I go to try to make a sixth group, and I would do 1 minus 4, I can't pull 4 away from 1. Not without going into a negative value, which, again, we haven't covered yet. So I have to stop here. I can only make 5 equal groups of 4 with the number 21. And then I have 1 left over. Okay? So the answer here is going to be 5 with a remainder of 1. And again, just thinking about if that's logical to you, if I take the number 5, okay, 5 and multiply it by 4, I'm saying that I had 5 equal groups of 4. So that gives me 20. Okay? And then my remainder was 1. So I add 20 and 1 together to get the original amount, the dividend of 21. And again, if you don't want to use subtraction, you can use multiplication. You can use multiplication. So 21 divided by 4 equals question mark. Again, work backwards. So question mark times 4 equals 21. So do we know a whole number that when we multiply it by 4, we get 21? No. So you can kind of start out and say, well, I know that 4 times 4 is 16. I know that 4 times 5 is 20. And I know that 4 times 6 is 24. Well, 24 is too big. Too big. And we know 4 times 4 is not going to work. That's too small because we could have made another group. So I go with 4 times 5. And once I see my result is 20, all I have to do is say, okay, well, the difference between 21 and 20 is just 1. So that's going to be my remainder. So this would be 5, okay, that right there, with a remainder of 1. Because when I get to 20, I need one more to get to 21. All right, let's look at one final problem. So we have 37 divided by 3. And we're not going to use subtraction here because realistically, you're going to find these answers by using multiplication, right? It's just quicker. So I'm going to put a question mark here. I'm going to put equals question mark. And we're going to work backward using multiplication. So question mark times 3 equals 37. So just thinking about our times tables here, just think about multiplying by 3. What's going to get me close to 37 without going over it? Well, I know 10 times 3 is 30. 11 times 3 is 33. I can keep going. I can keep making more groups of 3. So 12 times 3 is 36. 13 times 3 is 39. Too big. And you could have stopped when you got to 36 because you know multiplying the next number, right, when we got to 13 by 3, would add 3 to 36 and get you to 39. And we just needed to go up by one more to get to 37. So we would stop there and say, okay, well, the result or the quotient's going to be 12. But that's not the full answer because I kind of have one left over, right? I've made 12 equal groups of 3, but I have one left over. So that's my remainder. And again, just to review this, we start with 37, our dividend. We split it up into equal groups of 3, our divisor. We get 12. So we get 12 equal groups of 3. But there's a problem. We have one guy kind of left over, and so that's our remainder. And again, when you want to check something like this, and there's a remainder involved, you've got to multiply the quotient times the divisor, and then when you're done, add the remainder. That's going to give you your dividend back. And check this. 12 times 3 is 36. 36 plus 1 is 37. Hello, and welcome to Pre-Algebra Lesson 14. And in this video, we're going to learn about long division. The lesson objective for today is to learn how to divide multi-digit numbers using long division. Okay, so far in our pre-algebra course, we have reviewed how to do addition with whole numbers, how to do subtraction with whole numbers, and how to do multiplication with whole numbers. Now, what we saw in each case is that when we had large numbers that we were working with, like let's say with addition, if we wanted to add two large numbers together, we didn't do it in our head. We used a process called vertical addition. And what vertical addition does is it breaks it down into a series of easier steps. So, for example, if I want to add 24,322 and, I don't know, let's say 308, I didn't just go, okay, this is the answer. I would write 24,322 on top, 308 on the bottom. And I would go column by column until I got an answer. So essentially what we're doing again is breaking this down into a series of easier steps. Now we saw the same thing when we were subtracting large whole numbers. We used a vertical subtraction. Also when we were multiplying large whole numbers, we used a vertical multiplication. This is what long division is going to do for us. In the last lesson, we learned how to do some basic division, but we didn't see any division with large whole numbers. So if I asked you to do something like 20 divided by 4, pretty much everybody can do that without a long division. So 20 divided by 4 is what? You would use a related multiplication statement to find the answer. What times 4 equals 20, right? And from your knowledge of the times tables, you know that that question mark would be replaced with a 5, and so 20 divided by 4 is 5. But what if I asked you, what is 2,642,311 divided by 1,622? Most people cannot do that in their head. I definitely cannot. Now, I've met some people in college that could, but the majority of us cannot. So we would use a long division to solve a problem like that. And all long division is going to do is break this problem up into a series of manageable steps. let's start out by looking at a very simple problem, one that we can do without long division. I'm going to go through the steps here, and we're just going to work a lot of problems. I know most of you have done long division before, and this is going to just be a review. But even if you haven't, you can pick it up from this lesson. So let's try something like 30 divided by 6. That's an easy one. So to set up a long division, you'll have this new symbol, and it looks like this. And there's some variations of this. Sometimes you'll see your teacher go straight down. However you want to do it, I don't think it matters. You're just trying to get a result here. So whatever you're comfortable with. I try to make mine look like that. Now, you take your dividend. Remember, that's the left number of the division problem. That's the amount you start with. This is the dividend. That's going to go underneath the symbol. And a lot of teachers will call this the house. So it goes underneath the house you might hear. So the 30 goes there. This is for the dividend. Now, your divisor, which is 6 in this case, this is your divisor, is going to go to the left of this symbol. So it sits out here. This is for your divisor. Okay? Now, once you've set up the division problem like this, you go through a series of steps. Now, I'm going to write those steps down. I want you to copy them down on your paper. You have to memorize them. And there's a little trick I'm going to give you to do that. So the first step is to divide. And you're not going to divide the whole thing. You're going to basically take the dividend on one digit at a time. Okay, and I'll show you how to do that in a minute. So you divide, then you multiply, you subtract, you bring down, and then kind of this next step is repeat or remainder. And this will kind of make more sense once we get into the problem. But basically what this is telling you is that, again, you have a series of steps to get your answer. So you're going to have to repeat the process sometimes. When you come to the end of that, and there's no more numbers to say bring down, you're going to have a remainder. And in some cases, you're not going to have a remainder. The remainder might be 0. It doesn't matter. This is basically telling you, hey, stop the problem. You have your answer. All right, now how do we remember something like this? I know in a lot of places, we'll have kind of tricks to remember stuff. When you get to the order of operations, you're going to hear something like, please excuse my dear Aunt Sally, for parentheses, exponents, multiply, divide, addition, and subtraction. Well, the trick for the long division is going to be dad, mom, sister, brother, rover. Okay? You think about your family. So the D in dad for divide, the M in mom for multiply, the S in sister for subtract, the B in brother for bring down, and then the R in rover for repeat or remainder. So again, that's a little trick you can use to remember the steps. All right, now having said that, let's kind of move into our actual division. So what we're going to do is we're going to start by asking a question. We take the divisor here and we ask how many times does it go into the leftmost digit of the dividend? Okay, we're going to attack that dividend one digit at a time. So how many times will 6 go into 3? Now, a lot of people don't know what this terminology means when I say, how many times will 6 go into 3? All that's asking is, what is 3 divided by 6? What is 3 divided by 6? These two things are the same. If your teacher asks you how many times will 6 go into 3 and what is 3 divided by 6, she asks you the exact same question. It's just a different way to put it. So 6 goes into 3 0 times. And I want you to think about why. So I'm going to erase this real quick. And I want to think about 3 boxes. 1, 2, and then 3. Remember, if I say, what is 3 divided by 6, I'm taking 3 and I'm splitting it up into equal groups of 6. Now, we are not using fractions or decimals. Some of you are going to go out, oh, that's 0.5, or oh, it's 1/2. Well, if we're only using whole numbers, which is what we're doing here, the answer is 0. And the reason is because I cannot make a group of 6 having only 3 items. If I have $3 in my wallet and I need $6 to purchase a hamburger, I'm not going to get the hamburger. okay? Unless somebody loans me another $3. So the answer would be 0 with a remainder of 3, okay? 0 with a remainder of 3. I made 0 groups and I had 3 left over. Now, with long division, you never think about this part until the very end. So I'm never going to include this in my answer that goes up here. So once I ask how many times will 6 go into 3, I take this quotient part, and just this part, not the remainder, and I put it directly over what I was working with, okay? You have to think about place value when you're working with the long division problem because you're lining this up with the 3. That's what I was working with. I've done my first step here, which was to divide. Now I'm going to multiply. And what I multiply is the answer that I just had times the divisor. So 0 times 6. We know that 0 times any number is always 0. So 0 times 6 is 0. So that step is done, and then we subtract. Now, notice that I wrote the 0 directly underneath what I was working with. We're always going to do that. Line everything up by place value with what you're working with. So I'm going to subtract here. 3 minus 0. That's going to give me 3. And then I'm going to bring down. We're always going to be bringing down the next digit to the right. Next digit to the right. So now this is going to be a 30. And now we have this step that says repeat or remainder. So I just brought down this 0 to make a new number 30. So I'm going to repeat this process and go back up. And I'm going to start by dividing again. So now I'm going to ask how many times will 6 go into 30? So I'm basically saying what is 30 divided by 6? Okay, remember that's the same thing. If I say how many times will 6 go into 30 or what is 30 divided by 6, I've asked you the same question. So 30 divided by 6 equals what? We can solve this using our times tables. Remember, you just work backwards. What times 6 equals 30? Well, 5 does. So the answer would be 5. Now, I write 5 directly to the right of my previous answer. Remember, I was working with this 30 here. Where's the ones place for the 30? It's right here, so I'm going to line up that 5 right there. Now I go through my steps again. I'm going to multiply. Okay, I'm going to multiply. So 5, which is the answer we just got, times 6, the divisor, gives me 30. Write it underneath what you had. That's what we're working with. We got to line everything up based on that. Then we're going to subtract. 30 minus 30 is 0. And then we want to bring down. But there's nothing else over here to bring down. If I highlight this section over here, you see no more numbers to the right. So we're done bringing stuff down. So when we get to this step where it says repeat or remainder, if I had nothing else to bring down, I don't repeat. I go to the remainder part. Now, because this is 0, I know we say remainder there, but because this is 0, there basically is no remainder, right? So when we think about 30 divided by 6, it's 5 with no remainder. So to think about this more clearly, if I had 30 boxes and I split it up into equal groups of 6, I would end up with exactly 5 of those groups, right? I wouldn't have anything left over. Now, I know that for some of you, you'll be like, well, what step goes where? As you work more problems, you will get this down. You memorize this just like you memorize anything else. Over time, this will not be complicated at all. Now, I want to show you a little trick that you're going to use. And some of you will already be screaming and saying, why did you put a 0 right here? My teacher doesn't show me that. Well, the other way is kind of a shortcut. So let me erase this real quick. And I'm going to show you some other way. Recall that if I have a 0 next to this 5, this is still 5. Right? 5 is the same as a 0 and then a 5. Or if I put 0, 0, 0, 5, that's the same as 5. These zeros to the left of 5, they don't add any value to the number whatsoever. Now, let me start this problem over and show you what we could have done. So for the first step, divide, we could ask, okay, how many times does 6 go into 3? If you know you're going to get a result of 0, what you can do is just expand your selection to include the next digit to the right. Okay, so now I can just ask, how many times does 6 go into 30? Realize that if I would have done this the first way, how many times does 6 go into 3? 0. 0 times 6 is 0. Subtract and I get 3. Bring down the 0. I'm expanding my selection here anyway. I'm doing the exact same thing. It's just taking me longer because I went through all these steps to do it. So the shortcut is just start out by saying, okay, how many times does 6 go into 3? 0 times. Okay, so I can just expand this and say, now, how many times does 6 go into 30? We know the answer is 5 already. And the main thing is maintain your place value by putting the 5 directly over that 0. Think about that number 30. Where's the ones place for 30? Well, it's where the 0 is, so I'm putting the 5 there. And alternatively, if that's hard for you to remember, each time you kind of expand your selection, you would have had a 0. So I passed up that 3, so I would have had a 0 there. Right? Just think about it that way. Either way you do it, you're going to end up with 5. So then you would multiply 5 times 6 is 30. We'd subtract and get 0. Nothing to bring down over here. And so where it says repeat, we don't do that. We didn't bring anything down. Our remainder would be 0, meaning we don't have a remainder. And so 30 divided by 6 is 5. Okay, let's look at a slightly more challenging problem, but one that's still easy. Okay, I want to take a look at 100 divided by 5. So 100 divided by 5. What is that going to be? Again, we're going to set this up in long division format. So we're going to have this symbol that we're going to use. Remember, your dividend, which is 100, is going to go underneath, and the 5 is going to go off to the left. That's your divisor. Now, what are our steps? Let me try to paste this, and I'll put that right there. So here's our steps. Remember, you can think about your trick. Dad, mom, sister, brother, and then rover. Now, we're going to start with divide. So take your divisor, and then take on your dividend one digit at a time. So 5 goes into 1 how many times? So basically I'm asking, what is 1 divided by 5? That would be 0 with a remainder of 1, right? If I had one box and I said split it up into equal groups of 5 using whole numbers, again, not using fractions or decimals, I'm not going to be able to do that, right? I can't even make one group because I only have 1. I need 4 more to make just one group. So the answer would be 0. And again, we don't think about the remainder until the end. So I can put a 0 here, or I can use my shortcut. Remember, if I put 0 here and I go through and I multiply, 0 times 5 is 0. I subtract, I get 1. I bring down, I have 10, and then I would repeat. I could have gotten this 10 here just by expanding and not putting a 0 there. Right? So this is the shortcut. So I can say, how many times will 5 go into 10? 5 will go into 10 twice. Right? If you think about what is 10 divided by 5, go backwards. What times 5 equals 10? We all know from the times tables that that is 2. Now the main thing again is to maintain the place value. I don't want to put a 2 right here. If I think about that relative to this number 100, I'm saying that that 2 is in the hundreds place and it's not. Okay? That 2 needs to be relative to this 0. Think about it in terms of this. I was working with the number 10. Where's the ones place for the number 10? It's where the 0 is. Okay? It's right there. So I want to put the 2 directly in line with the ones place from 10. And again, alternatively, think about the fact that we would have had a 0 here if we would have done it the slow way. So 0, then 2. Okay, now we multiply. 2 times 5 is 10. And again, you want to line that up with the 10 and then subtract. 10 minus 10 is 0. Then bring down, so it's always the next digit to the right. And then repeat or remainder. Now, 0, 0 is the same thing as 0. Okay, I don't need 2 zeros there. I can just use 1. So when we repeat, we just go back up to the top and we divide. What is 5 into 0? Again, think about this using the properties of division. So I'm basically asking 0 divided by 5 equals what? Remember, if you take 0 and you divide it by a non-zero number, the answer is always 0. Okay? And if you reverse that, you can see why. What times 5 equals 0? Well, when you multiply, 0 times anything is always 0, so the answer is 0. Okay, so I write my 0 directly to the right of that 2, and then I'm going to multiply. 0 times 5 is 0, subtract, get 0, and then there's nothing else over here to bring down. So when we get to this step where it says repeat, we don't repeat because there's nothing else to repeat with. We have our remainder or our termination step. Now, this remainder is 0, meaning we don't have a remainder. So 100 divided by 5 is 20, no remainder, meaning if I had 100 of something, let's say boxes, I split them into equal groups of 5, I would get exactly 20. All right, let's take a look at another one. So we have 315 divided by 9. So again, we're just going to set up our long division. 315 divided by 9. Again, your dividend goes underneath. Your divisor goes to the left. Okay, so again, we want to divide, multiply, subtract, bring down, then repeat or remainder. Dad, mom, sister, brother, and then rover. Okay, so we start with divide. So we have our divisor here. And again, we're going to take on the leftmost digit of that dividend. So how many times will 9 go into 3? Meaning, what is 3 divided by 9? Well, you can't do 3 divided by 9 with whole numbers, right? 3 divided by 9 would just be 0, remainder 3. So we can just expand our selection and say, okay, well, it's not going to go into 3. How many times would it go into 31? How many times would it go into 31? So 31 divided by 9 equals what? Again, work backwards. What times 9 equals 31? Well, using our times tables, we know that there's no number or whole number that multiplies with 9 to give you exactly 31. So we have a situation where we want to get as close to 31 as possible without going over. So if I think about 3 times 9, that's 27. 3 times 9 equals 27. 4 times 9 would give me 36. This is too big. 36 is bigger than 31, so I have to go with 3. That's as close as I can get. So let's erase this and we'll put 3 down as our answer. And again, make sure to line that up with the ones place of 31, which we were just working with. So the 3 is going to go here. And again, alternatively, I would have had a 0 here if I would have went through the long way, right? When I said 9 goes into 3 0 times. So that's where your 3 is going to go. Now, we need to multiply, and let me kind of fix this a little bit. We need to multiply. We're going to do 3 times 9, okay? That's going to give me 27, and write that underneath the 31, right? Just underneath what we were working with. Then we're going to subtract. So I'm going to borrow here, and then 11 minus 7 is 4. 2 minus 2 is 0, so I just leave that blank. I don't need to put that. And then I bring down. Always the next number to the right. And I'm going to repeat, right? I brought something down. I have something new to work with. And I'm going to divide again. So 9 goes into 45. How many times? 45 divided by 9 equals what? Well, this one's simple. We can use our knowledge of the times tables to do this. What times 9 equals 45? Most of you will know that 5 times 9 is 45. So the answer would be 5. So I put a 5 directly next to that 3. So now we'd multiply. 5 times 9 is 45. And then subtract. We will get 0. Nothing else to bring down over here. I don't have any more digits to the right. So when we get to this step, we're not going to repeat. We just say, hey, we're at our step where we have our remainder. Now, the remainder is 0, meaning we just don't have one. It just tells us to stop, right? We've got our answer. So 315 divided by 9 is 35. And let's go ahead and check this. And particularly when you start out, you want to check everything. Just make sure you get the right result. And if you didn't, go back and see what you did wrong. It's probably some silly mistake. As long as you understand how to do the steps and you get the wrong answer, go back and check it and make sure that you didn't just make a silly mistake. The answer here is 35. And working backwards, 35 times 9 should give us 315. 9 times 5 is 45. 9 times 3 is 27, plus 4 is 31. So yes, we do in fact get our dividend back. So we have the correct answer. Okay, let's take a look at 942 divided by 3. So 942 divided by 3. And let's paste our steps. Okay, so again, we have divide, multiply, subtract, bring down, and then repeat or remainder. So we start out by asking how many times will 3, the divisor, go into the leftmost digit of that dividend. So in this case, it's 9. Now, 9 is bigger than 3, so we're not going to get a result of 0 here. We're basically saying, what is 9 divided by 3? I think all of us know that off the top of our head. It's 3, right? But if you didn't, you could just say, okay, well, what times 3 gives me 9? From your knowledge of the times tables, you know that would be 3. So put your answer directly above what you're working with. I'm working with that 9, so I'm going to put that 3 right there. And then I'm going to multiply. 3 times 3 is 9. Write that directly underneath the 9, and then subtract. 9 minus 9 is 0. And then we bring down. So I'm going to bring down this 4 here. So now we repeat the process, and we want to divide again. So how many times will 3 go into 4? Well, just once, right? If we think about what is 4 divided by 3, I would get 1 with a remainder of 1. And again, we don't think about the remainder until the very end, so we just put this part. So the answer would be 1. And notice how I write it directly to the right of that 3, okay? Maintaining place value. Now I multiply. 1 times 3 is 3. Then I subtract. 4 minus 3 is 1. Then I bring down. So I'm bringing down the next digit to the right, which is a 2. And then I repeat. Go back up, and we're going to divide again. And again, As you do this more and more, you see that these steps become very, very easy to go through. It just becomes very mechanical for you, right? Divide, multiply, subtract, bring down, repeat. Divide, multiply, subtract, bring down, repeat. And then at some point, you run out of numbers to bring down, and you end up with a remainder, which in some cases will be 0, meaning you don't have a remainder. Okay, so we divide again. 3 goes into 12. How many times? I'm asking, what is 12 divided by 3? And again, I can use a related multiplication statement and just ask, okay, what times 3 would equal 12? And from our knowledge of the times tables, we know that that would be 4. So I'm going to write a 4 directly next to that 1. And now I'm going to multiply. 4 times 3 is 12. Then we subtract. 12 minus 12 is 0. Nothing else to bring down. And so we're not going to use this repeat step. We go to the remainder, right? And the remainder is 0 here, meaning we don't have one. So 942 divided by 3 is exactly 314. And let's check it. Just going to work backwards and say, okay, well, 314 times 3 should be 942. 3 times 4 is 12. 3 times 1 is 3, plus 1 is 4. 3 times 3 is 9. 942. Again, that's our dividend that we started with. All right, let's take a look at one that will have a remainder. So 461 divided by 2. And again, our steps for the division: divide, multiply, subtract, bring down, and then repeat or remainder. All right, so we're going to start with divide. How many times will 2 go into 4, the leftmost digit of this dividend? Well, 4 divided by 2 is 2. I think all of us know that by now. So I'm going to put a 2 right here directly over that 4 that I was working with. And let me move this down just a little bit. And now I can multiply. 2 times 2 is 4. And put that directly underneath the 4 that you're working with and subtract. 4 minus 4 is 0. Now we bring down the 6, the next digit to the right. And we repeat, right? We go back up when we divide. So 2 goes into 6 how many times? Well, 3 times, right? Because 6 divided by 2 is 3, right? 3 times 2 is 6, so 6 divided by 2 is 3. So now we multiply. 3 times 2 is 6. Subtract. 6 minus 6 is 0. Bring down. I'm bringing down a 1 here. And then I'm going to repeat. I want to divide again. How many times will 2 go into 1? Well, it's not. If your divisor is smaller than your dividend that you're working with here, then you're not going to be able to do it using whole numbers. You're going to end up with a fraction, which we're going to cover later on. But for right now, 2 is not going to go into 1, right? You get a result of 0, remainder 1, which we don't think about the remainder till the end. So 2 goes into 1 0 times. Then you multiply. 0 times 2 is 0. And then we subtract. So let me kind of scroll down. 1 minus 0 will be 1. And nothing else to bring down over here. So we end up with repeat or remainder. We're not going to repeat. We didn't bring anything down. We actually have a remainder that's not 0 now. So the remainder is 1. And for most teachers, they want you to drag this back up here and write it next to the quotient. So I would write R1 like that. So 230 with a remainder of 1. Now I want you to remember what you do to check something with a remainder. It's a little bit more tedious. So you will multiply the quotient, which is 230, times the divisor to start. So 230 times 2. A lot of you can do that in your head because of the trailing 0 trick, right? 2 times 23 is 46. Put a 0 at the end, you get 460. But the long way, 2 times 0 is 0. 2 times 3 is 6. 2 times 2 is 4. Now, when I'm done with that, I would add to that the remainder, the amount that was left over. So 460 plus 1 would be 461. And think again why this is the case. I started out with 461 boxes. I split them into equal groups of 2. I was able to make 230 of those groups, but then I had 1 left over, right? I only used 460 out of the 461. I've got 1 that's just hanging out by itself. It doesn't have another box to make into another group of 2. So that is my remainder. Okay, let's take a look at another one. We have 193 divided by 9. So 193 divided by 9. And again, where's the steps? So we start out with divide. 9 goes into the leftmost digit of that dividend. 1, how many times? If this is smaller than this, the result's going to be 0. Okay? So I could put a 0 there, or again, I can just expand the selection and say, how many times will 9 go into 19? Well, 19 is bigger than 9, so I know that that's going to go in at least once. So 19 divided by 9 equals what? what times 9 equals 19? Well, there's no whole number that multiplies with 9 that gives you 19, but 2 times 9 would give you 18. That's as close as you can get without going over. So I'm going to put a 2 as my answer. And again, line that guy up. If I'm working with 19, where's the ones place for 19? It's right here. So that's where my 2 is going to go. Alternatively, as I keep saying, and I know you'll get tired of this, but I want to make sure that you're clear on the place value part, this would have been a 0. So the 2 would just go to the right of that. However you can remember that, place value is important in long division. Now we're going to multiply. 2 times 9 is 18. Put that underneath the 19 and subtract. 19 minus 18 is 1. Now we bring down, bringing down a 3 there. And then we repeat, right? We go back up to the divide. So how many times will 9 go into 13? Just once, right? Because we found that 9 times 2 was 18. That's too big, so it has to only go in just once. Now we multiply. 1 times 9 is 9. And we subtract. 13 minus 9 is 4. And nothing else to bring down over here, so we're not going to repeat. This is our remainder. Okay, 4 is our remainder. So drag it back up to the top and just put R4, right? Remainder 4. And again, to check something like this, just go backwards. So if this is 21 remainder 4, take your quotient, multiply by your divisor. 21 times 9. 9 times 1 is 9. 9 times 2 is 18. And then add your remainder back in. So 189 plus 4. 9 plus 4 is 13. 1 plus 8 is 9. Bring down the 1. You do, in fact, get 193 back, right? Your dividend. Okay, let's take a look at one with a 2-digit divisor now. So I have 126,323 divided by 15. So nothing is going to change here. The process is the same. When you start getting into bigger divisors, your guesswork becomes a little harder. And I'll show you what I mean by that. So here's our steps here. And we have 126,323. Okay, so we start out by asking, how many times will the divisor go into the leftmost digit of the dividend, right? The divide step. Well, it's not going to go in there. Again, if the divisor, which in this case is 15, is bigger than what you're trying to go into, right? Kind of think about it as your temporary dividend or your step-by-step dividend. In this case, it's 1. It's not going to work, right? You don't have enough to make a group of 15 with 1 using whole numbers again. So you would expand your selection, or you could put 0, whatever you want to do, and ask how many times will 15 go into 12? Well, again, 12 is smaller than 15, so it's not going to work. So again, you can put 0, or you can expand and say, well, how many times will 15 go into 126? Well, I know that I'll go in there, but I just don't know how many times, right? We don't work with 15 and 126 very often. So 126 divided by 15 equals what? So what times 15 equals 126? Here's where we can kind of do some estimating, okay? Now, I can think about 126 as just 120. Make it a little easier for us. And a lot of times you'll be able to get close and see where you need to go, and you can kind of fine-tune it with some extra multiplication. So I know that 10 times 15 is 150 using my trick for trailing zeros. That's too big. So what about 8 times 15? 15 times 8. So 8 times 5 is 40. 8 times 1 is 8, plus 4 is 12. So that's exactly what we need to get to 120. But what we needed was 126. So let's see if that would work out as our answer. So 15 times 8 we know is 120. We need to know what 15 times 9 is. Well, you know how to add and multiply. You know, you would just add 15 to 120. That would give you 135, right? No need to go through and do the multiplication. That's too big. It's larger than 126. So 8's going to be what we're going to use. That's as close as we can get without going over. So we're going to line up that 8 on top of the 6, which is the ones place for that number 126. And then we are going to multiply. So 8 times 15, as I just said, was 120. And then we subtract. 126 minus 120 is 6. Bring down. Always the next digit to the right, so we bring down that 3. And then we're going to repeat. Right? So we go back up and we divide. So how many times will 15 go into 63? So 63 divided by 15 equals what? So what times 15 equals, and let's round this down to 60. Because I think all of us probably know that 4 times 15 would give you 60. And think about it, that's as close as you're going to get to 63 without going over, because 5 times 15 would be 15 more than 60, or 75. So I'm going to use a 4 as my answer. So I'm going to put a 4 here, and then I'm going to multiply. 4 times 15, as I just said, was 60. And then we subtract. 63 minus 60 is 3. Then we bring down. So I'm bringing down this 2 here. And now I'm going to repeat. I want to divide. How many times will 15 go into 32? And this one's kind of easy, because if you just think about doubling 15, what is 15 times 2? It's 30. Right? That's as close to 32 as you're going to get. So we're going to put the answer of 2 and then multiply. 2 times 15 is 30. Then we're going to subtract. 32 minus 30 is 2. And then we're going to bring down. So bring down this 3 here. And now we're going to repeat. How many times will 15 go into 23? Well, we know the answer is 1 there, because 15 times 2, as we just said, was 30. That's bigger than 23, so we have to go with 1. Okay, so now we multiply. 1 times 15 is 15. We're going to subtract. 23 minus 15. We're going to borrow here. 13 minus 5 is 8. And then we're going to bring down, but there's nothing else over here. So we're at our last step. We're not going to repeat. We didn't bring anything down. So we're at the step where we say, okay, what's our remainder? So our remainder is 8. And we could just drag that back up to the top and say, okay, the remainder is 8. Now, I'm not going to go through and check this one because of the amount of work that would be involved. But if you want to check it at home, I advise you to do so just to get the practice. Take this number here, 8,421, multiply it by 15. When you're done, add 8, and you will get this number back, our dividend, 126,323. All right, so let's look at one final problem. We have 163,971 divided by 150. So again, as your divisor gets larger in terms of how many digits it has, your guesswork on each step is going to be harder. So let's write this in long division format. 163,971. Again, we're dividing this by 150. And let me paste the steps here. And so we begin with divide. So how many times will 150 go into the leftmost digit of that dividend? It's not going to go. Right? 150 is bigger than 1, so we expand that to 16. It's bigger than 16, so we expand that to 163. So 150 will go into 163 one time. And again, put the 1 directly over that 3. I can't stress this enough because I just have a lot of students that'll go, okay, it's once, and they put it over here. In terms of this number here, this, if you think about the whole number, you know, when you have an answer, this looks like it's in the 100,000s place, but really it needs to be here in the thousands place, right? So it's a completely different answer if you put that 1 over there. So make sure you line that up on top of the 3. And again, alternatively, you pass this number up, so it would have been a 0. You pass this number up, so it would have been a 0 until you got there. So that's where you would have lined it up to. All right, so now we're going to multiply. 1 times 150 is 150. Again, lining that up with 163. And then we're going to subtract. 163 minus 150. 3 minus 0 is 3. 6 minus 5 is 1. Bring down. Okay, we're going to bring down the 9. Can 150 go into 139? No, it cannot. So if I have 139 boxes, and using only whole numbers, I tell you to make a group of 150, you won't be able to. Right? You'd have 0 with a remainder of 139. So we put 0 here. Okay, we put 0 here. And we multiply. 0 times 150 is 0. And some of you at this point might say, okay, well, and over here we just kind of skipped it over. When you have a 0 in the middle of a number, it changes the value of the number. You can't use that shortcut in this case. So if I had 1005, these two zeros do add value to the number. But if I had the number, 17, and I put zeros off to the left, this is not changing the value of the number. So that's why we can skip that there. Once you get going, you can't skip that anymore. So if your result is 0, you have to write it and go through the steps. So 0 times 150 is 0, and then we subtract. So we get 139. Now we bring down. Okay, we're going to bring down that 7. And now we're going to repeat. So 150 goes into 1,397 how many times? So let's do this down here because this is going to be a tough one. So 1,397 divided by 150 equals what? So this is where it gets complicated. We don't know the times tables for 150. So we have to get somewhat creative. Now, using my trick for trailing zeros, 150 times 10 equals 1,500 or 1,500, however you want to think about that number. Now, that's clearly too big, but I can mentally subtract away 150 from 1,500. It's pretty easy to do. It's 1,350. That looks like that's going to work out. So it looks like we need 150 times 9. All right, again, take 150 away from this, you get 1,350. That's as close as you can get to this without going over. We go back up to the top here, and we put an answer of 9, and we multiply. 9 times 150, as I just said, was 1,350. Then we subtract. 7 minus 0 is 7. 9 minus 5 is 4. And then 3 minus 3 is 0. And 1 minus 1 is 0. Again, if you have zeros over here, it wouldn't change the value of the number. So I just don't put them. Right? So we have 47. So now we bring down this 1. And we have 471. So now we want to divide. How many times will 150 go into 471? Well, if I mentally think about 150 times 2. I think everybody can kind of do that in their head. That's going to be 300. 15 times 2 is 30. Put a 0 at the end. So what about times 3? Well, that's going to be 450. Right? I just add 150 to that. Pretty easy to do in your head. So that's as close as we can get without going over, because if I went times 4, it would be 600. Right? Adding it on 150, and that's too big. So we're going to use 3. Okay, we're going to use 3. So I write a 3 here, and then I multiply. 3 times 150 is 450. And I know it's cut off right now, but the next step would be to subtract. Let me scroll back down. 1 minus 0 is 1. 7 minus 5 is 2. And then we want to bring down. But when we come back up here, nothing else to bring down. So we can't repeat. Now we're at our step where we have a remainder. Right? This is what we have left over, and that is 21. So if I drag that back up here, I can just put R21. So again, if you want to check this answer, 1,093 with a remainder of 21, multiply 1,093, which is your quotient, by 150. When you get that result, add 21, and you should get this number back, the dividend, 163,971. Hello, and welcome to Pre-Algebra Lesson 15. And in this video, we're going to learn about exponents. Okay, for the lesson objectives, we want to learn the terminology associated with exponents. We want to learn how to write a repeated multiplication in exponent form. And we want to learn to solve problems that contain exponents. So what exactly is an exponent? Well, let me show you through an example. Let's say we had something like 3 times 3 times 3 times 3 times 3 times 3 times 3. That takes up a lot of room on my sheet. I wish there was an easier way to write that. Well, in fact, there is, using an exponent. Essentially, what I would do to write this in exponent form is I would count the number of 3's that I have there. I have 1, 2, 3, 4, 5, 6, 7. So I would take this number that I'm multiplying by itself, this 3, and I would write it down. So I would have my 3 there. And then I would put an exponent, which is a small little number that goes up in the top right corner, just telling me how many factors of 3 that I have. This number right here is called a base. It's called a base. When you write a number in exponent form, the base is the number that is being multiplied by itself. In this case, it's 3. Right? I have 3 times 3 times 3 times 3 times 3 times 3 times 3. So 3 is the base. The 7, again, this little small number in the top right corner, is the exponent. The exponent. And again, this tells us how many factors of 3 we have. Let's think about another one. Let's say I had 2 times 2 times 2. If I want to write this in exponent form, I have this number 2. That's going to be my base. 2 is going to be my base. Again, it's the number that we're multiplying by itself. And then I'm doing it 3 times. 1, 2, 3. I have 3 factors, so that's the exponent. 3 is the exponent. So for the purposes of pre-algebra, you can just think about an exponent as telling you how many factors of the base you're going to have. Because the only exponents we're going to look at this point will be whole numbers, usually 1 or larger. Okay, and in a lot of cases, it's just going to be 2 or larger. We have some special rules when we start dealing with exponents that are 0 and 1. So essentially for pre-algebra, you're just going to think about it using whole number exponents, and it's going to tell you how many factors of the base that you have. And again, when you think about 0 and 1, you'll have some special rules for those. So any number raised to the power of 1 is just itself. So in other words, if I have 6 and it's raised to the power of 1, and I say, well, what is 6 to the power of 1? Well, it's just itself. It's just 6. Or I could flip that and say, okay, I want to write 12 in exponent form. How would I do that? Well, I would take 12. That would be the base. And then I would take 1 and write that for my exponent. So if you have a number that's just hanging out by itself, let's say 13. And again, you want to write it in exponent form. You just write the number as the base and put a 1 as the exponent. So any number raised to the power of 1 is just itself. Now we have a rule for a number raised to the power of 0, but we're going to cover that later on because that's something we need to go through and explain. So for right now, we're just going to work with, again, whole number exponents that are generally going to be 2 or larger, and we know the rule for 1, so we're safe there. All right, so let's talk a little bit about some language that you're going to hear when you work with exponents. So when we raise something to a power, we generally say the number to the, and then that power. So for example, if I have 14 and my exponent is, let's say 7, this would be the number, which is 14, and then to the, in this case, it's the 7th power, right? Because it's a 7, so 14 to the 7th power. If I have 8 and my exponent is 4, this would be 8 to the 4th power. If I have 9 and my exponent is 13, it would be 9 to the 13th power, so on and so forth. Okay, so there's 2 special cases that I want you to know. And the first one is when we raise a number to the 2nd power, okay, meaning we have an exponent of 2, we say the number is squared. If you don't know this at this point, take out a pen and a piece of paper and write it down. You need to memorize that because moving forward, you're going to hear that all the time. You're going to have somebody say, what is 6 squared? What is 4 squared? What is 8 squared? And you might be going, I don't know what that means. When we say squared, we're meaning raised to the power of 2. So I could say this as 6 to the power of 2. I could say 6 to the 2nd power, or I could say 6 squared. They all mean the same thing. So very important that you understand that definition. And another scenario that's going to come up, when we raise a number to the 3rd power, we say the number is cubed. So that means you have an exponent of 3. Again, write this down. It's going to come up a lot. So if I have 4 to the 3rd power, we generally will say that's 4 cubed. Now, you're not wrong if you say 4 to the 3rd power, or if you have 4 squared and you say 4 to the 2nd power. It's just you need to know both in case your teacher asks you. They might say, what is 4 cubed? And you go, well, I don't know what that is. You'll be in trouble. So again, memorize that when someone says something is cubed, it means they have raised it to the 3rd power. When something is squared, they have raised it to the 2nd power. Okay, let's do a little basic practice here. We want to write each in exponent form. Nothing that's going to be too complicated. So I have the number 7, and it's being multiplied by itself. So I have 7 times 7 times 7 times 7 times 7. So the base is the number that is being multiplied by itself. So obviously that is 7. Again, this is the base. And then my exponent tells me how many factors of 7 I have. So it's 1, 2, 3, 4, 5. 5 is the exponent. Okay, so this is 7 to the 5th power. Here we have 6 times 6 times 6 times 6 times 6 times 6 times 6. So the base is obviously 6, right? That's the number that's being multiplied by itself. And then what's the exponent? What is the exponent? Let me just label this real quick as the base. The exponent, again, tells us how many factors of 6 we're going to have. 1, 2, 3, 4, 5, 6, 7. So this would be to the 7th power. This is my exponent. What about 9 times 9? Well, The base here, again, is the number that's multiplied by itself, and that's 9. So this is my base. And the exponent tells me how many factors I have. So I have 1, 2 of those. So the exponent is 2. This is my exponent. Very, very easy. What about 4 times 4 times 4? Again, my base is going to be the number that's multiplying by itself. So that's going to be 4. And then my exponent tells me how many factors I have. So I have 1, 2, 3. So 3 is my exponent. Okay, so I have here that we also need to be able to reverse this process. So what does that mean? Well, basically what I'm saying is that when you see a problem with exponents in it, you need to be able to reverse it and write it as a repeated multiplication. So in other words, if I have 10 to the 4th power, write this using multiplication. So I know the base is 10, so that's the number that's being multiplied by itself, and the exponent is 4, telling me I have 4 factors of 10. So this is 10 times 10 times 10 times 10. Right, I just did the thing I was doing before, only backwards. Right, I took it from where it had an exponent and wrote it with multiplication, whereas before I was taking with multiplication and writing it where it had an exponent. What about 9 to the 6th power? Well, my base is 9, so that's the number I'm multiplying by itself, and 6 is the exponent, that's how many factors I'm going to have. So 9 times 9 times 9 times 9 times 9 times 9. I have 1, 2, 3, 4, 5, 6. 6 factors of 9. What about 12 to the 10th power? Well, I'm going to have 10 factors of 12, right? My base is 12. Again, that's the number that's being multiplied by itself. And 10 is the exponent. It tells me how many of them I have. So this is 12 times 12 times 12 times 12 times 12 times 12 times 12. And I lost count. How many is that? 1, 2, 3, 4, 5, 6, 7. So I need 3 more. So times 12 times 12 times 12. So now we have 10 factors of 12. Then the last one we'll look at is 5 cubed. Or again, you could say 5 to the 3rd power or 5 to the power of 3. Doesn't matter as long as you know that this is 3 factors of 5. Right? The exponent is a 3 and the base is 5. So that means I have 5 times 5 times 5. Okay, so the next thing you need to be able to do is evaluate when you see an exponent. So if I see something like 2 to the 7th power, and your teacher says, what's the value for that? Or what's it equal to? Well, the first thing I'm going to do is I'm going to write this using multiplication. So in other words, I have 2 as my base, and I have 7 factors of 2. So just exactly what we just did. So 2 times 2 times 2 times 2 times 2 times 2 times 2. So 7 factors of 2. And then I just go through and multiply. And a lot of times, especially for these scenarios that come up often, you'll just memorize what the answers are. I already know that 2 to the 7th is 128. I don't even need to do the multiplication. But we're going to go through and say 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, 16 times 2 is 32, 32 times 2 is 64, 64 times 2 is 128. 128. What about 3 to the 4th power? Well, again, we're going to write this using multiplication and then just do the multiplication. So 3 to the 4th power is 3 times 3 times 3 times 3. Again, 4 factors of 3. The 4 is the exponent, tells me how many factors I have. 3 is the base, that's the number I'm multiplying by itself. So 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. 81. What about 17 squared, or 17 to the power of 2? Well, this is 17 times 17. And I don't know this off the top of my head. I would have to either use a calculator or do vertical multiplication. So let's just do that on the screen here. So 7 times 7 is 49. 7 times 1 is 7, plus 4 is 11. And now the benefit of this is I'm multiplying 1 times 17. So that's easy to do, right? I just shift this over here, and I can just basically write 17 as my answer. And now I can just add. Bring this down. 1 plus 7 is 8. 1 plus 1 is 2. So we end up with 289. And so we'll write this as equal to 289. Okay, what about 15 squared? Well, again, we would write this as 15 times 15, and then we would multiply. So I happen to know 15 times 15 off the top of my head, but in case you don't, you would do a vertical multiplication. This is 225, and this is one that's going to come up quite a bit. Okay, what about 4 to the 5th power? So this is 4 times 4 times 4 times 4 times 4. So this one's pretty easy to do in your head. 4 times 4 is 16. 16 times 4 is 64. 64 times 4 is 256. And then 256 times 4 is 1024. And again, this is another one that I have memorized. We'll learn later on that 4 to the 5th power is the same as 2 to the 10th power. And I know that probably doesn't make any sense to you right now, but later on you're going to understand why that's the case. So the answer for right now, though, is, again, 4 times 4 times 4 times 4 times 4, which gives us 1024. Okay, lastly, let's talk about 10 raised to a whole number larger than 0. This right here, what I'm going to teach you, is going to save you a lot of time because you come across these problems a lot, and there's a very simple way to solve them. So let's say I have something like 10 to the 2nd power. What's that equal to? Well, it's 10 times 10. Now, I taught you in the lesson where we talked about multiplying with trailing zeros, you can do 1 times 1 and then attach 2 zeros to this. So this is 100. Notice how 10 squared produced 2 trailing zeros. This is 2 trailing zeros. Look at 10 cubed. This equals 10 times 10 times 10. 1 times 1 times 1 is 1. 3 trailing zeros. 1, 2, 3. So 3 as the exponent, 3 trailing zeros. And I think some of you can already see where I'm going with this. If I have 10 to the 4th power, 10 to the 4th power, I get 10 times 10 times 10 times 10 equals 1 times 1 times 1 times 1, which is 1. And then 1, 2, 3, 4 trailing zeros. 1, 2, 3, 4. So again, the exponent is 4, and I have 4 trailing zeros. So here's the rule. If we're working with whole numbers and they're larger than the number 1, so meaning 2 and moving out forward, okay? I didn't include 1 in that because 10 to the 1st power is just 10, and we learned that earlier. But essentially what you do is you write a 1 followed by the exponent number of zeros. That's it. It's very, very simple. So this is especially helpful when we have some huge number. Let's say we have something like 10 to the 11th power. I could go through and write out, okay, 10 times 10 times 10, basically 11 factors of 10. You could go through and multiply them. I'd be there all day if I didn't use the trick for trailing zeros. Using this trick with exponents, it's very, very simple. I write a 1 and I follow it with 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Comma, comma, comma. So I end up with 100 billion. And go ahead and punch that up on a calculator. You see that it's correct. And again, this works. So you could do something like 10 to the 15th. That would be a 1 followed by 15 zeros. Or 10 to the 90th. That would be a 1 followed by 90 zeros. So using this technique can help you out a lot, because a lot of times on your test, you'll get at least 1 to 2 of these where they'll say, okay, what is 10 to the 4th? Or what is 10 to the 7th? And you just write a 1 and you follow it with 4 zeros. Or with 10 to the 7th, you write a 1 and you follow it with 7 zeros and you're done. Right? You don't have to sit there and go through and multiply and do all this extra work. Hello and welcome to Pre-Algebra Lesson 16. And in this video, we're going to learn about the order of operations. So the lesson objective for today would be to learn how to solve problems with multiple operations involved. Okay, so up to this point, we haven't really discussed any general rules for solving a problem with multiple operations in it. This is what the order of operations is going to do for us. The order of operations tells us which operation to perform in which order when we're faced with a problem that contains multiple operations. So I'm going to read through the order of operations and then we're going to work a bunch of problems. So kind of the first step, or you would say your highest priority when you're working a problem, would be to work inside of any grouping symbols. And then I have a side note here. If multiple grouping symbols are present, you start with the innermost set and work outward. Okay, then the second step, or your second highest priority, would be to perform all exponent operations. Okay, so anything that involves an exponent, you need to do that second. Then third, or your third highest priority, is multiplication and division. Now, a lot of students get confused with this. You want to multiply or divide working left to right. So multiplication does not come before division. Division does not come before multiplication. They are on the same level. You do them from left to right. So if I had something like 4 times 5 divided by 2, I would multiply first. So I would do 4 times 5 first, and then I would take that result, which is 20, and I would divide by 2. So this would be 20 divided by 2, which would give us 10. Okay? Now, if I kind of flip the order around, let's say we use some different numbers here. Let's say I had 10 divided by 2 times 3. In this case, division occurs to the left of multiplication, so we would now divide first. 10 divided by 2 is 5, and then we would multiply by 3, giving us 15. So you can see that multiplication and division, again, it's on the same level, it's the same step. We do it working left to right. Okay, then your lowest priority, your fourth priority, is addition and subtraction. So I have here add or subtract, again, working from left to right. So addition and subtraction occur on the same level, just as we saw with multiplication and division. So if you have something like 4 plus 3 minus 1, you would add 4 plus 3 first. 4 plus 3 is 7, and then you would subtract away 1. If I was to switch this around and put a subtraction sign here, an addition sign here, you would now subtract first, right? Because subtraction is to the left of addition. 4 minus 3 is 1. Then 1 plus 1 is 2. Okay, so we're going to start looking at some problems here. And really, there's not much to the order of operations other than memorizing what's the priorities. 1, 2, 3, 4. And a lot of students will use kind of some clever tricks to remember it. I know that one of them, when I was in high school, was, please excuse my dear Aunt Sally. Right? And you'll hear this all the time. You'll hear PEMDAS, PEMDAS. But you have to be careful with stuff like this. This is please excuse my dear Aunt Sally. You have to be careful with this because this is basically parentheses, exponents, multiplication, division, addition, subtraction. Remember, these two occur on the same level. And then these two occur on the same level. You have to remember for this step, it's left to right. And I can't stress this enough because I have a lot of students that kind of mess this up because they use things like this and they say, well, no, multiplication comes before division. PEMDAS. Multiplication, division, left to right. Left to right. Addition, subtraction, again, left to right. Left to right. So if you can't remember that, please take out a pen and a piece of paper, write that down. Multiplication and division are on the same level. We perform them left to right. Addition and subtraction on the same level. We perform them left to right. Okay, now having said that, let's start on our first problem. And we want to just evaluate each, which means we're just going to find the value. So when we look at 4 minus 3 plus 5, that's our first problem. We have two operations here. We have a subtraction operation and we have an addition operation. So which one are we going to do first? Again, addition and subtraction occur on the same level. So we're going to work left to right. So I start at the left part of the problem and I go to the right. So 4 minus 3 will be done first. And 4 minus 3 is 1. So I'm going to replace this part right here, this operation, with a 1. And then I'm going to write the rest of the problem. So then plus 5. And then 1 plus 5, I do that. That's 6. Very, very simple. Next, we have 5 times 2 minus 1. So our operations here, we have multiplication and we have subtraction. So multiplication has a higher priority. We need to do that first. So I'm going to do 5 times 2 first. So what is 5 times 2? Let me just highlight this. 5 times 2 is 10. So I'm going to replace this part right here, this operation, with a 10. I'm going to put a 10 there, and then I'm just going to copy what remains. So then I have minus 1. Minus 1. And now I'm free to perform that operation. 10 minus 1 is 9. Okay, for the next one, we have 4 squared minus 3. And if we look at what we have here, we have an exponent involved, and then we have subtraction. So the exponent has the highest priority, and so we would evaluate 4 squared first. 4 squared means that I have 2 factors of 4. So 4 times 4, that is 16. So I'm going to replace this with 16. And then we copy what's left from the problem. It's just minus 3. Minus 3. So 16 minus 3 would give me 13. Okay, so now we're going to make them a little bit harder. Up to now, we've only seen things with kind of 2 operations involved. Now we're going to kind of get into 3, 4, 5, and more operations involved in one problem. So we start out with the quantity 2 plus 1. And again, I say the quantity because 2 plus 1 is inside of a set of parentheses. Then we multiply by 3, then we multiply by 2. Now, the highest priority in any problem is always what's inside of the parentheses. So I would perform this operation before anything else. And where students get confused is they say, oh no, you have addition here. Well, it doesn't matter because when you have parentheses, you must work inside of them first. So we're going to do this first. So what is 2 plus 1? 2 plus 1 is 3. So I'm going to write that over here. I'm basically just replacing this with a 3. And then I copy the rest of the problem. I have times 3 times 2. So I'm just going to work this left to right. 3 times 3 is 9. And then 9 times 2 is 18. So this would be a final answer of 18. Okay, now we have 6 plus 8 divided by the quantity 5 minus 1. Again, we have this quantity here, 5 minus 1, because it's inside of parentheses, right? The 5 minus 1 is inside of parentheses. So we perform whatever operation is inside of parentheses first. So 5 minus 1 is 4. So I'm just going to replace this with a 4 and copy the rest of the problem. So 6 plus 8 divided by, and again, the result of this is 4. So now if we look, we have addition and we have division. So division is a higher priority. Okay, we want to divide before we add. So that means I'm going to do this problem first, which is 8 divided by 4. So 8 divided by 4 is 2. So again, this right here will be replaced with a 2. So I'll have 6 plus 2. 6 plus 2. And to finish this off, 6 plus 2 is 8. Okay, for the next problem, we have the quantity 1 plus 1 divided by, and then look inside of parentheses here, we have something that's a little bit longer than what we're used to. We have 6 minus 2 times 2. So we have 2 sets of parentheses here. Now here's what really matters. You need to make sure that you perform the operations inside of the parentheses separately from this division. Okay? So in other words, you'll get some result here, and you'll get some result here, and then you're going to perform your division, not before. Okay? That's what those grouping symbols are there for. So let's start out with the set of parentheses on the left. We're going to do 1 plus 1. We all know 1 plus 1 is 2. So we're going to replace this with a 2, and then divided by, and then inside of parentheses we have 6 minus 2 times 2. So we're not doing any division yet. We're still working inside of parentheses. Still working inside of parentheses. Now, once you get inside of a set of parentheses, you might have a decision to make. You see how you have subtraction here and you have multiplication. You have to reapply your order of operations. Multiplication occurs before subtraction. It's a higher priority. So we would do 2 times 2 first. Okay, so 2 times 2 we know is 4. So let me just circle this guy. This right here is going to be replaced with a 4. Okay, so equals 2 divided by, and inside of parentheses I'm going to have 6 minus, and the result of this again was 4. And we're still continuing inside of the parentheses, even though we just have one operation left. We want to do 6 minus 4, and that's 2. So we're going to have 2 divided by 2, right, because the result of this is 2. And then we finish this problem up by performing the division. 2 divided by 2 is 1. Okay, for the next one, we have the quantity 14 minus 2, then divided by, and here we have a 2 next to a set of parentheses. So again, that implies multiplication. So 2 times the quantity 5 plus 1. So we know we're going to start out by doing the operations inside of parentheses first before we do anything else. So we're going to start with 14 minus 2. 14 minus 2 is 12. So I'm going to replace this with a 12. Okay, and I just copied the rest of the problem. Next, we're going to work inside of this set of parentheses here. 5 plus 1 is 6. So I'm going to say this is 12 divided by 2. Then remember, this implied multiplication. So this will now be times 6. Okay? Just because we didn't have a multiplication symbol there, again, you have to remember that as we move higher in math, when you see a number next to a set of parentheses, again, it implies multiplication. So this is our problem now. We have 12 divided by 2 times 6. Remember, if we have division and multiplication, they occur on the same step. So we're going to work them left to right. So that means I'm going to divide 12 by 2 first and then multiply by 6. So 12 divided by 2 is 6, and then times 6. So then 6 times 6 is just 36, and that gives us our final answer. Okay, let's take a look at one final problem. So we have 6 squared minus, and then we have the quantity 2 plus 3 minus, and then we have another quantity 3 plus 13, and then finally divided by 4. So again, the highest priority you're going to face in any problem is always going to be what's inside of parentheses. So we have parentheses here, we have parentheses here, and let's figure out what 2 plus 3 is first. So I'm going to rewrite this part, 6 squared minus 2 plus 3 is 5, so I'm just going to replace this with a 5, and then minus, we have this inside of parentheses 3 plus 13, and then divided by 4. Now, the next step is to work inside of these parentheses. We're going to do 3 plus 13. So we're going to have 6 squared minus 5 minus, so what is 3 plus 13? That's 16. That's, again, 16. And then divided by 4. Okay, so now when we look at this problem, I have an exponent, I have subtraction, more subtraction, and division. So the exponent is what we're going to deal with first. That's the highest priority. 6 squared is 2 factors of 6, or 6 times 6, which is 36. So again, I just replace this with a 36, and I can copy the rest of the problem. So I have minus 5 minus 16 divided by 4. Now I have subtraction, more subtraction, and division. Division has the highest priority. So we would do 16 divided by 4 before we do anything else. 16 divided by 4 is 4. So I'd have 36 minus 5 minus, and again, this operation right here resulted in 4. And now I have just straight subtraction, so I'm going to work left to right. 36 minus 5 is 31, so that's 31 right here. And then we have minus 4. And then lastly, 31 minus 4 is 27, and that is our final answer. Hello and welcome to Pre-Algebra Lesson 17. And in this video, we're going to talk about integers. Okay, so for our lesson objectives, we want to discover a new set of numbers known as the integers. We want to use the number line to determine the relationship between integers. We also want to learn how to find the opposite of a number. And then lastly, we want to learn to simplify with multiple. And then you see this symbol here. Most of you at this point will know it as a subtraction symbol. Throughout this lesson, we're going to see that symbol used for different things. So I'm just going to put multiple and then show you this on the screen, say symbols. And again, we're going to change the context of that throughout our lesson. All right, so let's begin by talking a little bit about the whole numbers. Now, up to this point, we've only worked with the whole numbers. And typically, these are the numbers you work with in elementary school. We've reviewed how to add whole numbers, and we did that on a number line too. How to subtract whole numbers, again, we did that on a number line. We reviewed how to multiply whole numbers and how to divide whole numbers. And the reason I spent time on that was that if you had forgotten that, when you go to do these operations with integers, you're just going to be behind. So again, the whole numbers start with the number 0 and increase in increments of 1 out indefinitely. So again, remember you'll have these 3 dots here after 3. That just tells you you'd have 4, then 5, then 6. Essentially, that pattern just continues forever. Now, if you look at this illustration here, it's of a number line. And remember, this is just a visual representation of, in this case, it'll be the whole numbers, but in a second, we're going to see that we can draw a visual representation of the integers as well. So look how this is drawn. We have our first notch, or our leftmost notch, occurring where 0 is. And then each notch to the right represents the next whole number, right? An increase of 1. So you got 1, then 2, then 3, then 4, so on and so forth. At some point we stop and we put an arrow there. And the arrow just says that, hey, numbers are going to continue forever, right? And since this is a number line that represents the whole numbers, you can just basically assume that you'd have, 9, then 10, then 11, then 12, then 13, then 14, so on and so forth. So every number that is larger than 0 is known as a positive number. We can place a plus symbol, okay, the plus symbol, or you might know it as the addition operator, in front of a number to indicate that it is positive. We don't typically do this because numbers are by default positive when we work with them, right? That's what we're used to working with. So typically you will not put a plus sign in front of it. So for example, if you have the number 3, you would just write it like that. You know that it's positive. But if you wanted to, you could put the plus symbol in front of it to indicate, hey, this is a positive number. This is a positive number, positive 3. So when we encounter a number that is less than 0, okay, less than 0, we refer to it as a negative number, a negative number. So negative numbers always have and again, I talked about this previously in this lesson, this symbol right here, which we've used for subtraction up to this point. So this symbol, we put that sign in front. So if I wanted to, say, write down the number -3, I would put this symbol directly in front of a 3, and I would have a -3. So this is a negative -3. And again, if I wanted to write +3, I just write the number 3, or I could put a +3 in front of it. In this case, that plus is optional. But when you're writing -3, you have to write it. It's not optional because nobody will know that that's a -3. Again, the default value of a number is going to be that it's positive, right? Because that's what we normally work with. So before we move any further, what exactly is a negative number? So some of you might say, well, I don't know what a negative number is. Well, in most cases, all of you have seen some form of a negative number. You might not have worked with them directly in math, but you've seen a negative number before. One thing or one example that's used in almost every textbook would be a negative temperature. So you're watching the weather on TV or maybe on your phone or something like that, and you find out that tomorrow it's going to be, -5 degrees. Essentially, it's colder than 0. Right? It's going to be a lower temperature than 0, and they represent that with a negative value, -5. Another common example would be that you have a negative amount of money in your bank account. So let's say you have $5 in your checking account. You go to the store and you buy $10 worth of groceries. Okay? Let's say your bank covers the charge. So you had $5, you spent 10. So you're going to end up with -$5 in your account, plus probably a fee from your bank saying, hey, you spent more than you had. But that's another example of where we would use a negative value. Kind of a sports one that you could think about. Let's say that you're watching a football game and they hand off the ball, running back runs, and he loses yards. Let's say there's a loss of 4 on the play. Well, if you see them represent that with numbers, they're going to say, hey, that's a play that yielded -4 yards. So we have negative numbers around us. We don't use them as often as we do the positive numbers, but they are around us. Now let's talk a little bit about 0. So a lot of people get confused about this. They think that 0 is a positive number. It's not. 0 is special. So it is not positive or negative. It is neither. Later on, you're going to hear that 0 is an even number, but it is not positive and it's not negative. Okay, just think about it as being neutral. Okay, so now let's talk a little bit about the integers. Now the integers are important because from here on out, you're going to work with them a lot. So the integers include the whole numbers and their negative counterparts. So we already know what the whole numbers are. Again, I just put that on the screen at the beginning of the lesson. If you look at the integers here, if you just look at this part where it says 0, then 1, then 2, then 3, then comma, ... that's the whole number part. Okay, this is the part that we know. Whole numbers. Now what we're just introducing is numbers that are to the left of 0. So you kind of think about 1, well, it has a negative counterpart, -1. You think about 2, it has a negative counterpart, -2. We're just counting like we normally do. We're just counting a different way now. So the numbers are the same. You go 1, 2, 3, 4, 5. You just have negative symbols in front of them instead. So it's -1, -2, -3, -4, -5, -6, so on and so forth. All right, so let's take a look at the integers on a number line. So you'll see that 0 is at the center. And then to the right of 0, you have your positive numbers. Okay? And I'm going to put a plus symbol just out here to say that this is positive. So anything to the right of 0 is positive. Anything to the left of 0, you see how we use these negative signs, okay, directly next to the number to say that these numbers are negative. These are negative numbers. Negative numbers. So again, left of 0 is negative, right of 0 is positive, and 0 is neutral, okay? It's neither. Okay, so to understand the relationship between integers, we need to do some extra thinking. So what if I was to ask you, is -4 greater than 1? Is that true? Well, in fact, it's not. And what kind of trips people up is they see 4 and they see 1. And they say, well, 4 is a bigger number. -4 is actually a smaller number. As these numbers that are negative get kind of bigger, meaning you have bigger negatives, they're actually getting smaller. And to see why, let's look at a number line. So you remember in the lesson where we introduced the number line, I told you that as we move right on the number line, the numbers are getting bigger. So meaning 1 is bigger than 0, 2 is bigger than 1, 3 is bigger than 2, 8 is bigger than 4, so on and so forth. If a number is to the right of another on the number line, it is bigger. The same is true if a number is to the left of another on the number line, it's smaller. So 5 is smaller than 6 because it's to the left of 6. Or 2 is smaller than 4 because it's to the left of 4. Well, look, as we're moving this way, we're getting bigger and bigger negative numbers. But again, we're moving left, so the numbers are actually getting smaller. And you can kind of think about this using money if you want. I think that's the easiest way to think about it. If I have -4, if I have -$4 in my account, do I have more money or less money than if I have $1 in my account? What's the relationship between these two numbers? Well, 1 is a bigger number. -4 is going to be less than 1 because in this case, I actually owe $4. Not only do I not have any money, I actually owe $4 to somebody. So I'm in a much worse situation. So this is a smaller value than 1. So we would say -4 is less than 1. And if you ever get confused about it, you can think about it in two different ways. The first way is you can do this. You can draw yourself a little sample number line and say, okay, well, where is this on a number line? Where is this? Again, the one to the left is the smaller number. The second thing you can do is kind of use your common knowledge of numbers that you've worked with in the past. So let's say you have two positive numbers. You have 50 and you have 10. So everybody knows that 50 is a larger number. So 50 is greater than 10. But if I put negatives in front of these numbers, this is no longer true. We would have to flip this to in fact get a true statement. -50 is now a smaller number than -10 because -50 is a bigger negative number. All right, let's look at a quick exercise here. We want to replace each question mark with the inequality symbol less than or greater than. So we're going to start out with -2 question mark -5. So what's the relationship between these two numbers? -2 is here on the number line. -5 is here. Again, -5 is to the left of -2, so it's a smaller number. Remember, I told you that the symbol points to the smaller number. So if we look at -2 and -5, again, my choices would be to use this symbol, which is the greater than, or this symbol, which is the less than. Point the symbol to the smaller number. -5 is smaller, so we use the greater than. Okay, -2 is greater than -5. And again, thinking about it the other way, -2 is to the right of -5, so it's bigger. Or again, thinking about it the way I just said, -5 is to the left of -2, so it's smaller. Either way, -2 is greater than -5. What about 1 question mark -1? 1 question mark -1. So 1 on the number line is here. -1 is here. So -1 is a smaller number. It lies to the left of 1 on the number line. So we would have 1 and we would have -1. And I want to point the symbol to the smaller number. So again, I'm going to use a greater than symbol. Okay, the greater than symbol is going to point to the -1. So 1 is greater than -1. And again, if you get confused on something like that, just kind of think about money. If I have $1, do I have more than if I owed $1? Well, yes, I do. So 1 is a greater amount. Let's take a look at -7, question mark, -4. So here's -7, and here's -4. So -7 is to the left of -4 in the number line, so it's a smaller number. So we would have -7 is less than, again, the symbol's going to point to the -7 because that's smaller, -4. Okay, now let's talk about opposites, which are also known as additive inverses. So opposites are numbers that have the same distance from 0 on the number line, but lie on opposite sides of the number line. So if you kind of think about this, you would have like 1 and -1, 2 and -2, 3 and -3, 4 and -4. Basically, it's just the number and then the negative of that number. So you could make an infinite number of these. You can go through and say, okay, 5 and -5, 6 and -6, so on and so forth. So with opposites, it's a very easy concept. So to find the opposite of a number, we just change the sign. That's all you're doing, because if I say, hey, what's the opposite of 1? Again, you're just looking for that same value, but just with a different sign. So you would just change the sign and say, okay, well, the opposite is -1. So we want to find the opposite of each. And again, you might see this in your textbook if you're in pre-algebra. It might say find the additive inverse. Okay, so just know that those two terms are interchangeable. If I say, hey, find the additive inverse, or I say, hey, find the opposite, they're asking for the same thing. All right, so the opposite of 5 is -5. Again, all I do is I take the number and I just change the sign. So this is positive, it becomes negative. The opposite of -12 would just be +12. Again, just change the sign. The opposite of 315 would be -315. Again, just change the sign from positive to negative. And then the opposite of -1,718,311 would be +1,718,311. Very, very easy to find the opposite of a number. Okay, so now we're going to use this concept to actually look at some problems we're going to deal with. So I have here to simplify each, and we start off with something that looks kind of weird. We have what looks like a negative symbol or a subtraction symbol, and then in parentheses we have -4. So what does this mean? Well, essentially when you have this symbol directly next to a number, it's saying, hey, this is negative. This is negative. So I would read this as -4. When you have this symbol right here, and it's outside of a set of parentheses, basically what I'm saying is, hey, change the sign of whatever's inside of parentheses. But you could read this as the opposite of. The opposite of. So this would be read the opposite of -4. And it's just saying, hey, change the sign of -4, what would you get? So whenever you see this, what is the opposite of -4? It would be +4. Again, just as I showed you with these other examples, when I said, what is the opposite of -4, we just change the sign. That's all we're doing here. You just have to know how to read it. The opposite of -4 is 4. So that's why we'd write it that way. Now we have the opposite of -3. Again, this is the opposite of, and then this is -3. And again, all that's saying is, hey, whatever's in parentheses, which in this case it's -3, change the sign. So whatever's in parentheses, again, this is -3 in parentheses, change the sign, it would be +3. Or if you saw a negative symbol outside of a set of parentheses and there was a positive number in there, let's say it was 5, you would just change the sign of 5. Hey, what is the opposite of 5? -5. Okay, that's all you're doing. Okay, so before I kind of get into the next problem, I want to address something that I haven't talked about yet, but it's the concept of an odd or an even number. So I'm going to briefly talk about this. So an even number is a number that is divisible by 2. And when I say divisible by, I mean you divide it by 2 and you don't have a remainder. Okay? So in other words, 6 divided by 2 is 3. So 6 is an even number. Or 10 divided by 2 is 5. So 10 is an even number. 3 divided by 2 would be 1 with a remainder of 1. That would be not an even number. That's something called an odd number. So an odd number is not divisible by 2. Okay, not divisible by 2. 5 is an odd number. 5 divided by 2 would be 2 with a remainder of 1. So that's an odd number. And again, we'll get more into this when we get to the divisibility rules, but you need to have a basic definition of this to apply this trick that I'm going to teach you. All right, so what about when we see a scenario like this where we have multiple symbols in a row? So we have the opposite of negative 15. All right, kind of the slow way to do this is to think about, okay, the innermost set of parentheses contains negative 15. If I kind of move out of that, I would be asking for what is the opposite of this negative 15 here? Well, it's 15, right? You just change the sign. So kind of contained in these parentheses here, I would just get 15 as a result. So I'd have this negative out here, or again, asking for the opposite of, and then I would have inside of parentheses just a 15. Then this negative, or again, asking for the opposite of, is telling me to change the sign of whatever's in the parentheses one more time. So what is the opposite of 15? Well, that's just negative 15. So very, very easy, but if you had a longer problem, it would be ridiculously time consuming. The quick way to do this is just to realize that each time you have a pair of negatives, it's going to make a positive, right? So this one and this one are a pair, so that makes it positive, right? You recall that we ended up with a positive 15 inside the parentheses, right? And then we had the negative out there. Now, there's nothing else to pair up with this, so it becomes negative. So you think about a pair as being 2. So 2, 4, 6, 8, 10, 12. These are even numbers. So when you have a pair, things become positive. So all your problems where you have even amounts of those negative symbols will give you a positive. If you don't have an even amount of those symbols, meaning you have an odd amount of those symbols, you get a negative result. We have 1, 2, 3 of those, meaning we could only make one pair of negatives, and then we couldn't do anything with that one, so we had a negative result. We got a negative 15. If I had the opposite of negative 15 like that, now I have an even number of these symbols. Now I'm going to get a positive 15. So working backwards, this would make it positive 15. So we'd have the opposite of positive 15. And then this would make it negative. So we would have the opposite of negative 15. And then this last one would make it positive again, right? We have another pair. So this becomes 15. So just count the number of symbols that you have. Again, pair them up. So in other words, like this is a pair and this is a pair. So we end up with an even number of those symbols, so we get a positive result. Here's one that's pretty long. So we have the opposite of negative 24. So if you were to kind of work through this the slow way, you'd be like, okay, now this is going to make it positive, this is going to make it negative, this is going to make it positive, this is going to make it negative, this is going to make it positive. You'd end up with positive 24. But the quicker way to do it, again, is just to count the number of symbols you have. You have 1, 2, 3, 4, 5, 6 of them. 6 is an even number. 6 divided by 2 is 3, no remainder. So we know that the answer would be positive. Again, you can kind of also look at it and see, hey, can I pair these up? So this would pair up and become positive. This pairs up and becomes positive. This pairs up and becomes positive. Right? Each pair of those negatives makes a positive. And again, if you kind of look at one, let's say we only had 5. So the opposite of negative 24 like that. Now, this would make it positive. This would make it negative. This would make it positive. And then we'd have one more that would make it negative. So there's only 5. 1, 2, 3, 4, 5. So this would become negative 24 now. Again, it's an odd number. 5 divided by 2 is what? It's 2 with a remainder of 1. So it's not an even number. It's an odd number. So we get a result that is negative. Okay, let's look at one last problem. And look how long it is. So we have the opposite of negative 9. So again, if I could do this the long way, it's going to take some time. So in other words, this would make it positive. This would make it negative, positive, negative, positive, negative, positive, and negative. So we'd have negative 9. Again, the easy way is to count. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is an odd number. It is not divisible by 2. 9 divided by 2 is 4 with a remainder of 1. So it's an odd number. So that's why we get a negative result. And again, you can also pair them up. You can say, okay, well, this would make it positive. These would make it positive. These would make it positive. These would make it positive. But then this one is hanging out by itself. No other negative to pair with it. So we're going to end up with a negative result. And that's why we have negative 9. Hello and welcome to Pre-Algebra Lesson 18. And in this video, we're going to be learning about absolute value. So for our lesson objectives, we want to learn how to find the absolute value of a number. And also we want to learn how to simplify when absolute value is present. So in our last lesson, we were introduced to a new group of numbers known as the integers, right? And this allowed us to see some negative values or some values to the left of 0. So before we start working with these integers, adding and subtracting, multiplying, dividing, it's important that we learn the definition of absolute value. So if we look on the screen here, we see that the absolute value of a number is the distance, okay? The distance between that number and 0 on the number line. So what if I started out by asking you, what is the absolute value of the number 3? And the way we're going to ask for this is we're going to have these vertical bars around the number that we want to find the absolute value for. So this right here is basically saying, what is the absolute value of 3? Okay, that's what this means. Again, the vertical bars are surrounding the number we're trying to find the absolute value for. Now, following our definition that we were given, the absolute value of a number, again, is the distance between that number and 0 on the number line. So if I find 3 on the number line and I find 0 on the number line, I just need to count how far away it is. And it's just 1, 2, 3 units away. So the absolute value of 3 is just 3. Now, one thing I want you to note right away, what if I asked you for the absolute value of negative 3? You're going to find that you're going to have the exact same absolute value because it's 1, 2, 3 units away from 0 as well. So the absolute value of negative 3 is also equal to 3. This goes back to our definition of opposites. Remember in the last lesson where we talked about opposites, we said that opposites were numbers that lied on opposite sides of the number line. So in this case, you have 3 and negative 3. They're on opposite sides. And they had the same distance from 0. So this one has the distance of 3, right? You have to travel 3 units to the right to get to 0. This one has the distance of 3. You have to travel 3 units to the left to get to 0. So opposites are always going to have the exact same absolute value because they have the same distance from 0 on the number line. So for example, if I said, what is the absolute value of 7? And what is the absolute value of negative 7? In each case, the answer is going to be 7. Right? If I look at 7 and negative 7, in each case, I have to travel 7 units to get to 0. Right? 1, 2, 3, 4, 5, 6, 7. And from here, 1, 2, 3, 4, 5, 6, 7. So the absolute value of 7 is 7, and the absolute value of negative 7 is 7. So another thing I want you to note right away is that the absolute value of a number is never going to be negative. It's always going to be 0 or some positive value. And the reason for that is absolute value represents a distance, and a distance is not going to ever be negative. Right? For example, in real life, you think about waking up and going to work. You can either not go to work and drive 0 miles, or you can drive some amount of miles. It could be 10 miles, 20, whatever it is. Doesn't matter. And I know some of you will put in the comments that you could back up, but no, that's not driving a negative amount. Sorry. Do we really need to pull out a number line every time we want to find the absolute value of a number? Of course not. The rule is, if the number is negative, just make it positive. So for example, if I asked you for the absolute value of negative 37, you would just make it positive. It would just be 37, right? Essentially, if it's negative, make it positive. Negative 37 would be 37 units away from 0 on the number line. If the number is 0 or positive, keep it the same, okay? So if the number is 0, so if you have the absolute value of 0, 0 is 0 units away from 0 on the number line, so it's just 0. If it's some positive value, let's say it's, I don't know, 42. It's just that number, right? It's going to be 42 units away from 0 on the number line. All right, let's look at a few problems. So we want to find the absolute value of 19. So again, if it's a positive number, just keep it the same. So the absolute value of 19 is just 19. Because if we had a number line there, I would count 19 units to the left to get to 0 if I started from 19. Right? It's 19 units away. So the absolute value of 19 is just 19. What about the absolute value of 0? Well, again, 0 is 0 units away from itself on the number line, so the answer is 0. What about the absolute value of negative 24? Again, if you have a negative number, just make it positive. So I make this positive, and I get 24. Okay, what about the absolute value of negative 34,422? Well, again, if it's a negative value, just make it positive. So this would just be 34,422. Okay, now we want to replace the question mark with the correct symbol. So we have less than, greater than, or equal to. Okay, for the first one, we're going to look at the absolute value of negative 27, question mark the absolute value of 22. All right, so first let's think about what these are worth. So the absolute value of negative 27 is 27, and the absolute value of 22 is 22. Again, for this one, it was negative, so we just made it positive. For this one, it was positive, so it just stayed the same. So if we think about the relationship here, the absolute value of negative 27 is a larger number, so it's greater than the absolute value of 22. And again, the reason for this is because this ends up being 27 after we apply the absolute value. So 27 would be bigger than 22. And again, you want to point the symbol towards the smaller number. Okay, now we have the absolute value of 0, question mark the absolute value of negative 5. So the absolute value of 0 we know is 0. The absolute value of negative 5 is 5. Again, just change the sign from negative to positive. So which one's going to be bigger? Is 5 bigger or 0 bigger? Well, 5 is bigger. So the absolute value of 0 is going to be less than the absolute value of negative 5. Again, the symbol is going to point to the smaller value. What about the absolute value of negative 7, question mark 7? Well, in this case, the absolute value of negative 7 is 7. So 7 and 7 have the same value, so we're going to use an equal sign. So we're going to say the absolute value of negative 7 is equal to 7. So sometimes we're also going to have to simplify when we're working with absolute value. And one of the things you have to be careful about, in the last lesson I kind of gave you a little trick on how to simplify when you have a bunch of negatives involved. So I want you to look here and see that we have what? We have the opposite of the absolute value of negative 13. Now, let me just kind of put this to the side for a second. I want to show you this problem. So let's say we had the opposite of negative 13. We would count the number of those symbols we have. And again, if it's even, divisible by 2, the result is positive. If it's odd, not divisible by 2, it's negative. So here we have 1, 2 of those symbols. So that's an even number. So the answer is positive, right? Because you'd have the opposite of negative 13. That's just 13. Now, when you're working with absolute value, you can only count the number of symbols you have outside of the absolute value bars. And the reason for that is because, remember, the result of the absolute value operation always makes things non-negative. Okay, always makes it non-negative. So the least it's going to be is 0. Now, thinking about this, if I count only the negatives outside of this operation here, I only have 1. 1's an odd number, so I know the result's going to be negative 13. Right? Please don't make the mistake of trying to apply that trick with absolute value and getting it wrong, because some students will say, okay, I have 1, 2 of those symbols, 2's an even number, I got positive 13. No, because when you evaluate this the slow way, you would say, okay, the absolute value of negative 13 is positive 13, right? You make the negative positive, and then you have the opposite of positive 13, which becomes negative 13. So pay close attention when you have the absolute value operation involved. Okay, now we have the opposite of the absolute value of 21. So again, I would count the number of these symbols that I have outside of my absolute value bars. So I have 2 of them. 2 is an even number, so my result would be positive. But again, if you want to kind of do this the slow way, you have the opposite of, the result of this would be 21. So the absolute value of 21 is just 21, right? If it's positive, keep it the same. So we'll put this in parentheses. So this would be 21 here. And the opposite of 21 would be negative 21. So let's write this as the opposite of negative 21. And then one more time, we'll change the sign to positive 21. But again, the shortcut, count the number of those symbols you have outside of the absolute value operation, and that's going to tell you if it's even, you're going to have a positive number. If it's odd, you're going to have a negative number. Okay, here we have the opposite of, the opposite of, the opposite of the absolute value of negative 53. Again, pay attention. You have 1, 2, 3 symbols outside of your absolute value operation. Please don't count this one, because this one right here, you got to think about it. When we're done with this absolute value operation, this is going to be a positive number. It's not going to be negative, right? It's different than if I had the opposite of, the opposite of, the opposite of negative 53. In this case, this ends up being a positive 53, right? Because I have 1, 2, 3, 4 negatives. 4 is an even number. I'm going to end up with positive 53. This becomes positive, then negative, then positive. Here it's going to be different because I start out, basically you can think about this right here, it's just positive 53. The absolute value of negative 53 will be positive. So this is positive, it's not really negative. So this will end up going to negative, then positive, then negative, right? So that's why you'd end up with negative 53. Again, doing this the slow way, let me kind of show you this. The opposite of, the opposite of, the opposite of, the absolute value of negative 53 is 53. So I'm going to put that in parentheses. Now, change the sign. So this will become the opposite of 53 is negative 53. So the opposite of negative 53. Change the sign again. So it'll become positive 53. So the opposite of 53. And then change the sign one last time to negative 53. And again, I can't repeat this enough. If I just look at how many of these signs I have outside of the absolute value operation, if it's odd, which in this case I have 1, 2, 3, 3 is an odd number, I know I'm going to get a negative result. If it's even, right, divisible by 2, I know I'm going to get a positive result. Okay, last problem. We have the opposite of, the opposite of, the opposite of, and then the absolute value of 6 plus 3. Now, again, I can count the number of symbols I have outside of the absolute value operation. I have 1, 2, 3. So I know the result's going to be negative. Basically, I can just kind of eyeball this and see that I'm going to have the absolute value of 6 plus 3, which is 9. And I know I'd have negative 9, right? It's a very, very simple problem. But let's kind of go through it the slow way. So let's copy this, the opposite of, the opposite of, the opposite of, and then we know 6 plus 3 is 9. So inside of absolute value bars, we'd have 9. And even at this point, we can see we'd have negative 9 as a result. But again, let's keep going. So now we just take the absolute value of 9. That's 9. So we'd have the opposite of, the opposite of, the opposite of, and then we'd have 9. And now we would just go through and take the opposite. So the opposite of 9 would be negative 9. So we'd have the opposite of negative 9. Then take the opposite of negative 9, you get positive 9. So the opposite of positive 9. And then the opposite of 9 is just negative 9. So absolute value is a very easy concept overall. You just have to remember, if you're taking the absolute value of a negative number, make it positive. If you're taking the absolute value of 0 or a positive number, just keep it the same. Hello and welcome to Pre-Algebra Lesson 19. In this video, we're going to learn about adding integers. So the lesson objectives for today, we want to learn how to add integers using a number line. So this will give us a visual representation of what's going on, and it can be helpful if you're struggling with this topic. And then we're going to move on and learn how to add integers without a number line. So this is how we're going to solve our problems moving forward. Okay, so let's start out by talking about the scenario where we're going to use a number line. And basically, we'll start with the easier scenario where we're adding 2 or more integers with the same sign. So a positive plus a positive, which we already know how to do, or a negative plus another negative. So I have here that we would start at the left number that's on the number line. Then this plus here, this is basically for a positive number. If you have a positive number, it indicates a movement right. So for example, let's say I had 4 plus 5. We know that we could start out at 4 on the number line. And then because this is a positive number, I know that I'm going to move to the right. And in this case, I would move to the right by 5 units. And of course, we all know that 4 plus 5 is 9. Let's slide down here. And we see that this right here is for a negative number. And this indicates a movement left. So if I'm adding a negative number, basically I'm going to move to the left. So let's say I had something like 4 plus negative 5. Or actually, let's do -4 plus -5 to have the same sign here to make it a little bit easier. What's going to happen is I'm going to start out at -4 on the number line. And because I'm adding a negative number here, I'm going to move to the left by the absolute value of that number. So the absolute value of -5 is 5. So I'm going to start at -4 and go 5 units to the left. And that's going to put me at -9. And we'll see this in a moment. So I have here, use the absolute value of the number being added to determine how far to move. Let's look at some examples. We want to add each on the number line. And this is not going to be bad at all. Once you do a few of these, it's really, really easy. Okay, so the first thing is when we look at the number line, remember 0 is not positive and it's not negative. So it is neither. If I look to the right of 0, those are the positive numbers. To the left of 0, those are the negative numbers. As we move to the right, remember numbers are increasing in value. And if we move to the left, numbers are decreasing in value. So it's really important to remember that. So let's start out with 4 plus 5 on the number line. Again, all I have to do is start out at 4. And I'm going to add 5. So again, this is a positive number that I'm adding. So I'm just moving to the right by, you could say the absolute value of that number there, but the absolute value of 5 is just 5. So I'm just moving to the right by 5 units. So 1, 2, 3, 4, 5 units. So I end up at 9. So let me circle the starting and the ending. So we know that's 9. If I start with $4 and I make $5 today, well, now I have $9. So that's pretty simple. All right, the more challenging scenario occurs when you add two negative numbers. So thinking about -4 plus -5, well, we saw, let me put a little border here, that 4 plus 5 was equal to 9. Well, here with -4 plus -5, you would start at -4. So let me start here and I'll just circle that. And I'm going to add a negative number. So that means I'm going to go to the left, okay? And I'm going to go to the left by the absolute value of that number. So the absolute value of -5 is 5. So in other words, the sign here is telling me the direction. If it's positive, I'm going to the right. If it's negative, I'm going to the left. And then the absolute value of the number is telling me how far to move. So here I'm just moving 5 units to the left. So I'm going 1, 2, 3, 4, and then finally 5 units to the left. I'm going to end up at -9 there. Okay. And we can do this in our head if you just think about it with money. Let's say that I owe $4 currently. I owe $4 to maybe the bank or something like that. And I go out and I accumulate another debt of $5. So let's say I go out with my credit card and I spend $5. Well, how much do I owe? Well, I can just add those two debts together. -4 plus -5 would be -9. That's something you do in your head. You just say, okay, 4 plus 5 is 9. And then I'm attaching the common sign, which is negative, to show that I owe money, right? So I owe $9, or I could say it's -9 for the sum. Let's take a look at another one. Here we have a -2 plus -3. Before I do that, let me come over here and just do 2 plus 3. So again, you can see that there's a pattern emerging. So 2 plus 3 is what? That's 5. I could start at 2, and I could just go 1, and that color doesn't really show up. So let me change to orange here. So 1, 2, 3 units to the right, and I end up at 5. Okay, let me erase this and go back to -2 plus -3. So here I would start at -2. So let me put that there, and I'll circle this. I'm adding a -3. So again, if I'm adding a negative, the negative tells me I'm going to the left, and then by the absolute value of this number of units. So the absolute value of -3 is 3. So I'm going to the left by 3 units. So 1, 2, 3 units, and I end up at -5. So this is -5. Again, notice you got 5 here and you got -5 here. So I can just add the absolute values here and attach the common sign. If I owe $2 and then I owe another $3, well, that's 2 plus 3 or $5 that I owe. So that can be represented with -5. So all you're going to end up doing is adding the absolute values of the numbers. So just pretending like they're positive and then just attaching the common sign. Here again, you just say, okay, what if they were positive? So 2 plus 3 would be 5, and then attach that common sign, which is negative. Okay, let's look at one with more than 2 integers. So now we have 3 integers, all the same sign. So it's not really any harder. You're going to have -1 plus -2 plus -5. So if I start at -1 and I add -2, I'm just going to the left by 2 units. So 1, 2 units to the left. So that's going to put me at -3. And then I add another -5. So I'm going to go 5 units to the left. So 1, 2, 3, 4, 5. So I'm going to end up at -8 there. So I started at -1, I ended up at -8. So let me put -8 here. And again, you can think about this by just adding whole numbers. Let's say I had 1 plus 2 plus 5. 1 plus 2 is 3, 3 plus 5 is 8. Again, because all the signs here are negative, you would just attach that common sign. So I have a debt of $1 plus another debt of $2 plus another debt of $5. Let's say I owe Steve $1, I owe Chris $2, and I owe Mary $5. Well, how much do I owe in total? I can just add those guys together and I get a total debt of $8, which I can represent with -8. Okay, let's just do one more with the number line and then we'll move off of it. So we have -4 plus -3 plus -1. So let's start at -4. And then we're adding -3. So I'm going to the left, 1, 2, 3 units. So that puts me at -7. And then I'm adding -1. So I'm going one more unit to the left. So I started at -4 and I end up at -8. So this is -8. Once again, you could just add 4 plus 3 plus 1. So 4 plus 3 is 7. 7 plus 1 is 8. And you're just attaching the common sign. I owe $4. I have another debt of $3 and another debt of $1. How much do I owe in total? Well, I owe $8, which can be represented with -8. All right, so let's look at the rule, which I think is pretty easy at this point to understand. When adding 2 or more integers with the same sign, you add the absolute values and keep the common sign. So very, very simple. So I have here, let's try a few without the number line. We have -15 plus -11. So again, this is negative and this is negative. So just put a negative and then just pretend these two numbers are positive. What if I added 15 and 11? A lot of you can do that in your head. You know it's 26. But if you need to do a vertical addition, we can always stop and do that. 5 plus 1 is 6. 1 plus 1 is 2. So you just drag that up there and say this is -26. I owe $15 and then I go out and charge up another $11 on my credit card. How much do I owe in total? Well, I'm going to owe $26. So I can just say that's -26. What about this one? We have -7 plus -1 plus -3. Again, this is negative, and this is negative. So the answer is negative. Just use the common sign. Then just pretend like the numbers were positive. What if I added 7 plus 1 plus 3? 7 plus 1 is 8. 8 plus 3 is 11. So just put that here behind that common sign. So this becomes -11 as the answer. Let's do another one. So here we have -5 plus -1 plus -6 plus -14. So every sign here is negative. So the answer is negative. And then just add the absolute values. So 5 plus 1 is 6. 6 plus 6 is 12. And then 12 plus 14, I think a lot of you know that's 26. You can do it in your head, but let's just do it off to the side just so nobody's lost. 2 plus 4 is 6. 1 plus 1 is 2. So you're just going to bring that over here and say that the answer is -26. All right, so now let's move on and talk about the more complicated scenario. So this is where we're going to add 2 integers with different signs, or sometimes you'll add more than 2 integers. So you'll have many integers that you're trying to add and the signs are mixed. So what happens when we have mixed signs? Let's revisit our number line and try a few problems. Now, before we do this type of problem gives students the most trouble. When you look at, let's say, -8 plus -4, again, this is just an addition problem. We just saw this. Basically, you use the common sign is negative, and then you're just adding, right? You're just saying, well, what is 8 plus 4? That's 12, and then you're just attaching that sign. So this is -12, so that's really easy. I'm just going to tell you before we start this procedure is just as easy. You're now just doing a subtraction problem, okay? So think about -8 plus 4 first on the number line. So here's -8. And then I'm adding 4. So that means I'm going 4 units to the right. So I'm just going to go from right here, 1, 2, 3, 4 units to the right. So that puts me at -4. Does that make sense? I always tell people to use money in your head if you're trying to think about this. Let's say I have a bank account and currently I owe them $8. I go into the bank and I give them $4. Do I still owe money? Yes, I still owe $4. So it makes sense that this is -4 here. Again, I have not given them enough money to get back to 0 or to get back to where I don't owe any money. So basically you could think about always that if I have a negative here, let's say it's -8, that I have to add the opposite of that number. So let's say in this particular case, that's going to be +8 to get back to 0. And we could think about that problem. Let me erase this. So if I have -8, which is 8 units away from 0 on the number line, remember the absolute value of -8 is 8, I would have to go 1, 2, 3, 4, 5, 6, 7, 8 units to the right to get back to 0. So I have to add the opposite of the number to get to 0. Now, if I start adding numbers that are greater than 8, what's going to happen is now I'm going to have a positive balance in my account. Let's say I do -8 plus 9. Well, I'm going to go 1 more unit to the right on this number line, and I'm going to end up at 1 now. So now I have $1 in my account because I paid more money than I owed. So hopefully that does make sense. You can pause the video and really start to think about what's going on here. But essentially, this is going to translate into a nice little procedure for us. All we really have to do is first think about which number is bigger in terms of its absolute value. So which number has the bigger distance away from 0 on the number line. Let me get rid of this and go back to this as the original problem. Well, in this case, the -8 does, right? It's 8 units away from 0 on the number line. 4 is 4 units away from 0 on the number line. So this guy is going to be the winner in terms of our sign. So you use the sign of the number with the larger absolute value. Then I'm just going to put this in parentheses for right now. You think about these two numbers as if they were positive numbers, and you just subtract the larger minus the smaller. That's all you have to do. So it just becomes 8 minus 4. So 8 minus 4. And so this becomes the negative of 8 minus 4 is 4. So this is -4. Let's say you change this around, and now you have 8 plus, let's say, -4. Well, this is going to be a positive result. You could put a plus out here if you want, or you can leave it off. It's up to you. And then you're just going to subtract the absolute values. So what is 8 minus 4? So 8 minus 4, well, that's going to be 4. And that should make sense in this particular case. If I had 8, let me get rid of this problem right here. If I had $8 in my account, so let's start here, and I spend 4, or I have a debt of 4, let's say I charge up 4 on my credit card, well, basically when I settle up, I'm going to have $4. So I'm going to go 1, 2, 3, 4 units to the left, and I'm going to end up at 4. So we'll see later on that 8 plus -4 can be directly written as 8 minus 4. You can immediately go to that. So if I had something like, let's say 10 plus -5, I'll immediately just write that as 10 minus 5. So this is a very easy problem to do a conversion with. If you have something like, let's say -10 plus 5, well, this one's a little bit more tricky because the negative has the larger absolute value. So in this case, I just say, okay, well, I'm going to use the negative, and now I'm going to convert this into 10 minus 5 in my head. 10 minus 5 is 5, so this gives me -5. Okay, let's look at a few more. So here we have a 9 plus -7. So let's start out at 9 on the number line, and I'm adding -7. So I've incurred a debt of $7, or let's say someone took $7 away from me for a product that I bought, something like that. So I'm just going to move to the left by 1, 2, 3, 4, 5, 6, 7 units. So I end up at 2. So basically, you could have written this as 9 minus 7, which equals 2. Again, the larger absolute value here is 9. 9 is 9 units away from 0 on the number line, and -7 is 7 units away from 0 on the number line. So basically, I'm not taking away enough to get me to 0 or some negative value, so the answer is going to be positive. Right? And then you could just subtract the absolute values. 9 minus 7 is 2. If I change this around, let me put this a little bit tighter in there. If I change this around, and let's say I do -9 plus 7, well, now I owe $9, right? So I'm here at -9. I go into the bank and I give them 7. Now I still owe $2. So I've got to go 1, 2, 3, 4, 5, 6, 7 units to the right. And now I'm at -2. Right? So I started at -9 and I'm at -2. So I have not gotten out of the hole yet. So here you would say this is the negative of, and then you go 9 minus 7. So 9 minus 7. And let me make that 7 a little bit better. So this becomes -2. Okay, let's look at one more of these and then we'll just run through a bunch of examples. So we have -7 plus 12. So start out at -7 and I'm going to add 12. So I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I end up at 5. So here's -7. Again, that should make sense. If I owe $7 and I pay $7 off, I'm going to be at 0. But now I didn't just pay $7 off, I paid $12 into my account. So I should have $5 more left in my account. So this really becomes a subtraction problem. It becomes 12 minus 7, which is 5. Again, if this number is larger in terms of absolute value, you could just flip it around and turn it into a subtraction problem. You could really just say, okay, well, this is going to be 12 plus -7, which becomes 12 minus 7, which equals 5. This is something you're going to do mentally very, very shortly after you start working enough problems. If you started with something like -12 plus 7, well, then in this case, I owe $12, but I'm only paying off 7. So it makes sense that I should still be in the hole, right? Or have a negative account balance. So this will be negative. And then I'm just going to say, okay, what is 12 minus 7? Just subtract the absolute values, the larger minus the smaller. 12 minus 7 is going to be 5. So this ends up giving me -5. All right, let's go through the procedure and then we'll just run through a bunch of problems. So when adding two numbers with different signs, use the sign of the number with the larger absolute value. then think about the numbers in terms of their absolute values and subtract the smaller from the larger. So you're doing a subtraction problem, figure out what your sign is, and then just subtract the absolute values, larger minus smaller. That's all it is. Okay, so let's try a few without the number line. So here we have 13 plus negative 8. Again, you can easily convert that in your head into 13 minus 8. And the reason is simple. This guy is larger in terms of absolute value. I have $13. You could say I'm incurring a debt of $8. Whatever it is, I'm taking 8 away from what I have. So 13 minus 8 would just be 5. So the sign of the number with the larger absolute value is positive, and then you're subtracting the larger absolute value, which is 13, minus the smaller absolute value, which is 8. 13 minus 8 would give you 5. If you had negative 13 plus 8, well then the 8 that you're adding is not enough to cover the debt, right? You owe $13. So this guy will be negative. The larger absolute value is negative, so this sign will be negative, and then you're just doing what is 13 minus 8, which gives you now negative 5. So that's the difference between these two. I started with 13, which is a bigger number in terms of absolute value, and I added a debt of 8, or I subtracted away 8, however you want to think about that. Basically, I'm going to end up with $5 in my account. Here I owe $13, and I only pay off 8, so I'm going to have a negative here, and then I do 13 minus 8, I end up with a debt of $5. So that's the difference between these two. What about 12 plus negative 2? Again, the absolute value of 12 is bigger than the absolute value of negative 2, so this will be positive. And then you could just subtract the larger absolute value minus the smaller. So this turns into 12 minus 2, which is 10. If I had negative 12 plus 2, well, now this is going to be negative. I owe more than I'm putting back in. The absolute value of negative 12 is larger than the absolute value of 2, so this is going to be negative. And then you do the same subtraction. You're still going to do 12 minus 2. So this part's still 10, but I have that negative there. So this would be negative 10. What about 14 plus negative 23? So the absolute value of 14 is 14. The absolute value of negative 23 is 23. So we know this is negative, and then you're just going to do a subtraction. What is 23 minus 14? Let's borrow here and put a 1 there. 13 minus 4 is 9. 1 minus 1 is 0, so this is negative 9. And again, if you change this up and you said, well, I have a negative 14 plus 23, well, now I owe $14 and I'm putting 23 in my account. So of course I expect to have a positive balance, right? So the sign of the number with the larger absolute value is positive. So the answer would be positive. And now you can just change this into 23 minus 14, which of course we know is 9. What about negative 31 plus 25? Well, here the sign of the number with the larger absolute value is negative. So we're going to use that sign. And then you're just going to subtract the absolute values, larger minus smaller. So 31 minus 25. Let's borrow here and put a 2. Maybe that 5 could look a little bit cleaner. And let's put this as an 11. 11 minus 5 is going to be 6. 2 minus 2 is 0. So this would be negative 6 here. And again, if you had changed that up and said you have $31 and you add a negative 25, so basically you spend 25 or you incur a debt of 25, however you want to think about that. Well, what's going to happen is I have enough money to cover that. So I know I'm going to have a positive balance in my account because the absolute value of this positive number is larger than the absolute value of this negative number. And then I just do my subtraction. So larger absolute value minus the smaller. What is 31 minus 25? We know that's 6. So here that would be 6. Okay, let's do some problems where it's mixed. So what I'm going to tell you is when you do mixed addition, the way I like to do it is I like to add the numbers with the same sign first. It just makes it easier. You can reorder this using the commutative property. You can always add in any order. So I'm just going to say that this is 12 plus 7 done first, and then plus negative 15. So we know 12 plus 7 is 19. We've been doing that forever. So this is 19, and then plus negative 15. And then of course here, 19 has the larger absolute value. So the answer will be positive. And then you're just doing a subtraction. So larger absolute value minus smaller. So what is 19 minus 15? Well, that's going to be 4. What about 5 plus negative 2 plus 1 plus negative 7 plus 11 plus negative 14? So let me put 5 plus 1 plus 11 next to each other, and then plus negative 2 plus negative 7 plus negative 14. I'll put those next to each other. And again, just add the numbers with the same sign first. So those guys, let me do this in a different color. And those guys, you'll do them separately. So what is 5 plus 1? That's 6. 6 plus 11 is 17. Again, you can always stop and do a vertical addition. 1 plus 6 is 7. Bring down the 1. So that's 17. So this right here would be plus. Now you have negative 2 plus negative 7 plus negative 14. So I know that's negative. And then just add 2 plus 7, that's 9. And then 9 plus 14, A lot of you know that that's going to be 23. But 4 plus 9 is 13. So put the 3 down, carry the 1. 1 plus 1 is going to be 2. So this would be negative 23 here. So now, which number is larger in terms of its absolute value? Well, negative 23 is. So this would be a negative. And then you're just doing a subtraction. So what is 23 minus 17? A lot of you, again, know that's 6 already. But let's just do this over here so nobody is lost. Borrow here, and that 1 could be better. So this is 13 minus 7, which is 6. 1 minus 1 is 0. So this right here, you drag that up, and you would get negative 6 as the final answer. All right, let's take a look at one more of these. So here we have negative 3 plus negative 1 plus 8 plus negative 5 plus 9. So let's write negative 3 plus negative 1 plus negative 5 plus 8 plus 9. Okay, so negative plus negative plus negative here would give me a negative. And then just add the absolute values. So 3 plus 1 plus 5. 3 plus 1 is 4. 4 plus 5 is 9. So this is negative 9. And then plus, we know 8 plus 9 is 17. So now, if you think about this, this number is larger in terms of its absolute value. So our answer will be positive. And then you're just subtracting the larger absolute value minus the smaller. So you're just turning this around into what is 17 minus 9. And a good way to do this, I think, is to just reorder that and say this is 17 plus negative 9. When I see that immediately, I know that's 17 minus 9. And of course, that gives me a final answer of 8. Hello and welcome to Pre-Algebra Lesson 20. In this video, we're going to learn about subtracting integers. So the lesson objective for today, we're just going to learn how to subtract integers. And the procedure for this is pretty straightforward. If you know how to add integers, then you can automatically subtract integers. So I have here, the first thing you'd want to do is to leave the first number, and that means the leftmost number of the subtraction problem. We call that the minuend. This is going to be unchanged, so don't mess with that at all. The second thing is you're going to change the subtraction operation into addition. So instead of a minus, you're going to put a plus. Then the last thing is to change the second number. So that's the rightmost number of the subtraction problem. We call this the subtrahend. We're going to put this as its opposite. So just change the sign of the number. So basically you're changing your subtraction problem into addition of the opposite. Let's take a look at a few problems using the number line. I think this is not too bad overall. If you can add integers, then you can subtract integers. It's basically the same thing with just an additional step. So here we have 7 minus 9. So before we do anything, let's just think about this logically. If I have $7 in my account, then I can only spend $7 before I go negative. I think we all know that. So if I'm spending $9, well, I'm spending $2 more than I have, so I should expect to have a balance of -2. So if I think about this, using my procedure, I would keep the first number unchanged, so just write a 7. Then change this subtraction into addition, and then change the number being subtracted away. In this case, it's 9. You're going to put that into its opposite. So just change the sign. For positive 9, it would become negative 9. So this is 7 minus 9 is the same thing as 7 plus negative 9. So I have 7 and you take 9 away from me. It's the same thing as if I said, hey, I have 7 and I have a debt of 9 and we're going to settle up, right? So you're taking 9 away from me. It's the same thing either way. So when I think about this, using my procedure for adding integers, well, I want to use the sign of the number with the larger absolute value. The absolute value of negative 9 is 9. The absolute value of 7 is 7. So negative 9 has a larger absolute value. So we get a negative for the result. Now you're just going to do a subtraction. So you're going to do larger absolute value minus the smaller. So what is 9 minus 7? And this ends up giving me 9 minus 7 is 2. You apply the negative. This is -2. But we knew that already because we just thought about it logically. If I have $7 in my account and I spend $7, I'm at 0, but I'm spending 9. So I'm spending 2 more than what I have. So I should expect to be at -2 for my account balance. You can also think about this on the number line. Let's say again, we start out at 7. So this is my account balance here. And I take away 9, or you could say you add -9, whatever you want to do there. You're basically going to move 9 units to the left. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, and then finally 9. So I started at 7. Notice when I added -7 or subtracted away 7, I got to 0. And then if I subtract 2 more away or I add another -2, I'm going to be at -2 for the result. So 7 minus 9, which is the same thing as 7 plus -9, gives us -2. Okay, let's look at a similar problem. So here we have 5 minus 11. So again, if I have $5 in my account and I go through and I buy $11 worth of stuff, I know that I overspent by $6, right? Because if I spend $5, I'm at 0. And then basically I'm going to spend another 6 from what I have. So that's going to put me at -6. Well, we can show this by saying that I have 5, keep that leftmost number the same. I'm going to change the minus into a plus. So now this is addition. And I'm going to change that 11 into its opposite. So that would be -11. So this becomes what? Use the sign of the number with the larger absolute value. So -11 has a larger absolute value. So this would be negative. And then inside, just subtract the smaller absolute value from the larger. Or you can say the larger absolute value minus the smaller. However you want to think about that. It's going to be 11 minus 5 inside. So 11 minus 5 is 6. So this becomes -6 as the answer. Again, using the number line to see this visually, if you need that, here's 5. So I start out with $5 in my account, and I'm going to spend 11. So first, let's say we spend 5. So 1, 2, 3, 4, 5 units to the left. At that point, I'm at 0. So there's no more money in my account. Well, basically, I'm going to go another 6 units to the left because I'm spending $6 more, or I'm adding another -6, however you want to think about that. So I'm going to go another 1, 2, 3, 4, 5, 6 units to the left to end up at -6. So basically, I started out with 5, and I added -11, or I took 11 away, and I went 11 units to the left on the number line, so I end up at -6, or I owe $6 to the bank. However you want to think about that. Okay, we'll do one of these without a number line, and then I'm going to change it up a little bit. I'll go back to the number line. So for this one, we have 15 minus 18. So just write this as 15 plus a -18. So it starts to become pretty quick for you. Leave this first number unchanged. So 15 is unchanged. Change your subtraction to addition. Change the number being subtracted away into its opposite. So 15 minus 18 is 15 plus -18. So the -18 has the larger absolute value, so we'll use that sign. And then you're just going to subtract the larger absolute value minus the smaller. So 18 minus 15. So this becomes the negative of 18 minus 15 is 3. So this is just -3. Again, if I start with $15 in my account and I spend 18, so I'm taking 18 away from what I have, I would expect to basically have -3 because I spent $3 more than what I had. Okay, for this problem, we will return to the number line. So the leftmost number, you'll notice that that's a negative now. So this is actually going to make the problem a little bit easier. So let's just go with our procedure. The leftmost number is -5. I'm not going to mess with that. I'm going to change my subtraction operation into addition. And then I'm going to change the number that's being subtracted away. Here, that's +3. I'm going to put that as its opposite. So this will be -3. So we can write -5 minus 3 as -5 plus -3. And so we have this common sign that's negative. So the answer will be negative. And then you just add the absolute values. So 5 plus 3 would be 8. So the final answer here is -8. I think it's also useful to see this on the number line. So let's say that I start with -5. So I'm starting with this leftmost number here. And then whether I think about this as subtracting away 3 or adding -3, I'm moving 3 units to the left. So I'm going 1, 2, 3 units to the left. So I started at -5. I'm going to end up at -8. All right, what about -56 minus 18? So this would be -56 plus a -18. So basically, you know this would be negative because that's the common sign. And you could just add 56 plus 18. Some of you can do that in your head. It's going to end up being 74. But let's just go through this. So 6 plus 8 is 14. 4 down, carry the 1. 1 plus 5 is 6, plus 1 is 7. So that's 74. So this becomes a -74 for your final answer. What about -107 minus 29? So let's say this equals -107 plus a -29. So we know the answer is negative, and you're just going to say, well, what is 107 plus 29? So just add the absolute values. 7 plus 9 is 16. 6 down, carry the 1. 1 plus 0 plus 2 is 3. Bring down the 1. So this is 136. So again, drag that up there. We'll say the final answer is -136. All right, now let's talk about something that gives students a lot of trouble in this section, and that is subtracting away a negative is the same as adding a positive. So you might see something like 4 minus a -3, and we say that's equal to 4 plus 3. So minus a negative is plus a positive. I'll give you a little bit of an explanation in a moment. For right now, let's just use the procedure that we talked about earlier. So for the leftmost number, the minuend is going to stay the same. So this is 4 and this is 4. The subtraction operation becomes addition. So this is a minus and this is a plus. And then the number being subtracted away, again called the subtrahend, this guy is going to get changed into its opposite. So the opposite of -3 is +3. So just following the procedure we already talked about, you would get the right answer. So this becomes 4 plus 3, which we know is 7. You see that I have 4 minus 2 equals 2, 4 minus 1 equals 3, and 4 minus 0 equals 4. You'll see that each time the number that's being subtracted away, or the subtrahend, decreases by 1, the difference, or the result from the subtraction operation, increases by 1. That should make sense because I'm taking 1 less away, so the result, or the difference, should be 1 larger. So 4 minus 2 is 2, 4 minus 1 is 3, 4 minus 0 is 4. So now when we get into 1 less than 0, well, that's going to be -1. So I have 4 minus a -1, which gives me 5. So it's the same thing as if I said, what is 4 plus 1? Well, that's 5. Then 4 minus a -2, that's 4 plus 2, that's 6. Then 4 minus a -3, that's 4 plus 3, that's 7. Let's look at some examples. So here we have -7 minus a -20. So this becomes -7 plus 20. So again, minus a negative is plus a positive. Keep this first number unchanged, change the subtraction into addition. This number right here that's being subtracted away, it's -20, it becomes its opposite, which is +20. So this is what? The sign of the number with the larger absolute value is positive, and so you're just going to change this over into 20 minus 7, which becomes 13. What about -13 minus a -6? So -13 plus 6. Minus a negative is plus a positive. So the sign of the number with the larger absolute value is negative. So this will be a negative, and then just subtract the larger absolute value minus the smaller. So this is 13 minus 6. So this becomes negative. 13 minus 6 is 7. So -7. What about -94 minus a -17? So -94 plus 17. Minus a negative is plus a positive. So let me say that the sign of the number with the larger absolute value is negative. And then you're just going to go 94 minus 17. So in other words, you're saying the larger absolute value minus the smaller. So 94 minus 17. So this gives me what? Let me borrow here, put an 8, and this will be 14. 14 minus 7 is 7. 8 minus 1 is 7. So this would end up being -77. All right, let's wrap up the lesson. And what we're going to do now is talk about multiple operations, so basically subtracting more than 2 integers. So when we perform subtraction with more than 2 integers, the rules are the same. Change each subtraction to addition of the opposite. This is going to help you a lot because remember, addition is commutative, so you can add in any order that you'd like. So here we have 9 minus 3, minus 8, minus 12, minus 4. So let me go equals 9, the leftmost number, not going to mess with that. So I'm just going to copy that. And then everything else, you're going to go plus negative. So this will be plus -3, and then plus -8, and then plus -12, and then plus -4. So now what I'm going to do is I'm going to add all these numbers over here because they're all negative first, right? So I'm just going to keep 9, and then I'm going to say negative plus negative plus negative plus negative is going to be a negative. And then just add the absolute values. So 3 plus 8 is 11, 11 plus 12 is 23, and then 23 plus 4 is 27. So this would be -27 here. And I should probably show that in case you are not using a calculator. So let me do that real quick. So 3, 8, you have 12, and then you have 4. Really quickly, 2 plus 3 is 5, 5 plus 8 is 13, 13 plus 4 is 17, so put a 7 down, carry the 1, 1 plus 1 is 2. So this is 27, that's where I got that from. I know some of you are not using a calculator, and you're just getting up to speed with addition. So now we have 9 plus -27, so this right here would be a negative because the sign of the number with the larger absolute value is negative, and then you're going to subtract the larger absolute value, which is 27, minus the smaller, which is 9. So let's do that off to the side. So 27 minus 9, borrow here. This is a 1. This is a 17. 17 minus 9 is 8. Bring down the 1. So this is going to be 18. So we'd have -18 as the answer. Okay, let's do another one. So here we have -2 minus a -3 minus a -9 minus 14. So -2, don't mess with that. Minus a negative is plus a positive. Minus a negative is plus a positive. And then you have minus 14, that's plus -14. Okay, so I'm going to reorder this and put -2 next to -14. Those have a common sign. And then I'm going to put 3 and 9 together. And then basically negative plus negative is negative. 2 plus 14 is 16. And then plus 3 plus 9 is 12. So now we know the answer would be negative because negative 16 has a larger absolute value, and you're just going to do 16 minus 12. I don't think you need a vertical subtraction for that. It's just going to be 4. So this would end up being a negative 4 as the answer. Okay, let's just do one more. So here we have negative 5 minus a negative 17, minus 8, minus 9, minus a negative 4. So negative 5, don't mess with that. And then minus a negative is plus a positive. And then we're subtracting away 8, so that's plus negative 8. We're subtracting away 9, so that's plus negative 9. And then minus a negative is plus a positive. Okay, so I'm going to rearrange this and say that we have 17 plus 4, and then plus negative 5, and then plus negative 8, and then plus negative 9. So 17 plus 4, again, if you need to, you can just do a vertical addition. 7 plus 4 is 11. 1 down, carry the 1. 1 plus 1 is 2. So that's going to be 21. And then for this one, negative plus negative is a negative. And then we'll think about 5 plus 8, that's 13. And then plus 9, let's just do that off to the side. 3 plus 9 is going to be 12. 2 down, carry the 1. 1 plus 1 is 2. So that would be negative 22. I think we can all see that 21 plus negative 22 would be negative 1. But again, to go with the official procedure, we know that this would be negative because negative 22 has a larger absolute value. And so then you would just do the larger absolute value, which is 22, minus the smaller, which is 21. And so this is going to be the negative of 22 minus 21 is 1. So basically negative 1 for the final answer. All right, let's take a look at an alternative way to think about why subtracting away a negative becomes adding a positive. We saw this with a pattern. I'm going to give you one other approach to use. There are many available. Some people will show this as taking away a debt. Some people, instead of using a horizontal number line like I'm going to use here, you'll see a vertical number line, and maybe they'll use something like temperatures, so a positive and a negative temperature. Again, lots of different ways to think about this. So we're not going to actually do a number line subtraction if that's what you're thinking. What I'm going to do is think about the distance between 2 points on a number line. So let's start out with point A, and that's going to refer to 4. Let me highlight this as I go. So point A refers to 4 on the number line, and point B refers to 1 on the number line. Okay, so if I ask you for the distance between those 2 points, what am I asking for? Well, if I go from B to A or from A to B, how far do I need to travel? And remember, when we think about distance, like we talked about in the lesson on absolute value, it's non-negative. So it's either 0, meaning I get in my car and I don't go anywhere, or it's some positive value. So I go somewhere. If A is your house and B is the coffee shop, well, if I go from A to B, so from my house to the coffee shop, let's say that's 3 miles. On the return trip, when I go from B to A and I'm going back, well, my car's odometer doesn't say, okay, this is negative 3 miles because we're on a return trip. No, I go 3 miles there and I come 3 miles back. So the distance is 3 either way. So that's why you see this set up like that. So we can show this as the distance between A and B as being equal to 3. Now, what's another way to do this? Your book will give you a subtraction formula that involves the absolute value. I'm going to keep this simple, and I'm just going to say that we're going to subtract the larger number minus the smaller, just for the sake of this lesson, to keep it simple. So I'm going to say this could also be 4 minus 1, which would give us 3. So I can do it with subtraction, larger minus smaller, or I can go through and manually count, either going from B to A, 1, 2, 3, or from A to B, 1, 2, 3. Again, don't worry about the direction. It's just how far am I traveling. So we can see that the distance between A and B on this number line can be found as 4 minus 1, which is going to give us 3. So let's go into something we already looked at. So what about 4 minus a negative 3, which becomes 4 plus 3, which equals 7? We're going to show this using the distance between these 2 points. Now, instead of this point B being at 1, it's going to be at negative 3. Point A will still be at 4. So let me highlight this, and then this, and this. So let's think about the formula we just had. The distance between A and B, we saw a moment ago, we had 4, and then we had 1, so we did 4 minus 1, larger minus smaller. So now what I'm going to do is 4 minus a negative 3. So again, larger minus smaller. We know that negative 3 is smaller than 4 because negative 3 lies to the left of 4 on the number line. So this right here, if I went through and counted, starting from 4, well, I would go 1, 2, 3, 4. So at 0, I've traveled 4 units. And then to get to negative 3, I've got to go another 1, 2, 3 units. Okay, so that means that this distance right here is 4. So from right here to right here. And then this distance right here is 3. So from right here to right here. So I basically take that starting number, which is 4, and then I'm going to add on another 3. So how can I look at that and get that? Well, I need this part right here, which is the 4, and then I need to add the opposite of whatever this negative number is to get this plus 3, or to tack on an additional 3 to get the total distance. So this statement, 4 minus the negative 3, becomes 4 plus 3, which becomes 7 as the answer. Now, looking at another one, let's say that we had point A. Now that's going to be at negative 1. So A, that point is at negative 1. Point B will now be at negative 6. Well, I can still use the same strategy. So the distance between A and B would be what? Take the larger number. In this case, it's negative 1. Negative 1 is to the right of negative 6, so it's the larger number. And then minus a negative 6. So I'm just subtracting the larger minus the smaller. So this should give me the distance between these 2 points. So looking at this and just counting, I can see that if I go from B to A or A to B, it doesn't matter. 1, 2, 3, 4, 5. That's my expectation. So I should get a 5 here. But how do I go from negative 1 minus a negative 6 to 5? Well, I'm going to have to change this minus a negative to plus a positive. So we'd have negative 1 plus 6, which would give us 5. Hello and welcome to Pre-Algebra Lesson 21. In this video, we're going to learn about multiplying and dividing integers. For the lesson objectives for today, we're going to learn how to multiply integers, and we're also going to learn how to divide integers. All right, so at this point in the course, we should know how to multiply whole numbers together. And we know that unless we have a factor of 0, if we multiply two whole numbers together, we're going to get a positive product. So I have here, we all know that the product of two positive numbers is positive, even if you've never thought about it. So we have that a positive times a positive will give us a positive. All right, so now let's build up to the rules where we're going to multiply with negative numbers. So first we have 4 times 3. So from the multiplication tables, we know the answer is 12. But going back to earlier in the course, we said that multiplication was a shortcut for repeated addition. So really I could write this as 3 plus 3 plus 3 plus 3. So I have 1, 2, 3, 4 of these guys. And so, of course, I could add 3 plus 3 is 6, 6 plus 3 is 9, 9 plus 3 is 12. So I get 12 either from this guy or from the multiplication tables and going with this guy. So we see that it's just a shortcut for repeated addition. Now, what if I throw something in the mix like 4 times negative 3? Well, what does this mean? Again, if I follow this same thought process, well, it means that I have a repeated addition here where I have negative 3 plus negative 3 plus negative 3 plus negative 3 one more time. Well, we know how to add integers already, and basically we have a common sign, so we'll just put a negative right there, and then you could just add the absolute values. So 3 plus 3 plus 3 plus 3 is going to be 12. So the answer here becomes negative 12. Does this make sense? Just stop for a moment and think about it. Let's say that you are losing $3 a day at your business or whatever you're doing. So day 1, day 2, day 3, day 4, instead of adding those guys together, you could do a quick multiplication and say, okay, well, there's 4 days where I lost $3 each day. I would do 4 times 3 in my head and say that's 12, and then I would apply a negative to it because it's a loss. So that's basically what we're going to be doing when we multiply integers. Okay, we're going to think about the absolute values being multiplied, and then we're going to attach the sign that we need to. All right, now I want to show you something else because it's a little bit confusing when we go to negative 3 times 4, okay? The way I like to show this is using my commutative property. So let me erase this real quick. We already know that 4 times 3 is equal to 3 times 4. So we can legally switch the order of the factors. If I think about 3 times 4, let me write that out. So 3 times 4, this is what? This is now going to be 4 plus 4 plus 4, which is also going to give me 12, right? So 4 plus 4 is 8, 8 plus 4 is 12. So if I get something like, let's say, negative 3 times 4, I can legally switch the order and say that this is 4 times negative 3, and I'm right back to this definition right here, which gives me negative 12. So we can see that a positive times a negative gives me a negative, and a negative times a positive gives me a negative. Let's go through the same thing with this guy right here. I'm just going to slide down a little bit. So we have 5 times 2. So let's start out with what we know. This is 2 plus 2 plus 2 plus 2 plus 2. So I have 1, 2, 3, 4, 5 of these guys. And so we know that 5 times 2 from the multiplication tables would be 10. But again, you could add 2 plus 2 is 4, plus 2 is 6, plus 2 is 8, plus 2 is 10. So we can also do 5 times negative 2 in a similar way. So this would be negative 2 plus negative 2 plus negative 2 plus negative 2 plus negative 2. And of course, this would be negative 10. Now, if I change the order, let's say I was given negative 2 times 5. Well, of course, I could just flip it back, right? So it's going to give me the same answer because of the commutative property of multiplication. So I can just legally say that this is the same as 5 times negative 2, which would give me this negative 10. And if you were presented with, let's say, negative 5 times 2, well, you could flip that around into 2 times negative 5. And you could say that this is equal to what? This is negative 5 plus negative 5, which would be negative 10 as well. Okay, so let's look at the sign rules here. So we saw that a positive times a negative or a negative times a positive is going to give us a negative. So that's pretty easy to understand. Where we start running into problems is where you get negative times negative, and we say that's a positive. All right, let's quickly think about this pattern to show that a negative times a negative is a positive. There's other ways you can show this, but I think this is the quickest way and the easiest way to think about it. So if you have 3 times negative 3, we say that's negative 9. So we know that already, that 3 times negative 3 can be written as negative 3 plus negative 3 plus another negative 3. And of course, that is negative 9. Now, looking at this pattern, as we decrease this factor on the left by 1, so in other words, now this is going to be a 2, what's going to happen is the product here is going to increase by 3. So this 2 times negative 3 is equal to now only negative 3 plus negative 3. And so this would give me a negative 6. So I've increased by 3. Now if I go to 1 times negative 3, I'm increasing by 3 again, right? So this is negative 3. And the pattern just continues. So now this goes to 0 and this goes to 0, so I'm increasing by 3. Let me actually get rid of this. And I'm just going to show this as this going plus 3. And this going plus 3. And this going plus 3. So when you get here to negative 1 times negative 3, again, this is just decreasing by 1. So from 0, if I subtract away 1, I'm at negative 1. And this is still increasing by 3. So plus 3. This goes down by 1. This increases by 3. So plus 3 and then plus 3. So negative 1 times negative 3, again, using this pattern, would be positive 3. Then negative 2 times negative 3, using this pattern, would be positive 6. And then negative 3 times negative 3, using this pattern, would be positive 9. All right, so once you have the sign rules down, you're ready to multiply integers. And basically, if you can multiply whole numbers, then you could just blow through these problems. The first thing is you want to determine the sign of the product. So if you have a positive times a positive or a negative times a negative, so if you have the same signs, your answer or your product will be positive. And then if you have different signs, so a negative times a positive or a positive times a negative, your answer will be negative. So you have a negative product in that situation. So once you figure out what the sign is, you just want to multiply the absolute values. So it's really, really quick. So let's come through here and just blow through some of these problems. You have a negative 2 times 7. Negative times positive is negative. Again, different signs. Then just multiply 2 times 7, that's 14. So the answer is negative 14. Here we have 4 times negative 4. So you have a positive times a negative, that's a negative. So different signs, negative product. Then 4 times 4, just multiply the absolute values, that's 16. So the answer is negative 16. Here we have negative 11 times 5. So you have a negative times a positive, that's a negative. And then 11 times 5, that's 55. So this is negative 55. Here we have negative 12 times negative 9. So a negative times a negative is a positive. So when you first start doing this, you can write out a plus symbol if you want. Of course, it's not necessary. So I'm just going to do it just for the sake of completeness here. Now, I want to do 12 times 9. Some of you are still learning how to multiply. So I'll do that as a vertical multiplication. So 9 times 2 is 18. 8 down, carry the 1. 9 times 1 is 9, plus 1 is 10. So this is 108. So this is positive 108. Of course, you can keep the plus sign out there if you want, or you can just write 108. But negative times negative is positive, and also positive times positive is positive. So if you have the same sign, negative and negative, then basically you're going to have a positive product. Okay, here we have negative 10 times negative 4. So we know this is a positive. Again, you can put a plus sign out there or leave it off. It's up to you. And then if we're multiplying 4 times 10, right, you're multiplying the absolute values there. Well, you just multiply 4 times 1, that's 4. And then just attach one trailing 0. So this would be positive 40. Then here, a negative times a negative, again, is a positive. And then you're doing 15 times 14. Let me do that over here. So 15 times 14. 4 times 5 is 20. 0 down, carry the 2. And then 4 times 1 is 4, plus 2 is 6. And then let me erase this. 1 times 15 is 15. But remember, you're starting in the tens place here, so you've got to move this over. So you're going to put a 5 here and a 1 here. And then let me just add this. So bring down the 0. 6 plus 5 is 11. 1 down, carry the 1. 1 plus 1 is 2. So this would be 210. So this would be 210. All right, now let's talk about what happens if we multiply more than two integers. So this is just as easy. First, let me do this the long way, and then we'll think about what's going on. So let's say I work left to right, and I go negative 6 times 1, and that's going to give me negative 6. Negative times positive is negative. 6 times 1 is 6, so that's negative 6. So let me copy this. So times negative 8, and then times negative 4. So now you have a negative 6 times a negative 8. Negative times negative is positive, and then 6 times 8 would be 48. So this is positive 48, and then times negative 4. So here, positive times negative is negative, and then 48 times 4, some of you can do that in your head. It's going to be 192, but just in case you can't, 4 times 8 is 32, 2 down, carry the 3. 4 times 4 is 16, plus 3 is 19. So bring this over here. The final answer is negative 192. Now, an easier way to do this is to count the total number of negative factors. Now, if the total number of negative factors is going to be an even number, and I'll explain what that is in a moment, then you're going to have a positive product. If the total number of negative factors is an odd number, I'll explain what that is in a moment, then you're going to have a negative product. Let me actually erase this real quick. And I'm just going to put this up here. This is negative 192. I want you to see what would happen if I wrote negative 6 times negative 1 times negative 8 and then times negative 4. How would that change the product from this guy going to this guy? Well, what's happening is, in this particular case, notice that you have these two guys that you can pair up, and then you have this 1 left over. So basically you have 3 negative factors, and 3 is an odd number. Again, I'll explain what that is in a moment. So this guy right here gives me a negative product. But this guy, I have these two that I can pair up, and these two that I can pair up. So basically each pair creates a positive, right? Each pair of negatives. So negative times negative gives me a positive, and then negative times negative gives me a positive. So because I have 1, 2, 3, 4 negative factors, and 4 is an even number, this is going to be a positive product. So this would change this to positive 192. Now, when I say even and odd, what do I mean? We haven't gotten to what we call the divisibility rules yet, but basically, if you can divide a number by 2 and there's no remainder, so something like 2 divided by 2 is 1, 4 divided by 2 is 2, 6 divided by 2 is 3, so on and so forth, well, that's an even number, right? You can basically pair things up. So if I had, let's say, negative 6 times negative 1 times negative 8 times negative 4, and let's say I tacked on times negative 1 and then times negative 1, well, here's a pair, here's a pair, here's a pair. I have 6 negative factors, so that means I'm going to be able to pair these negatives up, and there's nothing left over, and so I'm going to end up with a positive result. So this would still be positive 192. Now, if I took one of these away, like this, well, now the answer is going to change into negative 192 because I can pair these guys up and pair these guys up, but this is a leftover. So that means that an odd number would be something that's not divisible by 2. So in this case, you have 1, 2, 3, 4, 5 of these guys. If I take that 5 and I divide it by 2, what's going to happen is I'm going to get 2 with a remainder of 1. So you have 1, 2, and then 1 left over. That 1 left over, or that remainder, is always going to give you a negative because I can't pair it with another one. If I go back to times negative 1, well, now I can pair it up. I have 6 of these guys. 6 divided by 2 would be 3, right? 1, 2, 3 of those guys. So this would give me a positive 192. Let's fly through this now. So we have negative 8 times 3 times negative 2 times 11. Okay, so I have 1, 2 negative factors. 2 is an even number. 2 divided by 2 is 1, no remainder. And so I know I'm going to have a positive product. So now I can just multiply absolute values. 8 times 3 is 24. 24 times 2 is 48. So I need to know what is 48 times 11 now. And so 1 times 48 is 48. And then this one, again, you've got to move down. 1 times 48 would be 48. And let's add here. So 8 comes down. 4 plus 8 is 12. 2 down, carry the 1. 1 plus 4 is 5. So let's drag that up there and say the final answer is 528. Okay, let's take a look at one more. So here we have negative 2 times 5 times negative 1 times 3 times negative 20 times negative 30. So this looks a lot worse than it is. First, again, I would count. I have 1, 2, 3, 4 negative factors. 4 is an even number. right? 4 divided by 2 is 2, no remainder. Again, you can always pair these guys up. So this guy and this guy, that's going to make a positive, and then this guy and this guy, that's going to make a positive. So if you have an even number of negative factors, you will get a positive result. So here I could just go through and multiply the absolute values. So 2 times 5 is 10, and then times 1 would still be 10, and then times 3 would be 30. Let me stop and write this out. So I have 30, and then forget about the signs here. We already know it's positive, times 20, and then times 30. Okay, well, what I can do is use my trick for trailing zeros. 3 times 2 times 3. 3 times 2 is 6. 6 times 3 is 18. So this is 18. And then I have 1, 2, 3 zeros that I'm going to attach to the end. So 1, 2, 3. So the final answer here would be positive 18,000. All right, now let's move on and talk about dividing integers. So this is just as easy as multiplying integers. So the first thing is we want to determine the sign of the quotient. And then once we've done that, we just want to divide the absolute values. So the sign rules are pretty easy. So basically, if you're dividing integers and you have the same sign, you're going to get a positive quotient. If you're dividing integers and you have different signs, you're going to have a negative quotient. So positive divided by positive or negative divided by negative will give you a positive. And then if you have a positive divided by a negative or a negative divided by a positive, you will get a negative. All right, before we get to the problems, let me take a few minutes here and think about where the sign rules come from. So let's start out with something we know. Let's say we have 15 divided by 3. So again, what does this mean? It means I have 15 of something, could be boxes, could be whatever, and I'm going to split it up into equal groups where each group has 3. So 3 boxes or again, whatever you have. So we can use a related multiplication statement, or again, you can use repeated subtraction. So you could go through and say, okay, this is 15 minus 3, and that would give you 12. And then you can go 12 minus 3, and that would give you 9. And then you would go 9 minus 3, and that would give you 6. And then 6 minus 3 would give you 3. And then 3 minus 3 would give you 0. So I did that 1, 2, 3, 4, 5 times. So the answer is 5. And of course, we already know that. So the answer here would be 5. Or you could have asked the question, what times 3 gives me 15, and the answer from the multiplication tables would be 5. So we know 5 times 3 is 15, so 15 divided by 3 is 5. Okay, so using that same logic, let's go ahead and ask the question, what is negative 15 divided by 3? Well, this would be what? I would put a question mark here and just say, well, question mark times 3 would give me negative 15. Well, for multiplying integers, we know that if this is negative, well, that's going to come from a positive times a negative or a negative times a positive. This right here is positive, so this has to be negative. So the question mark would be a negative. And then, of course, multiplying the absolute values, we know that 5 times 3 would give us 15. So this would be negative 5 here. So the question mark here would be negative 5. Okay, so that's one way to think about it. I have some things set up over here. So now we're doing 15 divided by negative 3 equals what? Well, again, what times negative 3 would be 15? Well, this right here would have to be a negative 5 now, because negative times negative would be positive. So negative 5 times negative 3 would be positive 15. So that means 15 divided by negative 3 would be negative 5. Now coming through here, negative 14 divided by negative 7 is what? Again, you could say what times negative 7 is equal to negative 14. So here you would want a positive, right? Because positive times negative is negative. So this would be a 2. 2 times negative 7 is negative 14. So negative 14 divided by negative 7 is positive 2. So here we have that a positive divided by a positive gives you a positive. You have a negative divided by a negative gives you a positive. So again, same signs, you get a positive quotient. Then you have a positive divided by a negative gives you a negative, and then a negative divided by a positive gives you a negative. So different signs, negative quotient. Okay, let's burn through some examples. So you have a negative 50 divided by 5. So again, negative divided by positive is negative, and then 50 divided by 5 would be 10. So this is negative 10. Here you have negative 40 divided by 4. So negative divided by positive is negative. 40 divided by 4 is 10, so this is negative 10 as well. So then we have negative 200 divided by negative 10. So negative divided by negative is positive, and then 200 divided by 10 is 20. And then coming down here, you have negative 34 divided by negative 17. Negative divided by negative is positive. 34 divided by 17 is 2. Then we have 27 divided by negative 3. So positive divided by negative is negative. 27 divided by 3 is 9, so this is negative 9. And then for the last problem, we have 16 divided by negative 4. Positive divided by negative is negative. And then 16 divided by 4 is 4. So this is negative 4. Hello and welcome to Pre-Algebra Lesson 22. In this video, we're going to learn about exponents with an integer base. So for our lesson objective, we want to learn how to perform operations with exponents that have an integer base. So before we get into the main content, let's just briefly review exponents. So recall that at this stage, we're using exponents to conveniently notate repeated multiplication of the same number. So for example, something like 3 times 3 times 3 times 3 times 3. I have 1, 2, 3, 4, 5 factors of 3, so I can write this as 3 to the 5th power. Right? The number that's being multiplied by itself gets written as the bigger number. This is known as the base. Okay, so that's 3 in this case. The smaller number in the top right-hand corner, this 5, is the exponent. Okay, it's the exponent. And so it's telling me that I have 5 factors of 3. Now, if we want to look at another example, let's say we had 7 times 7 times 7. The number that's being multiplied by itself is 7. So that's my base. That is my base. And then I have 1, 2, 3 factors of 7. So my exponent is a 3. So at this point, it's very, very easy to work with exponents. We've only worked with a base that's positive. What we're going to think about today is what happens when we have a negative base. Well, when we're working with exponents, we need to be extra cautious when dealing with negative numbers. There's some notational issues that are going to come up, and we're going to explain that in this video. So when working with a negative number that is raised to a power, the base does not include the negative part unless we use parentheses. Okay? So let me read this again. It's very important that you understand this. When working with a negative number that is raised to a power, the base does not include the negative part unless we use parentheses. So let's think about this problem using an example. I want you to pretend that your teacher tells you, hey, what is negative 2 squared? So you have your pencil, your paper, and you have a calculator. And you start out by writing negative 2 squared, just like that, no parentheses. And you go through, and from your knowledge of exponents, you say, okay, I have 2 factors of negative 2. So I have negative 2 times negative 2. Now you say, okay, negative 2 times negative 2 is 4. Now you pull out your calculator and you verify. You say, okay, I'm going to type in negative 2. I'm going to use the to the key, right? The to the key. And then I'm going to put a 2 in. So it's negative 2 to the power of 2. And I'll just erase that real quick and write it like this. And your calculator spits out an answer that says negative 4. And so you're thinking, what gives? Why did my calculator say that this is negative 4, whereas I think the answer is positive 4? Well, I'm going to tell you it's a notational issue. And here's why. So let me kind of erase this. This is wrong, by the way. So I'll erase this and show you why. All right, if I have negative 2 squared written like that, really what I'm saying is I want the opposite of 2 squared. So to make this clear, let me write this as negative 1 times 2 squared. And using our order of operations, we know that we would perform any exponent operation before we multiply. So essentially, I would have negative 1 times the result of this. 2 squared is 2 times 2, that's 4. So now I have negative 1 times 4, and that's negative 4. So you can see where we got the wrong answer, right? We just didn't have the right notation. So to get the notation correct for what your teacher asked you for, if your teacher said, hey, what is negative 2 squared? Well, essentially, I would need to put parentheses around negative 2. The negative and the 2 need to be enclosed so that they are both part of the base. So this now is a negative 2, and I'm squaring that. So this would be equal to negative 2 times negative 2. And this is now equal to 4. And you can verify this. Go ahead and type this in this way with your calculator. Make sure to put parentheses around the negative 2, and you will see that you get an answer of 4. Now you might be saying, what if I did this trick up here where I'm multiplying by negative 1? Well, it still works out. Let's say I did negative 1 times 2 enclosed in a set of parentheses, and I squared it. Well, essentially what's going to happen is I'd have what? Negative 1 times 2 multiplied by negative 1 times 2. And just to kind of simplify this, I just have multiplication involved. So I can just remove all those parentheses and just write this as negative 1 times 2 times negative 1 times 2. And commutative property tells me I can reorder this. So I'd have negative 1 times negative 1 times 2 times 2. So negative 1 times negative 1 is positive 1. Then positive 1 times 2 is 2. 2 times 2 is now 4. So we can see that our mistake was just with the notation, right? That's all it is. So moving forward, the only thing we need to realize is that if I have a negative number that I'm working with, and I want to raise it to a power, I have to enclose that negative number inside of a set of parentheses. Now, there are some scenarios where you'll get the same result, although the notation is wrong. And let me show you one of those. So let's say you had something like negative 4 to the third power written like this. The negative 4 is not inside of a set of parentheses. So technically speaking, because of the notation, this is the opposite, or you could say the negative of 4 cubed. I could write this as negative 1 times 4 cubed. And of course, following my order of operations, I would do 4 cubed first. That's 4 times 4, which is 16, times 4 again, which is 64. So this is negative 1 times 64, which is negative 64. Now, let's suppose that I enclosed this negative 4 inside of a set of parentheses. In the last situation we looked at, we went from negative to positive, right? We kind of corrected our mistake and we got a different answer. Will we still get a negative or will we get a positive here? Well, what you're going to find is that in this case, it will not change your answer. And then we're going to explain why that's the case. So let's say I enclose this inside of a set of parentheses. So now I have negative 4 times negative 4 times negative 4. Well, I have 3 negatives involved in this problem. 3 negatives is going to give me a negative. 3 is an odd number. In other words, I have one pair here of negatives that gives me a positive, but then I have one left over, right? So I'm going to end up with a negative result. So I would have a negative 64 in this case also. Now, knowing that, I'm going to go through and read some rules that you just want to remember when you're working with exponents. When the base is negative and enclosed in parentheses, the result is positive if the exponent is even, right? Because I would have an even number of negative factors. That gives me a positive result. The result is going to be negative if the exponent is odd, because I would have an odd number of negative factors. That's going to give me a negative result. And then the other scenario you need to be aware of is that when the base is negative and not enclosed in parentheses, the result is always negative. Always negative. Doesn't matter what the exponent is, because in that scenario, you're just saying, hey, I want the opposite of what you're doing over there. So, for example, the opposite of 4 squared. Because this negative 4 is not inside of a set of parentheses, this will always be negative, right? This will always be negative. So in this case, it would just be the opposite or the negative of 4 squared. 4 squared is 16, so this would be negative 16. If I was to write this with negative 4 inside of a set of parentheses, now I would get positive 16. Because in this case, I have negative 4 times negative 4. 2 negative factors gives me a positive result. So in this case, I'm thinking about, okay, well, my exponent is even. I'm going to get a positive result. Okay, let's use these rules and just do some practice. So we want to evaluate each. All right, so we have negative 3 inside of a set of parentheses, and it's squared. So this tells me that I have what? I have negative 3 times negative 3. So this is going to be positive 9. But again, what I can do is I can just look at, because this is inside of a set of parentheses and my exponent is even, I know my answer is going to be positive, right? I have an even number of negative factors. In this case, it's 2. And an even number of negative factors gives me a positive result. What about negative 3 raised to the 5th power? And notice how the negative 3 is enclosed inside of a set of parentheses. Well, I know the result is negative because I have an odd exponent there. 5 is an odd number. And so I would have an odd number of negative factors. And you can just think about 3 to the 5th power now. You don't even need to think about the sign anymore. 3 to the 5th power would be what? It'd be 3 times 3, that's 9, times 3 again, that's 27, times 3 again, that's 81, times 3 one last time, which would be 243. So this would be negative 243. What about negative 1 to the 38th power? Well, 38 is an even number, so we know the answer is going to be positive. Now, what's cool about the number 1 is when you multiply it by something, the number is unchanged. If I multiply 1 by itself, it doesn't change. So 1 times 1 is 1. Doesn't matter how many times I do that. If I go 1 times 1 times 1 times 1 times 1 times 1, the answer is 1. I could do this a million times, I still get 1. So 1 to the 38th power, forget about the negative. 1 to the 38th power would just be 1. The fact that we have a negative and it's enclosed inside of a set of parentheses tells me I just need to look at whether this exponent is even, which in this case it is, or odd. Since it's even, I know I'd have an even number of negative factors, and an even number of negative factors gives me a positive, so I end up with positive 1. What about negative 1 to the power of 71? Well, my negative 1 is enclosed inside of a set of parentheses, but my exponent is odd. So I would have an odd number of negative factors. Now that would give me a negative result. And I would just think about 1 to the 71st power is just 1. So I'd end up with negative 1 as my answer. Okay, now we have negative 10 cubed, and this negative 10 is inside of a set of parentheses. So again, I'm looking at this exponent. This exponent is a 3. That's an odd number, and so that tells me I'm going to have a negative result. Once I know the sign, I can just think about, okay, well, what would 10 cubed be? What would 10 cubed be? Well, I taught you a trick for this. Basically, when you have 10 raised to a whole number that is larger than 1, you just write down a 1 and follow it with the exponent number of zeros. So in this case, the exponent is a 3. So I would write 1, 2, 3 zeros, and I would get 1,000. You can just drag that up there and attach that negative to it. And you would end up with negative 1,000 as your answer. What about negative 8 squared? But again, notice how there's no parentheses around negative 8. So I'm not looking at the exponent here. I don't care that this exponent is even. The result is going to be negative, right? Because I'm basically saying, hey, what's the opposite of 8 squared? 8 squared is 64. When I take the opposite of it, I get negative 64. Right? And let me kind of write this out so you get a little bit more practice seeing this. So this is essentially negative 1 times 8 squared. So it's negative 1 times 64, which equals negative 64. Now what about negative 8 squared, where the negative 8 is enclosed inside of a set of parentheses? Well, now I'm looking at my exponent. I have a 2 there. 2 is an even number, so I know my answer is going to be positive. And now I can just think about, well, what is 8 squared? Okay, well, that's 64. And so my answer would just be 64. Okay, let's take a look at negative 5 cubed, where the negative 5 is enclosed inside of a set of parentheses. Well, in this case, my exponent is odd, so I'm going to get a negative result. Right? An odd number of negative factors gives me a negative. And now I just think about, well, what is 5 cubed? 5 cubed is 5 times 5, that's 25. Then times 5 again, that's 125. So my answer is negative 125. For the final problem, we look at negative 5 cubed, where there's no parentheses around the negative 5. Now, in this case, we also get a negative 125. And you might say, well, how come I got the same answer? Again, to explain this, in this case, I'm saying, hey, what's the opposite of 5 cubed? 5 cubed is 125. The opposite of that is negative 125. In this case, whether the exponent is odd or even, it doesn't matter, you always get a negative. And looking at this scenario, where I have parentheses around negative 5, I look at my exponent. If my exponent is odd, like it is in this case, I'm going to get a negative result. I would have had negative 5 times negative 5 times negative 5. Right? I have 3 negative factors. 3 is an odd number, so I'm going to get a negative result. Hello and welcome to Pre-Algebra Lesson 23. In this video, we're going to talk about the order of operations with integers. So the lesson objective for today would be to learn how to use the order of operations when integers are involved. Now, we previously talked about the order of operations when we wrapped up our section on the whole numbers. So now that we're wrapping up our section on the integers, we're going to revisit this topic and just do some examples with integers involved. So before I go through the order of operations, I just want to remind you, if you're using something like PEMDAS, so this is really, really popular in the United States. In other countries, you might hear BODMAS. It's basically telling you the same thing. You need to be really, really careful. A lot of people remember this as please excuse my dear Aunt Sally. So parentheses, exponents, multiplication, division, addition, and then subtraction. Remember, when you look at this, the M and the D, the multiplication and division, have the same priority level and they need to be worked left to right. I can't tell you how many times people memorize this and then they're looking at that and they're saying, okay, I need to multiply before I divide. They are on the same priority level. They are worked left to right. Then the other guy here is addition and subtraction. So same priority level. They're worked left to right. So if we go through this, we would say the first thing is to work inside of any grouping symbols. So that's why we have that P that stands for parentheses, but it's also for brackets or absolute value bars or anything that's a grouping symbol. The second thing would be to perform all exponent operations. So that's the E there. Now included in this would be something like a square root. So let's say you had something like the square root of 4. And we haven't talked about this yet in the course, and I'll explain as we get to an example, but actually we can convert this over to exponential form. So this is actually 4 to the 1/2 power. So if you have a square root involved or a cube root or something like that, you would actually do this on the same level. So I'll talk more about this as we get into a problem. Let's just erase it for now. So coming down here, you'll see the third and the fourth steps. This is where people get lost, right? So again, if I write out the PEMDAS, so PEMDAS like this right here is where everybody gets confused. So the M and the D. I have here multiply or divide working left to right. So if multiplication comes before division, working left to right, you do multiplication first. If division comes before multiplication, again, working left to right, you do division first. Same priority level. Don't let this ordering of the letters here trip you up. Then the same thing is going to go for the A and the S. So add or subtract, again, working left to right. Okay, with that being said, let's just jump in and look at some problems. So we want to evaluate each. All right, so let's take a look at the first problem. We have -3 times, then you have -2, and notice this -2 is wrapped, and this is being squared, and then plus you have -24, and then divided by 4. So what is the highest priority? Again, we start with parentheses. The only parentheses we have would be this guy right here, which is wrapping this -2, and this guy right here, which is wrapping the -24. So there's nothing to really do there with parentheses. Then we move on to exponent operations. So do we have anything with an exponent? Yeah, we have this -2 that's being squared. So I want to stop here and remind you of what we talked about in the last lesson. If you have -2 and it's wrapped, so it's inside of parentheses, and I square it, this is equal to -2 and then times -2, which is +4. Okay, you can do this on your calculator. Make sure you wrap it. So you would wrap it like this, -2. You would hit that key there, and then you would put your 2 in there, and then basically you would get a 4 as an answer. Now this is different versus if I did this. Let's say I wrote -2 like this. I did not wrap it, and then I squared it like this. Let's say you key that into your calculator. You're going to get an answer of -4. And you're probably going to be confused by that because you're saying, well, that's -2 squared. It's a notational issue. If I ask you for -2 being squared, you want to use this, okay? This is basically going to get translated into -1 times 2 squared. So in other words, the base here is actually 2, right? It's not -2 because this negative is outside of here. You could read this as the negative of 2 being squared. Okay, so this would end up being -1 times 2 squared would be 2 times 2 or 4. So this is -4. So if you key it into your calculator, you've got to make sure that you use the right notation so that you get the right answer. So let me get rid of this. And what we're going to do is put equals here. And I'm just going to replace this with a +4. So we have -3 and then times +4. And then plus you have -24 and then divided by 4. So I've taken care of my exponents. The next thing again is multiplication or division working left to right. So here I see that I have multiplication and I have division. Now working left to right, this multiplication occurs to the left of this division. So that means this guy right here is the higher priority. Let me unhighlight that. So that means I'm going to do -3 times 4. So a negative times a positive is a negative. So let me write that's a negative. And now I can just say, well, what is 3 times 4? That's 12. So this would be -12 here. Okay, then we have plus -24. And then divided by 4. So now I'm still on my multiplication and division step, and I have division here. So I'm going to divide -24 by 4. So -24 divided by 4 would be negative 6. Negative divided by positive is negative, and 24 divided by 4 is 6. So that's negative 6. So we would say this is negative 12, and then basically we would have plus negative 6, or you could write negative 12 minus 6, whatever you're more comfortable with. So the last thing here is just to do this addition. So negative 12 plus negative 6, you have a common sign. Both of these guys are negative, so the answer would be negative. And then you could just add the absolute values. So 12 plus 6 is 18. So this gives me a final answer of negative 18. All right, now before we move on to the next problem, I'm going to do this problem in a different way. I'm actually going to change it up. So you see we got negative 18 there. So what I'm going to do is actually write this problem as negative 3. And then instead of wrapping this, I'm just going to put times the negative of 2 being squared like this. Then plus, we're going to have negative 24. And then divided by 4. And I'm going to show you that you get a completely different answer. Now you're going to get positive 6, and the change is going to be because this guy right here is going to throw everything off because your sign is going to go from a positive 4 to a negative 4. So if you're keying this into your calculator and you're expecting to get the same answer as this, I'm going to show you where you're going to run into an issue. So let me copy this and let me paste this in. I'm just going to run through this really quickly. So we know the first thing we would do would be the exponent operations. But again, because this is the negative of 2 being squared, this becomes negative 1 times 2 squared in your calculator. 2 squared is done first because of the order of operations. So that's 4. So you get negative 1 times 4, which is negative 4. Okay, it's only positive 4 if this gets wrapped. So I'm going to replace this right here with a negative 4. So you'd have negative 3 times negative 4. Then plus negative 24 divided by 4. So now, just like we saw before, we're going to do this multiplication first, but now instead of a negative times a positive, we have a negative times a negative. So a negative times a negative is a positive. So negative 3 times negative 4 would be positive 12. Now we have our plus negative 24 and then divided by 4. So now we would do our division. So negative 24 divided by 4, that's going to be negative 6. So this becomes 12, and then plus your negative 6, or you could go 12 minus 6 if you want. And obviously the answer there is 6. So you see the other way we did it, when we wrap this, we got a negative 18. And when we don't wrap this, we get a positive 6. So it's very important to understand this notational issue. It's going to come up for the rest of your time that you're studying math. All right, let's take a look at the next problem. So here, another easy one. We have negative 20 divided by negative 5, then minus 12 times 2 plus 3 squared. Now, the first thing we want to do is work inside of parentheses or any grouping symbols. So we do have parentheses here, but they're just used for clarity, right? They're just used to wrap that negative 5. So you can ignore that here and just move into working with the exponents. So here we have 3 squared, so we'd want to do that first. So this is the highest priority. Let me copy all of this. So negative 20 divided by, you can wrap this or not wrap it. I'm just going to wrap it for clarity. So divided by negative 5, then minus 12, and then times 2, and then plus. So 3 squared is 3 times 3. That's going to be 9. So we've taken care of the exponents. And now we want to move into the multiplication or division. So let me write this one more time because people do get lost here. And it's very important to understand that multiplication and division occur on the same level. Okay, they're work left to right. So if you're using PEMDAS, or please excuse my dear Aunt Sally, or you're in a different country than me and you're using BODMAS, it's the same thing. You want to highlight these two and say that they are worked left to right. Okay, might want to put that down in your notes or something like that. It's very important to remember that. Let me erase this, and we're going to think about this. I have division right here, and then I have multiplication right there. Which one am I going to do first? Again, they're the same priority level. So I want to work left to right. So starting on the left, this operation occurs before this one. Okay, so that means I'm going to do my division first. So I'm going to divide negative 20 by negative 5. So negative divided by negative is a positive, and then 20 divided by 5 would be 4. Okay, so that's done. Then we have minus 12 times 2 plus 9. Now, the next step, because we're still on the multiplication or division level, would be to multiply 12 times 2. Now, if you want, you can convert this over. You could say this is plus negative and do it that way, or you can keep it like this. It's going to give you the same answer in the end. It's really up to you. So I'm just going to keep it like this. So I'm going to say this equals 12 times 2 is 24. So we would have 4 minus 24 and then plus 9. So here we have subtraction and we have addition. Now, when you have integers involved where you're dealing with positive and negative numbers, I like to convert all of the subtraction into a related addition problem. I think it just makes it easier. So I'm just going to go plus negative like this. And then because of the commutative property of addition, you can add in any order. Okay, so I can just say this is 4 plus negative 24. Maybe I could wrap that to make it more clear. And then plus 9. So I can add however I want. Typically what you'll do is you'll add the numbers with the same sign first. So I would say 4 plus 9 would be 13. And let me reorder that so nobody's lost. Let me reorder this to 4 plus 9 plus negative 24. 4 plus 9 would be 13. And now we have plus a negative 24. So now we want to do 13 plus a negative 24. So hopefully you have mastered adding integers at this point. I know when you have a different sign involved, it can be a little bit tricky for some people. But basically you want to look at these two numbers and say which number is larger in terms of absolute value. The absolute value of 13 is 13. The absolute value of negative 24 is 24. So negative 24 has a larger absolute value, so we're using that sign. So the result will be negative. So now I can just think about these numbers as if they were positive numbers, and I could just do a subtraction. Subtract the bigger minus the smaller. So what is 24? Let me do this off to the side. What is 24 minus 13? I think a lot of you can do that in your head at this point and say it's 11, but just in case you can't, 4 minus 3 is 1, and then 2 minus 1 is 1. So this is going to be 11. So this would be negative 11 for the answer. All right, let's take a look at the next problem. So this is a little bit more challenging, but still not that bad overall. So we have some brackets here, and inside the brackets, we have a set of parentheses, so negative 4 being squared, plus 52, that's inside the first set. Then plus inside the second set, you have negative 93 divided by 31, then plus 55. Then outside the brackets, we have divided by a set of parentheses here, which is 2 cubed minus 28 inside. All right. The first thing I want to do is work inside of any parentheses or grouping symbols. Well, you have brackets here, and then you have parentheses here. So what I'm going to do is actually start off inside the brackets. And when I do that, I want to reapply the order of operations. So in other words, I want to look for parentheses again. And let me change my highlighter color here. You see that you have that here, and then you have that here. Okay, so you want to make sure that you do what's inside the parentheses here, and then what's inside of the parentheses here separately, and then you can add. So it doesn't really matter if you do this one first or this one first. I'm just going to work on the one that's here on the left first. Let me put a little border here, and I'm going to say I have a negative 4 being squared plus 52. So let's do that first. Now, like we previously talked about, if you're keying this into the calculator, make sure that you wrap negative 4 before you square it. Otherwise, you're going to get the wrong answer. Because if you have negative 4 being squared, this is what? This is negative 4 times negative 4, which is positive 16. If you have the negative of 4 squared, again, the negative is not wrapped. So this is really negative 1 times 4 squared, which gives you negative 16. Two different results in your calculator. So if you don't make sure that you're wrapping this, you're going to get the wrong answer. So very important. So when we look at this, we see that we have an exponent operation and we have addition. So we would do the exponent operation first. It has the higher priority. We just said that negative 4 squared was 16, and then we would add that to 52. Now, I can pretty much do that in my head. I know that's 68, but just in case you can't and you're not using a calculator, again, you can always stop and do a vertical addition. So 52 plus 16, 2 plus 6 is 8, 5 plus 1 is 6. So that's how we get the 68. Okay, so let's erase everything. And how much work you want to show is up to you. I'm just going to show all the steps so nobody's lost. I'm going to put the brackets here. The result of this is 68. Then plus, I'm just going to copy this. So you have negative 93 divided by 31 plus 55. So that's inside the parentheses. Close down the brackets, and then we're dividing by. So inside these parentheses, you have 2 cubed minus 28. Okay, close that down. Let me slide down here a little bit. All right, now the next thing is we're still working inside the brackets. So now let's go into these parentheses here. And so basically you have negative 93 divided by 31 and then plus 55. So we would obviously divide before we add. Division has a higher priority level. Negative divided by positive is negative. When we think about 93 divided by 31, that one's a little bit tricky because, essentially you can't really benefit from doing the long division. You really have to say, well, what is 93 divided by 31, right? Because 31 goes into 9 0 times. So you have to expand this and say, well, 31 goes into 93, so I'm back to the original division problem. If you use multiplication, you would find that it's 3. 31 times 1 is 31, 31 times 2 is 62, and then 31 times 3 would be 93. So you basically have to use multiplication there. So 3 times 31, as I just said, is 93. Subtract here, you get 0, so there's no remainder. So this would end up being negative 3, right? So negative 93 divided by 31 is negative 3. Okay, let's get rid of this, and now we're going to add 55. Now, this one, again, it's a little bit tricky because you're adding integers with different signs. What I like to do is flip the order here and say this is 55 plus a negative 3. And then notice, if I had been given 55 minus 3, I can legally go to that. We can always convert our subtraction into a related addition. So change the subtraction into addition, change the number being subtracted away into its opposite. Okay, so this ends up just becoming 55 minus 3, which is going to be 52. So let's get rid of this, and let's say this equals, inside of brackets, 68 plus 52, and we'll close that down, and it's divided by, again, in the parentheses, we have 2 cubed minus 28. Okay, let's wrap things up by doing this addition here. I think it's probably something, again, you could do in your head, but there is some carrying there, so maybe you want to write it out. So 68 plus 52, 8 plus 2 is going to be 10. Put a 0 down, carry the 1. 1 plus 6 is 7, plus 5 is 12. So this would be 120. And say this equals 120, so we're done with that, divided by, again, inside the parentheses, 2 cubed minus 28. So now I want to work inside of these parentheses here, and I want to do 2 cubed first. Let me make that a little bit more clear. I want to do that first because that has a higher priority than the subtraction. So 2 cubed is 2 times 2 times 2, which is going to be 8. So let's say this is 120 divided by, you would have 8 minus 28. So now I want to do the subtraction. Again, what I like to do is go plus negative here and think about it that way. So if I have a negative 28 plus 8, then I'm using the sign of the number. Let me write 120 here. I'm using the sign of the number with a larger absolute value. So negative 28 has a larger absolute value, so I'm going to put a negative there. And then I'm just going to do a subtraction. So basically the larger absolute value minus the smaller. So basically you would say that 28 minus 8 would be 20. So this is divided by negative 20. Okay, so from here, it's actually pretty easy. We know positive divided by negative is a negative. And then you can think about 120 divided by 20. So again, we have another one where the long division doesn't really help you that much because 20 doesn't go into 1 or 12. So you have to go all the way into what is 20 into 120, which is basically going to give us 6, right? You have to use a related multiplication statement to figure that out. So 6 times 20 is 120. Subtracting, you get 0. So this becomes negative 6 as our final answer. All right, let's take a look at the next example. So this one's a little bit more tedious, a little bit more time consuming is what I would really say. So we have the square root of 64 times negative 9. Let me wrap this here so it's more clear. Then you have minus a negative 3, then plus. Remember, these vertical bars tell you that you want the absolute value of something, and those are grouping symbols. So we have the negative of 2 squared. So notice this negative here is not wrapped inside of parentheses. Then times negative 15, and then plus 4, and then divided by 2. I'm going to wrap this also for clarity. And then down here we have minus, and then we have these parentheses here. So you have negative 2, notice this one's wrapped, being squared, plus negative 8 divided by 2, and this is squared. The first thing I would do is think about what parentheses or grouping symbols do I have. When you have parentheses that are just used like these, just to wrap a number, don't worry about them. Okay, so you're just looking for grouping symbols like the absolute value bars there, or these parentheses here. Okay, so you have some operations inside. So where I want to start, let me get rid of this highlighting here so nobody's confused. Where I want to start, I'm just going to start inside of the absolute value bars. If you wanted to do this guy inside of here first, it's really up to you. I'm just going to start there. So I'm just going to copy this down here. So we have the absolute value of, again, be very careful. This is the negative of 2 squared times, I'm going to wrap this, so negative 15, then plus 4, and then divided by 2. We'll come back up in a moment. I'm going to need a lot of room for this. Let me come down here. And let me put equals here. So the first thing is you would think about, what's my highest priority? Well, inside of here, do I have any parentheses? Well, I have these parentheses, but they're just used to wrap a number. So really I don't. I could just move on to exponents. And here I have this exponent operation. But again, if you're keying this into your calculator, this right here is going to give you negative 4. This right here is going to give you positive 4. Again, this is the negative of 2 squared, so your calculator is doing negative 1 times 2 squared, which is giving it negative 4. This one, it would do negative 2 times negative 2, which will give it positive 4. So I've got to make sure that I use the right one if I want the right answer. So this right here would give me a negative 4, not a positive 4 because it's not wrapped. Then times. Here you have this negative 15, and then plus 4, and then divided by 2. Let me close that down. And now I'm thinking about, okay, I have multiplication, addition, and division. Multiplication and division are on the same priority level. They are worked left to right. So this one is to the left of this one. So I'm going to multiply first. So negative 4 times negative 15, negative times negative is positive, 4 times 15 is 60. So this right here, I'll put the absolute value of 60, then plus 4, and then divided by 2. So now I have addition and division. You want to divide first. So 4 divided by 2 is 2. So we'll say this is the absolute value of 60 plus 2. And then from here, 60 plus 2 is 62. So this would be the absolute value of 62. We can go ahead and do that operation now. The absolute value of a positive number is just the number. So the absolute value of 62 is 62. And I'm just going to come back up here and put equals. I'm going to copy this. So the square root of 64, then times negative 9, then minus a negative 3. And the result of this was 62. So now I'm just going to put plus 62. I'm just going to keep working. Then I have minus. This guy right here is not going to fit on this line. So let me slide down just a little bit. And I'm going to write inside of parentheses, you have this negative 2 being squared. Notice that this is wrapped. Okay, that's very important. Then plus negative 8 and then divided by 2. And then this guy is squared. Okay, let's put equals here. In terms of what to do next, you have these parentheses here that you need to work inside. So I'm going to think about, let me just write this down here. I'll just put a little border. And I'll say that we have this negative 2. Again, this is wrapped, being squared. Plus you have negative 8, and then divided by 2. And then we're going to square this. I'm just working on this part right now. So thinking about my order of operations inside, I have parentheses, but they're just used to wrap this number and this number. So I move on to exponent operations. So I have that here, right? So negative 2 being squared. So again, negative 2 being squared, because this is wrapped, you're going to get 4. If you don't wrap it, if you key it in your calculator like this, you're going to get negative 4. So again, we have to make sure that we're paying attention to which form we're using. So this right here would be a positive 4, and then plus a negative 8, and then divided by 2, and this whole thing is squared. All right, so now I have addition and division. I want to divide first. So negative 8 divided by 2 would be negative 4. This would end up giving me 4 plus a negative 4. Of course, you could write that as 4 minus 4 if you wanted to, and this would be squared. So 4 plus a negative 4, those guys are opposites or additive inverses or however you want to think about that. The sum is going to be 0. So we'll say this is 0 squared. Let me get rid of all this, and let me come back up and get rid of this border. I'm just going to copy things again. So I have the square root of 64 times this negative 9, then minus this negative 3, then plus 62, and then minus, this is going to be 0 squared. Okay, so I've dealt with all the parentheses and the grouping symbols. So now I want to move on to exponents. Now, this right here is worked on the same priority level as an exponent because the square root of 64, as we're going to learn later on, is the same thing as 64 to the 1/2 power. We won't talk about that for now. We'll talk about it much later on, but you just need to know that if you're seeing some type of square root or cube root or something like that in an order of operations problem, it's going to be with the exponents in terms of the priority level. Okay, let me get rid of this. And first, let's do the one we know. We know that 0 squared would be 0. So let me write the square root of 64 times negative 9 minus a negative 3, then plus 62. And you can write minus 0 if you want, or you can leave it off. Of course, if we subtract away 0, it's not going to do anything. So let's just leave it off. Okay, let me slide down here. And now let's think about the square root of 64. So at this point, we have not talked about square roots. And basically, all you need to think about is this. If I have the square root of some number, let's just say 4, then basically what I'm asking for is what number, when multiplied by itself, will give me this number under the square root symbol, which is called the radicand. In this case, for 4, you would immediately think about 2, right? 2 times 2 is 4. So the square root of 4 is 2. Now, some of you are going to say, well, hey, negative 2 times negative 2 is also 4. So we have a different notation for that. You have the negative of the square root of 4, which would be negative 2. So if I ask what positive number, when multiplied by itself, gives me 4, I want this notation here. So this is the principal, or some people say the positive square root of 4, that is positive 2. Then this one, I'm asking for what negative number, when multiplied by itself, gives me the radicand, right? So this is the negative of the square root of 4, and that's going to be negative 2, because negative 2 times negative 2 would be 4. Okay, so we understand that general concept, and so with that being said, we would say, well, what is the square root of 64? Well, what number, when you multiply it by itself, would give you 64? Now, you could factor the number, which we haven't talked about yet. Basically, right now, I think most of you know that that would be 8, because 8 times 8 is 64. Again, if you had the negative of the square root of 64, that's where you would get negative 8. Okay, we're asked for the principal square root of 64, which is positive 8. So that's the difference between the two. So let me get rid of this. Let me put equals. Let me put 8 times negative 9, and then minus a negative 3, and then plus 62. So I don't have any exponents anymore. I just have multiplication, subtraction, and addition. So I want to multiply before I do any subtraction or addition. So this is positive times negative, which is negative, and then 8 times 9 is 72. So this is negative 72. Now you have minus a negative 3, and then plus 62. So we have talked about the fact that minus a negative is plus a positive. So I know this is one that trips up a lot of students, but when you see minus a negative, it is plus a positive. So I'm going to rewrite this as negative 72 plus 3 plus 62. Again, minus a negative plus a positive. So then if you want to, since this is all addition now, you can reorder it. I'm just going to say this is 3 plus 62 and then plus negative 72. Again, that's my commutative property to where I can add in any order. Let me actually grab this. Let me paste this in here so we have some room. So now I'm just going to add 3 and 62 together. 3 plus 62 is 65. So you get 65 plus a negative 72. So at this point, you basically have to think about, okay, I'm adding these integers with different signs. Which number has the larger absolute value? The absolute value of 65 is 65. The absolute value of negative 72 is 72. So negative 72 has a larger absolute value, so we're going to use that sign in the answer. So this would be negative. Once you're done with that, just work with the numbers as if they were positive, and you're just going to do a subtraction of the larger minus the smaller. So I'm going to go 72 minus 65. Borrow here, this is a 6, this is a 12. 12 minus 5 is 7. 6 minus 6 is 0. So I'm just basically going to drag that 7 up here and say that negative 7 is my final answer. Now, if you didn't get negative 7, go back and just be very careful and check your work, okay? If you're using an online calculator to check or something like that, just make sure you're wrapping things correctly. A lot of times, the smallest error will give you a big change in the result, okay? So the answer you're looking for here is negative 7. All right, let's take a look at a tedious problem. So for this one, before we get started, I need to explain something about fractions. So at this point in the course, we have not talked about fractions, but we're going to get to that topic very shortly. If I had something like, let's say 20 divided by 5, I could actually write this division problem using a fraction. So I can take my dividend, or the starting amount, and put that up here in the top part of the fraction, which is called the numerator. And then I'm going to have my fraction bar. And then this divisor here, this 5, I'm going to put that in the bottom part of the fraction. This is called the denominator. So I can say this is 20 divided by 5, or 20 over 5, or 20/5. There's a lot of different ways you could say that. But either way, this is going to be a result of 4. And we'll cover this in more detail later on in the course. I just want you to understand that you can write a division using a fraction bar. So when you come across an order of operations problem with a fraction like this involved, you want to simplify the numerator and denominator separately, and then you will perform the main division. So at the end, I would perform the final value in the numerator divided by the final value in the denominator, just like we did 20 over 5 like that, and we got 4. So we're going to do something similar here. Okay, so what I'm going to do is start off with my numerator and just simplify that. So I'm just going to copy it. So negative 2 to the 5th power divided by 4, and then times, we have this negative 3, and then plus, so we have these parentheses like this. I'm just going to use a different color for clarity. And then we have this negative 3 being cubed, and then plus the absolute value of 4 minus 4 squared. Let me close that down, and let me change back to this color and close that down. Okay, I'm going to grab this. All right, let's paste this in. We're going to go real slow, just step by step. So the first thing is we're thinking about, do I have any parentheses or grouping symbols? Don't worry about the parentheses that are used to just wrap a number. So this and this, you can ignore that for now. You're just thinking about, do I have any parentheses with some operations inside that I need to do? Well, yeah, I have these parentheses here. So I want to start inside of there. But once I get inside, I need to reapply the order of operations. So I need to think about inside of here, are there any parentheses or grouping symbols? And the answer to that is yes. So if I come in here, I see that I have the absolute value bars there. And so those are grouping symbols. So I would want to start with this right here. So what is the absolute value of 4 minus 4 squared? Well, inside of there, you would think about, okay, I have subtraction and then I have an exponent. So I want to do the exponent first. So 4 squared is 4 times 4, that's 16. So this is the absolute value of 4 minus 16. So a lot of you can do that in your head at this point. So 4 minus 16 is negative 12. If you can't, you can rewrite this as 4 plus a negative 16. Okay, so that is what you can do if you're struggling with things like that. You can always change it into a related addition statement, and then you could just use your rules for adding integers with different signs. So what I would say is the absolute value of what? The absolute value of 4 is 4, and the absolute value of negative 16 is 16. So the larger absolute value comes from this guy right here, the negative 16, so you use that sign in the answer. So I know this is going to be negative. Then you would do a subtraction, the larger absolute value minus the smaller, so 16 minus 4 would be 12. So this is negative 12, and we want the absolute value of that, which is going to be positive 12. So let me get rid of all of this, just scratch work. And I think because this is going to take such a long time, that maybe I could just erase things. I'm just going to erase this, and hopefully you've copied that down, and I'm just going to put a positive 12 there. So we'll just erase things as we go. So now I'm still inside of these parentheses here. And now I have an exponent operation and I have addition. So the exponent comes first. You have negative 3 that is being cubed here. So this is negative 3 times negative 3 times negative 3. So it doesn't really matter that this is wrapped here. You have an odd exponent, so you have an odd number of negative factors. That's going to give you a negative, right? Negative times negative times negative will give you a negative. And then 3 times 3 is 9. 9 times 3 is 27. So this is negative 27. Okay, let me get rid of this and put in a negative 27 there. Okay, let me get rid of this. Now again, we're adding two integers with different signs. So you want to use the sign of the number with the larger absolute value. The absolute value of negative 27 is 27. The absolute value of 12 is 12. So negative 27 has a larger absolute value. So if I'm doing negative 27 plus 12, I know the answer is negative. And then I just do a subtraction. Larger absolute value minus the smaller. Let me put this off to the side. So you're going to go 27 minus 12. 7 minus 2 is 5. 2 minus 1 is 1. So I would drag this over here, and then basically you would have negative 15 as the answer. So let me erase this, and this is now negative 15. Okay, let me get rid of this. Now these parentheses, you could keep them if you want. They're wrapping the negative. You could drop them. It's really up to you. It's just personal preference. All right, so now that we've gotten rid of all the grouping symbols, we need to think about the exponent operations, and we have negative 2 to the 5th power. So negative 2 to the 5th power. Now this is an odd exponent, so it really doesn't matter. If you typed negative 2 like this to the 5th power into your calculator, you're going to get negative 32. And if you wrap it, you're going to get negative 32. And that's because you have an odd exponent. So with an odd exponent, then basically you're going to have an odd number of negative factors, which gives you a negative result. Here, this is basically always going to be negative. It's the negative of 2 to the 5th power. So your calculator treats this as negative 1 times 2 to the 5th power, which is negative 32. With this one, it's saying, well, what is negative 2 times negative 2 times negative 2 times negative 2 and then times negative 2? Well, that's going to be negative 32. So just two different ways to think about things. The answer is the same either way, but how you go about getting it is different. All right, let me get rid of this, and I'm going to replace this with a negative 32. So negative 32. And so now we have division, multiplication, and addition. And this really looks like an X. I'm trying to make this a little bit more clear there that that's a multiplication symbol. So you have this division here that's going to occur to the left of the multiplication. And again, this is where everyone gets tripped up. Because of the ordering of the letters in PEMDAS, everyone thinks that multiplication comes before division. They have the same priority level. They are worked left to right. So because the division occurs to the left of the multiplication, you want to divide first. So you want to say, what is negative 32 divided by 4? Negative divided by positive is negative. 32 divided by 4 is 8. So this is negative 8. So I'm just going to erase this and put in a negative 8 there. Okay, so now we have multiplication and addition. So we have negative 8 times negative 3 that would be done first. Multiplication is the higher priority. Negative times negative is positive. 8 times 3 is 24. So this will just be 24. And for the last guy here, we're basically adding these integers with different signs. So again, use the sign of the number with the larger absolute value. The absolute value of 24 is 24. The absolute value of negative 15 is 15. So we're going to use a positive here because this guy has a larger absolute value. So I know this is a positive. So then I would just subtract. What is 24 minus 15? A lot of you can do that in your head. You know it's going to be 9. But again, you can always do it off to the side. What is 24 minus 15? You'd borrow here. This is going to be a 1. This is 14. 14 minus 5, that's going to give you 9. Okay, let me get rid of this, and you don't need that plus symbol there. So basically, I'm going to come back up, and the result of the numerator is going to be 9. Then this is over. I'm just going to copy the denominator. So we have this negative of 4 squared minus the square root of 9. And then plus, you have the absolute value of 2 times this negative 3. And then plus 18 divided by 3 minus 15. Let me close down the absolute value bars there. Then plus, you have this negative 1 being squared. Okay, I'm going to grab this, paste that in there. All right, so a lot to do here. You have these grouping symbols here, so for parentheses, and then you also have the absolute value bars there. So I'm just going to start with this one, and then we'll simplify this completely, and then we'll work on this one, and then we'll see what else we have. So inside the parentheses, you have the negative of 4 squared minus the square root of 9. So what is done first? Well, in this particular case, you have an exponent operation, and then you have a square root here. I told you those are the same priority level. So it really doesn't matter if I do this one first or this one first. I'm going to basically do each one of these operations before I do this subtraction. So if I think about, again, the negative of 4 squared, you have to be careful there. Your computer or your calculator, whatever you're using, is saying this is negative 1 times 4 squared. So this is negative 16. Again, if you want positive 16, you have to wrap that. So you would have to do negative 4 wrapped in parentheses being squared, and that's going to give you 16. And I know I keep going over this again and again and again, and that's just because it comes up all the time as a common mistake. So let me get rid of this, and let me replace this with negative 16 here. And then the square root of 9, again, we are asking for what positive number, when multiplied by itself, gives you 9. Well, that's going to be 3, right? So I'm going to say that the square root of 9, or at least the principal square root of 9, is going to be 3. So now I have negative 16 minus 3. And so you can go plus negative here to make that a little bit cleaner. And let me wrap that. So we have the same sign here. So I'm just going to put a negative there and then just add the absolute values. So 16 plus 3 would be 19. So this is going to be negative 19 as the answer. Okay, let me get rid of this. And actually, I'm just going to erase things as I go. And I'll just say that this is negative 19. All right, so now I'm going to mess with this guy right here. So inside the absolute value bars, you will notice that you have what? You have multiplication, you have addition, you have division, and subtraction. So the multiplication occurs to the left of the division. So that means it has a higher priority. So I'm going to go 2 times negative 3 first. A negative times a positive or a positive times a negative will give you a negative. And then 2 times 3 is 6. So let's get rid of this and just put negative 6 there. Then I have addition, division, and subtraction. So you want to divide first. 18 divided by 3 is 6. So let's put a 6 there. And so now I have addition and then subtraction. So the addition and the subtraction have the same priority level. We're just going to work them left to right. So here we're seeing that the addition occurs to the left of the subtraction. You want to add before you subtract. So you have negative 6 plus 6. So I'm adding a number and its opposite or a number and its additive inverse. That's always going to give me 0. So this right here is 0. So you could write 0 if you want, or you could leave it off. It really doesn't matter. 0 minus 15 is still negative 15. So I'm just going to put negative 15 there. And if I take the absolute value, let me close this down so this is a little bit more clean. If I take the absolute value of negative 15, that's going to give me positive 15. Okay, the last thing here, let me move this down. The last thing here when we're looking through everything, we have an addition, we have another addition, and then we have an exponent operation. So I want to perform the exponent operation first. So you have a negative 1. Again, this is wrapped and it's squared. So this is negative 1 times negative 1, which is 1. And again, I'll show this one more time. If you had written the negative of 1 squared, this becomes, in your calculator, negative 1 times 1 squared, which becomes negative 1, right? So negative 1 times 1 is negative 1. Let me get rid of this. And of course, that form there, because it was wrapped, that's positive 1. Okay, so now we could just go through and add. Again, I like to add the numbers with like signs first. That's possible because of the commutative property. We can add in any order. So I could say that this is 15 plus 1 plus a negative 19 like this. So 15 plus 1 is 16. And then you have 16 plus a negative 19. Now, a lot of you can eyeball this and see that it's negative 3. But again, you can always go through the official procedure. So I would use the sign of the number with the larger absolute value. The absolute value of 16 is 16. The absolute value of negative 19 is 19. And so negative 19 has a larger absolute value. So we're using its sign. So the result is negative. And then you just subtract the larger absolute value minus the smaller. So 19 minus 16 is 3. So this is going to be negative 3 as the answer. So let's go back up and let's put a negative 3 there. So at this point, Again, you can convert this over. Remember, we said that 20 divided by 5 could be written as 20 over 5, which was 4. Well, if I have 9 over negative 3, I can convert that over, if it's easier for you, to 9 divided by negative 3. So either way, I'm just going to keep it like this as a fraction. But if you need to do that for right now because you're not used to working with fractions, that's fine. Basically, 9 divided by negative 3, a positive divided by a negative or a positive over a negative, that's going to be a negative. And then 9 divided by 3 is 3. So the final answer here is going to be negative 3. Now, this problem has so many different operations that if you didn't get negative 3, you really have to go back. A lot of times, problems like this, you just rip the paper up because there's just so many places you can go wrong. But you really want to go back and just check every step. And you can follow along with the video to see, well, what answer did I get for each step? And then, as I said before, the smallest mistake on a problem like this can give you a really, really different answer. Okay, so you're looking for negative 3 as the final answer. Hello and welcome to Pre-Algebra Lesson 24. In this video, we're going to look at some divisibility rules. So our lesson objective for today is just to learn how to determine if a number is divisible by. Then we have the numbers 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. So essentially, it's the numbers 2 through 12. Now we're going to hold off on this number 7 and this number 11 until the very end because the divisibility rules for 7 and 11 are a bit more time consuming. I'm not going to say they're complex, but they're more time consuming than the other ones. So what does it mean when we say a number is divisible by another? So a number is divisible by another if the result has no remainder. So for example, 25 is divisible by 5. So 25 is divisible by 5 because 25 divided by 5 is 5 and it does not have a remainder. 30 is divisible by 3 because 30 divided by 3 is 10 with no remainder. If I look at something like 19 divided by 4, is 19 divisible by 4? Well, no, it's not. If I take 19 and I divide it by 4, I'm going to get 4 with a remainder of 3. So because there's a remainder involved, 19 is not divisible by 4. So when we have a number that is divisible by another, the result has no remainder. So what we're going to do is we're just going to look at the divisibility rules. I'm going to do 2 through 12, and we're going to exclude 7 and 11 until the very, very end. The ones 2 through 12, excluding 7 and 11, are very, very easy. You just need to write them down as you go. You will memorize them as you practice, and then eventually you won't need your paper anymore. So let's begin by looking at divisibility by 2. So a number is divisible by 2 if it is even. So we've briefly kind of talked about even numbers, and I kind of gave you the definition of even and said that a number is even if it's divisible by 2. Well, yeah, that's true. But kind of the shortcut is the final digit is a 0, 2, 4, 6, or 8. That's the way you can tell if something's going to be even and therefore divisible by 2. Now, if you looked at, let's say, the first 10 numbers, you can see the pattern. If you look at 0, 2, 4, 6, 8, and 10, those are the even numbers here. The other numbers, and let me change the color here, 1, 3, 5, 7, and 9, those are called odd numbers. So if a number is not even, it's odd. So they alternate. You go even, then odd, then even, then odd, then even, then odd. And that's just how it goes forever and ever and ever. So again, for divisibility by 2, you're looking at the final digit of the number. If it's a 0, 2, 4, 6, or 8, then it is automatically divisible by 2. It is an even number. So for divisibility by 3, the sum of its digits is divisible by 3. And if you don't get it at first, the first time you add the digits, you say, well, I don't know if this is divisible by 3. You can keep adding digits. You can keep going until you find out, hey, is this number divisible by 3? For divisibility by 4, the final 2 digits of the number forms a number that is divisible by 4. For divisibility by 5, the final digit is a 0 or a 5. For divisibility by 6, the number is divisible by both 2 and 3. So for divisibility by 8, it's similar to the rule that we had for divisibility by 4. So the final 3 digits of the number forms a number that is divisible by 8. Then for 9, it's similar to the rule for 3. So the sum of its digits is divisible by 9. And just like we saw with 3, when we're checking for divisibility by 9, if we form the sum of the digits and we don't recognize whether that sum is divisible by 9, we can take that sum and we can sum the digits again. For divisibility by 10, the number ends with a 0. And then finally, for divisibility by 12, the number is divisible by both 3 and 4. All right, so let's get some practice going. So we want to determine whether each number is divisible by 2, 3, 4, 5, or 6. So I'm starting with the number 232. So is it divisible by 2? Is it divisible by 2? Well, a number is divisible by 2 if it's even. And again, I told you that a number is even if the final digit is a 0, 2, 4, 6, or 8. The final digit here is a 2, so this number is even. So yes, it's going to be divisible by 2. Now let's check divisibility by 3. So a number is divisible by 3 if the sum of its digits is divisible by 3. So what I would do is I would go through and say, okay, what is 2 plus 3 plus 2? 2 plus 3 is 5. 5 plus 2 is 7. So you would then ask yourself, if I divide 7 by 3, would I have a remainder? And yes, you would. 7 divided by 3 is 2 with a remainder of 1. 2 with a remainder of 1. So 7 is not divisible by 3, and therefore 232 is not divisible by 3. What about 4? So a number is divisible by 4 if the final two digits of the number forms a number that is divisible by 4. So just look at the final two digits of the number. Just think about only those two digits. So the number 32. Is that divisible by 4? Well, yes, it is. 32 divided by 4 is 8 with no remainder. So this would be a yes. Then what about 5? A number is divisible by 5 if the final digit is a 0 or a 5. So if I look at the final digit here, it's a 2. That's not a 0 and it's not a 5. So the answer would be no. And then lastly, we want to ask, is it divisible by 6? Well, a number is divisible by 6 if it's divisible by both 2 and 3. So 232 we found earlier is divisible by 2, but it's not divisible by 3. So if it's not divisible by both 2 and 3, it will not be divisible by 6. So this is a no. Okay, for the next one, we're looking at the number 93. And again, we're doing 2, 3, 4, 5, and 6. So for the number 2, remember, we're looking at, is it an even number? Meaning, does it end in 0, 2, 4, 6, or 8? This ends in a 3. 93 is an odd number. It's not even. It doesn't end, again, in a 0, a 2, a 4, a 6, or an 8. So it's not going to be divisible by 2. This is a no. What about 3? Well, to be divisible by 3, the sum of the digits for the number would be divisible by 3. So you do 9 plus 3, that's 12. 12 divided by 3 is 4 with no remainder. So therefore, because the sum of the digits, which is 12, is divisible by 3, the number 93 is divisible by 3. So this is going to be a yes. This is a yes. Now next, is this number divisible by 4? Now generally, you're going to ask, okay, the final two digits of the number forms a number that is divisible by 4. But we only have a two-digit number here. So we have to think about another trick. Now one of the things I'm going to teach you, and you'll understand why in the next lesson, 4 is built from 2 times 2. So for that reason, if a number is not divisible by 2, if a number is not even, it will not be divisible by 4 automatically. So we don't need to go through and say, okay, 93 divided by 4, is there going to be a remainder? 93 is an odd number. There is no odd number that's going to be divisible by 4. And so this is going to be no. Next, we look at 5. So for a number to be divisible by 5, the final digit is a 0 or a 5. Here our final digit is a 3, so this is going to be a no. And then the last one, is this number divisible by 6? A number is divisible by 6 if it's divisible by both 2 and 3. So we got a yes on 3, but a no on 2. So it's not going to be divisible by 6. So no. All right, let's look at one final problem, and then we'll look at some practice problems that deal with 8, 9, 10, and 12. So what about 300? So again, we're working with 2, 3, 4, 5, and 6. So is it divisible by 2? Well, yes, it is. When your final digit is a 0, it tells you it's an even number. And for divisibility by 2, we need the number to be even. What about 3? Well, you can see that that's yes right away, because if you sum the digits here, 3 plus 0 is 3. 3 divided by 3 is 1, no remainder. So that's a yes as well. What about 4? You look at the final two digits of this number. Now, you might find it odd. You see 0, 0. You say, well, what number does that form? It just forms 0. So basically, you're saying, is 0 divisible by 4? Well, yes, because 0 divided by anything other than 0 is 0 with no remainder. So this is 0, no remainder. So because it doesn't have a remainder, you can say that, yes, 300 is divisible by 4. So this is a yes. Then what about 5? Again, for 5, we're looking at the final digit of the number. And in this case, it is a 0. So yes, if a number is divisible by 5, it's going to have a final digit of a 0 or a 5. So this is a yes as well. And then lastly, for 6, we know that that's a yes because we just look at what we've already done for 2 and 3. Those are both a yes, so this is a yes. Right? For a number to be divisible by 6, it needs to be divisible by both 2 and 3. And in this case, it is. Okay, now we're going to look at 8, 9, 10, and 12. So determine whether each number is divisible by 8, 9, 10, or 12. All right, so we have 918. Again, we're working with 8, 9, 10, and the number 12. So the rule for 8 is that the final 3 digits of the number forms a number that's divisible by 8. Now, that's not really going to help us here because we have a 3-digit number. One of the things you can kind of think about is 8 is built out of 2 times 2 times 2. So if it's not an even number, which in this case it is, so if you had something like 917, you could just say no, right? That's an odd number. It's not even. It's not divisible by 2. So you could just say no right off the bat. But in this case, we do have an even number. So we really just have to check it by doing a long division. So we'd say 918 divided by 8. 8 goes into 9 once. 1 times 8 is 8. Subtract, you get 1. Bring this down. 8 goes into 11 once. 1 times 8 is 8. Subtracting, you get 3. Bring down the 8. 8 goes into 38 how many times? Now here's where you could stop because 8 times 5 is 40. That's too big. 8 times 4 is 32. So you know you're going to have a remainder, right? 4 times 8 is 32. I get a remainder of 6. So it didn't divide evenly, meaning we had a remainder. So we know that the answer here is just going to be no. So this is no. What about divisibility by 9? Well, that's a similar rule to 3. The sum of the number's digits will be divisible by 9. So we just sum this. 9 plus 1 is 10. 10 plus 8 is 18. Think about 18 divided by 9. That's 2 with no remainder. So this one's going to be yes. This will be yes. Then what about 10? So the rule for 10 is you look at the final digit, and if it's a 0, it's going to be divisible by 10. If it's anything else, it's not. So because this is an 8 for the final digit, so the answer is no. So what about 12? Well, for 12, we look at the fact that it needs to be divisible by both 3 and 4. Okay, 3 and 4. So we don't know if it's divisible by 4 yet because we haven't checked that. But for 3, if something's divisible by 9, it's automatically divisible by 3 because 9 is 3 times 3. So we got a yes on the divisibility by 3. Is it divisible by 4? Look at the last 2 digits of this number. If I had 18 divided by 4, would I get a remainder? Well, yes, I would. 18 divided by 4 is 4 with a remainder of 2. Right? If I did 18 divided by 4, 4 goes into 18 4 times. 4 times 4 is 16. Subtracting, you get 2. So 4 with a remainder of 2. So this one is going to be no. And again, although it's divisible by 3, it's not divisible by 4. And so because it fails that one, it's not divisible by 12. Okay, what about 16,299? So again, let's look at 8, 9, 10, and 12. So the number is not even. The final digit is a 9. So it's not an even number. It needs to end in a 0, a 2, a 4, a 6, or an 8 to be even. So because it's not an even number, it's not divisible by 2, so there's no way it's going to be divisible by 8. So this is a no. What about the number 9? Well, for 9, we sum the digits. So we have 1 plus 6, that's 7. 7 plus 2 is 9. 9 plus 9 is 18. 18 plus 9 is 27. So 27 divided by 9 is 3 with no remainder. This is a yes. What about 10? A number is divisible by 10 if the final digit is a 0. In this case, our final digit is a 9. So we're going to put a no there. A number is divisible by 12 if the number is divisible by 4 and 3. Although it would be divisible by 3. Again, if a number is divisible by 9, it's automatically divisible by 3. It's not going to be divisible by 4. And the reason for that is it's an odd number, right? If it's not divisible by 2, it can't be divisible by 4. So this is an automatic no. All right, we'll look at one last one, and then we're going to talk about the rules for 7 and 11. So here we have 10,800. Let me kind of change the colors up. So we have 8, 9, 10, and 12. So for 8, again, we look to see, first and foremost, is it even? And yes, it is, right? It ends in a 0. And then we can look at the final 3 digits of the number. That's 800. Is 800 divisible by 8? Well, yes, it is. And that should be easy for you because 800 divided by 8, you can pretty much do that in your head. That's 100, right? Because 100 times 8 would be 800. So we know that this would be a yes. Next, we look at 9. So we would add here. 1 plus 0 is 1. Plus 8 is 9. Plus 0 is still 9. Now, 9 divided by 9 is 1 with no remainder. So this would be a yes as well. Then what about 10? Look at the final digit of the number, and it's a 0. So this is yes. And then what about 12? Well, we know it's divisible by 3. If a number is divisible by 9, it's automatically divisible by 3. So that part checks out. But what about 4? The final 2 digits of the number would form the number 0. 0 divided by 4 would be 0 with no remainder, so it's divisible by 4. So the answer here would be yes. Because it's divisible by both 3 and 4, it is going to be divisible by 12. Okay, so what about the rules for 7 and 11? So I'm going to tell you the rules for 7 and 11, a lot of teachers just skip them over because they can be a little confusing. But in all reality, if you practice them, just like anything else, it's not that hard. So for 7, there's some steps you need to follow. The first thing you're going to do is remove the last digit from the number. Then you're going to take the number you removed and double it. Subtract this away from the shortened original number. And I put here that we may need to repeat the process a few times. Sometimes you have a large number and you'll do it once or twice and you just don't know if it's divisible by 7 yet. So you just keep going until you have a single number left and you can say, okay, is it 7? Or you can have a multi-digit number like 14 and say, okay, well, 14, I know that's divisible by 7. All right, so let's practice. Determine if each number is divisible by 7. All right, so we have 26,411. Now, the first thing I'm going to do is I'm going to remove the last digit from the number. So basically, just think about it as I'm cutting this number off, and I'm turning the number into 2,641. That's my new number. Now, the number that I cut off, what I'm going to do is I'm going to double it, meaning I'm just going to multiply it by 2. So 1 times 2 is 2. And then I'm going to subtract it away from this shortened number. So I'm going to subtract away 2. Now, what am I going to get? Well, I need to borrow here. 11 minus 2 is 9. Bring down the 3. Bring down the 6. Bring down the 2. Does anybody know if 2,639 is divisible by 7? I sure don't. So you would continue, right? You would just do the same thing. So now I'm going to go, okay, 2,639. Cut off the last digit. Bring that guy over here. I have 263 now as my shortened number. And I'm going to double 9. So I multiply it by 2. 9 times 2 is 18. So 9 times 2 equals 18. And I'm going to subtract that away from 263. So I'll borrow here. This becomes 5. This becomes 13. 13 minus 8 is 5. 5 minus 1 is 4. Bring down the 2. I have 245. I still don't know if this is divisible by 7, so I'm going to continue. I'm going to bring this over here. I have 245. Cut off the last digit. That's a 5. And so that leaves me with a shortened number of 24. Double 5. 5 times 2 is 10. Subtract that away from 24, and I get 14. So now I do have a number, and I know if it's divisible by 7. 14 divided by 7 is 2 with no remainder. So after going through this process, I can see that my original number, which is 26,411, is in fact divisible by 7. Okay, let's try another one. We have 6,480. And essentially what we want to do here, again, is just chop off the final digit. So I'm going to write this number as 648. And then I take that final digit and I double it. So what happens if I take 0 and I multiply it by 2? I get 0. So I can say 648 minus 0 if I wanted to, but we all know that's 648. So I continue. I chop off the final digit of the number again, and I'll have 64. And I'll take this over here, and I'll say, what is 8 times 2? All right, you're going to double it. 8 times 2 is 16, and we'll subtract that away. 14 minus 6 is 8. 5 minus 1 is 4. So I have 48 now, and I can already tell that 48 is not divisible by 7. And I know that through my multiplication tables. If I think about 48 divided by 7 equals what, work backwards. What times 7 equals 48? Well, I know that 6 times 7 is 42. 7 times 7 is 49. That's too big. So I don't have a whole number here that's going to work, and so I'm going to have a remainder, right? So I know that 48 is not divisible by 7, and therefore this number 6,480 is not going to be divisible by 7 as well. Okay, so let's look at the rule for 11 now. 11 is less complicated, but it's still more complicated than the rules that we looked at earlier. So the first thing you do is you find the sum of the digits in the odd places and subtract away the sum of the digits in the even places. And I'll show you how to do that in the example. Then the next thing is that if the result is a 0 or a number that is divisible by 11, then the original number is divisible by 11. So let's look at some examples. Determine if each number is divisible by 11. So what you'll do, if you get this on a test, just go through, starting at the leftmost number, and say, okay, this is position 1, then 2, then 3, then 4, then 5. So remember the difference between odd and even. An odd number would be something like 1, 3, 5, 7, 9, so on and so forth. An even number is a number that ends with 0, 2, 4, 6, or 8. So 2, 4, and then if we had a 6th digit, an 8th digit, something like that, we'd have even. So I want to start by just forming the sum of the digits in the odd places. So 9 plus 7 plus 0. So 9 plus 7 plus 0. Then I'm going to subtract away the sum of the digits that are in the even places. So we'd have 0 and then 2. So 0 plus 2 is 2. 0 plus 2. So 9 plus 7 plus 0 is 16. 0 plus 2 is 2. 16 minus 2 is 14. 14 is not divisible by 11. 14 divided by 11 is 1 with a remainder of 3. So this number, 90,720, is not divisible by 11. All right, let's look at 361,152. And again, we're going to start by labeling it. So the leftmost digit of the number, we're going to say that's in position 1, then 2, then 3, then 4, then 5, then 6. And what we're doing is we're going to sum the digits in the odd places. So the digits that's in the position of 1, 3, and 5. So 3 plus 1 plus 5. 3 plus 1 plus 5. And it's just a coincidence that the digits that's in the 5th position happens to be a 5. I know that can be confusing, but that's a coincidence. Now we're going to subtract away the sum of the digits that are in the even places. So in this position of 2, 4, and 6. So 6 is the number in the 2nd position, plus 1, which is the number in the 4th position, plus 2, which is the number in the 6th position. So again, 6 plus 1 plus 2. So 3 plus 1 is 4, 4 plus 5 is 9. Subtracting away 6 plus 1 is 7. 7 plus 2 is 9 as well. So when we do this subtraction, we get 0. Now remember, we said that it would be divisible by 11 if the result was a 0 or divisible by 11. Here we got a result of 0, so that tells me that this number, 361,152, is in fact divisible by 11. Hello and welcome to Pre-Algebra Lesson 25. In this video, we're going to learn about factoring whole numbers. So the lesson objectives for today, we want to learn how to determine if a whole number is prime, composite, or neither. And additionally, we want to learn to write a whole number as the product of prime factors. All right, before we get into factoring whole numbers, let's think about the concept of a prime number. So we have that a prime number is a whole number larger than 1 that is only divisible by itself and 1. So first, let's think about the whole numbers again. So we've talked about these a lot in this course. So let me write out the whole numbers here. And then basically, I'm going to start with the smallest whole number, which is 0. And then we increase in increments of 1. So next comes 1, then 2, then 3, then 4. And of course, at some point we have to stop. We can't list all the whole numbers. So I'm going to put a final comma and then the 3 dots here to show that the pattern continues forever. When we think about this definition, a prime number is a whole number larger than 1. So automatically, I've got to go into these numbers here, and I've got to basically say, okay, I'm only looking at the whole numbers, starting with 2, and going to the right, or starting with 2 and anything that's going to be larger. So it has to be divisible by only itself and 1. We know that every non-zero number is divisible by itself. So a non-zero number divided by itself will always give you 1. So 2 divided by 2 is 1, no remainder. We also know that every number is divisible by 1. If you divide a number by 1, you just get the number. So for example, 13 divided by 1 is 13. So when I think about, let's say, the number 2, that's going to be a prime number because it's only divisible by itself. 2 divided by 2 is 1, and 1. 2 divided by 1 is 2. In each case, you get no remainder, but there's nothing else you can really do with the number 2. So for that reason, 2 is a prime number. And we're going to find that 2 is the only even prime number. So that's really important. Any even number larger than 2 is going to be divisible by 2, and therefore not a prime number, because it would be divisible by something other than the number itself and 1. All right, it might be extremely helpful to memorize the first few prime numbers. So I have here the first 10 prime numbers. We have 2, that's the smallest prime number. And then we go to 3, 5, 7, 11, 13, 17, 19, 23, and then 29. So that's the first 10. There's an infinite number of prime numbers, and how many you want to memorize is up to you, but just doing the first 10 will greatly speed up your work in many cases. All right, so how can we check to see if a number is prime? So we're going to use the divisibility rules up to the square root of the number. All right, let's briefly touch on the concept of a square root again. So something like the square root of 64 is equal to 8 because 8 times 8 is 64. When I ask for the square root of a number, remember there's 2 different notations. The first one is the principal or positive square root of, in this case, 64. I am asking for what positive number, when multiplied by itself, gives me this, what we call radicand, or number under the square root symbol. Since 8 times 8 is equal to 64, the square root of 64 is equal to 8. And again, this is the principal or positive square root. If you want the negative square root, you need this notation here. So this is the negative of the square root of 64, and that equals negative 8. So this is asking for what negative number, when multiplied by itself, gives me the radicand, or number under the square root symbol. So since negative 8 times negative 8 is going to give us positive 64, the negative square root of 64 is going to be negative 8. So in this lesson, I'm only going to ask for the principal square root, so don't worry about this negative answer here. So if I asked you for something like the square root of 4, you're just going to answer 2. If I said, what is the negative square root of 4, which I'm not going to do in this lesson, that would be negative 2. Now, the reason it's important to understand about square roots, when we look at the factors of a number, and of course this is just going to be with positive factors, we would have something like for 64, 1 times 64, then 2 times 32, then 4 times 16, then 8 times 8. Now 8 is the square root. And what's going to happen is after this, you're going to have factors, but they're going to repeat. So in other words, the next one would be 16 times 4. Then you would have 32 times 2, and then you'd be back to 64 times 1. So this one right here and this one right here, those are just reversed in terms of the order. Same thing for this one, and then this one and this one. So you basically have duplicates after you hit the square root of the number. Now, in most cases, you're not going to get an integer answer when you take the square root of a number. So we're going to talk about that here. All right, so what if I asked you, is 103 a prime number? So to figure this out, we would need to use our divisibility rules up to the square root of 103. But you might stop for a minute and say, well, what is the square root of 103? I know that something like the square root of 100 is equal to 10, because 10 times 10 gives me 100, or here I've written that 10 squared is 100. Then the square root of, let's say, 121, I know that's 11, because 11 times 11 is 121. When we think about a number like 100 or 121, it's called a perfect square. So a perfect square is a number that can be formed as, let's say, an integer times itself to give you that number. So here, 100, we could form it as 10 times 10, or you could also do negative 10 times negative 10, but let's not worry about that for right now. Then for 121, we could do 11 times 11. So that's why it's a perfect square. Later on, you'll hear about something called rational numbers, and you will extend that definition to say that a perfect square is any number where you could basically take a rational number and multiply it by itself to get the number. But in this case, we're just dealing with integers, so we're just going to go with a simpler definition. Now, 103 is not a perfect square. There's no integer that I can multiply by itself to get 103. So if I say, what is the square root of 103? I'm kind of stuck. But really what you would want to think about is 10 squared is 100 and 11 squared is 121. Well, okay, this number right here is between these two perfect squares. In other words, writing this as an inequality, I could say 103 is greater than 100, and it's less than 121. So if I take the square root of 103, it should be greater than the square root of 100 and less than the square root of 121. Let me actually get rid of this for right now. So if I think about this, I'm just going to drag this up here. This would be that 10, which is the square root of 100, is going to be less than the square root of 103, whatever that ends up being, which is less than the square root of 121, which is 11. So just thinking about this, I can say, okay, well, this would be 10, and I know we haven't gotten to decimals yet, 10 point something. Okay, so it's going to be between 10 and 11. I don't really care what comes after that decimal point. I only care that it's going to be between 10 and 11, and I'm just going to go with that lower integer value. So I'm just going to go with 10. So I would check up to that. If you're lucky and you can use a calculator and you punch this in, you would get about, and I'm going to round this to the nearest hundredth, and we haven't talked about that yet, but I'm just going to put 10.15. So we haven't talked about decimals. We haven't talked about rounding decimals. Just trust me for right now that this is the answer. So it's about 10.15. You can see that that would be greater than 10 and less than 11, but you really don't need any knowledge of decimals. You're just going to, if you're using a calculator, cut this part off and just take that whole number. Just take that 10 and you're going to check up to whatever that is. Okay, so now that we've established that we're going to check up to 10, we can just run through the divisibility rules. For this one, it's going to be actually pretty quick. So we know that this is an odd number, so immediately you can mark out 2, 4, 6, 8, and 10. Then when you think about divisibility by 3, you sum the digits. So 1 plus 0 plus 3. 1 plus 0 is 1, plus 3 is 4. So you think about, is 4 a number that's divisible by 3? No. 4 divided by 3 would give you 1 with a remainder of 1. So because there's a remainder there, you can mark this out. And then if a number is not divisible by 3, it can't be divisible by 9, so mark that out. So now we're left with 5, which is pretty easy, and then 7, which is a little bit tricky. So 5, you just look at the last digit of the number. Is it a 0 or is it a 5? In this case, it's a 3, so 5 is out. So cross that out. And then we think about 7, which is the most challenging. We would think about cutting off the final digit of the number. So in this case, that's 3, so you just cut it off. And then basically over here, I'm going to double it. So 3 times 2 and you're going to subtract that away. So this would be what? 3 times 2 is done first. So that would be 6. So you get 10 minus 6, which gives you 4. So if this number is 0, or some number that's divisible by 7, then basically the number you were working with is divisible by 7. Here, this is a 4, so that's obviously not 0, and it's not going to be divisible by 7. So this will not be divisible by 7. So let's go ahead and say that this number, 103, is a prime number. Now you can see how much work it is to actually go through and check and see if something is prime. So in most cases, your teacher is going to give you something from a list that you've already memorized. But in case you get something that's not, you can go through and use this strategy to determine if something is prime. All right, now let's think about a composite number. So a composite number is a whole number that is greater than 1 and is divisible by a whole number other than itself and 1. So when we say it's a whole number that is greater than 1, again, it's the same numbers that we're working with. We write out the whole numbers, and then basically we start with 2, and then we move to the right on that list, or you say anything that's 2 or larger, that's what you're thinking about. So it's got to be divisible by a whole number other than itself and 1. So here are the first 10 composite numbers. So when you look at 4, 6, 8, 9, 10, 12, 14, 15, 16, and 18, notice that 4, 6, 8, 10, 12, 14, 16, and 18, those are even numbers. Again, they are automatically going to be divisible by 2 because they're even numbers, so they can't be prime numbers. They're automatically going to be composite numbers because they are divisible by some whole number other than itself and 1. So now looking at the other ones, we have this 9 here. 9 is divisible by 3. You have 15. 15 is divisible by 3 and also 5. And that's pretty much it for the first 10 composite numbers. Obviously, there's an infinite number of composite numbers, just like there was an infinite number of prime numbers. You can't memorize all of them, so you just have to go through the strategies to determine if you have something that's prime or composite. All right, now on your test, you might be asked about 0 and 1. Remember, in the definition for a prime number and also in the definition for a composite number, we specifically said it was a whole number larger than 1. So basically, we're starting with 2 and we're looking for anything larger. So what about 0 and 1? The numbers 0 and 1 are not prime, so they're not prime, and they're also not composite. If you get that question on a test, they are neither. Okay, you want to put that down. They are neither. They're not prime and they're not composite. All right, let's run through a few of these. So we want to determine if each number is prime, composite, or neither. We're going to begin with 123, and coming down here, you see that I have some numbers listed here. So starting with 2 and then going up to 11. So why did I stop with 11? Remember, we only need to check up to the square root of the number. Now, in this particular case, 123 is not what we call a perfect square. There's no rational number, or some books will say integer, that multiplies by itself to give you that number. So when I have this situation, I'm going to think about the fact that 11 squared is going to be 121. And then 12 squared is going to be 144. So these are things that I know. If you don't, you can do a multiplication. So if you're not using a calculator, you're just going to think about the fact that, okay, well then the square root of 121 is 11. And then the square root of 144 is going to be 12. Well, this number 123 is going to be between those two numbers. In other words, 123 is greater than 121 and less than 144. So then the square root is going to be somewhere between 11 and 12. I don't actually care where it is because I'm just going to go down to 11, right? So I only have to check up to 11. If your teacher is nice, then it's a lot quicker. You can just say, what is the square root of 123 in your calculator? And we're going to approximate this. And I get, if I round to the nearest hundredth, about 11.09. Okay, so about 11.09. And again, just cut this part off. Just get rid of this and just take the whole number part. And basically, I'm going to check up to 11. That's all you need to do. So looking at this, I know that this is an odd number. So immediately, it's not going to be divisible by 2 or 4 or 6 or 8 or 10. Okay, get rid of that right away. Then when I think about 3, well, this number you would sum the digits. 1 plus 2 is 3. 3 plus 3 is 6. Well, yes, 6 divided by 3 is 2, no remainder. So yeah, immediately I know this is a composite number. So this is a composite number. What about the number 51? Again, if I'm thinking about the square root of 51, if I'm lucky and I have a calculator, well, I would say that's about 7.14 if I round to the nearest hundredth. So I only need to check up to 7. Again, if you don't have a calculator, then just think about the fact that 7 squared is 49, and then 8 squared is 64. So if you think about this, get rid of this for a moment, we know that 51 is greater than 49 and less than 64. So that means when I take the square root of 51, I'm going to get something that's between 7 and 8. I don't actually care what it is. I know that I'm just going to go down to 7. So checking this, I need to look at 2, 3, 4, 5, 6, and then 7. So just going up to 7. This number's not even, so you can immediately get rid of 2, 4, and 6. And then just think about, is it divisible by 3? 5 plus 1 is 6. 6 divided by 3 is 2, no remainder. So yeah, this is going to be a composite number. All right, what about 59? So again, I can take the square root of 59 in my calculator if I'm lucky, and that would give me about 7.68 if I round to the nearest hundredth. Or if I don't have a calculator, I can think about the fact that 7 squared, again, is 49, and then 8 squared is 64. So the square root of 59, because, again, 59 is greater than 49 and less than 64, it's going to be between 7 and 8. Again, I don't care about this 0.68 part. I only care about the whole number, so I only care about that 7, just going down. So I want that 7 there, so I only want to check up to 7. This is not an even number, so I can get rid of 2, 4, and 6. Think about 3. 5 plus 9, that's going to be 14, so you can get rid of 3. 14 is not divisible by 3. Now for 5, again, the final digit has to end with a 0 or a 5. This does not end with a 0. If it did, it would be an even number. And it does not end with a 5. So let me get rid of that. So now we have to check 7. For that one, we know the rule is a bit complicated. It might actually be quicker to just do a division. But what you do is actually cut off the final digit of the number, and you double it. So 9 times 2, and you subtract that away. So basically, 9 times 2 is 18. So this would give me 5 minus 18. And this would give me negative 13. And forget about the fact that it's negative. Just say, is 13 divisible by 7? The answer is no. So you can cross this out. And then we can conclude that 59 is going to be a prime number. So it's only divisible by itself. So 59 divided by 59 is 1. And then also 59 divided by 1 is 59. All right, now let's actually move into factoring whole numbers. So I'm going to start off with a basic definition that, of course, we already know, but I want you to recall that 2 or more numbers that are multiplied together are known as factors. So in this multiplication problem, 3 times 5 equals 15. The 3 and the 5 are known as factors. They're being multiplied together. The 15, the result of the multiplication operation, is the product. Then 8 times 7 equals 56. The 8 and the 7 are the factors. The 56 is the product. So when we have factors that are prime numbers, they are known as prime factors. Now, a lot of times you're going to be asked to find the prime factorization of a number, and that just means you're going to break the number down into the product of prime factors. So I have here that it is often useful to write a number as the product of prime factors. We're going to have a lot of operations moving forward that are going to depend on this knowledge. So I have here to write a number as the product of prime factors. We continue to factor each factor until it's prime. So I'm going to start off with this 80 here, and then I'm going to show you how to do this with a factor tree, which is a great way to visually organize your work. So here I have, let's try to write 80 as the product of prime factors. So I'm just going to start off with 80 is equal to, just pick any 2 numbers other than itself and 1. So I'm not going to pick 80 and 1. I'm going to pick something like, let's say 8 and 10. So 8 times 10. And then just keep breaking these numbers down. So 8, I know that's 4 times 2. 2 is a prime number. And then times, for 10, I'm going to put 5 times 2. So 5 is prime and 2 is prime. But I can break 4 down and say that's 2 times 2. So then times 2 and then times, let me reverse the order here. So put 2 there and then times 5. So what do I have? I have 1, 2, 3, 4 factors of 2. So let's say this is 2 to the 4th power. And then times 1 factor of 5. So 2 to the 4th power is 16, and 16 times 5 is 80, right? So we've basically broken this down into the product of prime factors. And again, you're going to need to do this a lot moving forward. So this is the process you could use. Using a factor tree is generally a little bit better because it helps you to organize your work. This right here is kind of a mess and not organized. So in order to use a factor tree, you want to write the number to be factored and extend 2 lines below. So these lines that you're extending below, they're going to basically be called branches. Then you want to list any 2 factors of the number. So then other than the number itself in 1, and you're going to place each under one of the lines or what we call the branches. Then we're going to circle any prime factors. And for any factors that are not prime, we just repeat the process. So you're going to extend 2 branches, list any 2 factors other than the number itself in 1, and then you're going to circle the prime factors. So I have here, this continues until all factors are prime. Okay, let's look at some examples. We will look at 80 again using a factor tree. So let me write 80 here, and then these are going to be my branches. So you can do anything other than the number itself in 1. So before we did 8 and 10, let's change that up and do 16 and 5. So now, once you've listed 2 factors, check to see if one of them is prime. 5 is prime, so you're going to circle it and you're going to stop. For 16, it's not prime. I could say this is 4 times 4, and then you're going to check neither of those is prime. And so this is 2 times 2, and then this is 2 times 2. And so you're going to circle these. So this, 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 and this, those are all prime numbers. So this gives me that 80 is equal to 1, 2, 3, 4. So 2 to the 4th power times 5. Now let me do this a different way just to show you that you get the same result. Let's say I didn't start with 16 and 5. I could have done 8 and 10. So let's say I do 8 and 10. And so this, neither of those is prime. So I'm going to go 5 and 2. 5 and 2 are both prime. So I'm going to circle and stop. And then for 8, let's go with 4 and 2. And then 2 is prime, so circle that and stop. And then for 4, it's 2 times 2, so circle those and stop. So basically you get 2 times 2 times 2 times 2, which is 2 to the 4th power, and then times 5. So same thing either way. Let me just do it one other way just to show you that it doesn't really matter. So I'm going to go 4 and 20. Okay, so 4 is 2 times 2, and we're going to stop, right? So this is prime and this is prime. 20 is 4 times 5. 5 is prime, so we're going to stop. Then 4 is 2 times 2, circle those and stop. So no matter how you do this, you end up with 2 times 2 times 2 times 2, which is 2 to the 4th power, times 5. Okay, let's look at 95. So 95. So for this one, you might think about, okay, how do I get started? 95 is not something I really work with that often. If you notice the number ends with a 5, you know it's divisible by 5. So I would come over here, if you don't have a calculator, and just do a quick long division. 5 goes into 9 once. 1 times 5 is 5. Subtract 9 minus 5 is 4. Bring down this 5 here. 5 goes into 45 9 times. 9 times 5 is 45. Subtract and you get 0. So I could do 19 and then 5. So let me get rid of this. And we know 5 is a prime number. What about 19? Well, I did list this as one of the first 10 prime numbers. If you didn't know that, again, you can go through the process we talked about earlier in the lesson, and you could check and confirm that this is a prime number. So this right here, 95, would be equal to 19 times 5. What about 240? 240. So if a number ends with a 0, it's divisible by 10. Usually that's the easiest to start with. So I'll just say this would be 24 times 10. So then from here, I know that neither of these is going to be prime. So this right here would be 5 times 2. Circle these. 5 and 2 are both prime. For 24, a lot of different things you could do. You could do 4 and 6. You could do 8 and 3. You could do 12 and 2. Whatever you feel like. Let's just go with 4 and 6. So neither of those are going to be prime. So 6, I'm going to do 3 and 2. And this is going to be 2 and 2. Let me circle this and this and this and this. All of those are prime. So 240 would be equal to 1, 2, 3, 4 factors of 2, so 2 to the 4th power, and then times, you've got 1 factor of 3, and then times, you've got 1 factor of 5. Now, let's say, just for the sake of completeness, I get rid of this, and I would have started with, let's say, 20 times, let's say, 12. I'm just showing you it doesn't matter how you start. So 20 and 12, neither one is prime. This one, you could do 5 times 4. 5 is prime. 4 is 2 times 2. 2 is prime, and 2 is prime. 12, you could do 4 times 3. So 3 is prime, 4 is 2 times 2. And again, you get 1, 2, 3, 4 factors of 2, 1 factor of 3, 1 factor of 5. So it doesn't matter what you start out with. Just pick any 2 factors other than the number itself and 1, and you're going to be good to go. Just keep going down and breaking each number down this way. All right, what about 126? So this number, it's an even number, so I know it's divisible by 2. And then 1 plus 2 is 3, plus 6 is 9. So that tells me it's divisible by 3 and also 9. But because it's divisible by both 2 and 3, it's going to be divisible by 6. Let me do that off to the side. So 126 divided by 6. 6 does not go into 1, but it will go into 12 twice. 2 times 6 is 12. Subtract, you get 0. Bring down the 6. 6 goes into 6 once. 1 times 6 is 6. Subtract, and we get 0. So basically, you could do 21 times 6. So this would be 21 and 6. Now, 21 and 6, neither of those is going to be prime. 6 is going to be 3 times 2. Let's circle these. 3 and 2 are both prime numbers. 21 is 7 times 3. Let's circle those. 7 and 3 are both prime numbers. So let's say 126 would be equal to, let's go 1 factor of 2, and then times, we have 2 factors of 3. So let's say 3 squared, and then times 1 factor of 7. All right, what about 828? So it's kind of a big number. I know it's an even number, but I would look at the last 2 digits here. This is a 28, so this number is going to be divisible by 4. And I would also check and see if it's divisible by 3. 8 plus 2 is 10. 10 plus 8 is 18. So it will be divisible by 3 and also 9. Now, if a number is divisible by both 3 and 4, it's going to be divisible by 12. So I'm just going to start with that. So 828 divided by 12, and you could do something else. It's really up to you. So 12 goes into 82 how many times? Well, I know that 6 times 12 is 72. So let's put a 6 here. And 6 times 12 again is 72. Let's subtract. 2 minus 2 is 0. 8 minus 7 is 1. So this is 10. Bring down the 8. So 12 goes into 108 how many times? Well, from the multiplication tables, that would be 9. Because 9 times 12 is 108. So we'll subtract here and get 0. So I could go 69 times 12. 69 times 12. And again, you could have started with something else. It's really up to you. So for this one, I'm going to go 4 and 3. 3 is prime, so let's circle that and stop. 4 is 2 times 2. Those are prime. Over here for 69, let's think about that for a moment. So it's not an even number. And 6 plus 9 is 15, so this is divisible by 3. So let me start with that. So 69 divided by 3. 3 goes into 6 twice. 2 times 3 is 6. Subtracting, you get 0. Bring down the 9. 3 goes into 9 3 times. 3 times 3 is going to be 9. Subtracting, you get 0. So this would be 23 times 3. Let me get rid of this. So hopefully you remember that 23 is a prime number. That was in the list of the first 10 prime numbers. And 3, of course, is a prime number. Again, if you don't know that 23 is a prime number, you can quickly find that out using your divisibility rules, going up to the square root of the number. So let me write out that 828 is going to be equal to, we have 2 factors of 2, so 2 squared. Let me slide this down just a little bit here so it fits. And then times, and then you have 2 factors of 3, so 3 squared. And then times, you're going to have this 23. Let's do one more, and this is a really big number. Usually you get numbers that are at most 3 digits, but I'll do one with 4 digits just so you get some practice. So 4,320. Again, this ends with a 0, so it's not that bad. I would just start by saying, okay, well, this is going to be 432 times 10. And then for this one, this is 5 times 2. Circle these, you're done over there. So now you got to think about 432. So I know immediately, looking at the final 2 digits, that this guy right here, since 32 is divisible by 4, 432 will be divisible by 4. So you could start with that. But then again, if you look at 4 plus 3, that's going to be 7. 7 plus 2 is 9. So this number is also divisible by 3 and 9. Okay, so if it's divisible by 4 and 3, you can go with 12. There's other things you can do, but I'm just going to go with 12. So let's say 432 divided by 12. So 12 will not go into 4. It will go into 43. We're going to do that 3 times. 3 times 12 is 36. Let's subtract. I'm going to borrow here and say this is a 3, and this is a 1. 13 minus 6 is 7, and then 3 minus 3 is 0. So we're going to bring down this 2 here. So 12 goes into 72 exactly 6 times. 6 times 12 is 72. Subtracting, you get 0. So this right here is going to be 36 times 12. All right, for 36, we could do, let's say, 6 times 6. You could also do 4 and 9, whatever you want to do. And then for 6, we could go 3 times 2, and then 3 times 2. So we'll circle these. These are all prime numbers. Then for 12, let's go 4 and 3. I'll circle 3. And then for 4, this is going to be hard to fit. So let me branch down here like this. This is going to be 2 times 2. So let me circle those. Okay. This one's pretty big. Let me actually slide this whole thing over to the left so I can fit it. All right, let me write this 4,320. I'm just going to highlight my 2's. So 1, 2, 3, 4, 5 factors of 2. So this is equal to 2 to the 5th power. then times. So now let me go through with a different highlighted color, and I'm going to look for my 3's. So I got 1, 2, 3 of those guys, just so I don't miss anything. So this is 3 cubed, and then times, you've got that 1 factor of 5. Let me highlight that for consistency here. So I'm just going to put times 5. And you can verify that if you have a calculator, but basically 2 to the 5th power is 32. So this is 32, and then times 3 cubed would be 27, and then times 5. So if you want to punch that into a calculator real quick, you'll see that you do get 4,320. Or of course, you could do a vertical multiplication with these two right quick, and then do another one with this one and verify it the long way. Hello and welcome to Pre-Algebra Lesson 26. In this video, we're going to have an introduction to fractions. So for our lesson objectives for today, we want to gain a basic understanding of fractions. We also want to learn the difference between a proper fraction, improper fraction, and mixed number. So up to this point in our pre-algebra course, we've really only thought about the whole numbers and the integers. But what happens when we have an amount that is larger than 0 but less than 1? Something that's a part of a whole amount. Well, when we come across this scenario, we can turn to fractions for help. And I know some of you watching this video already have extensive experience with fractions, while others have no experience whatsoever. No matter what, all of us have worked with fractions in our everyday life, even if we haven't realized it. So a typical scenario would involve you splitting up a pizza with your friends. So as an example, let's take a look at this pepperoni and cheese pizza that we have on the screen. So the first thing I want you to notice is that the pizza is cut up into 4 equal parts. All right, we have 1, 2, 3, 4 equal parts. Now, when we work with fractions, we're going to have some whole amount that's cut up into equal parts. So our whole amount would just be the pizza. So 1 pizza is our whole amount. It's cut up into 4 equal parts. So that means if I have 4 parts, out of 4 parts, I have 1 pizza. Now, let's suppose that 3 of your buddies come over to the house, and there's a total of 4 of you. So let's put that there's 4 people. Now, in the interest of fairness, we're going to make sure that each person gets the same amount of pizza. So everybody's going to get 1 slice out of a total of 4 equal slices. So each person would get 1/4 of the pizza. Now, you might say, where did that 1/4 come from? Well, the 1 is called the numerator. This is the numerator. It's the top part of a fraction, and it tells us the number of parts being discussed or used. Since we're talking about how much each person's going to get, the numerator is a 1, because each person is getting 1 part, or in terms of the pizza, 1 slice. Now, the bottom number here is the denominator. This is the denominator. This tells me how many equal parts my whole amount is split up into. My 1 pizza, my whole amount, has been split up into 4 equal parts, so my denominator is a 4. Now, this middle part is called a fraction bar. Called a fraction bar. And later on, we're going to learn that the fraction bar represents division. We actually have the numerator divided by the denominator. But we don't need to think about that for now. Just think of the fraction bar as a way to separate your numerator, or your top part, from your denominator. So in this scenario where there's a total of 4 people, and we have 4 equal slices for our pizza, each person gets 1 slice out of 4, or 1/4 of that whole pizza. So as we just saw, fractions are generally used to describe how many equal pieces, how many equal pieces we have of a whole amount. Now, in the previous example, we talked about how many equal pieces each person got, right? Each person got 1/4 of a whole pizza. So let's take a look at this cookie here. So again, the cookie represents our whole amount. So 1 cookie is what we have. And again, you'll notice that it's split up into 4 equal parts. 4 equal parts. 3 of the parts, you'll notice, have chocolate chips. That's what these black circles are. And then 1 part has macadamia nuts. Okay, that's what the white circles are. What if I was to ask you how much of this cookie has chocolate chips? Well, again, 3 parts out of the 4 have chocolate chips, so our numerator is going to be a 3. Okay, our numerator is going to be a 3. Again, the numerator is the number of parts being used or discussed. In this case, we're discussing how much of the cookie has chocolate chips. That answer is 1, 2, 3. So we have 3 there. So that's our numerator. So let me just label this. This is the numerator. We have our fraction bar to separate the numerator from the denominator. And the bottom number of the denominator is a 4 because we have 4 equal pieces in our whole amount. Again, this is the denominator. What if I asked you how much of the cookie has macadamia nuts? Well, that would be 1/4, right? We have one piece or one part out of a total of 4 equal parts. So the numerator is going to change. Now we're discussing macadamia nuts, so that's going to be a 1. The denominator will not because I still have 4 equal parts in this cookie. So now we're talking about the fraction 1/4. As another example, let's take a look at this apple that's cut into 2 equal pieces. So we have one piece and then a second piece. So let's suppose it's me and you, and we're in a room, and we both want the apple. So we decide in the interest of fairness that we'll cut it down the middle, just like we have. Each person has an equal amount. How much will each person get? Well, each person gets one piece out of a total of 2 equal pieces. Right? The numerator is a 1. The denominator is a 2. All right, the numerator again tells me the number of parts being used or discussed. And again, we're discussing how much each person is going to get. Each person is going to get 1 part, so that's why the numerator is 1. The denominator is 2 because there's 2 equal parts in the whole amount, right? In the apple, we've cut it up into 2 equal parts, so the denominator is 2. Each person is going to get 1/2 of the apple. Now let's suppose as we're about to bite into this apple, 6 more people show up and they say, hey, we each want an equal amount. So now we've got to cut up the apple into 8 equal pieces. 8 equal pieces. And each person asks you, how much am I going to get? Well, they're going to get 1 piece out of a total of 8 equal pieces, or the fraction 1/8. Right? So 1 again is the numerator. And 8 is the denominator. So again, each person would get 1/8 or 1 piece out of a total of 8 equal pieces for this apple. Let's say that you're watching a video on the web, and this video has 3 equal parts. So let's say this is the first part. This is part 1, and then this is part 2, and this is part 3. Okay? And I know this might not be perfectly equal how I drew it, but let's just pretend that it's 3 equal parts. Now the part in red shows you what you've already watched. So what if I asked you the question, how much of this video have you watched so far? Well, if we look at the red progress bar, we see that that takes up 1 part out of a total of 3 equal parts for the video. So you've watched 1 part, again, out of a total of 3 equal parts. That's the fraction 1/3. Again, where 1 is your numerator, this is the numerator, and 3 is the denominator. Now what if I ask you the question, how much of the video is left? Well, I have this part here, and then this part here. So unwatched, we would have 2 parts out of a total of 3 equal parts. So that's 2/3. So 2 is the numerator in this case, and 3 is the denominator. Again, in each case, the video was split up into 3 equal parts. So that's where our denominator came from in the watched and the unwatched. For the watched, we had seen 1 part out of the 3. So that's how we got a numerator of 1. For the unwatched, we have not watched 2 parts out of the 3. So that's how we got a numerator of 2. All right, so I think we have the basics down on how to come up with a numerator and denominator. Let's just do a quick practice exercise to see if you can identify the numerator and denominator in each. And we're going to start out with 1/5. So the top number is the numerator. And I'm going to write it out for the first one, and then I'm going to abbreviate after that. And the bottom number, the 5, is the denominator. So for the fraction 1/5, you have 1 as the numerator, 5 as the denominator. So this means I have 1 part out of a total of 5 equal parts. Next, we'll look at the fraction 2/9. The 2 is the numerator, so I'm just going to put a capital N. The 9 is the denominator, and I'm going to put a capital D. So I have 2 parts out of a total of 9 equal parts. Next, we have the fraction 1/4. 1 is the numerator, that's the top number. 4 is the denominator, that's the bottom number. So for this scenario, I have 1 part out of a total of 4 equal parts. Then for 3/8, 3 is going to be our numerator, and 8 is going to be our denominator. Again, if I have 3/8 of something, I have 3 parts out of a total of 8 equal parts. Okay, we'll look at 2 more. 5/7, 5 is the numerator, 7 is the denominator. Again, the numerator is in the top, the denominator is in the bottom. And if I have 5/7 of something, I have 5 parts out of a total of 7 equal parts. Then for the last one, I have 15/17. So 15, the number on top is the numerator. 17, the number on the bottom is the denominator. If I have 15/17 of something, then I have 15 parts out of a total of 17 equal parts. So there's kind of more to fractions than just what we covered so far. Once you start getting higher in math, you're going to replace your division symbol with a fraction bar. And I kind of talked about this in the beginning when I said the fraction bar represents division. So I want to just quickly cover some important division rules that we need to remember when we're working with fractions. So the first one is going to be that any non-zero number that is divided by itself is going to result in 1. So if I have something like 4 divided by 4, I can now write this using a fraction as 4/4, or 4/4, and this is going to be equal to 1. And think about the scenario we had with a pizza. Let me just go all the way back up real quick. So kind of looking at this, I see that I've split up my pizza into 4 equal slices. So if I consume 4/4 of the pizza, or I eat 4 pieces out of a total of 4 equal pieces, then I've consumed 1 whole pizza. The next rule to remember is that 0 divided by any non-zero number is always 0. So 0 divided by, let's say, 3 equals 0. And now we can write this using a fraction as 0/3 equals 0. And just think about having something that's cut up into equal parts of 3, and you get 0 parts. So how much of it did you get? You got 0. Right? If I get 0 out of a total of 3 equal parts, I'm still getting 0. So fractions represent division of the numerator by the denominator. We can write a division problem using fractions. So again, if we see something like, let's say 8 divided by 4. This is traditionally how we write it in elementary school. Now we can write it using fractions as 8 divided by 4 like that. The numerator divided by the denominator. Here we have 8 divided by 4. 8, the leftmost number. The dividend goes up on top as the numerator. 4, your divisor, goes on the bottom as your denominator. So 8 divided by 4, we know that's 2. Or something like 20, divided by 5. We could write this as 20/5. Right? It's just the numerator divided by the denominator. So the leftmost number, your dividend, goes on top as the numerator. Your rightmost number, your divisor, goes on the bottom as your denominator. So 20 divided by 5 is 4. And we can do one more. Let's say we had, 100 divided by 25. So we could write this as a fraction. We take 100. That's going to be our numerator. And then 25 is going to be our denominator. Right? Numerator divided by denominator. 100 divided by 25 is the same as 100/25. And this is going to be equal to 4. Okay, so let's kind of wrap up our lesson by just talking about the differences between a proper fraction, an improper fraction, and a mixed number. So a proper fraction is used to describe a quantity whose value is less than 1. So the easy way to tell if you have a proper fraction is just to look at the numerator and see if it's less than the denominator. If it is, you have a proper fraction. So something like 2/5 or 5/7 or 2/11 or 1/9. In each case, the numerator is smaller than the denominator. If I got something like 15/7, that's not a proper fraction. The numerator is larger than the denominator. This is an improper fraction. Now, before we go any further, let me just try to warn you that your teacher might try to trip you up with some negative fractions. So let's say you get something like -2/3. -2/3. If you get a negative fraction, ignore the negative sign and just pretend the fraction's positive. So I'm just going to think about this as +2/3 and just look at the 2 and the 3. The numerator is smaller than the denominator, so it's a proper fraction. I can just put my negative sign back and say, okay, -2/3 is a proper fraction. If I had something like -11/3, 11/9. Ignore the negative sign. Pretend it's 11/9. And look at the 11. It's bigger than 9, so it's not a proper fraction. Okay, it's not a proper fraction. So that means negative 11/9 is not a proper fraction either. So kind of next up, an improper fraction is used to describe a quantity equal to or larger than 1. So kind of the easy way to think about this is that if your numerator is the same as or larger than your denominator, you have an improper fraction. So like 8/8, the numerator is the same as the denominator, so this is improper. Right? So equal to or larger than 1. If you had something like 13/11, equal to or larger than 1. Again, if you get negative numbers involved, just think about them as if they were positive, right? Take the absolute value before you think about the definition. So if I had something like negative 15/14, let's say I try to go by this definition. An improper fraction is used to describe a quantity equal to or larger than 1. Well, any negative number is less than 1. So if you try to apply this definition using this as a negative, you get the wrong answer. So that's what I'm saying. Just ignore the negative sign. Just look and see if the numerator is bigger than the denominator. 15 is larger than 14. And so you would know this is an improper fraction, right? Negative 15/14 is improper. Okay, the last thing we're going to learn about is called a mixed number. So a mixed number is kind of a fancy way to write an improper fraction, right? And you can go back and forth, and we'll see how to do that in the next lesson. So basically what it is, it's the sum of a whole number and a proper fraction. So something like 3 1/4. And what this is it's 3 plus 1/4. We just write it like this for convenience, right? And a lot of students get confused and think that's multiplication because they're sitting next to each other. But no, it's 3 plus 1/4. Or something like 6 1/8, right? This is 6 plus 1/8. But it's very important that you have a whole number and then a proper fraction. It can't be a whole number and an improper fraction. Okay, so let's look at one final quick exercise. We just want to determine whether each is a proper fraction, improper fraction, or mixed number. So we're going to take a look at 7/5. So the numerator is larger than the denominator. This is improper. Again, that's all you need to look at. 3/11, the numerator is smaller than the denominator, so this is proper. For 4/5, the numerator is smaller than the denominator, so this is proper. For 9 1/8, it's easy to see that this is a mixed number, right? It's a mixed number. And I don't think anybody gets confused between mixed numbers and proper fractions and improper fractions. They mostly get confused on the definition between a proper fraction and an improper fraction. For a mixed number, you have a whole number just hanging out to the left. So it's pretty obvious that it's a mixed number. For 10/7, the 10, the numerator is larger than the 7. So this is an improper fraction. For 6/7, the 6, the numerator, is smaller than the denominator, 7. So this is proper. Hello and welcome to Pre-Algebra Lesson 27. In this video, we're going to talk more about mixed numbers and improper fractions. So for our lesson objective, we want to learn how to change a mixed number into an improper fraction and vice versa. Meaning we also want to learn how to take an improper fraction and change that into a mixed number. All right, so we're going to begin by learning how to take an improper fraction and change that into a mixed number. So this is very, very simple. Just write down the steps, use them as you practice, and just like anything else, over time, you can just kind of throw your paper away because you will memorize this. So the first step is just to divide the numerator by the denominator. So if I have something like, let's say 10/3, okay, let's say 10/3, I would take 10 and I would just divide it by 3, just like that. So 3 goes into 10 3 times. 3 times 3 is 9, subtract and get 1. So this division gives me 3 with a remainder of 1. So let's kind of copy this. We're going to bring it down to the next step. Okay, so I have here that the quotient is the whole number for the mixed number. So this 3 here, which remember, that's our quotient, that's going to be the whole number for the mixed number. So the 3 will be your whole number part. Then the remainder, which in this case, that's that 1 there, is the numerator of the fraction part. So I'm going to put a 1 there. Now, where do I get my denominator for the fraction part? Well, it's the original denominator from the improper fraction. So that doesn't change. That's still your denominator here for the fraction part. And remember, that was a 3. 3 1/3 is the same thing as 10/3. Okay, 3 1/3 is the same thing as 10/3. All right, let's take a look at some examples. We're going to start out with 18/7 or 18/7. So again, my first step is just to do a basic division. So I'm going to take 18 and I'm going to divide by 7. So 7 goes into 18 twice. 2 times 7 is 14. Subtract and you get 4. So the answer here is 2 with a remainder of 4. So again, to convert this into a mixed number, the quotient part, which is 2, is going to be the whole number part. The remainder, which is 4, is going to be the numerator for the fraction part. And then your denominator for the fraction part is the denominator from the improper fraction. So that's going to be 7. Or you could just say, okay, it's my divisor from when I did my division, right? 18 divided by 7. However you want to remember that. So 18/7 is the same as, or is equal to, 2 4/7. All right, let's take a look at another one. We have 19/3. So again, we just set up a basic division. 19 divided by 3. So 19 divided by 3. And 3 is going to go into 19 6 times. 6 times 3 is 18. Subtract and we'll get 1. So that's our remainder. So we get 6 with a remainder of 1. So again, the 6, the quotient part, is your whole number. The 1, which is your remainder, is going to be the numerator for your fraction part. And then the denominator for the mixed number is going to be 3, right? It's the same denominator as from the improper fraction. So 19/3 is the same as, or again, is equal to 6 1/3. What about 11/7? So again, we're going to divide. We have 11, and we're dividing by 7. 7 goes into 11 once. 1 times 7 is 7. Subtract and we get 4. So the remainder here is 4. So 1 with a remainder of 4. And let me kind of move this down so I can write my answer. Move that over there. So this is equal to, again, the whole number part will be 1, right? That's your quotient. The numerator for the fraction part will be 4. That comes from my remainder. And then the denominator for the fraction part is the denominator from the improper fraction. So that's a 7. So 11/7 is equal to 1 4/7. All right, what about 31/15? So again, we set up a long division. We have 31 divided by 15. So 15 goes into 31 twice. 2 times 15 is 30. Subtract and we get 1. So this is 2 with a remainder of 1. So again, the 2, the quotient part, is your whole number. 1, the remainder, is your numerator for the fraction part. And then 15, which is the denominator from the improper fraction, is going to be the denominator for the fraction part. So 31/15 is equal to 2 1/15. All right, let's take a look at one more. So we have 59/8, or 59/8. So again, divide 59 by 8. 8 goes into 59 7 times. 7 times 8 is 56. Subtract and get 3. So this would be 7 with a remainder of 3. So this is going to be equal to, again, the whole number part is going to be 7. You get that from your quotient. The numerator for the fraction part is going to be 3. Again, that comes from your remainder. And then the denominator for the fraction part is 8. That comes from your improper fraction. So 59/8 is equal to 7 3/8. So really that was pretty easy overall. Your general strategy for those type of problems, again, just write down your steps, use the steps as you practice, and then after you get enough practice, you won't need to look at those steps anymore. You will have memorized them, right? So these things will become automatic for you. Now we're going to talk about changing from a mixed number to an improper fraction. And this isn't going to be any more difficult. So the first step is to multiply the denominator of the fraction part by the whole number part. So if we had something like, let's say 3 1/8, I would take the denominator of the fraction part, which in this case, that's this 8 here, and I would multiply it by the whole number part. So I would have 3 times 8 to start. So 3 times 8. And let me copy this. We're going to bring this down to the next step. Then the next thing we want to do is add the result to the numerator of the fraction part. So I have this 3 times 8 here. That's to be done first. When that's done, I'm going to add the numerator of the fraction part. So that's 1. So I can put plus 1 here if I want. And because of the order of operations, I would do 3 times 8 first, and then I would add 1 to that result. So I really don't need to do anything to clarify that if I just follow the order of operations. But if you want to make it completely crystal clear, you can put parentheses around 3 times 8 just to say, hey, I absolutely must do 3 times 8 first before I add 1 to that. The result of this is the numerator for the improper fraction. So 3 times 8 is 24. And if I add 1 to that, I get 25. All I'm missing now is my denominator. And the denominator is going to be the same as the denominator from the fraction part for the mixed number. So that's going to be an 8. So we have 25 eighths here. Now what I want to show you is we know how to go from 25 eighths to 3 1/8. Again, we set up a division. So 25 divided by 8. 8 goes into 25 3 times. 3 times 8 is 24. Subtract and get 1. So the remainder is 1. So if I convert between this and a mixed number, I would get a 3, which is what we have here for my whole number part. My remainder is a 1, so that's the numerator for the fraction. And my divisor is an 8, or my denominator for the fraction is an 8, so that's going to be my denominator for the fraction part of the mixed number. So 25 eighths is the same as, or is equal to, 3 1/8. All right, so we're going to begin with 8 1/3. And really very simple overall. Again, if you wrote down the steps, step 1 is to multiply the denominator of the fraction part by the whole number part. So I'm going to take 3, which again is the denominator of the fraction part, multiply that by 8, which is the whole number part. So I would start out with 8 times 3. 8 times 3. Now once I've done that, it tells me to add the result to the numerator of the fraction part. And recall that I put parentheses around 8 times 3 to make it crystal clear that we multiply that before we do any addition. But again, you don't need to do that because of the order of operations. If I come over here and I put plus 1, okay, because I'm adding the numerator from the fraction part next, whether I have parentheses around 8 times 3 or not, it doesn't matter, right? The order of operations tells me, hey, multiply before I add. But for this lesson, I'm going to put parentheses around it just so we're clear. We're doing 8 times 3 first before we add that result to 1. So 8 times 3 is 24, and 24 plus 1 is 25. And now, where do I get my denominator from? Again, the denominator is the same denominator from the fraction part of that mixed number. So this is going to be over 3 over 3. So 8 1/3 is equal to 25 thirds. Okay, let's take a look at 9 4/7. So again, the first step is to multiply the denominator of the fraction part by the whole number part. So this right here, this 7, is getting multiplied by 9. So what is 9 times 7? I'm going to put that in parentheses. And then when we're done with that, we add the result to the numerator of the fraction part. So the numerator for the fraction part is 4. So I'm going to say plus 4 when I'm done. And my denominator is going to be the same as the denominator from the fraction part of the mixed number. So that's going to be a 7. So 9 times 7 is 63. And then if I add 4 to that, I'm going to get 67. So this would be 67 over 7, or I could say 67 sevenths. What about 3 5/8? Well, again, we want to start out by multiplying the denominator of the fraction part by the whole number part. So I'm going to take 8 and multiply it by 3. So 8 times 3. Then when I'm done, I'm going to add to that the numerator of the fraction part. So in this case, that's this 5 here. And this is going to be over. My denominator from the fraction part of the mixed number is an 8. So that's going to stay the same, right? That's going to be my denominator for the improper fraction as well. So now I just crank this out. 8 times 3 is 24. 24 plus 5 is 29. So this is going to be 29 over 8, or again, 29 eighths. And we could just say that 3 5/8 is equal to 29 eighths. What about 13 5/11? Well, again, I'm going to take this part right here, this 11, the denominator from the fraction part, and I'm going to multiply it by the whole number part. So we would have 11 times 13. Now, once we've performed this operation, we're going to add the result to the numerator of the fraction part. So I'm going to add that to 5. So plus 5. And this is going to be over. Again, we use the denominator from the fraction part of the mixed number. So this is going to be over 11. So what is 11 times 13? 11 times 13. A lot of you already know that it's 143. Well, let's go ahead and crank this out. 3 times 11 is 33. And then 1 times 11 is 11. So we're going to add, bring down the 3. 3 plus 1 is 4, bring down the 1. So again, 143. If I add 5 to that, I'd have 148. So this would be equal to 148. And again, that denominator is going to be 11. So 13 and 5/11ths is equal to 148 elevenths. What about 107 ninths? Well, again, we're going to start by taking the denominator from the fraction part, multiplying it by the whole number part. So you'd have 9 times 100, 9 times 100. And then when we're done, we're going to add to it the numerator from the fraction part. So that's a 7. I'm going to add a 7 on there. My denominator stays the same as the denominator from the fraction part of the mixed number. So that's going to be a 9. And let's just crank this out. What's 9 times 100? Well, we have 2 trailing zeros here. So I just need to do 9 times 1. That's 9. Then attach 2 trailing zeros to the end. So that would give me 900. Then I would add 7 to that. So that would be 907. And then over 9. So 107 ninths is the same as 907 ninths. Hello and welcome to Pre-Algebra Lesson 28. In this video, we're going to learn how to find the greatest common divisor, which I've abbreviated as GCD. So the lesson objective for today is just to learn how to find the greatest common divisor, again abbreviated GCD, for a group of numbers. So before we kind of get into the lesson, I want to clear something up that causes a lot of confusion for students. As someone who makes a lot of video tutorials, one thing I've noticed is that if I post a video on, let's say, finding the greatest common divisor, like we have here, students will watch that and they will post in the comments, hey, do you have anything on finding the greatest common factor? And my reply will always be, yeah, you just watched it. If someone's asking you to find the greatest common divisor for, let's say, 2 numbers, it's the same thing as if they asked you to find the greatest common factor for those 2 numbers. So if I said something like, what is the greatest common divisor of, let's say, 12 and 30, it's the same thing as if I asked you, what is the greatest common factor of 12 and 30? Same exact thing. And to kind of think about this for a second, we all know that if we have 4 times 3 equals 12, that 4 and 3 are called factors. They're called factors of 12. But really, they're also divisors, right? So if I have 12 and I divide by 4, I get 3. There's no remainder there. If I have 12 and I divide by 3, I get 4. There's no remainder there. If a number is a factor of another, it's also a divisor, meaning if I take 12 and I divide it by any of its factors, I'll get a result that doesn't have a remainder. So when we ask for the greatest common divisor and we ask for the greatest common factor, we're asking for the same thing. So when working with 2 or more numbers, the greatest common divisor, again I abbreviate this GCD, is the largest whole number that is a divisor of all numbers. And I could have just as easily said, when working with 2 or more numbers, the GCF, the greatest common factor, is the largest whole number that is a factor of all numbers. Again, we can interchange those. Now, actually finding the greatest common divisor or the greatest common factor for a group of numbers is very simple. Go ahead and write down the steps and then use them as we practice. And then again, as you do more practice, you won't need to look at the paper. You will have committed the steps to your memory. So for finding the greatest common divisor, the first thing you want to do is find the prime factorization of each number. We all know how to do that at this point. We learned it a few lessons back. You can use a factor tree or some other method that you've learned if that's more comfortable for you. The next thing we're going to do is create a list of prime factors that are common to all numbers. And this part's important. When you're creating that list, make sure that the prime factors are common to all numbers. If you're trying to find the greatest common divisor for, let's say, 5 numbers, and you have a prime factor that's common to 4 of them, but not common to the 5th number, you can't use it. It has to be common to all numbers. Then the last thing, you're just going to take that list that you made, and you're going to form the product of the numbers on the list. That's going to give you your greatest common divisor. Right? So the greatest common divisor is the product of the numbers on the list. Very, very easy. So we're going to jump in and look at some practice problems. We want to find the greatest common divisor for each group of numbers. We're going to start out with this GCD of 12 and 20. So what is the greatest common divisor? Or I could have just as easily said, what is the greatest common factor of 12 and 20? The first thing we're going to do is find the prime factorization of each number. I'm going to do that using a factor tree. But again, if you have another method you're more comfortable with, use that. So for 12, I'm going to start out with 4 times 3. Again, you can just start out with any 2 factors for 12. It doesn't matter what it is. And then anytime I have a prime factor, I just circle it and I stop. So 3 is prime, I circle it and I stop. 4 is 2 times 2. 2 is prime, so I'm going to circle both. And then now let's do 20. I'm going to start out with 5 times 4. Again, any 2 factors for 20 would work. 5 is prime, circle that and stop. 4 is 2 times 2. 2 is prime, so circle both. Now that we have the prime factorization for each number, and let's just write it out. We have 12 is 2 times 2 times 3, and 20 is 2 times 2 times 5. We're looking to see what is common to both. And I know a lot of people will make a table, and we'll do that kind of when we get to some bigger numbers. For right now, we can kind of eyeball it and see that we have 1 2 that's in common, and then a second 2 that's in common, and nothing else that's in common. So if we were to form a list, that list would contain 2 2s, right? 2 2s. So for my greatest common divisor, remember, I just formed the product of the numbers on the list. So the greatest common divisor is going to be 2 times 2, which is going to be equal to 4. Right? And I could have just as easily written greatest common factor of 12 and 20 is 2 times 2, which is 4. Again, these are the exact same thing. I want to embed that in your head so that you understand it. All right, let's take a look at the greatest common divisor of 36 and 54. So again, start out by finding the prime factorization for each number. For 36, it's 6 times 6 we could do. So 6 is not prime, so we're going to continue. 6 is 2 times 3, and 2 times 3 over here. And 2 and 3 are both prime, so we're going to circle all of these. And we're done. Now for 54, I could think about 9 times 6. And neither number is prime, so we're going to continue. 9 is 3 times 3. 6 is 3 times 2. And all of those are prime. So we're going to circle all of these. And we have our prime factorizations. So 36 is 2 times 2 times 3 times 3. 2 times 2 times 3 times 3. 54 is 3 times 3 times 3 times 2. So I'm going to write this as 2 times. I'm just going to put a space here because I don't have another 2. And then I'm going to put times 3 times 3 times 3. And I'm basically just doing that so that we can glance at this and see what's common, right? So I can look right now and see that I have a 2 that's common to both. I have a 3 that's common to both, and another 3 that's common to both. So if I was to make a little list, it would contain 1 2, 1 3, and then a second 3. So the greatest common divisor of 36 and 54 is going to be equal to 2 times 3 times 3. So 2 times 3 is 6. 6 times 3 is 18. So your greatest common divisor for 36 and 54 is going to be 18. All right, let's take a look at one with 3 numbers involved. So not any more difficult, just a little bit more tedious. The more numbers you put in there, the more tedious it gets. So we have the greatest common divisor of 25, 80, and 90. So we're going to find the prime factorization for each number. 25 is 5 times 5, and 5 is prime, so we're going to circle both. 80, I'm going to start out with 8 times 10. 8 is 4 times 2. 4 is 2 times 2. Now 2 is prime, so I'm going to circle all of these guys. And then 10 is 5 times 2. 5 and 2 are prime, so I'm going to circle those guys. And then what about 90? Well, I'm going to do 90 as 9 times 10. Neither is prime, so I continue. 9 is 3 times 3. 10 is 5 times 2. And all of these are prime, so I'm going to circle them. So now I have my prime factorizations. So 25 is 5 times 5. So I'm just going to write this like this. 5 times 5. 80 is 2 times 2 times 2 times 2. Then times 5. And then 90, I got 2 times 3 times 3 times 5. So one thing we can do is we can write the numbers that are common on top of each other so it makes it completely clear. And I kind of did that in the last example, but as you get better at this, you really don't need to do it. Particularly when you look at 25, you see that it's 5 times 5. So right away you know that when you go to the other numbers, you're only looking for a 5, right? Because that's all that's involved in here, and it has to be common to everything. So I'm not looking at any of these 2's, and I'm not looking at any of these 2's or 3's here. So really I would just highlight this 5, and this 5. I just have one 5 that's common to everything. Now there's a second factor of 5 in the prime factorization of 25, but it's not matched in the prime factorization of 80 or 90, right? There's just one 5 in the prime factorization for 80 and 90. So we can only put one 5 on our list. So it makes it really easy. The greatest common divisor of 25, 80, and 90 is going to be 5. I don't need to multiply anything here. There's only one number that's in common to everything, and again, that's 5. All right, for the last problem, let's look at one that's a little challenging. So we have the greatest common divisor of 198, 165, and 132. So let's start out by just factoring 198. So I know it's an even number, so I know it's at minimum divisible by 2. Now, it's not going to be divisible by 4 because if I look at the final two digits here, 98, that's not divisible by 4. So let's go ahead and just start out with dividing this guy by 2 and just seeing what we get. 2 will go into 19 9 times. 9 times 2 is 18. Subtract, you get 1. Bring down the 8 there. 2 goes into 18 9 times. 9 times 2 is 18. Subtract, you get 0. So 99 times 2 gives you 198. So 2 is a prime number, so we can circle this and stop. 99 is not. Right away when I look at 99, I'm thinking, is it divisible by 9? 9 plus 9 is 18, so yeah, it's divisible by 9. So this is 9 times, and you might know by now this is 9 times 11. But again, in case you didn't, you could just do a long division, 99 divided by 9. Now, we should know at this point that 11 is a prime number, so we'll circle that and stop. And 9 is 3 times 3. So 3 is prime. We're going to circle these. And we have our prime factorization for 198. It's 2 times 3 times 3 times 11. Let's write this on the next page. So 198 is 2 times 3 times 3 times 11. Okay, let's do 165 now. So just like with 198, I don't know two factors for this number off the top of my head. But again, using my divisibility rules, I see it ends in a 5. So I know I can do 165 divided by 5. 5 goes into 16 3 times. 3 times 5 is 15. Subtracting, get 1. Bring down the 5. 5 goes into 15 3 times. 3 times 5 is 15. Subtracting, get 0. So 33 times 5 gives me 165. Now 5 is a prime number, so I can circle this and stop. 33 is not. I know that 33 is divisible by 11. 33 divided by 11 is 3. So 33 would be 11 times 3. And 11 and 3 are both prime. So circle both of those. And so for 165, we get 3 times 5 times 11. Okay, for the last one, we have 132. And I can see that this number is even right away. So I know it's divisible by 2. The last two digits form the number 32, so that's divisible by 4. And 1 plus 3 is 4, 4 plus 2 is 6. 6 divided by 3 is 2, no remainder. So it's divisible by 4 and 3, so it has to be divisible by 12. So 132 divided by 12. 12 goes into 13 once. 1 times 12 is 12. Subtracting to get 1. Bring down the 2. 12 goes into 12 once. 1 times 12 is 12. Subtracting to get 0. So 12 times 11, okay, 12 times 11 would give me 132. Again, we know 11 is prime. 12 we could write as 4 times 3. 3 is prime. 4 is 2 times 2. 2 is prime, so we're going to circle both. So 132 is 2 times 2 times 3 times 11. Now we're going to form a little list and look for what's common. So I have a 2 in the prime factorization of 198. I don't have it in 165, so it's not going to be common in everything. Although I have 2 factors of 2 here, I can't use 2 in my list because, again, it's not common to everything. What about 3? I have that in 198, I have it in 165, and I have it in 132. So I can put one factor of 3 in that list. Now I have a second factor of 3 here, but I don't have a second factor of 3 in 165, so it can't go into the list. Now the last thing we'd look at in the prime factorization of 198 is 11, and that's going to be common to everything. So there's an 11 here and here. So really the only thing that's common to all 3 would be one factor of 3 and one factor of 11. So when I build my GCD, my greatest common divisor, for 198, 165, and 132, it's going to be equal to, again, the product of the numbers on the list. So 3 times 11, or 33. Hello and welcome to Pre-Algebra Lesson 29. In this video, we're going to learn about simplifying fractions, otherwise known as reducing a fraction to its lowest terms. So the lesson objective for today is just to learn how to simplify fractions. And again, as I just said, this is also referred to as reducing a fraction to its lowest terms. So I just want to make you guys aware of a little notational change that's going to start in this video. Now, for a lot of you who haven't taken algebra yet, you've only used this symbol to imply multiplication. Right? This is for multiplication. So if I wanted something like 6 times 7, I write 6, then that symbol, then 7, and we know that equals 42. But kind of as you move higher in math, this symbol is going to go away. You're going to use some other method, right? And there's multiple methods you can use. I know earlier in the course we talked about a number being next to parentheses implies multiplication. You're going to have that. But primarily what we're going to use is a dot. Okay, we're going to use a dot. So if I wanted 6 times 7, I could write it like this. This symbol also means multiplication. So 6 times 7 equals 42. Or we could do 2 times 8, that equals 16. Right, I'm just replacing this familiar symbol with this new dot. And that's all that we're going to change. Now you might ask yourself, why do we go back and forth between these symbols? Well, as you get higher in math, you start working with variables. And this symbol here will get confused with the variable x, which is very, very common in algebra. So we have to switch to something else so that it's crystal clear what we want you to do. So before we kind of get into the math of simplifying fractions, I want you to take a look at these two rectangles on the screen. Now we have part of each rectangle that's shaded green and part that's just white. If I was to look at this top rectangle here, it's cut up into 2 equal parts. Here's the first part, here's the second part. So if I was to ask you to represent the amount that's shaded green with a fraction, you would come up with the fraction 1/2. Right? So shaded, you have one part, that's going to be your numerator, that's shaded, out of 2 equal parts. So that's the fraction 1/2. Now when we look at the rectangle below, we see that it's split up into 4 equal parts. So 1, 2, 3, 4. But I want you to observe that these 2 parts here take up the same space as this one part here. These two parts here, the parts that are shaded green, take up the same space as this one part here. So if I wanted to represent the shaded amount for this bottom rectangle, okay, so what's shaded in green? I now have two parts, okay, two parts, so that's my numerator, out of a total of 4 equal parts. So 4 is my denominator. So now we can visually see that 1/2 is the same as or is equal to 2/4. But you might say, how is that the case? How is that mathematically possible to have the same value from two different numbers? Well, let's just erase this 2/4 for a second and just start out with 1/2. All of you know at this point that if I multiply a number by 1, the number remains unchanged. So for example, if I multiply 5 times 1, I get 5. If I multiply 277 times 1, I get 277. If I multiply 1/2 times 1, I get 1/2. Now all of us also know that any non-zero number divided by itself is 1. So if I had 2 divided by 2, 2 divided by 2, this is the same thing as the number 1. So let's say I multiply 1/2 times 2 over 2. I'm basically multiplying 1/2 by 1. Now I know we haven't multiplied fractions yet officially, but essentially all we're going to do is multiply the numerator times the numerator and put that over the denominator times the denominator. So I would do 1 times 2, that would give me 2, and I would multiply 2 times 2, and that would give me 4. So I took 1/2 and I multiplied it basically by 1. It's a complicated form of 1, but 2 over 2 is 1. And I ended up with 2/4. So that's how we can have the same value out of two different fractions. And I could keep going. I could have multiplied 1/2 by, let's say, 5 over 5. 5 over 5 is 1. 1 times 5 is 5. 2 times 5 is 10. So 5/10 is the same as 1/2. So equivalent fractions are fractions that have the same value. And we just saw that with 1/2, 2/4, and 5/10. Those are all equivalent fractions because at the end of the day, they have the same value. So now that we understand how two or more fractions can look different but have the same value, let's talk about reducing a fraction to its lowest terms. So a fraction is considered simplified, okay, simplified, or your teacher or your textbook might say reduced to its lowest terms when the numerator and denominator have no common factors other than 1, okay, other than 1. So to reduce a fraction to its lowest terms, or again, to simplify a fraction, you start out by factoring the numerator and denominator completely. Then you're going to cancel all common factors between the numerator and denominator. All right, so we're going to jump in and look at some practice problems now. We want to reduce each fraction to its lowest terms. Okay, we're going to begin with 15 over 27. So the first thing we want to do is factor the numerator and denominator completely. Now you've probably gotten pretty good at factoring whole numbers at this point. So you can use a factor tree if you need to, but for some of the smaller numbers, you probably have memorized the prime factorizations already. Like 15 you should know is 5 times 3. You shouldn't need a factor tree for that. 27, you know it's 3 times 3 times 3. 3 times 3 times 3. If you need a factor tree, pause the video and make one. You know, you have 9 times 3. 3 is prime, circle that. 9 is 3 times 3. Circle both of those. So you see that you get 3 times 3 times 3. Now, after you've done that, you're looking to cancel common factors between the numerator and denominator. So in other words, if I have a 3 in the numerator, I can cancel that with one of the 3's in the denominator. Essentially, all I'm doing is I'm saying, hey, I have 3 over 3, and that's the same thing as 1. So when I go through, I don't have this 3 anymore. I just have a 5 in the numerator. And when I go through here, I don't have this 3 anymore. So I just have a 3 and another 3 in the denominator, and 3 times 3 is 9. So I'm basically saying that 15/27, or 15 over 27, is the same thing as 5/9. And again, reverse this process to kind of get a little insight as to what happened. So you have 5/9. If you multiply it by 3 over 3, again, 3 over 3 is the same thing as 1. So I'm not changing the value of the fraction. 5 times 3 is 15. 9 times 3 is 27. Okay, let's look at 18 over 60. So again, we want to factor the numerator and denominator completely. So for 18, let's just do a factor tree. Let's start out with 6 times 3. So 3 is prime. Let's circle that. 6 is 2 times 3. 2 and 3 are both prime. Let's circle those. So 18 is 2 times 3 times 3. 2 times 3 times 3. For 60, let's do 10 times 6. 6 is 2 times 3. Those are both prime. So circle 2 and circle 3. 10 is 5 times 2. And those are both prime as well. So circle 5 and circle 2. So we're going to have 2 times 2. 2 times 2 times 3 times 5. So what's common between numerator and denominator? Well, I have one factor of 2 in the numerator that I can cancel with one factor of 2 in the denominator. 2 over 2 is equal to 1, so we can just remove that. Now, I have one factor of 3 in the numerator that I can cancel with one factor of 3 in the denominator. And then that's all. I have this 3 up here, but I have no other 3 down here to cancel it with. Then I have this 2 down here, but no other 2 up here to cancel it with. Right? I've already canceled out this 2. I can't use it again. And then finally, I have this 5 here. No 5 up here to cancel it with. So our simplified version of this fraction, I have a 3 in the numerator. And then in the denominator, I have 2 times 5, or 10. So 18 over 60 is equal to 3 over 10, or 3/10. Let's take a look at 95 over 20. Again, we want to factor each number. So 95, I know, is 19 times 5. And those are both prime numbers. So we're going to circle those. So 19 times 5. 20 I know is 4 times 5, and 4 is 2 times 2. So 2 times 2 times 5. Now what's common between numerator and denominator? I have a 19 in the numerator, no 19 in the denominator. I have a 5 in the numerator, and I have a 5 in the denominator, so I can cancel those common factors between numerator and denominator. And then I have 2 2's in the denominator, but I don't have anything in the numerator that matches that. So my answer, I'm going to have a 19 in the numerator, and I'm going to have 2 times 2, or 4, in the denominator. So I end up with 19/4 as my answer. All right, what about negative 26 over 156? So we've never worked with a negative yet. And basically, when you see a negative, when you factor the number, just write a -1 out to the side, and then just write the prime factorization for the number 26. So for 26, it's 13 times 2. So I'm going to write -1 times 13 times 2. Right? -1 times 13 is -13. -13 times 2 is -26. All right. Then we have 156. So let's make a factor tree for that one. So 156, I know that it's divisible by 2, and it's also divisible by 4, because 56 is divisible by 4. So let's do that off to the side. What is 156 divided by 4? 4 goes into 15 3 times. 3 times 4 is 12. Subtracting, get 3. Bring down the 6. 4 goes into 36 9 times. 9 times 4 is 36. Subtracting, get 0. So this would be 4 times 39. 4 is 2 times 2. And 39 is 13 times 3. So let's circle all of these because they're all prime. So we would have 2 times 2. 2 times 2 times 13 times 3. Now what can we cancel between numerator and denominator? We can cancel this 13 in the numerator with this 13 in the denominator. We can cancel this 2 in the numerator with one of the 2's in the denominator. Doesn't matter which one, just one of them. Now all I have left in my numerator is a -1. So that's going to be my numerator. And in the denominator, I have 2 times 3, or 6. So our simplified version is -1/6. All right, let's look at -33 over 77. So again, I have a negative value here. Just write -1 times, and then do the prime factorization for 33. And that's just going to be 3 times 11. What about 77? Well, 77 is 7 times 11. So 7 times 11. And as time goes on, you're going to recognize right away that the greatest common divisor of 33 and 77 is 11. So you're just going to kind of mentally divide each number by 11. So in other words, if I had -33 over 77, Once I'm good at this, I'm not going to go through these steps. I'm going to say, okay, 33 divided by 11 is 3. So this would be negative 3 over 77 divided by 11 is 7. So I end up with negative 3/7. So you're going to be able to mentally do this after some practice. But for right now, it's best not to skip any steps. So we see that we have a common factor of 11 between the numerator and denominator, and that's all we can cancel. So we end up with negative 1 times 3, or negative 3, over 7. So you end up with negative 3/7 as your answer. What about 64 over 288? So 64 I know is 2 to the 6th power. So 2 times 2 times 2 times 2 times 2 times 2. Again, if you didn't know that, you could do a factor tree, right? 64 is 8 times 8. 8 is 4 times 2. 2 is prime, so we're going to circle these. And then 4 is 2 times 2. Just after a while, you're going to start to recognize what the prime factorizations are for some of these common numbers. So I got 1, 2, 3, 4, 5, 6 factors of 2, which we have up there. And then what about 288? Well, I know it's divisible by 2, and 88 is definitely divisible by 4, so I can start with that. Let's divide 288 by 4 and see what we get. 4 goes into 28 7 times. 7 times 4 is 28. Subtracting gets 0. Bring down this 8 here. 4 goes in 8 twice. 2 times 4 is 8. Subtracting gets 0. So 72 times 4 is 288. Now, without making a factor tree, I know that 4 is 2 times 2. I know that 72 is 9 times 8. Okay? 9 is 3 times 3. 8 is 3 factors of 2. Again, if you're not comfortable with this yet, go ahead and make the factor tree. It's not a big deal. So 288, again, 4 times 72. 4 is 2 times 2. 72 is 8 times 9. 8 is 4 times 2. 9 is 3 times 3. 3 is prime. 2 is prime. And then 4 is 2 times 2. And then that's prime. So we have 1, 2, 3, 4, 5 factors of 2. So 2 to the 5th power times 2 factors of 3 are 3 squared. So 2 to the 5th power times 3 squared. And that's exactly what we got up here. We have 1, 2, 3, 4, 5 factors of 2 and 2 factors of 3. Okay, so now we're looking to cancel common factors between numerator and denominator. I can cancel this 2 with this 2, 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 and then this 2 with this 2. Now I have a last 2 up here because I have 1, 2, 3, 4, 5, 6 factors up here, but I only have 5 factors of 2 in the denominator. So I'm going to have 1 factor of 2 up here that I can't cancel with anything because I had 1 more up here than I had down here. These 3's I don't have anything to cancel with up in the numerator. So my simplified version of this fraction, I'm going to have a 2 in the numerator and 3 times 3, or 9, in the denominator. So we end up with 2/9 as our answer. All right, so now we have 25 over negative 135. 25 over negative 135. 25 is just 5 times 5. Negative 135, again, if you have a negative involved, just write -1 and then just do the prime factorization for 135. So 135, it ends in a 5, so I know it'll be divisible by 5. And what is that? 135 divided by 5. 5 would go into 13 twice. 2 times 5 is 10. Subtracting, get 3. Bring down the 5 there. 5 goes into 35 7 times. 7 times 5 is 35. Subtracting, get 0. So 27 times 5 is 135. And we know 5 is a prime number. We can circle that. And 27 we know is 3 factors of 3. Right? It's 9 times 3. 3 is prime. 9 again is 3 times 3. And 3 is prime. So we're going to circle both of these. So 3 times 3 times 3 times 5. So what can we cancel between numerator and denominator? Well, all I can do is cancel this 5 with this 5, and that's it. All right, I have one more 5 here, but nothing to cancel with down here. And I have some 3's down here, nothing to cancel with it up there. So we just end up with 5 in the numerator and 1, 2, 3 3's in the denominator. 3 times 3 is 9, 9 times 3 is 27. Then multiply by -1, you get -27. Now, I can keep it as 5 over -27. I could also write this as -5 over 27, or I could write this as negative and then 5 over 27. All of these are the same thing. Remember that when we divide integers, a positive divided by a negative is a negative, or a negative divided by a positive is a negative, or you can just have the negative out here just saying, hey, the fraction is negative, and then 5/27. All of these mean the same thing. You have a -5/27 as your answer. Okay, let's take a look at 4/19. So 4 we know is 2 times 2. 19 is prime. If I looked at the greatest common divisor, or again, the greatest common factor of 4 and 19, your answer would be 1. So when you have this situation, you're not going to be able to simplify the fraction any further, and you just end up with 4/19 as your answer. Hello and welcome to Pre-Algebra Lesson 30. In this video, we're going to learn about multiplying fractions. All right, so the lesson objective for today is just to learn how to multiply 2 or more fractions together. I'm going to give you an initial procedure, and then I'm going to modify it slightly. We're going to start doing something called cross-canceling, and that's going to allow us to simplify while we're doing the multiplication problem so that we don't have to simplify after. But let me give it to you this way first, and then we'll do the modification. So to multiply 2 or more fractions, you're going to multiply the numerators together, and then you're going to place the result over the product of the denominators. And I have here we want to simplify, but we're going to change this up a little bit as we work through the problems. Now, before we get started, let me give you a brief explanation in terms of why we do this as the numerator times the numerator over the denominator times the denominator, and then we simplify. So let's suppose that I start off with a pizza, and I'm going to split this up into 4 equal slices. So each slice will be 1/4 of the pizza. So let's say this is 1, 2, 3, and then 4 slices. Suppose that I eat a slice of this pizza for breakfast, and then another one for lunch, and then a final one for dinner. So how much of the pizza did I eat? 3/4. How much of the pizza is left? 1/4. So we know that at this point. But how could I have gotten that 3/4? I would have said that, well, I ate 1, 2, 3, so I could just count pieces of pizza out of a total of 4 equal pieces of pizza that were available in this whole amount. So I could have said that this is 1/4, that's me eating at breakfast, plus 1/4, that's me eating at lunch, plus 1/4, that's me eating at dinner. So this should give me 3/4. Now, we're not going to really talk too much about adding fractions here. This is something we'll cover later on. It's a little bit complicated, but basically, if you have the same denominator, so here you have a 4, and a 4, what you do is you keep that denominator the same, and you just add the numerators. So you see that this is 1 plus 1 plus 1. So my 1 slice from breakfast plus my 1 slice from lunch plus my 1 slice from dinner, that 1 plus 1 plus 1, that gives me 3 slices that I ate out of a total of 4 slices in that whole pizza. So now that we understand that we should get 3/4 from 1/4 plus 1/4 plus 1/4, what we can do is transform this into a related multiplication statement. Remember, if you have something like, let's say 3 times 5, this is going to be 5 plus 5 plus 5. So either way, whether you do the multiplication from the multiplication tables or from the repeated addition here, you're going to get 15. So the same thing should be true here. If I write this as 3, because I have 1, 2, 3 of these guys, times 1/4, I should get 3/4. And how would we do that? Well, you could write 3 as 3 over 1. 3 divided by 1 is going to be 3. So I haven't changed anything. And then you could just multiply the numerators together. 3 times 1 would give me 3. And then you could put that over the product of the denominators. So 1 times 4 would give me 4. So that's how you would get 3/4. So you'll see me say we want to multiply the numerators together, put this over the product of the denominators. All right, let me give you another example here because it's not going to be that straightforward when you see something like, let's say 1/2 times 1/4. Well, what in the world does this mean if you try to translate it into repeated addition? We saw that when we had 3 times 1/4, this became 1/4 plus 1/4 plus 1/4 if we write it as a repeated addition. But if I write 1/2 times 1/4. Well, I don't have 3 of these. What I want is 1/2 of this. So basically, it's like saying I want 1/2 of 1/4. So I have this first pizza, which is cut into 4 equal slices. What we're going to actually have to do is take this 1/4. Let me just mark this off right here. So this would be 1/4 of the pizza. And let me do this over here. Now this guy is cut into 8 equal slices. So let me mark this off. What you're going to have to do if you say that you want 1/2 of something, well, you need to cut it into 2 equal parts. So I'm going to slice this guy. Let me use a different color here. I'm going to slice this guy right here. And I want 1 out of those 2 equal parts. So I want this slice right here. Let me count these up. So this is 1, 2, 3, 4, 5, 6, 7, 8. So I want 1 slice out of a total of 8 equal slices. So this would give me 1/8. Because basically I'm starting with 1/4 of this whole amount. So 1 piece out of a total of 4 equal pieces. And I'm saying, hey, give me half of that. So it's kind of like I got this slice and I said, okay, well, we need to split it. So we split it like this, or I cut it in half. And now how much do I have? Well, I have 1 piece out of 8 pieces now, instead of having 1 piece out of 4 pieces. So this becomes the fraction 1/8. Now, when you look at it, again, it's the same procedure. Multiply the numerators. 1 times 1 would give me 1. And then put this over. You're going to multiply the denominators. 2 times 4 would give me 8. So 1/2 times 1/4 would give me 1/8. All right, let's take a look at some examples. So you'll find this process to be very, very easy. We have 2/5 times 1/7. So just following the procedure, we're going to multiply the numerators together. So 2 times 1 would give me 2. We're going to place that over. We're going to multiply the denominators together. So 5 times 7 would be 35. Now, 2 is a prime number, and 35, we just saw that came from 5 times 7. 5 is a prime number, and 7 is a prime number. So really, there's nothing here that I can cancel, right? The GCF is going to be 1. So we would say the simplified answer here is 2/35. All right, so here's one that's going to be a little bit tricky. So first, let's use our procedure. So we have 3/10 times 5/12. I'm going to multiply numerator times numerator. So 3 times 5 is 15. This is over denominator times denominator. So 10 times 12, that's 120. Okay, well, here is the problem. You see that this guy right here is the correct answer, 15/120, but it's not simplified. So if you report an answer and it's a fraction and it's not simplified, your teacher will probably at minimum take points off. Some of them will mark it wrong. It just depends on your teacher. So what you'd actually have to do is factor this, and you're going and undoing what you just did, right? So 15, you're going back to 3 times 5. And let me make that 3 a little bit better. And then for 120, if I break that down completely, 10 is going to be 5 times 2. And then 12 is 4, which is 2 times 2, and then times 3. Let me extend that a little bit. Now we know how to simplify fractions already. Basically, I'm looking at the numerators and the denominators, and I'm seeing what's common. So I can cancel this with this. 3 divided by 3 is 1. Now I would advise you at this point to put a 1 there. A lot of people will leave it off. It just depends on your preference. Some teachers will make you do it. Some teachers will tell you to put a 1 there and put a 1 there. And some teachers will say it doesn't matter. But the thing is, when you look at this one, I'm going to cancel this 5 with this 5. So I'm going to put a 1 here and a 1 here. Now, if your scratch work looks like this, let's say you get rid of all of this stuff. Well, the problem is the temptation for most students, they're going to say, okay, there's nothing in the numerator. I've canceled everything away. So they write a 0. Really, it's a 1, right? Because 3 divided by 3 was 1, and 5 divided by 5 was 1. So that's why if you put a little 1 there as a reminder, you can say, okay, well, I need to multiply 1 by 1. That's going to give me 1, and this is over. 2 times 2 times 2, that's going to be 8. So remember, it's just like I did the problem. 3/3 times 5/5 times 1 over, let's say 2 times 2 times 2, that's going to be 8. This is exactly going to give me the same answer as this. What happens is 3/3 is 1, right? So I can just say this is 1. 5/5, that's 1. So it's 1 times 1 times 1/8, which is 1/8. So this is the correct answer. You don't want to put a 0 up there. Okay, let me get rid of this. When we look at what we did, we double worked, right? First we multiplied, then we had to factor and break the multiplication back up, and then we canceled. What we actually want to do is cancel before we multiply. And this process is called cross-canceling. So to do this, you first want to look at your fractions and see, can I simplify them? So 3/10 can't do anything there. 5/12 can't do anything there. So once you're out of options there, you want to look at the numerator of this fraction, let's just say the left fraction, and the denominator of the right fraction. So this numerator and this denominator. And then you're going to do the same thing. Let me change my highlighter color here. So then this numerator and this denominator. And you're just going to ask the question, can I cancel any common factors between this numerator and this denominator, or this numerator and this denominator? Basically, are there any common factors between any numerator and any denominator? That's what you're asking. So to make this easier to see, I'm just going to break it down like we had it. So I'm going to put 3 over, we know 10 is 5 times 2, and then times, I'm going to put 5 over, 12 is 2 times 2 times 3. This 3 can cancel with this 3. So this numerator and this denominator, there's a common factor of 3. Again, I would put a 1 here. You can even put a 1 here if you want for clarity. You don't need it, but you can put it. Then here, you look at this numerator and this denominator, you can cancel this 5 with this 5. Again, you could put a 1 here and a 1 here. And then when you go through and multiply, well, 1 times 1 would give you 1. And this would be over. Let me make that a little bit better there. You would have, again, you can think about this as 1 times 2 or just 2 because 1 times anything is just itself. So really it's just 2 times 2 times 2, which is going to be 8. Again, this 1 would not change anything if you multiplied by it. So you end up with 1/8, which is the simplified answer. And notice that we didn't have to double work. We went ahead and canceled before we did the multiplication. So once we get our product, it's already simplified. All right, now that we understand the procedure, let me go a little bit quicker through the process. So we have 9 over 20 times 5 over 33. So I can't simplify this and I can't simplify this. Now, you could continue to do this and break it down all the way. So you could say this is 3 times 3 over 20 is 5 times 2 times 2. And then times you have 5 over 33 is 3 times 11. You can do it this way. And then again, I can just look at this numerator and this denominator. So let's cancel this 3 with this 3. Again, you could put a 1 here if you want and a 1 here if you want, just as a mental reminder. And then you can cancel between this numerator and this denominator, this 5 with this 5. So let's put a 1 here and a 1 here. All right, so this would give me what? So you have 3 times 1, which is 3, over, you're going to have 2 times 2, which is 4, times 11, which is 44. So you end up with 3 over 44 as your simplified answer. Now, let me show you a faster way to get this. Let me get rid of this, and we're going to go even faster. So here's how I do it. I would look at this guy and say, okay, well, 33 and 9, in my head, I'm immediately thinking, okay, well, 33 is divisible by 3. 33 divided by 3 is 11. So I'm going to cross this out and just put 11. Then 9 divided by 3 is 3, so I'm going to cross this out and put a 3. So basically, I'm dividing this guy by 3 and this guy by 3, and I'm just putting the result there. 33 divided by 3 is 11. 9 divided by 3 is 3. It's the same thing as if I factored and canceled. So this guy would look at 20 and I would look at 5. Well, 20 divided by 5 is 4. So cross this out, you could put a 1 there, and cross this out, you could put a 4 there. So 5 divided by 5 is 1. 20 divided by 5 is 4. It's a little bit faster than factoring. So now you just multiply 3 times 1, that's 3. And this is over 4 times 11, that's 44. Okay, let's look at one with 3 fractions involved. So we have 7 over 15 times 21 over 25 times 3 over 14. This is simplified, so is this, so is this. So what I would think about is 7 and 14 have a common factor of 7. So 7 divided by 7 is 1. 14 divided by 7 is 2. And then coming through here, now I have 21. Well, 21 is 7 times 3. Well, there's no 7 in any denominator now because I canceled this one away. But there is a 3. 21 divided by 3 would be 7. And then 15 divided by 3 would be 5. So I'm just canceling a common factor of 3 there. And then looking at this last one here, I have a 3, but this is a 5, this is 5 times 5, and this is a 2. So basically I'm stuck, I can't do anything else. So this would end up being what? 1 times 7, which is 7, times 3, which is 21, over, you'd have 5 times 25. You can stop and do a vertical multiplication for that. I think a lot of you do know that 5 times 5 times 5, or 5 cubed, is 125. So basically it would be 125 times 2, which is going to be 250. So 21 over 250 would be your simplified answer. Again, if that's a little too fast for you, you can always stop and break things up. So you can say that this would have been, let me do this down here. So 7 over 5 times 3, and then times 7 times 3 over 5 times 5, and then times 3 over 7 times 2. If you need to do this, it's fine. So I'm going to cancel this 7 with this 7. I'm going to cancel this 3 with this 3. And basically, that's it, right? So I'm just left with, I'm going to put a 1 here. Again, if I left that off, then I would have to go back and say, okay, well, this canceled, this is a 1. So a lot of times I leave that off because I know that, but for your scratch work, I think you should put it at this point so you're not confused. So this would be 1 times 7, which is 7, times 3, which is 21, over. You have 5 times 5 times 5. Again, that's 125 times 2, which is 250. So if you want to do it like this because it's a little bit easier for you right now, then it's fine to break up the numbers completely and factor everything into the product of primes. In a lot of cases, as you move forward, you won't need to do that because it's just a little bit too time consuming. Okay, let's talk about the next topic here. So we're going to multiply whole numbers by fractions. So we have 6 times 1/3. So this would be what? You just take 6 and put it over 1, and you multiply it by 1/3, and you can cross cancel here. 6 divided by 3 would be 2. Right, so basically this is 2, and it's 2 times 1, which is 2 over. Again, you could write a 1 there. 1 times 1 is 1. So this is 2 over 1, or 2. And if you think about this, 6 times 1/3, 6 times 1/3 would be what? Well, this is 1/3 plus 1/3 plus 1/3. Let me make that 3 a little bit better. Plus 1/3 plus 1/3, and then plus another 1/3. So if I had 1/3 of a pizza plus another third plus another third, at this point right here, I'd have a full pizza. So this is 1 pizza. And then I'm doing the same thing over here. So this right here, this would be another pizza. So 1 plus 1 is 2. So this tells me I should have 2 pizzas. Again, if you do this using the addition that we're going to learn about later, you would basically keep this denominator the same because it's called a common denominator. And you would just add the numerators. So 1, 2, 3, 4, 5, 6 of those guys. You'd basically have a 6 up there. So you'd have 6 divided by 3 basically, which is going to be 2. Okay, let's take a look at 7 times 3 over 49. So this would be 7 over 1 times 3 over 49. And I'm going to say that 49 divided by 7 is 7. So this is 7. So now basically this is a 1 right here. So you can just forget about it. You could say it's 1 times 3, which is 3, over 1 times 7, which is 7. But you could also say 1 times anything is itself. So you could just say, okay, this is going to be 3/7. All right, here we have 19 over 15 times 5 over 38 times 36. So basically what I would do is treat this as 19 over 15 times 5 over 38 times 36 over 1. Let's go through and see if we can cancel. So I know that 38 is 19 times 2. So for this one, this would cancel with this. This would be a 1, and this would be a 2. Again, 38 divided by 19 is 2. 19 divided by 19 is 1. Then here, 15 divided by 5 is going to be 3. And 5 divided by 5 is going to be 1. Now for this one, as you get faster, you're not going to say, okay, well, 36 divided by 3 is 12. And then you'll say, well, 12 divided by 2 is going to be 6. You would do that in one shot. So in other words, what you could have done here, let me get rid of these cancelings here. You could say that 36 divided by 6 is going to be 6, and then basically cross those out because 3 times 2 is 6. Now again, you can write this as a 1, or as you move forward, you're just going to realize that that's canceled, so it's 1. So basically, this is a 1, this is a 1, 1 times 1 is 1, and 1 times anything is itself, 6 over 1 is 6, so this gives me a final answer that's just going to be 6. All right, let's look at another one. So we have 4 over 15 times 5 over 24 times 7 over 12 times negative 4. Okay, so 4 over 15 times 5 over 24 times 7 over 12 times negative 4. I'm going to write that over 1. All right, let's think about what we can do here to cancel. So starting with the 4 divided by 4 is 1. 24 divided by 4 is 6. And then 5 divided by 5 is 1. 15 divided by 5 is 3. And then if we keep going, I have a 7 here. 12 is going to be 2 times 2 times 3. This is 6, this is 3, so I can't do anything with that. All right, then I have this negative 4. Let me write that as negative 1 times 4. And what you could do is divide 4 by 4, you get 1, and 12 divided by 4 would be 3. So looking at what I have left in the numerators, 1 times 1, you can forget about those, it's not going to change anything. Then times 7, so let's just start with 7. So basically 7 times negative 1, that is negative 7, and this is over. Down here you have 3 times 6 times 3. So 3 times 3 is 9. 9 times 6 is 54. And then times 1, that's still 54. So this would give me negative 7 over 54 as my answer. All right, let's take a look at 2 quick word problems. So we have Fred spent 2/5 of his $50 allowance on comics. How much did he spend? So this is typical. When you see 2/5 of this $50, so what you're going to do is take 2/5 and multiply it by 50. And so I'm going to cancel this 50 with this 5. 50 divided by 5 is 10. Again, you could put a 1 down there if you want. And then just multiply. 2 times 10 is going to be 20. Again, you can go over 1 if you want, but it's just going to be 20 at the end of the day. So when it asks how much money did he spend, the answer is going to be $20. Right? That's 2/5 of his $50. All right, now we have a recipe requires 1/2 cup of sugar. If we only want to make 3/4 of the recipe, how much sugar is needed? So again, just take 3/4 and multiply it by 1/2. And what is this going to give me? Nothing's going to be able to cancel here. This is simplified. This is simplified. 3 and 2, 1 and 4. Nothing I can do. So just multiply 3 times 1, that's 3. Over 4 times 2, that's 8. So basically, we could say that you would need 3/8 cup of sugar. Hello and welcome to Pre-Algebra Lesson 31. In this video, we're going to learn about dividing fractions. All right, so the lesson objectives for today, we want to learn how to find the reciprocal of a number, and then additionally, we want to learn how to divide fractions. All right, so now we're going to talk about how to find the reciprocal of a number. This is something we need when we start dividing fractions in a little while. So to find the reciprocal of a number, we interchange the numerator and denominator. So what do I mean by interchange? Well, let's start with a simple example. Let's say we had the fraction 4/5, and I want to interchange the numerator and denominator. Well, basically, I'm going to take this denominator from the fraction that I'm starting with, and that's going to become the numerator for the reciprocal. So this would be a 5 up here. And then let me put my fraction bar. I'm just going to take this numerator here from the fraction that I'm working with and drag that down into the denominator for the reciprocal. So the numerator becomes the denominator and the denominator becomes the numerator. That's what I mean by interchange the numerator and denominator. So the reciprocal of 4/5 is going to be 5/4, and you could reverse that and say the reciprocal of 5/4 would be 4/5. Now, when we multiply a number by its reciprocal, the result is always going to be 1. So let's say we go back to 4/5, and the reciprocal is 5/4. So why is the result going to be 1? Well, think about it. This denominator becomes this numerator. So it's basically 5/5, which is 1, right? You can cross cancel here. Let's just put a 1 here and a 1 here. And then this numerator becomes this denominator. So it's 4/4, that's 1. So cancel this with this, and I'll put a 1 here and a 1 here. Well, if you multiply these together, you could just think about this as 1 times 1. That's going to give you 1. All right, so now let's look at a few problems. We are asked to find each reciprocal. So we are given 2/3. If you want to find the reciprocal, again, I'm just going to take this denominator and drag it into the numerator. And then I'm going to take this numerator and drag it down into the denominator. So the reciprocal of 2/3 will be 3/2. Again, you can go 2/3 times 3/2 if you want to check your work. So 2/2 is 1, and then 3/3 is 1. And so you have 1 times 1, which is 1. Again, the product here should always be 1. Okay, what about 8/9? So again, let's take this denominator here, bring it up into the numerator. Let's take this numerator here and drag it down into the denominator. So the reciprocal of 8/9 is going to be 9/8. All right, what about one with a negative involved? So let me take some time with this one. So if you have this set up here, the first thing you could do is just put a negative out in front, and then basically you could interchange the numerator and denominator. So I could bring the 5 up here, and then I could bring the 1 down here. So the denominator becomes the numerator becomes the denominator, and I just basically copied the negative sign. So the reciprocal here is -5/1, which is just -5. But there's other ways that you could have thought about this. You could say that this is equal to -1/5. You could also say this is equal to 1/5. Remember, a negative divided by a positive or a positive divided by a negative, that's going to give you a negative in each case. So 3 different ways to write the same thing. So you could choose to do it this way. You could say this is -1/5, and then you can bring this denominator up into the numerator, and you can bring this numerator down here into the denominator. So either way, it's going to be -5, right? 5/-1 is just -5. Okay, let's look at one more problem. So now we're given an integer. So we have -4. So what are we going to do? Well, basically, you want to change this into a fraction by writing it over 1. So I can write -4/1 like this. Dividing by 1 leaves the number unchanged. So this is still -4. So now I'm just going to take this denominator and bring it up into the numerator, and take this numerator, bring it down into the denominator. So the reciprocal of -4 is basically -1/4. You can write this again as -1/4, or you could write it as 1/-4 as we have here, or you can say it's -1/4, whatever you want to do. All right, now let's move on and talk about dividing fractions. So I have here to divide fractions, we multiply the first fraction. So that's going to be your fraction on the left we call that the dividend in your division problem, by the reciprocal of the second fraction. So that's the fraction on the right. That's going to be your divisor in the division problem. So for example, let's just say I had something like 3/8 divided by 1/2. This first fraction, or the leftmost fraction, would be unchanged. So you would just copy that down. Then you would multiply by the reciprocal of the second fraction, or the fraction on the right. So this is times 2/1. So basically at this point, it's just a multiplication problem. So between 8 and 2, there's a common factor of 2. 8 divided by 2 is 4. 2 divided by 2 is 1. And then you would multiply 3 times 1, that's 3, over 4 times 1, that's 4. So the answer here would be 3/4. All right, so the process of dividing fractions is pretty easy overall, but some people have a really difficult time understanding where the process comes from. So on the next two examples, I'm really going to break this down. I'm going to start off with a whole number divided by a fraction. I think that's the easier one to understand. So I'm just going to start off with some things we already know. So right now I have 4 boxes on the screen, and I'm just going to say this is 1, 2, 3, and then 4, just to count them out. Now let's suppose I asked you, what is 4 divided by 4? What does that mean again? Let's go back to basic division. Well, I'm asking how many equal groups of 4 can be made from 4. So here I have 1, 2, 3, 4. So this whole thing would be a group, right? So this would be a group of 4. So 4 divided by 4 would be 1. I can make one of those groups. I think we all know that at this point. Let me get rid of this, and let me change the problem up. So let's say we said 4 divided by 2 now. So we know this equals 2, but again, I'm asking how many equal groups of 2 can be made from 4? Well, here's a group, right? So 1, 2, and then another 1, 2. So 4 divided by 2 would be 2. Now, what if I change this up a little bit and I said, what is 4 divided by 1/2? Well, using the procedure I just gave you, you could write 4 as 4/1 and then multiply by the reciprocal of this, which is 2/1. So that should give me 8. Well, let's think about this down here. What does it mean to have 1/2 of something? Well, it means I have a whole amount. Let's say it was a pizza, or in this case, a box, and I split it into 2 equal parts. And then each part is 1/2. So this right here is 1/2, and this is 1/2. Then this is 1/2, and this is 1/2. This is 1/2, and this is 1/2, and then this is 1/2, and this is 1/2. So if I go through and just count them, how many 1/2s do I have? Or how many 1/2 of a boxes do I have? Well, I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, well, that starts to make a little bit of sense in terms of why I got 8 as the answer. When I say 4 divided by 1/2, what I'm actually asking is how many equal groups of 1/2 can be made from 4? Well, what you need to do is start out with the fact that you have 4 of these guys, so 4 boxes. So I'm just going to write that. And then in each box, there's going to be 2 half boxes, right? So 2 half boxes. So I need to actually multiply by 2, because here I'm getting 2, here I'm getting 2, here I'm getting 2, and here I'm getting 2. So that's why this turns into the problem 4 times 2, which gives us 8. If we go a little bit further and we think about something like 4 divided by 1/4, well, it's the same principle here. Let me go through and write these in. So this is 1/4, this is 1/4, this is 1/4, and this is 1/4. Okay, so thinking about this, if you went through and counted, what would you have? So this is 1, 2, 3, 4, and then you have 4 of those, so that's 16. So basically this turns into 4 of these boxes, 1, 2, 3, 4, and then in each box, there's 4 1/4s. So I'm just going to do 4 times 4. So this becomes 16. Again, 4 stays the same, multiply by the reciprocal of 1/4. The reciprocal of 1/4 is 4/1, or just 4, so this becomes 16. Okay, let me give you an alternative way to look at this. A lot of people will teach this with what we call a complex fraction. So let's say we had 4 divided by 1/2. So I'm going to write this as 4/1 divided by 1/2. Now, we haven't talked about complex fractions yet. We're going to get to them later on in the course. For right now, a complex fraction is a fraction that contains another fraction in its numerator, its denominator, or both. So basically, all I'm going to do is take this part right here, which is the dividend, and I'm going to bring that up here into the numerator of the complex fraction. So this is 4/1. So this right here is the numerator. And then I'm going to have my fraction bar. So this is the fraction bar for the complex fraction. You could think about it as the main, so the main division. And then down here, I'm going to grab my divisor, and that's going to become my denominator here for the complex fraction. So this is 1/2, and let's just say that this right here would be your denominator. Okay, so the idea with this method is you're just going to transform the denominator into 1. And in order to do that, you would multiply this 1/2 by its reciprocal, which is 2/1. A number of times its reciprocal is always 1, like we talked about earlier. But to make that legal, you'd have to also do that to the numerator. So the problem is 4/1 over, and then you have 1/2. And all I'm going to do is multiply the denominator by 2/1. And to make that legal, I'm going to multiply the numerator by 2/1. So I'm basically just multiplying the numerator and denominator of the complex fraction by 2. And this would be equal to what? Well, these guys down here, these are reciprocals. So 2/2 is 1. So let me put a 1 here. 1 times 1 would just be 1. So the denominator of the complex fraction is 1 now. Then up here, I just do 4/1 times 2/1. So 4 times 2 would be 8. You could put over 1, I guess, if you wanted to, but 8/1 is just 8. So at the end of the day, this is 8/1, which is 8/1, which becomes 8. So that's another way to show where it comes from. Again, you can use either method to prove it to yourself and think about how things work. I like using the visual example with the boxes, but some people prefer this method. All right, let's look at one that's a little bit more complicated to explain. So suppose you had 1/2 divided by 1/8. Again, let's use the procedure to start. So 1/2 times the reciprocal of 1/8 is 8/1. And so essentially, you can think about 8 and 2 have a common factor of 2. 8 divided by 2 is 4, and then 2 divided by 2 is 1. So this is canceled. You could just write this as a 1. So it's basically 1 times 4, which is just going to be 4. How can we show this and prove that we should take 1/2 and multiply by the reciprocal of 1/8? Well, again, you could have written this as a complex fraction. So you could do that again. So you could say this is 1/2 over 1/8. And again, if I want to make this denominator for the complex fraction into 1, I'm going to multiply by the reciprocal of this fraction here. So this is times 8/1, and then I'm going to do that to the numerator to make that legal. So you see that this right here is going to cancel. So this is a 1, and you could put a 1 down here. So this is a 1 now. And so this would be equal to, well, basically it's this 1/2, which we're starting with over here on the left, times this 8/1, which is the reciprocal of this rightmost guy here, this 1/8. So we end up with what? Again, like we just did, 8 divided by 2 is 4, and 2 divided by 2 is 1. So this is just 1 times 4, which is going to be 4. I mean, you can go through and say this is 4/1, and then over 1, and then this becomes 4/1 like this, and this is 4, but I think we can all see that this is 4. All right, let me give you a visual explanation in terms of why 1/2 divided by 1/8 ends up giving you 1/2 times, take the reciprocal of this, it's 8. So this ends up giving you 8/2 is 4. Okay, so we've seen this already using the complex fraction method. But if you want to look at this visually, what you would need to do, because you're dividing by 1/8, just start with some whole amount. You could take a pizza, a box, whatever you want to work with, and you're going to divide it up into 8 equal parts. If you're working with a pizza, you're going to have 8 equal slices. So let's say this is 1, 2, 3, 4, 5, 6, 7, 8. If I was asking myself the question, how many groups of 1/8 would be in 1? It's 1 divided by 1/8. This would be 1 times, take the reciprocal of this, so it would be 8. So this is 8. And you can go through and count that. I have 1, 2, 3, 4, 5, 6, 7, 8 1/8 in this whole pizza. Now, I don't have a whole pizza. I only have half of a pizza. So let's mark this out like this. So maybe this is going to be my half of the pizza. And I'm not really good at drawing, so I'm going to go over. But basically, if you ask yourself the question, well, how many 1/8 are there in 1/2? Well, you have 1, 2, 3, 4. So it makes sense that we're getting 4. We can visually see that. But again, why do we end up multiplying by 8? Well, 8 is the number of slices or equal parts in the whole amount. And then I don't have a whole amount. I only have half of that. So you're asking yourself the question, what is 1/2 of 8? And that's how we end up getting 4. So that's how you want to think about this. So hopefully this makes sense for you visually. You can always pause the video and think about it, or make your own example with a pizza or boxes or whatever you want to use. All right, so now that we understand the procedure, let's just blow through some problems. I think you're going to find this to be really easy once you get started. So we have 2/3 divided by 4/9. So leftmost fraction, you're going to leave that unchanged. And then we're going to multiply by the reciprocal of the rightmost fraction. So basically, I'm going to take 4/9 to find the reciprocal. That's going to be 9/4. The numerator becomes the denominator becomes the numerator. So now we can just go through and multiply. Let's cross cancel. So basically, between 2 and 4, you have a common factor of 2. So 4 divided by 2 is going to be 2. 2 divided by 2 is going to be 1. And then between 9 and 3, you have a common factor of 3. So 9 divided by 3 is 3. And then 3 divided by 3 is 1. So this right here is canceled, right? This is a 1. So basically, you're just going to have 1 times 3 halves, which is 3 halves. So that's going to be your answer. What about 6/7 divided by 15 over 28? So the leftmost fraction, the first fraction, stays unchanged. And we're going to multiply by the reciprocal of the second fraction or the rightmost fraction. So this 28, the denominator, becomes the numerator. Then this 15, the numerator, becomes the denominator. So the reciprocal of 15 over 28 is going to be 28 over 15. Okay, now we're ready to do some multiplication. So basically looking at 28 and 7, well, 28 divided by 7 is 4. So 28 divided by 7 is 4, and 7 divided by 7 is 1. So then between 6 and 15, each is divisible by 3. So 15 divided by 3 is 5. 6 divided by 3 is 2. So what I'm left with is 2 times 4, which is 8. So that's my numerator. Over 1 times 5, that's 5. That's my denominator. So our answer here is going to be 8/5. What about 1/3 divided by 7? So the leftmost fraction, 1/3, we're going to keep that unchanged. And we're going to multiply by the reciprocal of what's on the right. Now, again, if this is not a fraction, if it's an integer or a whole number or something like that, then basically you're going to write it over 1. So let me actually change this up a little bit. Let me put divided by 7 over 1. And so this equals, you'd have 1/3 times the reciprocal of 7 over 1 is 1/7. So again, this 7, which is the numerator, becomes the denominator. This 1, which is the denominator, becomes the numerator. Now we just multiply. So nothing to cancel here. So 1 times 1 would be 1 over 3 times 7. That's going to be 21. So you get 1 over 21 as your answer. What about 2/9 divided by -4? So again, we can go 2/9 divided by -4 over 1. So let's say this equals, you have 2/9. So leftmost fraction, that's unchanged. And then times the reciprocal of the rightmost fraction. So again, the reciprocal here, let's just write -1 over 4. Again, you could write the negative down here if you want, or you can put it out in front. It really doesn't matter because when you're multiplying, a positive times a negative will give you a negative. So you could just put the negative sign in there and then forget about the signs and just work with the absolute values. So looking at it now, you can see that you have 9 and 1, nothing you can really do with that. And then you have 2 and 4. So there's a common factor of 2. So 4 divided by 2 is 2. 2 divided by 2 is 1. So we already know that this is negative. So let's just multiply 1 times 1. That's going to be 1 over 9 times 2. That's going to be 18. So the final answer here is -1 over 18. What about 12 divided by 1/3? So let's write this as 12 over 1. And then basically, instead of divided by 1/3, I'm going to go times 3 over 1. So this guy stays unchanged. I just wrote 12 as 12 over 1. And then I'm multiplying by, I'm just going to take the reciprocal of 1/3. So 3 comes up into the numerator, 1 goes down into the denominator. So now you just multiply. So 12 times 3 is 36. And this is over 1 times 1, that's 1. And of course, anything over 1 is just itself. So this just is equal to 36. All right, let's take a look at the next one. So we have -7 over 24 divided by 9 over -8. Okay, so what I'm going to do here is say the first fraction, -7 over 24, is unchanged. And then times the reciprocal of this fraction. I'm just going to put the negative out in front, and then I'll write 8/9 like this. Let me make these negatives a little bit better here. So this is -7 over 24 times -8/9. Okay, so we know that negative times negative is positive. You can put that there as a little reminder and then erase it or scratch it out after, or you could just leave it. It doesn't matter. And then I'm just going to work with the absolute values. So forget about the negative signs now. I'm going to think about, okay, well, 24 and 8, there's a common factor of 8. 24 divided by 8 is 3. 8 divided by 8 is 1. And then 7 and 9, nothing really in common there. 7 is a prime number, and 9 is 3 times 3. So what I'm going to do is multiply. We're going to say 7 times 1 is 7. Remember, I already know this is positive, so forget about the negatives here. And then down here, I have 3 times 9. That's going to be 27. So again, you can erase this at this point. You know it's positive. So you would say the answer is 7 over 27. All right, let's take a look at a problem with 2 divisions involved. So here we have 3/5 divided by 21/10, and then divided by 9/11. So the way I would do this problem, I would convert these divisions into multiplication by the reciprocal. It's just going to make it a little bit faster. The other way you could do it is you could do 3/5 divided by 21/10. So you could find that result and then divide that by 9/11. So that's up to you. It will give you the exact same answer. I'm going to do this as 3/5. I'm going to convert this division to multiplication by the reciprocal, so times 10 over 21. And then I'm going to convert this division into multiplication by the reciprocal, so times 11 over 9. So once you have it written this way, now it's a little bit easier because I can go through and just cancel things in one shot. So I can say, are there any common factors that I can cancel away between any numerator and any denominator? So looking through here, I have a 3 here and I have a 21 here. So 3 divided by 3 is 1. 21 divided by 3 is 7. So now looking at 10 and 5, well, yeah, 10 divided by 5 would be 2. 5 divided by 5 would be 1. Now looking at everything else, it looks like I'm basically done. So I would just multiply the numerators. 1 times 2 times 11, that's going to be 22, and put that over. You'd multiply the denominators. 1 times 7 times 9, that's going to be 63. So the answer here would be 22 over 63. And again, if you want to pause the video and try it a different way, you can do this division first, and then get that result, and then divide by this. You will still get 22 over 63. Hello and welcome to Pre-Algebra Lesson 32. In this video, we're going to learn about finding the LCM, otherwise known as the least common multiple. So our lesson objective for today is just to learn how to find the least common multiple, again that's abbreviated LCM, for a group of numbers. So before we start talking about finding the least common multiple, we have to have a general understanding of what a multiple is. And there's a lot of different definitions that kind of float around, but for the purposes of pre-algebra, we're going to use this one. So to obtain the multiples of a number, we multiply the number by each non-zero whole number. So in other words, if we think about the whole numbers, remember they start with 0 and increase in increments of 1 out indefinitely. So all I'm going to do is exclude 0 from this list. So in this case, I'm going to start with 1 and increase in increments of 1 out indefinitely. So I'm going to take a number, multiply it by 1, then 2, then 3, then 4, then 5. Each result is a multiple of that original number. So let me give you an example. So let's take a look at finding the multiples for the number 3. So again, we want to multiply 3 by each non-zero whole number to obtain the multiples. So I'm going to start out with 3 times 1. So 3 times 1 is 3. And then I'd move on to 3 times 2. 3 times 2 is 6. Then I'd go to 3 times 3. 3 times 3 is 9. Then 3 times 4. 3 times 4 is 12. Then 3 times 5. 3 times 5 is 15. And you can kind of see where I'm going with this, right? I'm starting with 1, and then I'm increasing in increments of 1. So I'm multiplying by 1, then 2, then 3, then 4, then 5. And if I continued, it'd be 6, then 7, then 8, so on and so forth. But really, you can just list the multiples. You can kind of see that we're just increasing in increments of 3 every time, right? So if I think about kind of the multiples of 3, we have 3, then 6, then 9, then 12, then 15. And again, we're increasing in increments of 3. So then after 15 comes 18, then 21. And I'm going to put 3 dots here to say this pattern is going to continue forever, right? Increasing in increments of 3. And I'm just going to put here that these are the multiples of 3. Let's take a look at another one. What if I asked you to find some multiples of 11? So I take that number 11, and again, I'm going to multiply it by each non-zero whole number. I'm just going to start with 1 and just increase. So 11 times 1 is 11. Then 11 times 2 is 22. Then 11 times 3 is 33. Then 11 times 4 is 44. Then 11 times 5 is 55. And obviously, you can continue this forever, right? There's no largest whole number. After 5 would be 6, then 7, then 8, so on and so forth. But I just want to generate a few of them so you can get an idea of what a multiple is. So let's write the first few multiples for 11. So it's 11, 22, 33, 44, 55. Then it would be what? 66, right? We're increasing in increments of 11. Then 77. And of course, at some point I can stop and put 3 dots to say, hey, this pattern where we're increasing in increments of 11 is going to continue forever. So these are some multiples of 11. So now that we have a basic understanding of how to find the multiples of a number, let's introduce this next concept called finding common multiples. So common multiples are just multiples that are common to all numbers of a group. So let's say that we have two numbers, and these two numbers, let's say they're 4 and 5. So let's say I want to find the multiples. Find the multiples of 4. So I'm going to write them just right here. So I'd start with 4, right? Because that's 4 times 1. Then I'd increase in increments of 4. So I'd go to 8, then 12, then 16, then 20, then 24, then 28, then 32, then 36, and I'm going to continue this down here. Then 40, then 44, then 48, then 52, then 56, then 60, and I'm going to put comma, dot, dot, dot. So the 3 dots just tell me that, hey, we're going to keep increasing in increments of 4 out indefinitely. And again, the way I figured this out is I start by multiplying 4, the number that I want to find the multiples for, by each non-zero whole number, just starting with 1. So 4 times 1 would be 4, and I'd increase to the next largest whole number. So now I'd multiply by 2. 4 times 2 is 8. Between here and here, I just increased by 4. So that's how I knew to go from 4 to 8. Now when I multiply by 3, I'm just increasing by 4 again. Right? This is plus 4, and I'm going to do that again. This is plus 4, so now I'm going to go to 12. And you just keep doing that. 12 plus 4 is 16. 16 plus 4 is 20. 20 plus 4 is 24. Again, so on and so forth. Now, if I did the same thing for the number 5, let's say I want to find the multiples of 5. So I would start out with 5 times 1, and that's going to give me 5. Then 5 times 2 is 10. Then 5 times 3 is 15. Each time, I'm just increasing in increments of 5. So then I'd have 20, then 25, then 30, then 35, then 40, then 45, then 50, then 55, then 60. And we're going to stop there. Okay, again, the 3 dots are telling me that this pattern, where we're increasing in increments of 5, is going to continue forever. Now, what's important here is to look through these two lists that we've generated. The list that we have for the multiples of 4 and the list that we have for the multiples of 5, we want to see what's common to both. Meaning, what number do we have in this list that's also in this list? So looking through here, I see that 20 appears here and also here. I see that 40 appears here and also here. And I see that 60 appears here and also here. So what it looks like is that every 20 numbers, we're going to have a multiple that's common to 4 and 5. Right? The next one would occur at 80. Right? If you went through here, you'd have 60, then 64, then 68, then 72, then 76, and then 80. And here you'd have 60, 65, 70, 75, 80. So it would next occur at 80, then 100, then 120, so on and so forth, just every 20 numbers. So we can see that we'd have an unlimited number or an infinite number of common multiples between 4 and 5 because these numbers continue forever, right? They're not going to stop. But what's important for this lesson is to be able to see what the least common multiple is, meaning what's the lowest in value. And that occurs here at 20, right? At 20. That's where it first happens, and that's the lowest in value, right? 20 is less than 40, it's less than 60, it's less than 80, it's less than all the other common multiples that will come in the future if we were to list out all the multiples. Let's try another one. Let's say we wanted to find the least common multiple between 15 and 20. So let's say we had 15, and we want to find the multiples for that number. We'd start out with 15 times 1, that's 15. Then you go to 15 times 2, that's 30. Then 15 times 3 is 45. And again, you can see that you're just increasing in increments of this number, right? I'm going up by 15 each time. So after 45 is 60, then 75, then 90, then 105, then 120, so on and so forth. I'm just going to put the 3 dots to say, hey, we're going to keep increasing in increments of 15 out indefinitely. Now, what about the multiples for 12? So for 12, we'd start at 12 and just increase in increments of 12 out indefinitely. So 24, 36, 48, 60, 72, 84, 96, 108, and let's put 120, and comma, dot, dot, dot. Again, the 3 dots are telling me that that pattern, where we're increasing in increments of 12, is going to continue forever. Now, when I look through the 2 lists here, I'm looking for multiples that they share, otherwise known as common multiples. So the first one's going to actually occur at 60. Right? We have a 60 in this list and a 60 in this list. And then you're going to see that they have common multiples at 120. Right? So 60 more. Started at 60, then it goes 60 more, and it happens again. And then it'll happen again 60 more after that. So it would happen at 180. And then it would happen at 240. And then it would happen at 300. So on and so forth. But again, if we want the least common multiple, we want the lowest value. So we want this one that occurs at 60. The one that started it all, the first one that kind of appears between the 2 lists. And so the LCM of 15 and 12, we can kind of notate that this way, would be equal to 60. Right? That's the least common multiple. Again, 120 is a common multiple, but it's not the least common multiple. Very important that you understand that. So far we've found the least common multiple by just listing the multiples of each number and just looking for the smallest that's in common. Now this method is slow, it's tedious, and it's impractical. So when you start taking tests on finding the least common multiple, you're going to use a different procedure. And basically what you're going to do is you're going to use the prime factorization of each number to build your LCM. So we're going to cover this right now. So finding the LCM from each number's prime factorization. So the first thing you're going to do is you're going to factor each number completely. Then the next thing we want to do is list the prime factors of each number in a table. And this isn't completely necessary. It's just a way to kind of organize your numbers and see what you're going to need. The next thing you're going to do is generate a list that contains each prime factor. But I'm going to tell you that this is where people get tripped up at. Although you need each prime factor, when a prime factor is repeated between 2 or more numbers, include only the largest number of repeats from any of the prime factorizations. Now, this step right here, again, is going to cause a lot of confusion, especially if you've never found the LCM before. So just write this down, and as we practice, I'm going to explain what this means. Now, the last step is to just generate your LCM. And the LCM is just going to be the product of the numbers on the list that we have created. All right, so let's look at some practice problems. We want to find the LCM for each group of numbers. We're going to start with a pretty easy one. We want to find the LCM for 9 and 12. So the first thing we want to do is factor each number completely. At this point, you probably don't need a factor tree to factor 9 or 12. So 9 we know is 3 times 3. And 12 we know is 4 times 3. And 4 is 2 times 2. So now what we're going to do is make a little table to organize our factors. Just going to make it nice and clear for us to see what we have in common. So I'm going to make a nice little table. I'm going to put 9 here and 12 here. And when you make your table, you're looking for the smallest prime factor between any of the numbers. So the smallest prime factor is a 2 that occurs in 12. I have 2 factors of 2. So let's start out by doing that. And then if I look in 9, I don't have any 2s. So I'm just going to put like a little space here to say, hey, there's no 2s in 9. I'm just going to kind of X that out to say they do not share that. Now, the next thing I'm going to do is look for my next smallest factor, which is a 3. In 12, I have 1 of those. In 9, I have 2 of those. So I'm going to put a little space here to say they don't share a second copy of 3, although they do share 1 copy of 3. So let me just highlight that. Now, here's where it gets kind of tricky. For the LCM of 9 and 12, each and every prime factor that occurs between these numbers has to go in that list. So in other words, we have 1, 2, and then a second 2 that occurs in the prime factorization of 12. So that has to go in. We have 1, 3, and then a second 3 that occurs in the prime factorization of 9. So that has to go in. The tricky part is not including this 3 here that's in the prime factorization of 12. You might say, well, why not? If I put a third 3 in here, I would get a common multiple for 9 and 12, but I wouldn't get the least common multiple. When there's a prime factor that is shared, you only use the largest number of repeats. So in other words, when we look at this, we see that we have 3 that's shared between 9 and 12. Once I see that, I only put the largest number of repeats that occurs between the 2 prime factorizations. In the prime factorization of 9, I have 2 factors. In the prime factorization of 12, I have 1 factor. So the largest number of repeats would be 2 factors. So when I build the list for the LCM, it only gets 2 factors of 3, not 3 factors of 3. Okay, that's very important that you understand that. Once you have that down, you simply multiply the numbers on the list. 2 times 2 is 4, 4 times 3 is 12, 12 times 3 is 36, and we have our LCM. Right? The LCM of 9 and 12 is simply going to be 36. And if you wanted to verify that, you can go through and kind of list out the multiples of 9. So it would be 9, then 18, then 27, then 36, then 45, then 54, so on and so forth. And then for 12, you'd have 12, 24, 36, 48, 60, again, so on and so forth. You can immediately see that 36 is the least common multiple, right? 36 is the least common multiple. All right, let's take a look at another easy one. So we want the least common multiple for 8 and then 42. So 8 we know at this point is 3 factors of 2. 42, let's just use a factor tree for that. I know it's 21 times 2. 2 is prime. 21 is 7 times 3. 7 and 3 are prime. So 42 is going to be 2 times 3 times 7. All right, so let's build a little table just to organize these numbers. All right, so my smallest prime factor is a 2. So in 8, I have 3 of those guys. So 2 times 2 times 2. And in 42, I just have 1. So I'm going to put a blank space there and there. And then in 42, I have a 3. I don't have a 3 in the prime factorization of 8. And then I have a 7. I don't have a 7 in the prime factorization of 8 either. So I'm going to put some X's here to say that, hey, these aren't included. And we can look to see what's in common. And basically, they just have 1 factor of 2 that's in common, right? So when we build our LCM, for 8 and 42, we're going to, again, include every prime factor that occurs between the prime factorizations. Don't think about 2 for a second. 42 has a 3 and a 7. So I'm going to put 3 times 7. There's no 3 in 8, and there's no 7 in 8. So I don't have to worry about how many I'm going to put in. It's just going to be 1 occurrence for each number. When we get to this number 2, again, if it's something they share, you only put the largest number of repeats that occurs between the 2 prime factorizations. In the prime factorization of 8, we have 3 factors of 2. In the prime factorization of 42, I only have 1. So the largest number of repeats would occur in the prime factorization of 8, where I have 3. So that's what's going to go in my list. So I'm going to put 1, 2, 3 factors of 2 when I'm building my LCM. So now I just need to go through and multiply. 2 times 2 is 4, 4 times 2 is 8, 8 times 3 is 24, and then 24 times 7, 24 times 7, 7 times 4 is 28, 7 times 2 is 14, plus 2 is 16, so this would be 168 for my answer. All right, let's take a look at the LCM of 20 and 35. So 20 is going to factor to 10 times 2. 2 is prime. 10 is 5 times 2. 2 and 5 are both prime. 35 is simply 5 times 7. Those are each prime numbers. So let's go ahead and just make a table. For 20, I've got 2 times 2 times 5. 2 times 2 times 5. For 35, I don't have any 2's, so I'm just going to X those out. I do have a 5, and then I have a 7, which I don't have up here. So I can see that they just have 1 5 in common between the 2 of them. So to build my LCM for 20 and 35, Again, every prime factor between the prime factorizations of the number has to go in. So 2 goes in, then another 2 goes in. It's just when you have something that's shared, you put the largest number of repeats between the two prime factorizations. Now, the largest number of repeats is going to be 1. I have 1, 5 in this prime factorization and 1, 5 in this prime factorization. So when I build this, I only put 1, 5 in my list. Right? I don't need 2, just 1. Right? The largest number of repeats when something is shared. And then I need to put this 7 in. So now everything is accounted for. I've got 1, 2, I've got a second 2, I've got only 1, 5 because they share it, and the largest number of repeats is 1, and then I've got a 7. So now I can just multiply. 2 times 2 is 4, 4 times 5 is 20, 20 times 7 I can do as 2 times 7, that's 14, and attach one trailing 0, and I get 140 as my answer. All right, let's look at the least common multiple for 16, 18, and then 30. So we're going to factor each number. So we've got 16. You can start out with 4 times 4. 4 is 2 times 2. And of course, 2 is prime, so we're going to circle all of those. For 18, let's do 9 times 2. 2 is prime, and 9 is 3 times 3. 3 is prime. For 30, let's do 6 times 5. 5 is prime. 6 is then 3 times 2. 3 and 2 are both prime. So let's make ourselves a little table. So we have 16, we have 18, and we have 30. So our smallest prime factor in any of the prime factorizations is 2. And in 16, I'm going to have 4 factors of 2. So 2 times 2 times 2 times 2. Now in 18, I only have 1 factor of 2. So I'm going to put a 2 here and then some blank spaces here. And let me just X those guys out. Then in the prime factorization of 30, I only have 1 factor of 2. And let me put some blank spaces there and X this out. So the next smallest prime factor is going to be a 3. So in 18, there's 2 of those. And then in 30, there's only 1. So I'm going to put a blank space here and here and here. And let me just X that out. And then the next highest is going to be a 5, and that's only in the prime factorization of 30. So I'm going to space that out and that out. Let's put an X there and there. And let's go down and build our LCM now. So the LCM for 16, 18, and 30. Again, we're going to include every prime factor from all of these prime factorizations. We're just going to have a special rule when any of them are shared. So in this example, they share 1 factor of 2. Everything has at least 1 factor of 2. So when that occurs, we put the largest number of repeats between any of the prime factorizations. 16 has 4 factors of 2, so that's what's going to go on our list. We're going to put 1, 2, 3, 4. Again, don't make the mistake of putting 6 in there. Don't say, okay, I have 1, 2, 3, 4, 5, 6. When there's something that's common, you want to put the largest number of repeats that occurs in any of the prime factorizations. Now, the next number we're going to look at is 3. And you'll notice that 3 is shared between these two prime factorizations. So since 3 is shared between these two prime factorizations, I want the largest number of repeats in any of the prime factorizations. And in this case, it's going to be 2 that occurs in the prime factorization of 18. So that means that we're going to have 2 factors of 3 when we build our LCM. And then the last number is 5. It only occurs in the prime factorization of 30. So we just throw that guy in there. We just need to multiply. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 3 is going to be 48. Times 3 again is 144. Then multiply by 5, you'll get 720. Now, I don't want you to get confused on this problem. Some of you might say, okay, well, when we did this one, they didn't all have a factor of 3 in it. That doesn't matter. If you're working with 3 numbers, or 4 numbers, or 5 numbers, if the prime factor is shared with at least 2 prime factorizations, you're always going to go with the largest number of repeats that occurs in any of those prime factorizations. In this case, we had 2 factors of 3 that occurred in the prime factorization of 18. That's more than the 1 that occurred in the prime factorization of 30. So we put 2 factors of 3 when we built our LCM. And again, we get 720 as our answer. All right, let's take a look at one final problem. We want to find the LCM for 120, 40, and then 225. So these numbers are kind of big, but not really. So 120, it ends with a 0, so we know we could do 12 times 10. 12, we could do 4 times 3. 3 is prime. 4 is 2 times 2. 2 is prime. 10 is 5 times 2. 5 and 2 are both prime. For 40, we'll do 4 times 10. 4 is 2 times 2. 2 is prime, so we're going to circle those. 10 is 5 times 2. 5 and 2 are both prime. Then for 225, that's 15 times 15. 15 is 5 times 3. 5 and 3 are both prime. Let's go ahead and build our table now. So for this, I'm going to put 40 first, then 120, then 225. So the smallest prime factor that occurs is 2. In 40, you've got 3 of them. 1, 2, 3. In 225, you don't have any. And in 120, you have 3 as well. 1, 2, 3. So for 225, I'm going to space these out and just put some X's in here. Okay, so the next smallest prime factor is going to be a 3. In 40, we don't have any. In 120, we have 1. And in 225, we have 2. So I'm going to space out here, and here, and here. Let's put some X's here. The next smallest prime factor is going to be 5. In 40, we have 1. In 120, we have 1. And in 225, we have 2. So I'm going to space these out and put an X here and here. So now when we build our LCM, so the LCM for 40, 120, and 225, again, we're going to include in this list each and every prime factor from all of the prime factorizations. If something's repeated between at least 2 of the prime factorizations, we're going with the largest number of repeats for that prime number. So when I start out, I notice that 40 and 120 both have 3 factors of 2 in their prime factorization. I always want to go with the largest number of repeats. Now the largest number of repeats is just 3, right? 3 factors of 2, they each have the exact same amount. So when I build my LCM, I'm going to have 2 times 2 times 2. Now the next number that we come across is 3. Now 3 is shared between 120 and 225, but there's more factors of 3 in the prime factorization of 225. You have 2 factors of 3 here, only 1 here. Again, when something's shared, you go with the largest number of repeats. So the largest number of repeats would be 2. That again occurs in the prime factorization of 225. So I'm going to put 2 factors of 3 when I build my LCM. Now lastly, we have 5. Now everything has at least one 5 in it. So again, if it's something that's shared, you go with the largest number of repeats. The largest number of repeats occurs in the prime factorization of 225. There's 2 5s there, so I put 2 5s in when I build my LCM. And now we just need to multiply. 2 times 2 times 2 is 8, times 3 is 24, times 3 is 72, times 5 is going to be 360, and then times 5 one more time is going to be 1,800. And again, that's going to be our LCM for 40, 120, and 225.
Hello and welcome to Pre-Algebra Lesson 33. In this video, we're going to learn about adding and subtracting fractions. So the lesson objectives for today, we want to learn how to add and subtract fractions with a common denominator. We want to learn how to find the LCD, which is the least common denominator of 2 or more fractions. And then we want to learn how to add and subtract fractions without a common denominator. All right, so let me read this before we get started. So when we add or subtract fractions, we must, meaning it is not optional, have a common denominator. So when they're exactly the same, that's what we mean by a common denominator. All right, let's just start off with some easier examples where we're already given a common denominator, and then later on we'll deal with the more complicated scenario where we don't have a common denominator and we need to get one. So let's say you had the problem 1/5 plus 2/5. Well, I want you to notice that the denominator here is 5 and the denominator here is also 5. So we have a common denominator, meaning the denominators are exactly the same. So that means that I can immediately start and I can add these fractions together. But how exactly do I add 1/5 and 2/5 together? Well, let's think about that with this little pizza here. Let's say that I buy a pizza and I split it up into 5 equal slices. So let's say this is 1, 2, 3, 4, and then 5. So I eat one slice of pizza. So let me mark this out. So this is the slice that I'm going to eat. Now we know at this point that we could represent the amount of pizza that I'm going to eat with this fraction 1/5. I'm taking one part out of a total of 5 equal parts. In the terminology of a pizza, I could say I'm getting one slice out of a total of 5 equal slices. Let's say that a friend comes over and now he's going to get 2 slices out of a total of 5 equal slices, or 2/5 of the pizza. So let's say he's going to take, let me change my color up a little bit. Let's say he takes this one and he takes this one. So how much pizza did we eat together? Well, that's the addition problem, 1/5 plus 2/5. So looking at this, easily I can just count and say it's 1, 2, 3 out of a total of 5 pieces of pizza. So that would be the fraction 3/5. 3 slices out of a total of 5 equal slices. How could we have gotten this 3/5? Well, what we would want to do is have this 1/5 plus 2/5 be equal to, we would add the numerators together. So my slice plus my friend's 2 slices, so that 1 plus 2, that's going to give me the 3 slices we ate. Now notice this part right here is not going to change. This denominator is going to stay as a 5. I'm not going to add those 2 denominators together. I have a common denominator, so I'm just going to leave that alone, and it's just going to keep moving forward as I simplify this problem. So I start off with 1/5 plus 2/5. This equals 1 plus 2, so this numerator plus this numerator, over the common denominator of 5, and then it ends up giving me 3/5. Now, when you get your answer, you want to think about, can I simplify? In this case, 3 is a prime number and 5 is a prime number, so really we can't do anything to simplify. So my answer here would just be 3/5. Let's just blow through a few of these problems. If you have a common denominator, it's going to be very, very easy. So we have 3/8 minus 2/8. So again, we have a common denominator. So all you have to do is perform the operations with the numerators and place that over the common denominator. When you're done, you're just going to simplify. So I'm just going to say this is 3 minus 2 over the common denominator of 8. 3 minus 2 is 1, and this is over the common denominator of 8. So this gives me 1/8. Now, can I simplify? No. So we'll just go ahead and leave 1/8 as the final answer. What about 7 over 13 plus 4 over 13? Again, what I want to do is add the numerators, so 7 plus 4, place that over the common denominator. I have a 13 and a 13, so this will stay as a 13. So this becomes what? 7 plus 4 is 11. So this is 11 over 13. 11 and 13 are both prime numbers, so the greatest common factor here would be 1, so this is simplified. 11 over 13 is your final answer. All right, let's look at 3/4 plus 1/4. So again, just perform the operations with the numerators. We're going to go 3 plus 1 over the common denominator here is 4. So this becomes 3 plus 1, which is 4, over 4. Now, of course, we can simplify because 4 over 4 is 1. Any non-zero number divided by itself is always going to be 1. You could think about this with a pizza. If you had a whole pizza and you split it up into 4 equal slices and you still had all 4 slices, well, then you still have 1 pizza, right? So 4 out of 4 slices would give you 1 pizza. What about 3 over 15 plus 2 over 15? So this would be 3 plus 2, just add the numerators, over the common denominator of 15. So 3 plus 2 is 5, so this is 5 over 15. You could rewrite this, let me just do this down here. You could rewrite this denominator as 5 times 3. And then you can cancel. 5 divided by 5 is 1. Remember, if your numerator cancels completely, you want to write a 1. A common mistake there is to write a 0. So 5 divided by 5 is 1. It's almost like we did the problem like this. Let's say I did 5 over 5 times 1 over 3, right? If we did the multiplication, this would be 5 over 15, which is what we have. So now if I cancel, this divided by this is 1. And so basically you have 1 times 1/3, which is 1/3. third. So that's why we get 1/3 as the simplified answer. Okay, let's look at 7 over 20 minus 3 over 20. So this would be 7 minus 3. Again, just working with the numerators. Over the common denominator of 20. 7 minus 3 is 4, so this would be 4 over 20. And if I think about 20, it's 5 times 4. So let's go ahead and say this is 4 over 5 times 4. So I'm just going to cancel this with this. Let me actually use a different color there so it shows up better. So cancel this with this. And then what I'll do is put this as a 1. Again, you do not want to put a 0 there. That's very common when you mark this out to see a student leave that and then say, okay, this is 0 over 5. No, this is going to be a 1. 4 over 4 is 1. So this would be 1 over 5 or 1/5. Okay, let's take a look at 1/3 minus 2/3. So we're going to subtract 1 minus 2 over the common denominator of 3. So 1 minus 2 is actually going to give me a negative. So if we think about that, 1 minus 2, again, you can always convert this if you need to. You can say this is 1 plus a negative 2, and then just use your rules for adding integers. So this ends up giving me a negative because the larger absolute value is negative. And then you would basically do larger absolute value minus smaller. So 2 minus 1 would be 1. So this would end up giving me -1. A lot of you know that 1 minus 2, you have 1, you take away 2, you get -1. Okay, let me get rid of this. So this would be -1 over 3. Now it's important to realize that when you have fractions, if you have -1 over 3, this is equal to 1 over -3, which is equal to the negative of 1 over 3. So 3 different ways to write that. A negative divided by a positive is going to be equal to a positive divided by a negative, which is equal to just the negative of that guy. Okay, so 3 different ways to write that. It's actually really important that you understand that. And we're going to use that in an example coming up. Okay, let's look at this one. So we have 31 over 50 minus 6 over 50. So we're going to do 31 minus 6 over 50. So 31 minus 6 is going to be 25. So you have 25 over 50. And we know that we could write 50 as 25 times 2. So this would become 25 over 25 times 2. Let's go ahead and cancel this 25 with this 25. So again, that's going to be a 1. And this will be equal to 1/2. Okay, let's look at one more of these. So I'm just going to think about what happens when we have some negatives already. So we have -1 over 8 plus 5 over -8. So here's what I would do. Notice that you have an 8 and then a -8. You can legally move this up here, like we talked about a little while ago. So what I would do is rewrite this problem as -1 over 8 plus -5 over 8. That is completely legal. Again, 5 over -8, positive over negative, is equal to negative over positive. You have to have exactly the same denominators. So you need 8 and then 8. You could, if you wanted to, do -8 and -8, but I think it makes it a little bit more complicated to understand, so I'm not going to do it that way. When you look at it here, you have 8 and -8, so those are not exactly the same, so you need to do something like this here in order to do the addition. So now what I would do is say this is -1 plus a -5 over the common denominator of 8, and so here, I'm just going to put that this is going to be negative, add the absolute values. 1 plus 5 is going to be 6. So this is -6 over 8. Now we're not done because we can simplify. I think I grabbed too much there. So let me just move this over here and I'll just get rid of that and draw that back in. So with this one, what I would do is write -1 and then times 2 times 3. And then for 8, let's write 2 times 2 times 2. And I'm going to cancel a common factor of 2 between numerator and denominator. So let's go ahead and do this one with this one. You could write a 1, but it's kind of unnecessary here because the numerator is still going to have something. It's really necessary when the numerator is completely canceled out, and that's where you're tempted to write a 0. In this case, you won't have a temptation to do that. So I'm going to go ahead and say that the numerator would be -1 times 3 or -3. And this is over 2 times 2, which is 4. So this would be -3/4. So you could write it like this. You could write 3 over -4, or a lot of people just put the negative out in front. So you say -3/4. Whatever you want to do, it's all the same answer. All right, now let's talk about the more challenging procedure. So we're going to do adding and subtracting fractions without, so let me highlight that, a common denominator. So the first step is to find the LCD. So this stands for least common denominator. This is going to be the LCM, which is the least common multiple of the denominators. So this right here causes a lot of confusion. If someone asks you to find the LCD, they are just asking you to find the LCM of the denominators. That's all it is. Then I have here for the next step to write equivalent fractions with the LCD as each denominator. I'm going to show you how to do that momentarily. Then we're going to add and subtract the numerators and simplify. So these two steps right here, we already know how to do that because we just did a ton of exercises where we already had a common denominator and we would just add or subtract the numerators, place that over the common denominator, and then just simplify. All we need to do is figure out how do we get the LCD and then how do we write equivalent fractions with the LCD as each denominator. All right, let's jump in and just look at a problem. When we get done with this problem, I'll go back and show you why this makes sense using some pizzas again. So let's start off by finding the LCD. So the LCD is the LCM of the denominators. I know this is very confusing. The denominators here, you have 3 and 4. So you have 3 and 4. So forget about the fact that we said LCD. If I asked you for the LCM or the least common multiple of 3 and 4, what would you do? You would first say, okay, well, 3 is a prime number, so I'm not going to factor that. And 4 is 2 times 2. Well, everything has to go in. So 3 has to go in, and then 2 factors of 2, those are going to have to go in. There's nothing that's common between the factorizations. So basically, it's just 3 times 4, right? It's going to give you 12. So I'm going to erase this and say that this is going to be 12. The next part is a little bit tricky. So basically, you have 1/3 and you have 1/4. And we've said that the LCD, which is the LCM of the two denominators, is 12. So what I want to do is I want to rewrite each fraction as an equivalent fraction where 12 is the denominator. So how can we do that? Well, I could multiply the denominator here by 4, and I could multiply the denominator here by 3. Let me put my addition sign in. But is that legal to do that? Well, not if I just do it like this. What I would have to do is match this number from the denominator in the numerator. So I would do 4 over 4 here and then 3 over 3 here. The reason this is legal is because 4 over 4 is going to be 1, right? So this equals 1. Any non-zero number divided by itself is going to be 1. And if I multiply by 1, I don't change the number. So it's just like I said, 1/3 times 1, well, that's 1/3. I am not changing the number. I'm just changing what it looks like temporarily so I can do my addition. Okay, so let me get rid of this. And we're going to first multiply. So remember, we're multiplying 1 times 4, numerator times numerator, that's 4. And this is over 3 times 4, that's going to be 12. So denominator times denominator. So plus 1 times 3, so that's going to be 3, over 4 times 3, that's going to be 12. So at this point, I have a common denominator. I have 12 and I have 12. So it's just like the problems we did earlier. So you're going to add your numerators. So 4 plus 3, put that over the common denominator, that's 12. And so 4 plus 3 is 7, and this is over 12. So it's really that simple. The only two additional steps you need to do is to first find the LCD, which again is the least common multiple, or LCM, of the denominators. So 3 and 4, you're looking for the LCM of those two numbers, you get 12. Then you're going to transform each fraction into an equivalent fraction where the LCD is its denominator. So think about, what do I need to multiply each denominator by to get to a denominator of the LCD? And then you got to match that in the numerator and the denominator so that you're multiplying by 1 so that it's legal. So once you've done that, you're at the point where we were at the beginning of the lesson where we had a common denominator, and then you can just add or subtract your numerators, put that over the common denominator, and then simplify. All right, let me quickly explain why 1/3 plus 1/4 ends up becoming 4/12 plus 3/12, which gives us 7/12 in the end. So I'm going to use an example with pizzas. I think it works out kind of nicely. So let's assume that I buy 2 pizzas that are completely identical, and when I first get them, they're not sliced up. So I take the first one, the one on the left, and I cut it up into 3 equal parts. So you could say I slice it up into 3 equal slices. So 1, 2, and then 3. Now if I eat one piece out of the 3 equal pieces here, well, I've eaten 1/3 of the pizza. So let's say I've eaten this right here. So that is going to be represented with the fraction 1/3. Then let's say this pizza over here, I'm going to cut it up differently. So let's say I go 1, 2, 3, 4 equal parts, or 4 equal slices since it's a pizza. And let's say that my friend, he's going to eat 1 slice here. So he eats this slice right here. So let's say plus 1/4. Well, if we try to figure out how much pizza we ate, we can't just immediately do this problem here. We know that we didn't eat a full pizza. Even though there's 2 pizzas here, the amount of pizza I ate plus the amount of pizza he ate it's not even going to add up to one pizza. But we can't really figure out immediately what amount of a pizza we ate, because if I try to add this one to this one, well, those are not the same, right? So this slice is not the same size as this slice because the pizzas are cut up differently. Obviously, looking at the fact that these two pizzas are the same size, well, this 1/3 of the pizza is going to be more than this 1/4 of the pizza. So what can we do? We would have to slice the pizza up in such a way that we can add like parts of a whole amount. So what do I mean by that? Let's start again with this 1/3 and then plus this 1/4. So you see here now I have 12 slices. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now I don't have two pizzas here because between the amounts that me and my friend ate, it's not even going to be a full pizza. So I'm just transferring everything in terms of one pizza so nobody gets confused about having two pizzas. So what I'm going to do now is think about, okay, if I cut this up into 12 pieces here, because that's the LCM of 3 and 4, how can I transform this amount of pizza to match over here? Well, I'd multiply this by 4/4, like we did earlier. So that would end up giving me 4/12. So if I go through and look at it, well, I would have eaten 1, 2, 3, 4 pieces of pizza had it been split up in such a way that I had 12 equal pieces of pizza. And you can see that this would be 1/3, right? So you go 1, 2, 3, 4, that's a third. Then 5, 6, 7, 8, that's another third. Then 9, 10, 11, 12, that's another third. So I still ate a third of the pizza. It just looks different. Then plus, over here, I'd multiply this by 3/3. And so this would give me 3/12. So let's say that I take 5, 6, and 7 for that, and I'll use a different color. So my friend, he eats 5, 6, and 7. So now we can clearly see just by counting, it's 1, 2, 3, 4, 5, 6, 7, that it's going to be 7 pieces of pizza that were eaten out of a total of 12 pieces. We could have also just done 4 plus 3, which again gives us 7/12. All right, let's look at some examples now. So we have 1/4 plus 1/2. So what is the LCD? The LCD is the LCM of the denominators. So 4 and 2. So I think you know that that's going to be 4. Again, 4 is going to be 2 times 2. And 2 is a prime number. It's not going to factor. So basically, you want 2 factors of 2. You could think about this as 1, 2, and here you have 2 2s. So you want the largest number of repeats, and that's going to be 2 2s or 4. Let me get rid of this. And basically, in this particular case, the 1/4, you don't have to do anything with that because the denominator is already the LCD, which is 4. So then plus for 1/2, you're going to need to multiply this by 2/2. And so this gives you 1/4 plus 1 times 2 is 2 over 2 times 2, that's 4. So this gives you 1 plus 2, which is 3, over the common denominator of 4. So 3/4 would be your simplified answer. 3 is a prime number, and 4 is 2 times 2. So your GCF is going to be 1 there. So really, that's your simplified answer. All right, let's look at 5/21 plus 3/14. So this one will be a little bit of work. So the LCD is the LCM of 21 and 14. And so 14 is 2 times 7. And then 21 is going to be 3 times 7. So when you build this, it's going to be what? You're going to put a 2 in. You're going to put a 3 in. And then you only put in 1 7. There's 1 7 here and 1 7 here. So if it's common, just put the largest number of repeats between any of the factorizations. It happens once here and once here, so only 1 goes in. And let's put equals here. 2 times 3 is 6. 6 times 7 is 42. So here we would say that we have 5/21, and then times, let me just put this here, plus 3/14, and then times, let me put this here. When you think about this, you can look at this list and say, well, what do I need to get to 42? Well, basically, you have 7 times 3, I would need a 2, right? So you can say 2/2. Also, you can take this and divide by this. So 42 divided by 21 is 2. Whatever you want to do. Sometimes people will erase this and then put this as 42, and they've lost that information, so they start freaking out. Just you can take this and just divide it by this, and 42 divided by 21 would be 2. So I need to multiply by 2 so that I can get to 42. Then over here, I would need 3/3. 14 times 3 would be 42. So this would be equal to what? 5 times 2 is 10 over, we know that the denominators are 42, so you can just write them in. And then 3 times 3 is 9, and this is over 42. So now 10 plus 9 would be 19 over the common denominator of 42. So 19 is a prime number, and we know 42 is 2 times 3 times 7. We just factored it. So the GCF here is 1. So this is as simple as you can get it. 19 over 42 is your answer. All right, let's look at one that's a little bit tricky. So we have negative 7 over 3 plus 2 over negative 15. The idea here is that if you have a negative in the numerator or the denominator, what I would say is to put them in the numerator. Okay, so here it's in the numerator. I'm just going to move this up here. So I'm going to say this is negative 7 over 3 and then plus negative 2 over 15. You don't want to have opposite signs in your denominators. You want to make sure that when you get a common denominator, they're exactly the same. They can't be opposites. So you wouldn't want to end up with 15 and negative 15. Here, when you think about the LCD, which is the LCM of 3 and 15, well, 3 is a prime number and 15 is 3 times 5. So basically, the 3 goes in and the 5 goes in. The 3 only goes in once because you have it here and you have it here. So you're only putting in 1. So it's just going to be 15. So this would just be, let me erase this and I'll just put that the LCD is equal to 15. We can say this equals, we'll have negative 7 over 3. I'm going to multiply this by 5 over 5 because 3 times 5 is 15. And then plus you have negative 2 over 15. So I don't need to mess with this one because the denominator is 15 and that's the LCD. So don't do anything there. So I'll say this equals negative 7 times 5 is negative 35. This is over 3 times 5 is 15. And then plus you have negative 2 over 15. Let me slide down a little bit here. So this equals what? You would just add the numerators, negative 35 plus negative 2. We know that's negative. And then add the absolute values. 35 plus 2 is 37. So this is negative 37 over 15. Now you could write this as a mixed number if you want. It's really up to you because you have an improper fraction here. So you could leave it like this. 37 is a prime number, so you're not going to be able to simplify. But you could say that this is negative what? So you could say 37 divided by 15. 15 goes into 37 twice. 2 times 15 is 30. Subtracting, you get 7. So that's your remainder. So you would say that this is negative 2 and then 7 over 15. Okay, so you could write it like that if you wanted to, or you could keep it like this, negative 37 over 15. Really, it's personal preference unless your teacher tells you which one they want. All right, let's take a look at 11 over 12 minus 3 over 20. So the LCD here is the LCM of 12 and 20. So 12 is going to be 4 times 3, so 2 times 2 times 3. And then 20 is 4 times 5, so 2 times 2 times 5. Okay, so what I'm going to do here is think about the fact that I have 2 that's common. So you want the largest number of repeats, and that's going to be 2 of them. So you want 2 times 2, which is 4. And then times, you're going to put in a 3, and then times 5. So 4 times 3 is 12. 12 times 5 is 60. So this would end up giving you 60. Okay, let me put equals here, and I'll just go down here. So 11 over 12. So what do I need to multiply the denominator by to get to 60? Well, notice that you have 4 times 3 there. That's 12. So you need another 5. So let's go ahead and put 5 here and then 5 up here. And then minus 3 over 20. Let me make this 3 a little bit better. I'm going to multiply this by, and that's not much better. So let me do that one more time. I'm going to multiply this by what? So 20 times 3 would be 60. So 3 over 3. So let's say this equals, and 11 times 5 is 55. Over 12 times 5 is 60. And then minus 3 times 3 is 9 over 20 times 3, that's 60. And now we can just subtract. So what is 55 minus 9? So maybe you want to do that as a vertical subtraction. Let's borrow here. This would be 4. This would be 15. 15 minus 9 is 6. Bring down the 4 there. So this would be 46. So you could say that this is going to be 46 over 60. Now, I know that 46 and 60 are even numbers. So at minimum, I can cancel a common factor of 2. So 46 would be 2 times 23, and 23 is a prime number. And then 60 is going to be 2 times 30. So I can cancel that common factor of 2 between numerator and denominator. And so this gives me 23 over 30 as my final answer. All right, what about 14 over 15 minus 17 over 25? So the LCD is the LCM of 15 and 25. So 15 is going to be 3 times 5, and 25 is a perfect square. It's 5 times 5. So this would be what? 3 goes in, and then for 5, you want the largest number of repeats because it's common. Here it's 1, here it's 2, so you're going to put in 2 of those guys. So 3 times 5 would be 3 times 25, so that's 75. So let me actually erase this and just put 75 like this. And let me get rid of this border, and I'll put equals here, and we'll just come down here. So 14 over 15. What do I need to multiply 15 by to get to 75? Well, 5. So I'm going to do times 5 over 5, and then minus 17 over 25. What do I need to multiply 25 by to get to 75? Well, 3. So times 3 over 3. All right, so 14 times 5, let me do that off to the side. It's going to be 70, but let's do that off to the side. So 5 times 4 is 20. 0 down, carry the 2. 5 times 1 is 5, plus 2 is 7. So this is 70. So let's say this is 70 over. We know that, again, this is going to be 75. And then let's get rid of this. Now you have 17 times 3. Let's do that here real quick. So 3 times 7 is 21. 1 down, carry the 2. 3 times 1 is 3, plus 2 is 5. So that would be 51. So let's go minus 51. And again, we know this denominator is 75. So let's say this equals what? I think we could do 70 minus 51 in our head. That is going to end up giving me 19, which is a prime number, over 75. So this would be simplified. Again, 19 is a prime number. We know what 75 factors into. It's going to be 3 times 5 times 5. So nothing you can really do there other than to say that 19 over 75 is your simplified answer. All right, let's take a look at one final problem. So now we have more than 2 fractions involved. So you see we have 2/3 plus 1/4 minus 5/8. So again, let me just start by figuring out, well, what is the LCD? This is the LCM of the denominators. So 3, 4, and then 8. Okay, so 3 is a prime number, so don't worry about that. 4 is going to factor in a 2 times 2, and then 8 is going to be 2 times 2 times 2. Okay, so basically between 4 and 8, you see that you have 2 factors of 2 here, but 3 factors of 2 here, so you're going with the largest number of repeats. So I'm basically going with 8 here, and then I need the 3 there, so it's going to be 8 times 3, which is 24. So let me go ahead and just say that this is going to be equal to 24. Okay, let me write this down here because I'm going to need some room. So the LCD is equal to 24. Okay, let me get rid of this. And I'm just going to say that this is equal to 2/3 times, what do I need to multiply 3 by to get to 24? Well, 8. So I'll multiply this by 8 over 8. And then plus we have 1/4 times, what do I need to multiply 4 by to get to 24? Well, 6. So 6 over 6. This is probably not going to fit. So let me move this down here. Let me actually rearrange everything and move this over here. And I'll just drag this over here. Okay. Then minus, we have 5/8 times. What do I need to multiply 8 by to get to 24? Well, 3. So this is 3 over 3. All right, let me slide down here and just say equals. So first, let me just simplify everything. 2 times 8 would be 16 over, we know all the denominators would be 24. Then plus 1 times 6 is 6, again over 24. And then minus 5 times 3 is 15, and then over 24. So when you have all these different operations going on, again, if it's addition and subtraction, that's worked left to right. So I'm just going to think about it like I have this. 16 plus 6 minus 15 over the common denominator of 24. That's all I'm really doing. So I'm going to add first, and then I'm going to subtract last. So 16 plus 6, well, 16 plus 4 is 20, plus another 2 is 22. So this is 22 minus 15 over 24. And then 22 minus 15, well, that's going to be 7. So this ends up giving me 7 over 24. Now, 7 is a prime number, so you're not really going to be able to do anything. We know 24 is 3 times 8, right, or 2 cubed. So you really can't do anything to simplify there. It's just going to be 7 over 24 for the simplified answer. Hello and welcome to Pre-Algebra Lesson 34. In this video, we're going to learn about comparing fractions. So the lesson objective for today is just to learn how to compare the size of 2 or more fractions. All right, so in order to compare the size of 2 or more fractions, one thing we can do is we can convert all of the fractions into equivalent fractions with the same denominator. So with this first procedure I'm going to give you, you're basically going to figure out what is the LCD, or the least common denominator. You're going to transform each fraction into an equivalent fraction where the LCD is its denominator, and then you're going to compare the numerators. So given the fact that you have the same denominators, the largest numerator will belong to the largest fraction. This is one way to do it. It's the slower way, but we're going to use it to build up the concept. As we get further along in the lesson, I'll give you the shortcut, which basically involves just cross multiplying. All right, we want to replace the question mark with either the less than symbol or the greater than symbol. And we're going to start with something very easy just to get an understanding of the concept. We have 3/8 and then a question mark and then 5/8. So to think about this, I have a little pizza, and the pizza has been split up into 8 equal slices. So let's say that this is 1, 2, 3, 4, 5, 6, 7, 8. So let's say that we're at a party, and basically I say that I'm going to eat 3 slices of pizza. So let me mark these out. So I'm going to get this piece, I'm going to get this piece, and I'm going to get this piece. So I've taken 3/8 of the pizza, 3 slices out of a total of 8 available. And then you say, okay, I'm going to go ahead and take 5 out of the 8 slices and just finish the pizza off. So let's say you take this one, and then this one, and this one, and this one, and then this one. Well, who got more pizza? Well, of course you did. You got 5 slices out of 8, whereas I only got 3 slices out of 8. So when we have the same denominator, it's very easy to compare. We just think about what numerator is bigger. 5 is bigger than 3, so we can say that 5/8 is a bigger fraction. With this one, the 3/8 is on the left, so we would say 3/8 is less than 5/8. Of course, you could flip that around. Let me write that over here. You could say that 5/8 is greater than 3/8 if you were presented with the problem in a different way. Let's look at one that's a little bit more tedious. So now we have 2/5 question mark 3/7. So it's not as straightforward here because the denominators are not the same. So what we have to do is convert this over to where each fraction has the same denominator. Again, as we get further along the lesson, I'm going to give you a shortcut to do this very, very quickly. For right now, let's just build up the concept. So we have 2/5 and then we have 3/7. So when we think about the least common denominator, remember this is the least common multiple of the denominators. So of 5 and then 7. So this is equal to what? Well, 5 is a prime number and 7 is a prime number. So just multiply those two together. So this is 5 times 7, which is 35. So basically all I have to do is multiply this by 7/7 and multiply this by 5/5. And so that would give me 14/35. So 14/35. And then this would be 15. So 15/35. So let me actually move this over here like this and this like this so we know what we're talking about. And basically now that we have the same denominator, so this is 35 and this is 35, then I'm looking at which numerator is larger. In this case, 15 is bigger, so I'm going to put a less than here. So 14/35 is less than 15/35. In terms of the original problem, remember 2/5 is now 14/35, so I would say 2/5 is less than 3/7 is now 15/35, so we'll say 3/7. So to answer this, we'll say 2/5 is less than 3/7. All right, let's take a look at 7/20 and then a question mark 5/12. So let me actually write this. So 7/20. I'm going to leave some space and then I'm going to write this one 5/12. The first thing is with this method, we're going to find the LCD, which is the least common multiple of these denominators for 20 and then 12. Let's think about 20 for a second. I don't think we need a factor tree. 20 is 4 times 5, and 4 is 2 times 2. So this is 2 times 2 times 5. For 12, again, I don't think we need a factor tree. It's very simple. It's 4 times 3, and 4 is 2 times 2. So let's say 2 times 2 times 3. Now, when you look at these prime factorizations and you're trying to build your LCM, if there's something that's common, in this case, you have a 2 here and a 2 here, you want to go with the largest number of repeats between any of the factorizations. So here I have 2 factors of 2, and here I have 2 factors of 2, so the largest number of repeats would be 2. So I'm going to put in 2 times 2. The big mistake is everybody puts in 2 times 2 times 2 times 2, or they put in 16 there, right? You only need 4. Then here I want to put in the 5, and then I want to put in the 3. So everything goes in. So if something's common, put in the largest number of repeats between all of the prime factorizations. Okay, let me get rid of the scratch work. And you can just multiply now. So 2 times 2 is 4. 4 times 5 is 20. And 20 times 3 is going to be 60. So this would be 60. To figure out what I need to multiply by, all you do is take this LCD here, which is 60, divide by the denominator. So 60 divided by 20 is 3, so I need to multiply by 3/3. And then over here, I divide 60 by 12 and I get 5, so I need to multiply by 5/5. So this is going to end up becoming 7 times 3 is 21, so this would be 21/60. This, 5 times 5 is 25, so this would be 25/60. So now it's very easy, right? We have the same denominator, 60 and then 60, and I could just compare the numerators. So 21 is less than 25, so we would say 21 over 60 is less than 25 over 60. Again, to put this in terms of the original problem, that's how we want to answer. So 7 over 20 is going to be less than 5 over 12. All right, let's take a look at one that's pretty tedious, especially if you're doing it the slow way. In the future, we're just going to cross multiply, so it'll be a lot quicker. But let's start out by finding the LCD, which is the LCM of these denominators. So 14 and then 34. So I would factor 14, that's 2 times 7. And then I would factor 34, so that is 2 times 17. So to build up the LCM, you would basically put one factor of 2 in. Again, it's common to both of these factorizations, so you just put 1 in, the largest number of repeats. Then times, you have 7, and then times 17. You can get rid of this if you want. And then basically, you can go through and crank this out. A lot of you are using calculators at this point. If you're not, just do 2 times 7, that's 14. 14 times 17 is going to be 238. You can always stop and do a quick vertical multiplication. So 14 times 17. 7 times 4 is going to be 28. 8 down, carry the 2. 7 times 1 is 7, plus 2 is 9, so this is 98. Let's erase this and shift down. Let me actually move this up here. And then 1 times 14 is 14, so 4 and then 1. Let's put some addition there. Bring down the 8. And then 9 plus 4 is 13. 3 down, carry the 1. 1 plus 1 is 2. So it's 238. Okay, let's get rid of this. Now, let me put this over here and say this is 5 over 14 times, I need to get to 238. Now notice that 14 is 2 times 7, so I would need to multiply by 17 to get to 238 in terms of the denominator. So I'm going to multiply the numerator and denominator by 17. Now you could have also said, what is 238 divided by 14? And you get 17. So that's another way to do it. And this guy over here, let's do 15 over 34. And we're going to multiply by, what do I need? Well, 34 times 7 would be 238. So 7 over 7. So now that we have that figured out, you can actually get rid of this if you want. You don't need it anymore. You would just do some multiplication. We know that the denominator is going to end up being 238 in each case. So let's put that up there. What is 5 times 17? Well, some of you might know that that's 85. Again, if you don't, you can always stop and do a little vertical multiplication. 5 times 7 is 35. 5 down, carry the 3. 5 times 1 is 5, plus 3 is 8. So that's 85. Okay, so the other one is going to be 15 times 7. So 15 times 7. 7 times 5 is 35. 5 down, carry the 3. 7 times 1 is 7, plus 3 is 10. So this would be 105. So if I think about the denominators, they're the same. So I just want to compare the numerators. So 105 is larger. So this guy right here, this 85 over 238 is smaller or less than 105 over 238. So I'll go ahead and translate that into the original problem. Let me get rid of this so I have some room. And I will just say that 5 over 14 is less than 15 over 34. All right, let's take a look at an example where we have the same numerators but different denominators. So we have 2/3 question mark 2/5. So let me write this out. So 2/3 and then 2/5. Let's start with the LCD method, and then we'll show you a little shortcut for this one. So we have the LCD is going to be the LCM of the denominators, so 3 and then 5. So because 3 and 5 are both prime numbers, we can just multiply them together. 3 times 5 would be 15. So I'd multiply this by 5 over 5, and I'd multiply this by 3 over 3. Let me get rid of the scratch work here. And so this 2 times 5 would be 10 over, we know the denominator is 15. Here, 2 times 3 is 6. We know the denominator is 15. Let me get rid of this and get rid of this. So given the fact that we have the same denominators now, we can just compare the numerators. So the larger numerator will belong to the larger fraction. So 10 is larger than 6, so we can say that 10/15 is greater than 6/15, which is going to translate into 2/3 being greater than 2/5. Now, we could have found that in a much quicker way. In fact, if we have the same numerators, all we have to do is look at the denominators and see which one is smaller. So whichever one is smaller belongs to the larger fraction. So I know that's a little bit tricky the first time you hear it. When you have the same numerators, you want to look at the denominators and see which one is smaller. So the smaller denominator will belong to the larger fraction. So here, 3 is smaller than 5, so 2/3 is greater than 2/5.
Let me make this simple and give you a visual example with some pizzas. So let's say that you go to the pizza shop and you buy 2 identical pizzas. You get back to the house and you split them up in different ways. With the first pizza, or the one on the left, you're going to split it up into 3 equal pieces. So 1, 2, and then 3. With the one on the right, you're going to split it up into 5 equal pieces. So 1, 2, 3, 4, 5. So let's say this one's for you and this one's for a friend. So let's say you decide that you want to eat 2 pieces of pizza. So maybe you eat this piece right here and then this piece right here. So you've eaten 2/3 of the pizza. Now, when you think about your friend, he also wants to have 2 pieces of pizza. So let's say he eats this piece of pizza and then this piece of pizza. Okay, so I'm going to represent that with 2/5. So who ate more pizza, given the fact that there were identical pizzas before you sliced them up? Well, you did, right? You had 2/3 of the pizza and he had 2/5. In other words, your 2 is going to be a larger amount than his 2 because we're talking about the slices themselves being different, right? So your slices are larger. So when you eat 2 larger slices, that's going to be more than your friend who's eating 2 smaller slices. Okay, so you're thinking about how the pizzas are split up. So that tells me that 2/3 is going to be greater than 2/5. All right, let's take a look at 2 problems where we're asked to arrange from least to greatest. Once we're done with that, I'll show you the shortcut and we'll be able to move through these problems more quickly. All right, so we have 5/6, 11/12, and then 3/20. So we are asked to arrange these from least to greatest. Sometimes they want you to put in commas like you see here. So put the smallest, then comma, the next smallest, then comma, you would have the largest because here we have 3. And then sometimes they want you to use inequality symbols. So I'll just give you both ways in case you are asked for one of those on your test. So first and foremost, I would get the LCD, which is the LCM of the denominators. So 6, 12, and then 20. Okay, so this equals what? For 6, this factors in a 2 times 3. For 12, this factors into 4 times 3, so 4 is 2 times 2. And then 20 is going to be 4, which is 2 times 2, and then times 5. So when I build my LCM, again, if something is common, you want to think about the largest number of repeats. So here for 2, it occurs once here, twice here, and twice here. So the largest number of repeats is 2. So I'm putting 2 factors of 2 in when I build my LCM. Then I'm looking at 3. So it occurs once here and once here. So I'm putting in 1. And then I'm looking at 5. It only occurs once here. So I'm going to throw that in. 2 times 2 is 4. 4 times 3 is 12. 12 times 5 is 60. So this would be 60. So I'm going to say 5/6 times, in order to get a denominator of 60, I need to multiply by 10. So I want times 10/10. And then 11/12. If I want a denominator of 60, I need to multiply by 5/5. And then 3/20. If I want a denominator of 60, I'm going to multiply by 3/3. Okay, let me get rid of this. We know that in each case, the denominator would be 60. So let me just write that in real quick. And then we'll do our multiplication. So 5 times 10 is 50. Then 11 times 5 is 55. And then 3 times 3 is 9. Okay, let me get rid of this. So thinking about how we would order this, the denominators are the same. So you have 60, you have 60, and you have 60. So I'm just thinking about, in terms of the smallest fraction, I would have the smallest numerator. So that would be 9. So that belongs to 9/60. So let's say that this is 9/60, and then comma. The next smallest, I'm looking for 50 here, because 50 is smaller than 55. So I would go 50/60. And then the largest is going to be the 55/60. So if I want to write this in terms of what we had originally, which is always what you want to do, well, if you think about 9/60, again, that's going to be 3/20. So let's list that first. So this is 3/20. I'm going to put a comma. 50/60 is going to be 5/6. So this is 5/6. Put a comma. And then 55/60 is 11/12. So 11/12. So if you're asked to do this with commas and arrange from least to greatest, this is how you would do it. So 3/20, comma, 5/6, comma, 11/12. They may ask you to arrange them from greatest to least. Sometimes they do that. So then you would put 11/12, comma, 5/6, comma, 3/20. A lot of times they'll also ask you to do this with inequality symbols. So generally speaking, you'll do this from least to greatest, but you can also see it from greatest to least. So I would say that this is 3/20 is less than 5/6,
which is less than 11 over 12. All right, let's look at one more of these. So this one's pretty simple. We have 2/5, 2/3, 2/7, and then 1/6. With this one, I would not find the LCD. It's going to be a little bit faster since we have the numerators 2, 2, 2, and then a 1. I can just say this is times 2 over 2, which is going to give me 2 over 12. So let me go ahead and say, I'm just going to temporarily line this out. I'll bring it back in a moment, that this is 2 over 12. Okay, so given the fact that we have the same numerators now, the smallest fraction is going to have the largest denominator. Remember, if you have the same numerators, then the largest fraction is going to have the smallest denominator. So that means the smallest fraction is going to have the largest denominator. So if I think about this, the largest denominator is 12. So that means 2 over 12 or 1 over 6. Let me just bring it back. That's going to be the smallest. So let me say that this would be 1 over 6 and then comma. The next largest would be 7. So I'm going to put 2 over 7 and then comma. The next largest would be 5. So I'm going to put 2 over 5 and then comma. Lastly, the smallest denominator here is 3. So I'm going to use 2/3 as the largest. So again, when I think about these, I've already transformed this over. Let me temporarily put this back so we can think about it. So this is 2 over 12. Going back to my pizza example, if I think about having 2/3 of a pizza, I'm going to eat more of that pizza than if I had 2/5 of it. Here I'm eating 2 slices and here I'm eating 2 slices. But again, with the 2/3 example, the slices are bigger. With the 2/5 example, the slices are smaller. So that's why we would say that this 1/6 here, which is 2 over 12, is going to be smaller than 2 over 7, which is smaller than 2 over 5, which is smaller than 2/3. So if you want to use inequalities, we'll say 1/6 is less than 2/7, which is less than 2/5, which is less than 2/3. All right, so now let's get into the shortcut. So we can determine which fraction is larger by cross-multiplying and comparing the results. So now we're back to replace the question mark with the less than symbol or the greater than symbol. All right, so let's start off with this example here. So we have 4/9 question mark 5/12. So I'm going to build you up to the shortcut. We're going to start with what we know. So we have that the LCD is going to be the LCM of these denominators. So 9 and then 12. What is 9? It's 3 times 3. What is 12? It's 3 times 4, and 4 is 2 times 2. So 2 times 2 times 3. So when you build this, again, you look at this and you say, okay, well, there's going to be 2 factors of 2. So 2 factors of 2. But then I only need 2 factors of 3, right? Because there's 2 factors of 3 here and 1 here. Go with the largest number of repeats between any of those prime factorizations. So I'm going to put in 2 factors of 3. Get rid of this. We know that that's basically 4 times 9, which is 36. So let's put this as 36. So at this point, we know, using our slower procedure, we would say 4 over 9, and then times, what do I need to multiply 9 by to get to 36? Well, 4. So I would do times 4 over 4. And then over here, I have 5 over 12. What do I need to multiply 12 by to get to 36? Well, 3. So times 3 over 3. And so this becomes 16 over 36. And then this becomes 15 over 36. And now that we have a common denominator, we can just compare the numerators. So 16 is greater than 15. So you'd say 16 over 36 is greater than 15 over 36, which gives me 4/9 is greater than 5/12. Okay, so we've been doing it that way. And it's a little bit slower than what I'm going to show you now. So let me erase this and let's talk about the shortcut. In every case, you can just multiply the 2 denominators together to get a common denominator. It's not always going to be the least common denominator. Sometimes it will be, it just depends. But you can always just get a common denominator by doing that. So let's say I erase this and I erase this. And I just say, okay, I'm not going to find the LCD here. I'm just going to get a common denominator. So I would multiply this by 12 over 12. And I would multiply this by 9 over 9. Okay, well, 4 times 12 is 48. And then 5 times 9 is 45. It actually does not matter what the denominator is because I know it's going to be the same, right? Because I'm multiplying the 2 denominators together. It's just in a different order. Here it's 9 times 12 and here's 12 times 9. Now 9 times 12 or 12 times 9, we know that's 108. So let's just go ahead and write that for completeness. At this point, I can just compare the numerators. So 48 is larger than 45. So you would say 48 over 108 is greater than 45 over 108. Okay. So what can we learn from this process? what I could have done, let me get rid of this for a moment. I could have just said, well, if I multiply those two denominators together, they're going to be the same. So I don't really care what they are. I just need to figure out what is this numerator times the other denominator, and what is this numerator times the other denominator, and just compare those numbers to figure out which fraction is bigger. So in other words, I can say 4/9 and then 5/12, and I can do something called cross multiplying. So take this denominator and multiply it by this numerator. 9 times 5 is 45, and that's the exact same thing we got here. 5 times 9 is going to be 45. And then you're going to take this denominator, which is 12, and multiply it by this numerator, which is 4, and that's going to give you 48. So 4 times 12 is 48 done this way. So it's just a much quicker way to obtain which fraction is bigger. I only need to think about the 48 and the 45. 48 is bigger, so I'm going to go with 4/9, the fraction that is next to, as the bigger fraction. So I can say that 4/9 is greater than 5/12 using this cross-multiplying method. Okay, let's blow through a few examples. So we have 2/3, and then you have a question mark, and 4/5. So again, you're just going to cross multiply. So 3 times 4 is 12, and then 5 times 2 is 10. So 12 is greater than 10. So you can say that 2/3 is smaller, right? So 2/3 is less than 4/5. What about 4/3 question mark 6/5? So don't worry about the fact that you have improper fractions here. It's not going to matter. You can use the same strategy. So let me write 4/3 and then 6/5. And again, we're just going to cross multiply. 3 times 6 is 18. Then 5 times 4 is 20. So 20 is bigger. So you would say 4/3 is greater than 6/5. Let me give you one example with some negatives. So these are a bit tricky because everything I said is going to now be reversed when you're thinking about a negative. So when I think about -3/4 and 2/-7, the first thing you want to do if you have negatives involved, bring your negative here into the numerator. And that's legal because a negative divided by a positive or a positive divided by a negative is a negative. I could just as well put the negative out in front, or I could put the negative in the numerator or the denominator. It's all legal. So let me put them both in the numerator, and then I would cross multiply. So 4 times -2 is -8, and 7 times -3 is -21. Okay, so here's where we got to be really, really careful. When we think about a bigger negative, it is further to the left, and it is therefore a smaller number. So -21 is a bigger negative, and therefore a smaller number than -8. So -21 would be next to the smaller fraction. So you would say that -3/4 is less than -2/7. If you had gotten the problem 3/4 and then 2/7, notice that the answer would be flipped. So you cross multiply here, you have 8, and then you have 21. Right? So 21 is greater than 8. So here you would say that 3/4 is greater than 2/7. But because these guys are negative, it's going to get reversed, right? Because now 3/4 becomes -3/4, and that's going to be a bigger negative and therefore a smaller number than this -2/7. All right, let's look at one more example where we arrange from least to greatest. So we have 2/15, 3/7, and 4/13. So what I do is just start with any two that you want. It doesn't really matter. So let's start with 2/15 and then 3/7 and just figure out the relationship. So 15 times 3 is 45, and then 7 times 2 is going to be 14. So this one is obviously smaller. So we'll say 2/15 is less than 3/7. Okay, so erase this. And now you can take this one right here, this 3/7, and compare it to 4/13. So I'm going to say 3/7 and then 4/13. You'll cross multiply. So 7 times 4 is 28. And then 13 times 3 is 39. So 3/7 is bigger. So I'm going to say that 3/7 is greater than 4/13. So we know that 2/15 is less than 3/7. We could also turn that around and say 3/7 is greater than 2/15. Here we see that 3/7 is also greater than 4/13. So I know that 3/7 is actually the biggest number. I only now need to compare these two numbers and see which one is larger. So let's slide this down a little bit and cross multiply. So 15 times 4 is 60, and then 13 times 2 is 26. You can say that 2/15 is going to be less than 4/13. So this would be the smallest number. So let me change my color here. So this is 2/15. I'll put a comma. This one would be in the middle. So it would be 4/13. And then the largest would be this 3/7. If you want to write this using inequality symbols, you would typically go from least to greatest in the order of the number line.
but you could reverse that if you want. It's pretty much up to you. In most cases, you're going to see 2/15 is less than 4/13, which is less than 3/7. Hello and welcome to Pre-Algebra Lesson 35. In this video, we're going to learn about ratios and rates. Okay, so for the lesson objectives for today, we want to learn how to write a ratio that describes a given situation, and we also want to learn how to write a unit rate that describes a given situation. So we're going to kind of just start out with a basic definition here. We're going to say that a ratio is a comparison of two quantities with the same units. And later on, we're going to talk about rates, and a rate is basically a special ratio where the units are going to be different. To kind of start off here, we're going to use ratios a lot moving forward. And they're actually something that will help you in your everyday life. As an example, let's say that you're at a school dance. And at this school dance, you talk to the chaperone and they tell you that there are 4 boys for every 2 girls at this dance. So 4 boys for every 2 girls at the dance. Well, we can describe this relationship by writing a nice little ratio. And there's 3 main ways we do this. So if we want the relationship between boys and girls, we can write boys to girls like this as a fraction. And so boys is in the numerator. So I'd put the number of boys in my numerator when I write the ratio. Girls is in the denominator. So I'd write the number of girls in the denominator when I write the ratio. And we'd say it differently, right? Instead of saying 4/2, we would say 4/2. Now, if we flip this and said girls to boys, this would be 2/4, right? It's relative, right? The number of girls I have is 2 to the number of boys that I'm told that I have is 4. Now, there's more ways to write it, but I want to show you something before I get into that. When you have a ratio, you always want to simplify it, just like we did when we work with fractions. So we know that 4/2 or 4/2 as a ratio is the same as 2/1. If I divide 4 by 2, I get 2. If I divide 2 by 2, I get 1. Now, one main difference is if I'm working with fractions and I have 2/1, I just write that as 2. When I'm working with a ratio, I have this relationship between boys and girls, so I leave the 1 there because I'm saying I have 2 boys for every 1 girl. 1 girl. And then over here, I could just rewrite this as 1/2. Some other ways that we could write this ratio. I could write boys to girls like this using a colon. Okay, so this would be 2/1, right? Because I have 2 boys for every 1 girl. And then I could also write it using the word 2. I could say boys to girls like this. And I could say 2, the word 2, not the number 2, 1, like that. So all of these are ways that we can write a ratio. Most commonly, I would say you're going to see it this way or this way, right? As a fraction or with a colon. This is sort of uncommon, right? Sort of uncommon, but still you may see it from time to time, so you need to know that we're talking about a ratio when we see something like this. So let's kind of continue with this example, and I'll show you a common test question for ratios. So remember, we had 4 boys for every 2 girls. And we said that this simplified to a ratio where it's boys to girls of 2/1. Now, your typical question would say something like, if there were 42 kids at the dance, how many were boys, how many were girls? So let's think about that. So out of 42 kids, we're going to put boys, question mark, and then girls, question mark. How would we figure something like this out? Well, the first thing I would do is I would take my 2 numbers in my simplified ratio and I would add them together. So I have 2 boys to 1 girl. So 2 plus 1 is 3. So that tells me in one group, I will have 3 kids, and I will basically have 2 boys, and I'll have 1 girl. If I have 42 total kids,
Essentially, I'm saying, how many equal groups of 3 can I make out of 42? Well, 42 divided by 3 is 14. So I'm essentially saying I have 14 of these groups, so I would multiply the numbers here by 14. So 2 times 14 would give me 28. So this tells me that for 42 kids, I would have 28 boys. And I would multiply 1 times 14 and get 14, so I'd have 14 girls. And if this isn't clear for you, let me just kind of make a little chart. So we would have kids, and then we would have boys, and then we would have girls. So if 3 kids attend, we know that 2 are boys, 1's a girl. And we're going to increase in increments of 3 here. So if we go from 3 to 6, then we're going to have what? We've doubled here, so we have to double everything here. Now we're going to have 4 boys and 2 girls. Right? All I did was multiply everything here by 2. 2 times 2 is 4, 1 times 2 is 2, 3 times 2 is 6. Right? Everything has just been doubled. Well, if I now go to 12 kids, essentially I'm taking the original amount and just multiplying it by 4. Right? So I have 4 times the amount of kids there. So instead of 2 boys, multiply by 4, I'd have 8. Instead of 1 girl, multiply by 4, I'd have 4. So we can take this all the way up to, let's say, 42. And basically it's 14 times the original amount. So I just multiply everything here by 14. 2 times 14 would be 28. So I'd have 28 boys. 1 times 14 would be 14. So I'd have 14 girls. All right, so let's take a look at a different problem. So we have a mixture that contains 24 milliliters of alcohol for every 8 milliliters of water. And we want to state the ratio of alcohol to water. So I'm just going to do this using a fraction, but again, if you want to use a colon, you can do that as well. So again, the ratio of alcohol to water, so alcohol to water. Notice that alcohol, the first word or the word that occurs before the word to, is in the numerator. Water, the second word, occurs in the denominator. So I have 24 milliliters, 24 milliliters to 8 milliliters. And again, with a ratio, you're going to have the same units, so you don't really have to write them because you can kind of think of them as just canceling each other out. So we could just write 24 over 8. And if we simplify this, we know that 24 divided by 8 is 3. So really I'd write it as 3 to 1. And again, very important, leave the 1 there. I know generally when we work with fractions, we just write that as 3. But with a ratio, we're talking about the relationship where we're saying we have 3 milliliters of alcohol to every 1 milliliter of water in this mixture. Now it says to state the ratio of water to alcohol. So again, if your words are flipped, you just flip your ratio. So water to alcohol. Remember, when we looked at alcohol to water, the simplified version was 3 to 1. So when we look at water to alcohol, it's going to be 1 to 3, meaning I have 1 milliliter of water for every 3 milliliters of alcohol in this mixture. Let's take a look at some follow-up questions. So let's suppose that we have a 120 milliliter mixture. So I'm going to write here that we have a 120 milliliter mixture. We want to know how many milliliters of alcohol are in the mixture and how many milliliters of water are in the mixture. Let me kind of scroll down to the next page and get a little room going. Again, I'm going to write that it's a 120 milliliter mixture. And let's just write the ratio of alcohol to water. Alcohol to water. And remember, that's 3 to 1. 3 milliliters to 1 milliliter. And again, I left off the milliliter because, you know, we could write that in there if you want. But again, these would basically cancel out. And you just write it as 3 to 1. That's just very common. That's what we do. All right, so if we want to find out how much alcohol is in this mixture and how much water is in this mixture, we have to think about what would be in one group. So one group would be 3 plus 1 or 4. 4 milliliters. That's one group. And you basically have 3 milliliters of alcohol. And you're going to have 1 milliliter of water. So how many of these groups can I make out of 120 milliliters? Well, you take 120 and you divide it by 4 and you would get 30. So I can make 30 of these groups. So I would just multiply 30 by 3 to get the amount of alcohol I'm going to have. 30 times 3 is 90. So I'm going to have 90 milliliters of alcohol. And I would multiply 1 times 30 to find out how many milliliters of water I'd have. 1 times 30 is 30. So I would have 30 milliliters of water. In a mixture with 120 milliliters, with an alcohol to water ratio of 3 to 1, you're going to have 90 milliliters of alcohol and 30 milliliters of water. So similar to ratios, a rate is a special type of ratio that compares two quantities with different units. So when we start talking about rates, we're generally going to be talking about something known as the unit rate. And that's going to be the amount of something per 1 unit. So generally speaking, we just divide the numerator by the denominator to get a unit rate, or the rate per single unit. So as an example, we have Jeff earned $63 in 9 hours. What is the unit rate in dollars per hour? So you just kind of set this up just like you would with a ratio. So we're going to put $63 in the numerator, and we're going to put 9 hours in the denominator. And essentially, to find the unit rate, or the amount of dollars that he earns per 1 hour, you're going to take the number in the numerator, which is 63, and divide it by the number in the denominator, which is 9. We know that 63 divided by 9 is 7. So when we basically just simplify this, we end up with $7 per 1 hour. Or he earns $7 per hour. We have that Jennifer drove 125 miles in 5 hours. What is the unit rate in miles per hour? So this is a common one you might use on a trip somewhere. So we have 125 miles. We'll put that in the numerator. And we'll have 5 hours. We're going to put that in the denominator. We're trying to find out how many miles per 1 hour. So again, we take the number in the numerator. We divide that by the number in the denominator. So 125 divided by 5 is 25. So this numerator is going to be 25 and then miles. And in the denominator, this is going to be a 1, and then it's going to be hour. So she was going 25 miles per 1 hour. So one common thing we use unit rates for is to compare prices. And a lot of times when you go to the grocery store, you'll see next to the price, it's this much per unit. Might be this much per ounce or this much per gallon, so on and so forth. So in our example here, we have that 5 gallons of milk sells for $15, while 10 gallons of milk sells for $20. Which option has a lower cost per gallon? So what we would do is take the dollar amount in each case and divide it by the number of gallons of milk we're getting in each case. That'll give us the unit rate, or the price per gallon of milk. So the first scenario is $15 for 5 gallons of milk. So if I take 15 and divide it by 5, I get 3. So this is essentially $3 per 1 gallon, right? And I could put gallon of milk, but just going to kind of shorten that a little bit. The next scenario is 10 gallons for $20. So I'm going to set this up as $20, and then in the denominator, I'll put 10 gallons of milk. And again, I'm going to do 20 divided by 10. That's going to give me 2. So my new numerator will say $2, and then per, again, 1 gallon. 1 gallon. So obviously this is cheaper. So between these two scenarios, this one is going to be cheaper, right? Spending $20 on 10 gallons of milk gets you a price of $2 per gallon. And again, if you were to spend $15 on 5 gallons of milk, you'd be paying more per gallon, or a price of $3 per gallon. Hello and welcome to Pre-Algebra Lesson 36. In this video, we're going to learn about proportions. So our lesson objective for today is just to learn how to determine if two ratios represent a proportion. So in the last lesson, we learned all about ratios, and we didn't go too much into depth, but we learned enough for pre-algebra. Now we're going to start talking about proportions, and this is another topic where we're going to go way deeper once we get into Algebra 1. But before we can start talking about proportions, we have to be able to answer a simple question. And that question is, how do we determine if two fractions are equal? Well, we're going to use something called the equality test
for fractions. And basically what this tells us is that two fractions are going to be equal if their cross products are equal. So for example, let's say we take something like 1/2 and, I don't know, let's say 6/12. We can eyeball this and see that these two fractions are equal. I know that if I divide 6 by 6, I get 1. If I divide 12 by 6, I get 2. 1/2 and 6/12, they're equivalent fractions. So the equality test for fractions tells me that I can multiply this denominator by this numerator and this denominator by this numerator, right? The cross products, we're multiplying across, and I should get the same answer. 2 times 6 would give me 12, and 12 times 1 gives me 12 as well. So we have the same value, and so we know those two fractions are equal. Let's try another one. Let's say we have something like 1/4 and, I don't know, let's say 3/7. We know these two fractions are not equal. One of the ways we can tell is that these two fractions are reduced to their lowest terms or simplified, and so I know that they're not going to be the same value. So I can multiply 4 times 3, that would give me 12, and 7 times 1, that would give me 7. 7 and 12 are not equal, so these two fractions are not equal. Now you might be asking, how does this little test work? How come when we have the same value here, we know that we have equal fractions or equivalent fractions? Well, you remember when we were talking about comparing fractions, we found that when we cross multiplied, if 12 was greater than 7, that tells us that 3/7 is the greater fraction. So that stems from the fact that we're comparing the numerators here if we had multiplied each fraction, top and bottom, by the other fraction's denominator. So, for example, if I have 1/4 and 3/7, what I can do is I can form a common denominator of this fraction's denominator times this fraction's denominator. 4 times 7 would be 28. Now, you can always do this. It's not always going to give you the least common denominator, but it will give you a common denominator. So if I multiply this fraction, top and bottom, by the denominator of this fraction, well, what I get? 1 times 7 is 7. That's what we had here. And then 4 times 7 is 28. So you get 7 over 28. Now, if I do the same thing over here, so I have 3 over 7, I'm going to multiply this top and bottom by the denominator of the other fraction, so times 4 over 4. 3 times 4 is 12. Notice that's what we got here. And then 7 times 4 is 28. So now it's easy to compare these two fractions. They have the same denominator. I just look at the numerator. And I know that 12 is bigger than 7, so this is the greater fraction. So 7/28 is less than 12/28. When we cross multiply, we are shortcutting this process. I am just saying, hey, all I need to know is what's the numerator going to be, right? In this case, I know the numerator is going to be a 7, and I know the numerator is going to be a 12 over here. 7 is less than 12, so I know this fraction is going to be smaller. I don't care what the denominator is going to be because the denominator is going to be the same, and again, that allows me to compare the numerators only. So again, when two fractions are equal, their cross products are equal. So if we have a problem like this, 1/4 is equal to 7/28, and I have a big question mark here. So we kind of have to prove it and say, okay, is this true or is this not? So I would just find the cross products. So I'd multiply 4 times 7, that gives me 28. I'd multiply 28 times 1, that gives me 28. So yes, these are equal. Yes. And one of the things you can do, if you have both fractions in their simplest form, you can easily tell if they're equal, right? Because if I can't reduce this any further, I can't reduce 1/4 any further. But if I look at 7 over 28, I can reduce that. 28 is divisible by 7. So if I divide 28 by 7, I'd have 4. If I divide 7 by 7, I'd have 1. So I'd end up with 1/4. What about 2/5 is equal to 6 over 20? Again, we can just form the cross product. So 5 times 6 is 30. And 20 times 2 is 40. So 40 is not equal to 30. So these two fractions are not equal. So no. What about 3/4 is equal to 9/12? Again, form the cross products. So 4 times 9 is 36. And 12 times 3 is also 36. So this would be a yes. These two fractions are equal. What about 17 over 12 is equal to 34 over 24? So we'd multiply 12 times 34. 2 times 4 is 8. 2 times 3 is 6. 1 times 34 is 34. Bring down the 8. 6 plus 4 is 10. 1 plus 3 is 4. So this is going to be 408. Then we're going to do 24 times 17. So 24 times 17. 7 times 4 is 28. 7 times 2 is 14, plus 2 is 16. And then 1 times 24 is 24. So bring down the 8. 6 plus 4 is 10. 1 plus 1 is 2. 2 plus 2 is 4. So this is going to be 408 also. So these two fractions are equal because their cross products are equal. So yes. All right, let's take a look at one final problem. We've got 12 over 13 is equal to 48 over 65. So multiply 13 times 48. So 48 times 13. 3 times 8 is 24. 3 times 4 is 12. Plus 2 is 14. And then 1 times 48 is 48. Bring down the 4. 4 plus 8 is 12. 1 plus 1 is 2. Plus 4 is 6. So that's 624. And then 65 times 12 is what we're going to do next. So 65 times 12. 2 times 5 is 10. 2 times 6 is 12. Plus 1 is 13. And then 1 times 65 is 65. 3 plus 5 is 8. 1 plus 6 is 7. So that's 780. So 780 is not equal to 624. So no, these are not equal fractions. All right, so let's talk about what a proportion is now. So when two ratios are equal, or you could say when two rates are equal as well, they are called a proportion. And really you could extend that and say when two fractions are equal, they represent a proportion. So those examples that we looked at earlier, where we said yes, those were proportions. We start out with this example, 3 shrubs to 12 feet. And then we have 6 shrubs to 24 feet. And we're saying they're equal. So if this is true, then we'd have a proportion. Now the way you check this, if I have shrubs in the numerator here, I've got to have shrubs over here. I can't have shrubs here and then trees over here. That doesn't make any sense. And then whatever's in the denominator has to be the same. So feet here and feet here. So once you've checked that, all you need to do is cross multiply with the numbers. If the result of the cross products there are the same, you have a proportion. So in other words, here I would take 12 and multiply it by 6. 12 times 6 is 72. Then I would take 24 and multiply it by 3. 24 times 3 is also 72. So yes, here we have a proportion. Let's take a look at another one. Here we have 600 miles to 10 hours. And we're saying that's equal to 300 miles to 5 hours. Now, again, you're looking at what's in the numerator. We have miles here, miles here. What's in the denominator? We have hours and then hours. So that part checks out. Then you just work with the number parts. So I'm going to cross multiply. I'd have 10 times 300. So basically we just put another 0 at the end of 300. That's 3,000. Then I'm going to multiply 5 times 600. So 5 times 6 is 30. And then we have 2 trailing zeros. So we put 1, 2 zeros at the end. And in each case we get 3,000. So yeah, this is a proportion. So yes, this is a proportion. Here we have 12 points to 48 games. We're saying this is equal to 36 points to 96 games. So again, we check everything out in the numerator, points and points. In the denominator, we have games and then games. So that's all okay. Then we're just going to cross multiply with the numbers. So 48 times 36. And just in the interest of time, we'll do that with a calculator. It's 1,728. And then we do 96 times 12. And that's 1,152. So these two numbers are not the same. So this is not a proportion. So not a proportion. All right, for the next one, we have $2 to 7 euros. We're saying this is equal to $5 to 18 euros. So again, we have dollars and dollars, euros and euros. So that's okay. Now we would cross multiply. 7 times 5 is 35. 18 times 2 is 36. 36 and 35 are not equal, so we don't have a proportion. So just not a proportion. Okay, let's take a look at one more problem. Again, this is really, really simple. So we have 13 gallons to 4 acres, and we're saying this is equal to 39 gallons to 12 acres. So again, we have gallons and gallons, and acres and acres. So that checks out. So then we just want to cross multiply the number parts. So 4 times 39 is 156. And then 12 times 13 is also 156. So those two numbers are the same, so we do have a proportion. So yes, this is a proportion. Hello and welcome to Pre-Algebra Lesson 37. In this video, we're going to learn about operations with mixed numbers. So the lesson objective for today is to learn how to add, subtract, multiply, and divide mixed numbers. So when we add or subtract mixed numbers, we're going to add or subtract the fractions first, followed by the whole numbers. So let's just start out with an example. We have 3 1/2 plus 6 1/4. So I want you to remember that if we see something like 3 1/2, this is really 3 plus 1/2, right? It's just written this way for convenience, right? We don't want to take up all the space with a plus sign each time. So 6 1/4 is really 6 plus 1/4. So to add these two mixed numbers, all we're going to do is just kind of rewrite them as 3 plus 1/2 and then plus 6 plus 1/4. And then I'm going to do some reordering. Remember, I can do that with addition because it's commutative. So I'm going to put my fractions next to each other. I'm going to put 1/2 plus 1/4. And then I'm going to put my whole numbers next to each other. So I'm going to put plus 3 plus 6. So now what I'm going to do, again, as I said, I'm going to add the fractions first, and then I'll add the whole numbers last. So what if I had 1/2 plus 1/4? What would I do? Well, I'd find my LCD, and between 2 and 4, I know the LCD would be 4, right? 4 is 2 factors of 2. 2 does not factor. So if I have 1/2, again, plus 1/4, I'd multiply 1/2 by 2 over 2 so that I could get the denominator of 4. So 1 times 2 is 2, over 2 times 2, that's 4. And then we're adding to that 1/4. So we'd add these numerators. 2 plus 1 is 3. And we place that over the common denominator of 4. All right, so let me erase all this and just kind of go back up to the top now. So we know at this point that adding the fractions here gives us the result of 3/4. So I'm going to put 3/4 plus, and then again you have 3 plus 6 there. Now adding the whole numbers are easy, right? 3 plus 6 is 9. You can do that in your head. So now when I look at it, I have 3/4 plus 9. If I just reorder this one more time to 9 plus 3/4, I can then use my convenient notation that I have up here, the way that we just write a mixed number, right? So this is going to be equal to 9 and 3/4. All right, let's take a look at another one. We have 6 3/8 plus 2 1/12. So again, what I'm going to do is I'm going to rewrite this. I'm going to put 6 plus 3/8 and then plus 2 plus 1/12. So I'm going to reorder this addition to where the fractions are next to each other and the whole numbers are next to each other. So I'm going to put 3/8 plus 1/12 and then plus 6 and then plus 2. And again, you don't have to do that. You can just kind of add these together and add these together, and you'd end up with the same result. I just do this so that it's convenient to see what we're doing. All right, so moving on now. We're going to add our fractions first. And let's just do this down here to make it convenient. So if I have 3/8 and I have 1/12, what's going to be my LCD? Well, it's going to be the LCM, the least common multiple, of 8 and 12. So again, how do we figure something like that out? Well, we've been working with fractions for a long time now. We know that 8 factors into 3 factors of 2. So 2 times 2 times 2. We know that 12 is 2 factors of 2, and I've already accounted for that, and then 1 factor of 3, so that's got to go in. So basically my LCD is going to be 2 times 2 times 2, or 8 times 3, which is 24. So when I'm adding these fractions, what I'm going to do is I'm going to first transform the fractions into equivalent fractions where they have a denominator of 24. So I'm going to multiply this by 3 over 3, and I'm going to multiply this by 2 over 2. So what we're going to get is 3 times 3, that's 9, over 24, plus 1 times 2 is 2, again, over 12 times 2, which is 24. So now we have our common denominator. We can just add the numerators. 9 plus 2 is 11, and that's going to be over the common denominator of 24. So let's erase all this and go back up. We know what the fraction part's going to be. It's going to be 11 over 24. So I'm going to put equals 11 over 24. and then plus. Now the whole number parts, 6 and then 2, we add those together, that's going to give us 8. And again, I can just reorder this one more time. 8 plus 11 over 24. And again, to write this as a mixed number, we just simply drop out that addition sign, right? Just for convenience. So this is really going to be 8 and 11/24. All right, let's take a look at one final addition problem, and then we'll move on to subtraction, multiplication, and division. So we're adding 9 and 1/5 plus 13 and 1/4 plus 2 and 7/8. Again, I'm going to just write this out as 9 plus 1/5 plus 13 plus 1/4 plus 2 plus 7/8. And I'm going to reorder it again to where my whole numbers are next to each other and my fractions are next to each other. Let me just put my whole numbers first. So let's do 9 plus 13 plus 2. And then plus, down here I'm going to put my fractions of 1/5 plus 1/4 plus 7/8. So let's take care of the fraction parts first. And we're going to scroll down and do that. So if I have 1/5 plus 1/4 plus 7/8, again, I need to find the LCD to start. So what's my LCD going to be? Again, it's going to be the least common multiple for these denominators. So of 5, 4, and 8. So 5 doesn't factor, so that goes in. 4 is 2 times 2. And 8 is 3 factors of 2. So because I already have 2 factors of 2 in here, I just need to add one more in. So the LCD is going to be 5 times 2, which is 10, times 2 again, which is 20, times 2 one more time, which is 40. So I need to rewrite each fraction as an equivalent fraction with 40 as its denominator. So for 1/5, I'm going to multiply by 8 over 8. For 1/4, I'm going to multiply by 10 over 10. And for 7/8, I'm going to multiply by 5 over 5. Okay, so 1 times 8 is 8. Over 5 times 8, that's 40. Then plus 1 times 10 is 10. Over 4 times 10, that's 40. Then plus 7 times 5 is 35. Over 8 times 5, that's 40. So we have 8 plus 10, that's 18, plus 35, which is going to give us 53. So we'd have 53 over the common denominator of 40. Now, when you get a result that is greater than 1, remember, you're working with mixed numbers here. So your fraction part has to be a proper fraction. This is an improper fraction. So what you want to actually do here is convert this into a whole number part and a fraction part, right? And that fraction part is going to be a proper fraction. And we remember how to do that, right? We take 53 and we would divide it by 40. So 40 goes into 53 once. 1 times 40 is 40. Subtracting, we get 13. We would have 1 and 13 over 40 as our mixed number there. So let me erase all of this. And we're going to go back up to the top. And I'm just going to rewrite this right here. 9 plus 13 plus 2 plus. I just found out that the result from adding the fractions was 1 and 13/40. So I'm going to put a 1 here to add along with my whole numbers, and then plus 13 over 40. This fraction part I don't need to do anything else with. So now I'm just going to add these whole numbers together. 9 plus 13 is 22. 22 plus 2 is 24. Then 24 plus 1 is 25. So I would have 25 plus 13 over 40. And again, as a mixed number, we just write this as 25 and 13/40. Okay, now let's look at some subtraction problems. And really, when you work with subtraction problems, they're not any more difficult, except for the simple fact that sometimes you'll be subtracting fractions, and the fraction you're subtracting from is too small. So you have to do a little bit of borrowing, and we're going to come across that in the next problem. So we're going to start out with 23 1/3 minus 20 1/7. So again, what I'm going to do is I'm going to subtract the fraction parts first, and then I'm going to subtract the whole numbers. So in other words, I'm going to take 1/3 and I'm going to subtract away 1/7. Now you have to do it in that order here because remember, subtraction is not commutative like addition. So I'm going to take 1/3 and I'm going to subtract away 1/7.
Now to do this, I need to get a common denominator going. And my LCD here would be the product of the denominators, 3 times 7. And that's because 3 and 7 are both prime numbers. So I'm going to multiply this by 7 over 7. I'm going to multiply this by 3 over 3. And we're going to end up with 7 over 21 minus 3 over 21. And that's going to give me 4 over 21. Right? 7 minus 3 is 4 over the common denominator of 21. So now that we know the fraction part, we only need to subtract the whole number part. And again, I have to be specific about how I do it. It's 23 minus 20. If I do it in a different order, I'll get the wrong answer. So 23 minus 20 would be 3. So what we end up with is 3 for the whole number part, and then 4 over 21 for the fraction part. All right, let's take a look at another subtraction one. So we have 14 and 3/5 minus 5 and 13/15. So we would start this problem out the same way. So we do 3/5 minus 13/15, right? Just subtract your fractions first, get that out of the way. What's going to happen is you're going to find out that 3/5 is smaller than 13/15. So the result of this is going to be a negative number. Now we don't want that. So what we're going to do is we're going to end up borrowing from the whole number part. So let me show you how to do that. The first thing I'm going to do is pretend that I don't know that this number is smaller. So I'm going to start out by saying, okay, the LCD between the two fractions is 15. So I'd multiply this by 3 over 3. And what would happen is I'd see that, okay, I have 9 over 15 minus 13 over 15. And I'd say, okay, this is going to result in negative 4 over 15. You know, what do I do now? Again, to correct this, I'm going to borrow. So instead of having 14 there, I'm going to rewrite this and say that this whole number is going to be 13. And instead of 3/5, what I'm going to do is I'm going to add 5/5. So that's where this 1 went. I took 1 away, and I basically said, okay, instead of having 14, I now have 13. That 1, where it went, I wrote it as 5/5, and then I'm adding that to 3/5. So essentially my fraction part now is going to temporarily be 8/5, right? So you can just think of this as having 13 and 8/5. And that's not how we write mixed numbers, right? We always want a whole number and a proper fraction, but we're just doing it so that we can perform our operation. So if I have this as 13 and 8/5, now when I look to subtract the fractions, what I'm going to have is I'm going to have 8/5 minus 13/15. Again, the LCD is still going to be 15, so I'd multiply this by 3 over 3. And what we'd end up with now is we'd have 3 times 8, that's 24, over 3 times 5, that's 15, minus 13 over 15. And you can see that 24 is bigger than 13, so you can do the subtraction and not get a negative number. So 24 minus 13 is going to give us 11. So this ends up being 11 over 15 for our fraction part. Now, when we subtract the whole numbers, now we have a different whole number to work with. Because we lent 1 to our fraction, we no longer have 14 as our whole number part, we have a 13. So we have to keep that in mind. So we would do 13 minus 5, and 13 minus 5 is going to give us 8. So 8 and 11/15 would be our answer. Okay, let's take a look at another one. We have 12 and 4/9 minus 8 and 7/8. So again, when I have a subtraction problem and I'm working with mixed numbers, I'm going to try to subtract my fraction part first, and then I'm going to worry about the whole numbers. So I would subtract 4/9 minus 7/8. 4/9 minus 7/8. Again, you got to do it in that order because subtraction is not commutative. Now, when I look here, I see that 9 and 8, they're not going to have any common factors, right? 9 is 3 times 3. 8 is 3 factors of 2. So really the LCD here is going to be the product of the two denominators, or 72. So I'd multiply this by 8 over 8, and I'd multiply this by 9 over 9. And when you do this, you see you have a problem, right? 8 times 4 is 32. So this would be 32 over 72. Minus 7 times 9, that's 63 over, again, 72. So when we perform this subtraction, we end up with a negative result. And although we can do it that way, it makes it more complicated. So to keep things nice and simple, let's erase all this. And I just want you to, again, temporarily think about this. We're going to borrow 1 from this whole number. So instead of 12, I'm going to have 11. And so this 4/9 here, I'm going to just temporarily add 1 to that 4/9, but just using fractions. So instead of 4/9, if I add 1 in fractional form, I'm going to add 9/9, and that's going to give me 13/9. So instead of having 4/9 there, I basically have 13/9. And again, this is now 11 for the whole number part. So now if we subtract fractions, I would do 13/9 minus 7/8. We're going to have the same LCD. So I'm going to multiply this by 8/8. I'm going to multiply this by 9/9. And let me just scroll down here so we have a little room. 13 times 8 is 104. And this would be over 9 times 8, that's 72. Then we'd subtract away 7 times 9, that's 63. Over 8 times 9, that's, again, 72. 104 minus 63 is 41. And this is over the common denominator of 72. So the result of subtracting the fractions would give us 41 over 72. So this is 41 over 72 for that part. And now we just subtract the whole numbers. So remember, I don't have 12 anymore because I borrowed to do my subtraction with the fractions. So I have an 11 here, and then I'm just subtracting away 8. 11 minus 8 would give me 3. So we'd end up with 3 and 41 over 72 as our answer. So now we're going to start doing some multiplication and division. And we're going to change something up here. Now when you add or subtract mixed numbers, generally what everybody's going to say is to add or subtract the fraction parts first, then add or subtract your whole number parts. Now, alternatively, if you wanted to, when you add or subtract mixed numbers, you could have converted those mixed numbers into improper fractions, perform the addition or subtraction, and then you can convert them back to mixed numbers if you have to. It's totally up to you which way you want to do it. It's just usually faster to do it the way that I showed you. Now, when we multiply or divide mixed numbers, we're going to convert each mixed number into an improper fraction. Once we're done, if it's required, we'll convert the answer back to a mixed number. Sometimes your teacher won't tell you to convert it back. You can just leave it as an improper fraction. Whatever they want you to do, just follow the instructions you're given. So we're going to start with 5 2/5 times 3 1/7. So what I'm going to do is convert each of these into an improper fraction. 5 times 5 is 25, plus 2 is 27. So I'd have 27/5 times 7 times 3 is 21, plus 1 is 22, over 7. So again, when I multiply, I always look to cross cancel first. There's no common factors between anything here, so I just do the multiplication. 27 times 22 is going to give me 594. And this is over 5 times 7, which is 35. So our answer here is 594 over 35. Now, like I said, if you wanted to, you can leave this as an improper fraction. If your teacher makes you, convert it back to a mixed number. So let's do 1 or 2 where we convert it back, and then we'll just leave them as improper fractions moving forward. So 594, we're going to divide that by 35. 35 goes into 59 once. 1 times 35 is 35. Subtract here, 9 minus 5 is 4. 5 minus 3 is 2. Bring down the 4. 35 is going to go into 244 6 times. 6 times 35 is going to give us 210. Subtract here. 4 minus 0 is 4. 4 minus 1 is 3. So that's going to give us 34 as the remainder. So as a mixed number, this would be 16 and 34 over 35. Okay, for the next one, we have 8/11 times 4 1/2. So I'm going to keep 8/11 unchanged. That's already a fraction. And I'm going to multiply by 4 1/2 after I convert it into an improper fraction. 2 times 4 is 8, plus 1 is 9. So we'll have 9 halves here. We look to see what we can cross cancel. I know that 8 is divisible by 2. 8 divided by 2 is 4. So just think about canceling a factor of 2. That would give me 4. Cancel a factor of 2. That would give me 1. So now I basically have 4 times 9, that's 36. Over 11 times 1, that's 11. So I get 36/11 as my answer. Now again, for the last time, we're going to convert this into a mixed number. Again, this is something you should already know how to do. So if your teacher requires it, go ahead and do it. But again, a lot of teachers will just say, however you get the answer, as long as it's simplified, it really doesn't matter. So 36 divided by 11. 11 goes into 36 3 times. 3 times 11 is 33. Subtract and get 3. So if we write this as a mixed number, we'd have 3 and 3/11. 3 and 3/11. Now we have 4 and 2/5 times 6 and 1/4. So I'm going to convert each into an improper fraction. 5 times 4 is 20, plus 2 is 22. So we'd have 22 over 5 times, for this one, 4 times 6 is 24, plus 1 is 25, and that's over 4. And we can see we can do some cross-canceling here. I know that 25 is divisible by 5. 25 divided by 5 is 5. So this will cancel out completely and become 1. This will cancel and become 5. 22 is divisible by 2, and so is 4. So 22 divided by 2 is 11. 4 divided by 2 is 2. So now we have 11 times 5, that's 55. Over 1 times 2, that's 2. So we end up with 55 halves as our answer. Let's take a look at a few division problems now. So we have 8 and 2/9 divided by 7 and 1/2. Again, what I want to do is change each of these mixed numbers into an improper fraction, then do the division. So 8 and 2/9, I'm going to change this. 9 times 8 is 72. 72 plus 2 is 74. And this is going to be over 9. And we're dividing by 7 and 1/2. 2 times 7 is 14. 14 plus 1 is 15. So that's 15 halves. And again, if you're dividing fractions, the first fraction or the left fraction stays unchanged. So 74/9, we don't do anything to that. Then we're going to multiply by the reciprocal of 15 halves. So that's going to be 2/15. And we'll look to see if we can cross-cancel anything. Nothing I can really do here. 74 is not divisible by 3 or 5, so I can't really cancel anything. So we just multiply. 74 times 2 is 148. And this will be over 9 times 15, which is 135. So my answer here is 148 over 135. All right, for the next one, we have -6 divided by 2 and 1/8. So we have -6, and since we're dealing with fractions here, I'm going to go ahead and write that as -6 over 1, and then divided by, I'm going to convert this into an improper fraction. 8 times 2 is 16, plus 1 is 17, so you'd have 17 over 8. Again, to divide fractions, this leftmost fraction, -6 over 1, will stay unchanged, and we'll multiply by the reciprocal of this fraction, so times 8 over 17. So nothing I can cross-cancel here, so I just need to multiply. -6 times 8 is -48, and this is over 1 times 17, or 17, so we get -48/17 as our answer. All right, final problem. We have 2 and 1/5 divided by 4 and 1/3. So again, I'm going to convert each into an improper fraction. 5 times 2 is 10, plus 1 is 11. So this will be 11/5. And then divided by 4 and 1/3, I'm going to have 3 times 4, that's 12. 12 plus 1 is 13. And then over 3. So 11/5 times the reciprocal of 13/3 would be 3/13. Nothing to cross cancel. 11 times 3 is 33. 5 times 13 is 65. So we'd have 33 over 65 as our answer. Hello and welcome to Pre-Algebra Lesson 38. In this video, we're going to learn about complex fractions. So the lesson objective for today is to learn how to simplify a complex fraction using two different methods. So before we kind of get started, let me just give you a basic definition for a complex fraction. A complex fraction is a fraction that contains at least one fraction in its numerator or denominator. It could have a fraction in its numerator and denominator as well. So let's start out by looking at a problem. So here's a complex fraction. We have 1/5 plus 2/5 over 1/3 plus 4/3. So notice how we have an operation in the numerator and in the denominator, and there's fractions in both the numerator and the denominator. So one way you can simplify this is to simplify the numerator and the denominator separately, and then you're going to have a main division. This is going to be your main division for the complex fraction. So if we kind of go through here, and let me just erase this real quick. If we kind of go through here and simplify the numerator, we already have a common denominator. So we have 1/5 plus 2/5. We would just add 1 plus 2, that's 3. Put that over the common denominator of 5. And then in the denominator here, we have 1/3 plus 4/3. Again, we have a common denominator, so we can do 1 plus 4, that's 5. Put that over the common denominator of 3. So at this point, we have a complex fraction that's nothing more than a division problem. We have 3/5 basically divided by 5/3. So if you saw that problem written this way, you would know that you take 3/5 and leave it unchanged, and you're going to multiply by the reciprocal of the second fraction, which is 3/5 as well. So you're going to do the same thing here. You just got to get used to looking at it differently. We have 3/5 again divided by 5/3, so 3/5 is going to stay the same, and we're multiplying by the reciprocal of what we're dividing by. So the reciprocal of 5/3 again is 3/5, and we just multiply. 3 times 3 is 9, 5 times 5 is 25, so we get 9/25 as our answer. All right, for the second problem, we have kind of an easier one. This is basically just a division problem. We have 4/15 over 12/13. This is the problem 4/15 times the reciprocal of what we're dividing by. So times 13 over 12. Now I can cross cancel here. The greatest common divisor between 4 and 12 is 4. So if I divide 4 by 4, I get 1. If I divide 12 by 4, I get 3. Nothing I can really do between 13 and 15. So we'd end up just multiplying here. 1 times 13 is 13. Over 15 times 3, that's 45. So this is going to simplify to 13 over 45. All right, let's take a look at 5 plus 3/2 over -2. So again, we're going to work by simplifying the numerator and denominator separately. Our denominator here is simplified already, so I can just kind of copy that. I don't need to do anything. For the numerator, if I have 5 plus 3/2, I got to get a common denominator going there. So I can write 5 as 5 over 1, and the least common denominator I'm going to be able to form here is going to be 2. So I can take 5 over 1 and multiply it by 2 over 2, and I'm going to add that to 3/2. So continuing, 5 times 2 is going to be 10. That's going to be over 2 plus 3/2. And I'm just going to copy this denominator for the complex fraction. That's -2. And I'm going to continue down here. But in the numerator of the complex fraction, I have a common denominator now of 2. So I'm just going to add the numerator. So 10 plus 3 is 13. So that's 13 over 2. And basically we could say this is divided by or over -2. Now to make this easy on ourselves, I'm going to write -2 as -2 over 1. So now I can see this problem as 13/2 divided by -2 over 1. So again, it's just a division problem at this point. This fraction here, 13/2, will stay unchanged. And I'm going to multiply by the reciprocal of -2 over 1, which would be 1 over -2, or you could put -1 over 2. It doesn't really matter. Nothing to cross cancel, so we just multiply. 13 times -1 is -13. 2 times 2 is 4. So you get -13/4 as your answer. All right, let's take a look at another one. So we have 3/7 minus 5 over 21. That's the numerator for the complex fraction, and this is over. You have 5/8 plus 2/5. So this one will be a little bit tedious to work through. So let's kind of just simplify the numerator here, and then we'll work on the denominator in a minute. So we have 3/7 minus 5 over 21. So we got to get a common denominator going. And the least common denominator we're going to be able to form is going to be 21. Right? 21 is 7 times 3. Here we just have a 7. So what I'll do is I'll multiply 3/7 by 3 over 3. That'll give me a denominator of 21 there. Then minus 5 over 21. So 3 times 3 is 9. So we'll have 9 over 21 minus 5 over 21. That's going to give me 4 over 21. So my simplified numerator for the complex fraction is 4 over 21. So I'm just going to write up here that this is 4 over 21, and then over. Let's figure out what the simplified denominator for the complex fraction is going to be. So we have 5/8 plus 2/5. So 5/8 plus 2/5. Now, to find the LCD here, 5 is a prime number, and 8 is 3 factors of 2. So the LCD is basically found by multiplying 8 times 5. That would give you 40. So what I'm going to do is I'm going to take 5/8 and multiply by 5 over 5. And I'm going to take 2/5 and I'm going to multiply by 8 over 8. So 5 times 5 is 25. And of course this is over 40, right? 8 times 5 is 40. Then plus 2 times 8, that's 16. And again, this is over 5 times 8, which is 40. So 25 plus 16 is going to be 41. And then the common denominator is 40, so this is over 40. All right, so we have 41 over 40 here. So my simplified denominator, again, is 41 over 40.
So now we basically have a division problem. We have 4 over 21 divided by, or over, 41 over 40. So to divide this, we take 4 over 21, leave that unchanged. We multiply by the reciprocal of what we're dividing by. So the reciprocal of 41 over 40 is 40 over 41. And we can see that we can't really cross cancel here because 4 is 2 times 2, 41 is a prime number. 21 is 7 times 3, and 40 is 2 times 5 times 2 times 2. So nothing I can cancel here, so I just multiply. 4 times 40 is 160 over 21 times 41, and that's 861. So we're going to end up with 160 over 861 as our answer. So let's take a look at 5 minus 1/9, and then this is over 3. So I'm going to write this as 5 over 1 because I'm working with fractions. And I'm going to multiply 5 over 1 by 9 over 9 so that I can have a common denominator of 9. So then minus 1/9, and this is all over 3. So 5 times 9 is 45, so this would be 45 over 9 minus 1 over 9, and then this is all over 3. Continuing down here, in the numerator of the complex fraction, I have a common denominator now, so I would do 45 minus 1, that's 44, over the common denominator of 9, and then this is divided by, or over, 3. Now when we work with fractions, I like to have fractions everywhere because it makes it easier to think about what I'm doing. So instead of just having a 3, I'm going to write 3 over 1. So I can see the division problem is 44 over 9 divided by 3 over 1. That's easy to do. So we have 44 over 9, that stays the same. And we multiply by the reciprocal of 3 over 1, which is 1/3. So 4 plus 4 is 8, so it's not divisible by 3. So there's not really anything I can do to cancel here. So I just go through and multiply. 44 times 1 is 44. 9 times 3 is 27. So we end up with 44 over 27 as our answer. So alternatively, we can find the LCD of all denominators involved, then multiply the numerator and denominator of the complex fraction by the LCD. So when I say multiply the numerator and denominator of the complex fraction by the LCD, you have to pay close attention to that. And I'll show you why in this example. So we have 4/5 over 2/5. So what's my LCD here? Well, the denominator of this fraction is 5. The denominator of this fraction is also 5. So the least common denominator is going to be 5, right? Because they both have the same denominator. So when we say we're going to multiply the numerator and denominator of the complex fraction by 5, I'm essentially saying I'm going to multiply this part here by 5, and I can do by 5 over 1 if it makes it more convenient, and then this part by 5 as well. Right? This is the numerator of the complex fraction, this is the denominator of the complex fraction, and each part gets multiplied by 5. Again, this is legal because I'm multiplying by 5 over 5, which is 1. So if you go through, what's going to happen is this 5 will cancel with this 5 will cancel with this 5, and I will be left with 4 over 1, which is 4, divided by 2 over 1, which is 2. Right? So I can keep it like this in fractional form, or I can rewrite it if I want and just say this is 4 divided by 2. Right? Because this way I would have 4 over 1 times the reciprocal of 2 over 1, which is 1/2. It's the same thing as 4 over 2. Right? So when we do this division, 4 over 2, or 4 divided by 2, is 2. All right, here's one that's a little bit more complicated. We have 1/4 plus 3/5, and this is over 3/8 plus 5/12. So look at all your denominators involved. You have a 4, a 5, an 8, and a 12. So what's your LCD here? Again, this is the LCM for 4, 5, 8, and 12. So if you think about what we're going to put in the prime factorization for the LCM, 4 is 2 times 2. 5 doesn't factor, so it just goes in. 8 is 3 factors of 2. I already put 2 factors of 2 in, so I only need to put in the largest number of repeats between any of the prime factorizations. So I'm just going to add 1, 2 in there. Then 12 is 4, which is 2 times 2, that's already accounted for, times 3. So I'm going to put times 3. That's all I need to add to it because I already have 3 factors of 2 in there. So if I multiply this out, 2 times 2 is 4, 4 times 5 is 20, 20 times 2 is 40, 40 times 3 is 120.
So now what we're going to do is we're going to multiply the numerator of the complex fraction by 120. And you can do, again, 120 over 1 if that makes it more convenient for you. And you're going to multiply the denominator of the complex fraction by 120 also. So what is this going to give us? Well, you have to use the distributive property here because you have some addition going on. So 120 times 1/4. Think about what that would be. So 120 basically over 4, and that would be 30. So I'm just going to write this over here. This would be 30 plus, next you'd have 120 times 3/5. So 120 times 3/5. And let me write this over 1 to make it a little bit more convenient. So I can cross cancel 120 with 5. I know 120 divided by 5 is 24. So this cancels with this and gives me 24. And then 24 times 3 is 72. So the denominator is gone. You can put it over 1 if you want, but basically it's gone. So we're just going to put a 72 there. And again, if you wanted to write 30 over 1 plus 72 over 1, you can, but it's just completely unnecessary. So we'll just write it like this. And then our denominator, again, we're going to do the same thing. We're going to multiply 120 times 3/8, and then we're going to add to that 120 times 5/12. So for 3/8 times 120, and again, we can put 120 over 1 if we want. 120 divided by 8 is 15. So I can cancel this with this and get 15. 3 times 15 is 45. So you'd have 45 over 1 or just 45. And then plus, again, we're going to multiply 120 times 5/12. So we'll have 5/12 times 120. Again, you can put that over 1 if you want. 120 divided by 12 is 10. So this cancels with this and gives you 10. 5 times 10 is 50. And again, you can put that as 50 over 1 if you want, but I'm just going to put 50. So now we have 30 plus 72, and I'm going to write that down here. That's going to be 102 over 45 plus 50, and that's going to be 95. So our fraction has been simplified to 102 over 95. Okay, let's take a look at one more like this. We have 3/5 plus 1/2, and this is over 5/6 minus 1/3. So look at your denominators involved. You have a 5, a 2, a 6, and a 3. So what's the LCD? Well, it's going to be the least common multiple of 5, 2, 6, and 3. So again, 5 doesn't factor, so that goes in. 2 doesn't factor, that's going in. 6 is 2 times 3. I already have a 2, so I'm just going to put a 3 in. And then 3, we already have that in there. So 5 times 2 is 10. 10 times 3 is 30. So that's going to be your least common denominator. And so again, what we're going to do is we're going to multiply the numerator of the complex fraction by 30. And I'll put times 30 over 1. And we're going to also do that to the denominator. So times 30 over 1. And again, if I multiply by 30 over 30, I'm multiplying by 1. I'm not changing the value of the fraction. I know it looks more complicated, but really you're still doing the same thing. You're multiplying by a complex form of 1. So again, we're going to do this using the distributive property. So we would have 30 over 1 times 3/5 to start. So 30 divided by 5 is 6. So I cancel this with this and get a 6. 6 times 3 is 18. So this would be 18 over 1, or just 18. Then plus. Next, we're going to have 30 over 1 times 1/2. And I can do this down here, but basically we know that we would have 30 divided by 2 in that case, right? Because we're just saying, what is half of 30? That's 15, right? 30 divided by 2 is 15. So I'll put a 15 here. And this is over. Next, we have 30 over 1 times 5/6. So 30 over 1 times 5/6. So I know that 30 divided by 6 is 5. So cancel this with this, and I'll get a 5. 5 times 5 is then 25. Then minus. Next, I'm going to do 30 over 1 times 1/3. So 30 over 1 times 1/3. 30 divided by 3 is 10. So this would cancel and become 10. And I'm just left with 10 times 1, or 10, over 1, which we can just write as 10. So simplifying this, I have 18 plus 15, which is 33, over 25 minus 10, which is 15. Now I'm not done because I always want to report a fraction in its simplest form. I know that there's a common factor of 3 between 33 and 15. right? 33 is 3 times 11. 15 is 3 times 5. So really, if I just divide each by 3, I'm going to end up with 11 over 5, or 11/5 as my final answer. Hello and welcome to Pre-Algebra Lesson 39. In this video, we're going to learn about decimal fractions. All right, so our lesson objectives for today would be to learn how to change a decimal fraction into a decimal. And then also, we want to learn how to change a decimal into a decimal fraction. So basically, we're going to go back and forth between a decimal and a decimal fraction. So before we get started, I want you to think about the very first lesson where we started talking about fractions. What I told you there is that although some of you didn't have any experience with fractions in your math class, you had seen fractions in your everyday life. Every time you and a group of friends get together and you split something up, so if you got together and you split up a pizza, or you split up a cookie, or you split up an apple, or whatever it was, you gained some experience with fractions even though you didn't know it. It's going to be the same thing for decimals, right? So although you might not have seen decimals yet in your math class, you have worked with them in everyday life. One example is that you are absolutely bombarded with decimals every time you go shopping for anything. So let's kind of get started with our lesson with a basic definition. So when we start talking about decimals, kind of the introduction to that would be the decimal fraction. So a decimal fraction is a fraction whose denominator is a power of 10. Let me reread that. A decimal fraction is a fraction whose denominator is a power of 10. So what do we mean by that? The denominator is a power of 10. It means you can take the denominator and rewrite it as 10 raised to a whole number that is 1 or larger. So here are some examples of some decimal fractions. So we have 5/10 here, and you can see that this 10, I could rewrite that as 10 to the power of 1. Here I have 3/100. I can rewrite 100 as 10 to the power of 2. Here we have 700,000ths, and I can rewrite this 100,000 in the denominator as 10 to the 1, 2, 3, 4, 5. There's 5 zeros here, so 10 to the 5th power. So in each case, we have a decimal fraction because the denominator is a power of 10. And again, more specifically, that means that 10 is raised to some whole number that is 1 or larger. So to kind of get our feet wet with decimals, let's kind of run through a typical scenario. So let's suppose you go to the grocery store and encounter a can of tuna priced per can at $1.38. So this is typically how you're going to see decimals. Now, let me just skip the dollar sign real quick and just write 1.38. Now, the first thing I want to draw your attention to, you might not know that this is called a decimal point. This is a decimal point. Now, what's to the left of the decimal point? This 1, this is just a whole number. This is what we've been working with forever. So I'm just going to put that this is a whole amount. A whole amount. And in terms of money, I just have $1 there. Now, this part that occurs after the decimal point, or to the right of the decimal point, is part of a whole. It's part of a whole. Again, we've already seen this with fractions. And if I was to think about $1.38, kind of using fractions, well, okay, $1 is kind of a whole amount. It's a $1 bill. Just think about 38 cents for a minute and how you could relate that in fractional terms. Well, if I had everything in pennies, let's say, it takes 100 pennies to make $1 or one whole amount. So if I only have 38 pennies out of the 100 pennies that are needed, really what I have is I have 38 out of 100, or 38 parts out of the 100 needed to make a whole amount. Remember, when we work with fractions, our denominator is the whole amount split up into equal parts. So this is me taking $1 and just splitting it up into equal parts of 100. That's what would happen if I got $1 in pennies. And then if I only have 38 of those pennies, well, then I have 38 parts out of 100, right? So this 0.38 is the same thing as 38 over 100. So really, we can kind of see already that we can go back and forth and write 1.38 as 1 and 38 hundredths. right? These would actually be the same. Here you have a whole amount, and then you have part of a whole. Here with your mixed number, you have the same thing. You have a whole amount, or your whole number part, and then you have your fractional amount, your part of a whole. You have 38 parts out of 100. So kind of the first thing we're going to learn is how to change to a decimal. So if you're starting out with the decimal fraction, the first thing you're going to do is count the number of zeros in the denominator, and then you're going to delete the denominator. So if I had something like, let's say 56 over 100, I would count 2 zeros. So 2 zeros. And once I have that information, I can just delete the denominator, right? I'm just going to have the number 56 now. And I'm going to have 56, and I'm going to know that I have 2 zeros for that denominator. Then the next thing in the numerator, which is the number 56 that we have, move the decimal point to the left by the number of zeros we counted in the denominator. So again, we had 2 zeros. But some of you at this point might be saying, how do I move the decimal point to the left? I don't know where it is. If you have a whole amount, you can always write a decimal point after the rightmost digit. So I can write 56 as 56 and then a decimal point. And another thing I'm going to teach you is that after this decimal point, you can put as many zeros as you want. You might see some prices in stores look like this. $56, you might see a decimal point with 2 zeros at the end. Or you might see $38 like this. Or $27 like this. After that decimal point, you can put as many zeros as you want, and you're not changing the value of the number. This is still 56, or in this case, since I have a dollar sign, it's still $56. So with that being said, we're going to move our decimal point to the left by the number of zeros we counted in the denominator. We counted 2 zeros, so I'm going to the left 2 places. So we would end up with 0.56. Now another practice that you might get into when you start working with decimals is if you have a decimal point and you don't have a whole number amount, you'll probably put a 0 out in front. This 0 does not change the value of the number. It's just kind of used for clarity, right? So that people, when they're eyeballing it, will say, okay, oh, I have a 0 first. Well, that's a little weird. So that draws their attention to the fact that there's a decimal point so that they don't miss it, right? You don't want to mistake 0.56 or 56. All right, let's look at the first one here. So we have 40 over 100. So again, the first thing I'm going to do is count the number of zeros in the denominator. Again, I have a situation where I have 2. So I have 2 zeros. And then I'm going to delete the denominator. So I don't actually have to do that. I'm just going to write over here, I'm just going to write the numerator without the denominator. So I'm just going to write 40. Then the next step is to move the decimal point by the number of zeros that we counted in the denominator. Again, we counted 2 zeros. So again, I can put my decimal point here after the final digit of 40. And I'm going to move it 2 places to the left. And that's going to give me 0.40. Now I want to draw your attention to something. If I have a 0 right here, it's the same thing as if I erased it and had 0.4. Again, after you have a decimal point, once you have your final non-zero digit, you can add as many zeros as you want. So 0.4 is the same as 0.40000000. Where people get confused is, let's say you have a bunch of zeros, but then you have a non-zero digit involved. Let's say you have a 9 at the end. This is different than 0.4. Those are not the same. If I have all zeros, then it's the same. But if I have something that's not zero that kind of is at the end or even in between, let's say I had a 9 here and then a bunch of zeros, that's still not 0.4, right? You can't have it interrupted in any way. It has to be 0 all the way down. So having said that, we can rewrite this answer as just 0.4. All right, let's take a look at another one. And I'm going to kind of shorten this up a little bit. And one of the things I want you to realize here, and you're going to use this later on in math, when you divide by 10 or some power of 10, and when I say a power of 10, I mean 10 raised to a whole number that's 1 or larger, you move your decimal point 1 place to the left for every 0 in that power of 10. So just forget about your procedure for a second and just say, okay, I have 7 divided by 10. So I'm going to write 7 and I'm going to write my decimal point. I have 1 0 in this power of 10, so that means I'm moving my decimal point 1 place to the left, and I'll end up with 0.7 as my answer. Again, you can still use that procedure. That's kind of a procedure you're going to get in a book. Count the number of zeros you have in the denominator. You have 1 0. Delete the denominator. So I would have just wrote this as 7. And then move the decimal point one place to the left for every 0 that you count in the denominator. So it goes over here. And again, you end up with 0.7. All right, let's look at 85 over 10,000. So again, I'm going to use that kind of shortcut because when we find a shortcut in math, we kind of want to use it. So I'm just going to write 85. And then I'm dividing by 10,000. So this is a power of 10 with 1, 2, 3, 4 zeros. So basically, all I need to do is move my decimal point 4 places to the left. So I put a decimal point after the final digit in 85, and I go 1, 2, and then I see that, what do I do here? I don't have any more places. When that happens, I can put zeros in. So I can put a 0 in here, and then 3, and then 4, and I'm able to complete that. So now I'm going to end up with 0.0085 as my answer. What about 5 and 35 over 1,000? Well, what happens is if you have a mixed number and you're doing this, just take the whole number part and go ahead and just write that. Then we'll follow that with 35 over 1,000 expressed as a decimal. So to do that, I have 35, and basically I'm dividing it by 1,000. So I have 1, 2, 3 zeros in this power of 10, right? 1,000 is basically 10 to the third power. So all I need to do is move the decimal point 1, 2, put a 0 in, 3 places to the left. I'd have 0.035. So if I have 5 and 35 thousandths, then basically I have 5.035. The decimal point with 0.35 after it is 35 thousandths. And then the 5 is just the same. Okay, so now we're going to go backwards, right? We're just going to reverse what we just did. So we're going to be going from a decimal to a decimal fraction. Now, one of the things I want to tell you right away, we're not going to be simplifying here. And the reason is if you want to report something as a decimal fraction, again, the denominator has to be specific. It has to be a power of 10, right? Meaning that it's able to be expressed as 10 raised to a whole number that is 1 or larger. So the first thing we're going to do is write any whole number if you have one. Then you're just going to count the number of decimal places. And basically when we say count the number of decimal places, we're saying that we're counting the number of digits that occur after the decimal point. And these are only digits that are going to add value to the number. So for example, if I have the number 0.38700, I don't have 5 decimal places here. Some people would say, okay, I have 5 decimal places. I don't. I only have 3. These two don't add any value to the number. This is the same thing as 0.387. So I would count 3 decimal places here. So once you know that, you take that decimal part. So that's the part that occurs after the decimal point, and you put it over a denominator that begins with a 1 and is followed by the same number of zeros as decimal places. So for 0.387, basically you write 387 in your numerator, you write a 1 in the denominator, and you follow it by 3 zeros. Right, and that's because we had 3 decimal places here. If I had, let's say, made the mistake of including these 2 zeros here, I would end up putting 5 zeros down here, and I would get an incorrect answer. This is wrong, right? Because these zeros didn't add any value, so I don't have a denominator of 100,000. I would take these away and then just say, okay, I have 3 decimal places, so I'm going to have 1, 2, 3 zeros. This is 387 over 1,000. All right, so we're going to start out with 0.05. And again, this 0 out here to the left of the decimal, that's just for clarity, right? We don't need to do anything with that. So the first thing I'm going to do is I'm going to count the number of decimal places that I have. So after the decimal point, I'm looking to see what I have. I have a 0 and then a 5. So I have 2 decimal places. 2 decimal places. And remember, this 0 matters because it's followed by a 5. If I have 3.00, these zeros do not add any value. But the second I follow that 0 with a non-zero digit, let's say 3.03, this 0 does matter now, So because I have, again, a 5 that follows the 0, this 0 does matter. So we have 2 decimal places. Now, the next thing we want to do is write our decimal part. So that's the part that occurs after the decimal. In this case, that's a 0, 5. And the numerator of the fraction. And we're going to put the denominator of the fraction as a 1, followed by a 0 for every decimal place we have. So we had 2 decimal places, so you get 2 zeros. Now, a couple things here. I don't need to have this 0 in front of the 5 because that adds no value to the number. When you're working with whole numbers, I can always put zeros to the left. So I can put as many zeros to the left. This is still 5. Kind of similar to when I'm working with decimals. I put a decimal point. I can put as many zeros here. It's still 5. What I can't do if I have a whole number, I can't just start adding zeros in. This number is now 5,000. It's not 5 anymore. So the last thing I'm going to draw your attention to is a lot of you will say, okay, well, you can simplify this fraction. It's 1 over 20. Well, yeah, we can, but it's no longer going to be a decimal fraction, right? It's just a regular fraction at that point. And a decimal fraction has a definition where the denominator, again, is a power of 10. So we're going to leave it as 5 over 100. And that's exactly what you're going to do if your teacher says that she wants a decimal fraction, right? Do not simplify it. All right, for the next one, we have 21.34. And again, if we have a whole number part like we have here, we're going to write that first. Now, for the fraction part, I'm going to kind of make this simple. Take the part that occurs after your decimal point, just write it as the numerator. So 34 goes in the numerator. Put your fraction bar, then put a 1, and then you can kind of just mentally look at this and say, okay, I have 1, 2 decimal places, so I know I have 2 zeros. So we get 21 and 34 hundredths as our answer. And it's really, really that simple. You can go through the procedure each time, but after you work 5 or 6 problems, you can kind of just do a lot of this stuff mentally. What about 0.3975? Well, I'm just going to take the decimal part, again, the part that occurs after the decimal point, write that in my numerator, so 3975, or 3,975. For my denominator, I'm going to put a 1, and I'm going to follow that up with a 0 for every decimal place I have. Well, for decimal places, I have 1, 2, 3, 4. So this is going to get 1, 2, 3, 4 zeros, or 10,000 for the denominator. So we get 3,975 over 10,000. Okay, for the last one, we have 4.279. And again, I'm just going to write this whole number here to start. For the fraction part, just take this, your part that occurs after the decimal point, put that in the numerator. I got my fraction bar. I'm going to put a 1 in the denominator. And again, I'm going to follow that up with a 0 for every decimal place that I have. So I have 1, 2, 3 of those guys. So I'm going to put 1, 2, 3 zeros here. And I end up with 4 and 279 over 1,000. Or I could say 4 and 279 thousandths. Hello and welcome to Pre-Algebra Lesson 40. In this video, we're going to learn about comparing and rounding decimals. So the lesson objectives for today, we want to learn the place values to the right of the decimal point. We also want to learn how to compare 2 or more decimals and determine their rank. And then finally, we want to learn how to round decimals. So in our last lesson, we introduced decimal fractions. And then we learned how to go back and forth between decimal fractions and a number that has a decimal point. So in this lesson, we'll dig a little bit deeper into decimals before we move on and start doing some operations with decimals. So the first thing I want to show you is an expanded place value chart. So kind of in our very first lesson where we learned about place value, we saw everything to the left of the decimal point, right? We have the ones, the tens, the hundreds, the thousands. As we move to the left, remember each place, if I think about the ones place as starting with a 1, every time I go to the left, I just multiply by 10 to get to that next place. So 1 times 10 gives me 10. Now I'm in the tens place. 10 times 10 gives me 100. Now I'm in the hundreds place. 100 times 10 gives me 1,000. Now I'm in the thousands place. And so on and so forth. That pattern would continue forever. Now that we have a decimal point involved, we have some place values that go to the right of the decimal point that we need to become familiar with. So the first thing immediately to the right of the decimal point is the tenths. And I got a lot of students that will guess that this place is called the oneths, right? Because this is the ones,
the tens, the hundreds. And you have a similar pattern over here. It's just you don't have a oneths place, right? You start off with the tenths place. And I'm going to explain why in a second. So you have the tenths, the hundredths, the thousandths. Then you have the 10 thousandths, the 100 thousandths, the millionths, the 10 millionths, the 100 millionths, the billionths, so on and so forth. And that continues in a usual way, right? After billionths, you'd have 10 billionths, 100 billionths, trillions, so on and so forth. Now, one of the things I want to show you right away, and just following this pattern that I just demonstrated, again, if you start off right here in the ones place, you have the number 1. I know that if I go to the left, I multiply by 10. So if I go this way, I multiply by 10, so times 10, and I get to the tens place. 1 times 10 is 10. Multiply times 10 again, go this way, get to 100. But if I was to go backwards and go to the right, really I could think about starting out at 100, dividing by 10 to get to 10. So to go this way, just think about dividing by 10. Another way to think about dividing by 10 is multiplying by 1/10, right? We learned about how division and multiplication are related. If I have 100 divided by 10, it's the same thing as if I said, what is 100 times 1/10, right? That's 100 divided by 10. Either way, it's the same thing. So what I'm going to show you here is that as you keep going to the right, so as we move from here to here, again, we're dividing by 10 or multiplying by 1/10, dividing by 10. So when we get to 1, let me just erase everything to this point. When we get to 1 and we pass over the decimal point, it's no different. So think about having 1 and multiplying by 1/10. Well, 1 times 1/10 is 1/10. So that's how we get to the tenths. Then if I multiply 1/10 times 1/10, I get to 1/100. And that's the hundredths place. Do it again. 1/100 times 1/10 is 1/1000. That's the thousandths place. So as I'm going to the right, I'm multiplying by 1/10, or I'm dividing by 10. Again, either way you want to think about that. As I'm going to the left, I'm multiplying by 10. So if I take 1/1000 and I multiply by 10, I'd get to 1/100. If I did that again, I'd get to 1/10. If I did that again, I'd get to 1, right? I'd pass over my decimal point. I'd be at 1, then 10, then 100, then 1,000, so on and so forth. So although you might not memorize the names right away, you can kind of put it together by just using this pattern. All right, so we're going to do a quick little exercise similar to when we worked with place values for whole numbers. We just want to state the place value for each digit. And let's start out with this number 0.175. And this 0 is just for clarity. I can put it in the ones place, but really there's no point. I'm just thinking about these numbers that occur after the decimal point. So let's fill in our place value chart. I have a 1 that will go in my tenths place. Let me kind of make that a little better. I have a 7 that's going to go in my hundredths place. And I have a 5 that's going to go in my thousandths place. And so remember, if you have 0.175, you could write this as a decimal fraction as 175 over, you have a 1 followed by 3 zeros, right? Because you have 3 decimal places. 1, 2, 3. And look at your bottom number. It's 1,000. Look at your rightmost digit of this number. It's in the thousandths place. So now, having said that, let's go ahead and label everything. So the 1 is going to be in the tenths place, the tenths place. And notice how everything after the decimal point has a THS, right? So you have 10 and then you put a THS, 100 and then you put a THS, 1,000 and then a THS, you know, so on and so forth. Then for 7, that's going to be in the hundredths place, hundredths. And then lastly, we have a 5 that's in the thousandths place. The thousandths place. All right, let's take a look at the next one. So we have 3.128. So the 3 is obviously in the ones place. Then we have our decimal point. And then we have a 1 in the tenths place, a 2 in the hundredths place, and then an 8 in the thousandths place. All right, so let's label this. So 3 again is in the ones place. Of course, we know that position already. And the 1 is in the tenths The 2 is in the hundredths. Hundredths. And then finally, the 8 is in the thousandths. The thousandths. All right, we have a really long number now. So we have 15.77201,958. So 15, here's your decimal point. You have 77201,958. Now, I want you to notice something. Again, I want to draw your attention to the fact that the rightmost digit here is in the 100 millionths place. So what that means is that, just thinking about pure numbers, forget about the this part of this number. If I have 100 million, it looks like this. So what that tells me is that my denominator here, if I was to write this part, just the part that occurs after the decimal point, as a fraction, the denominator would be 100 million. All right, I can take this off now. And then go ahead and put a fraction bar. The top part would be 77201,958, or the number 77,201,958. And again, if you follow your official procedure, you'll get the same answer. You would write this part right here as your numerator, and then you'd put a 1 followed by a 0 for every decimal place. We have 1, 2, 3, 4, 5, 6, 7, 8. And I have 1, 2, 3, 4, 5, 6, 7, 8 zeros. So that does match up. And of course, if we were to write this number, it does have a 15 out here as a whole number. So I would need to put a whole number part. Let me just kind of scoot this over a little bit. And then I could write 15 and 77,201,958 100 millionths. Okay, that's how you would say that. All right, but let's get back to what we're doing. And of course, we want to label the parts of the number. And I don't even know if I can fit this on the screen, but I'm going to try my best. So the 1 is in the tens place. This is the tens. The 5 is in the ones. The 7 is in the tenths. The tenths. This 7 up here is in the hundredths. Hundredths. Then we have a 2 that's going to be in the thousandths. Then my 0, let me draw an arrow over here. This is going to be in the 10 hyphen thousandths. And then my next number, which is this 1 here, that is going to be in the 100 hyphen thousandths. Then I have this 9 that's going to be the millionths. Then I have the 5. The 5 is going to be in the 10. Put a hyphen and then millionths. And then finally I have this 8, and that 8 is going to be in the 100. The 100 hyphen millionths. Millionths. So if you're already really good with working with place value for whole numbers, learning this will be really quite easy because everything is very similar. It's just a simple fact that at the end, you put a THS. You just put a THS. So you're going in a familiar way. If you can just remember that as you move to the right, you are basically multiplying by 1/10 or dividing by 10. You can go through and say, okay, if I have something in the tenths place, you can think about just 1 over 10. To figure out what the next place over is, just multiply by 1 over 10, and you'd end up with 1 over 100. So you could say, okay, I'm in the hundredths place now. All right, so the next topic we're going to talk about is something that students kind of struggle with. So we want to know, how can we compare the size of 2 or more decimals? So we're going to kind of think about how to do this through a practice exercise. We want to replace each question mark with the less than or greater than symbol. And for the first problem we're going to look at, we have 0.285 question mark 0.287. So you're looking at these two numbers, and it's not completely obvious right away which one is bigger. It's not like if we looked at 13 and let's say 5. I know 13 is bigger than 5 right away. For these two, you might struggle a little bit. So what I want you to do is just stack the numbers on top of each other. So you have 0.285 and 0.287.
and just line everything up by place value. So this decimal point is going to line up with this decimal point. You have the tenths that are in line, the hundredths, the thousandths, and if you had more digits, it'd be so on and so forth. Now what I'm going to do is I'm going to start at the very left of each number, and I'm going to compare digits that have the same place value. So these zeros are irrelevant. I just kind of move on. I'm going to look at this 2 and this 2. Now those numbers are the exact same, so I'm just going to move to the right. I have an 8 and an 8. Those numbers are the same, so I'm going to move to the right. Now I have something different. I have a 5 and I have a 7. Now we all know that 7 is greater than 5, so that tells me that the number that has the 7 is the bigger number. So basically what you're doing is you're just moving to the right until you find corresponding digits that are different. The digit that's larger is going to belong to the bigger number. So for this relationship here, the number 0.287 is bigger, so I would put a less than sign in here, right, to replace that question mark. Let's go ahead and officially do that. We'll put that 0.285 is less than or smaller than 0.287. And again, that's because this 5 here, that's in the thousandths place, is smaller than this 7 that's in the thousandths place for this number. But again, up to that point, they look identical. Let's look at another one. We have 12.9251. We have a question mark and then 12.9051. So again, these numbers look kind of similar. So stack them on top of each other. So we'll have 12.9251 and 12.9051. And when you have some whole number parts involved, you have to line those up as well. The key here is you want to think about lining up the decimal point. When you do that, everything else is going to take care of itself, right? I have the tens places lined up, the ones, the tenths, the hundredths, the thousandths, the 10,000ths. And again, if I had more digits, it would go so on and so forth. All right, so we're going to start all the way at the left. And one thing you have to make sure of is that these numbers have the same number of digits. So if I had something like 112.9051 and 12.9251, obviously this one's bigger, right? Because it has another digit to the left. But that's not the case here. We have 12 and we have 12. So that part is the same. So we're going to move on past this decimal. We have 9 and 9, and then we have 2 and 0. So once I see something that's different, again, whichever is the larger digit belongs to the larger number. So this number is going to be bigger because 2 is greater than 0, right? And those numbers are in the same position. So that tells me that 12.9251 is going to be greater than 12.9051. And again, the reason for that is everything is identical until we get to this 2. This 2 that's in the hundredths place is bigger than this 0 that's in the hundredths place for that number. For the next one, we have 0.00535051, question mark 0.00500000. Now, one thing you might notice right away, remember in the last lesson I taught you that when you have a decimal point, after your final non-zero digit, the zeros after it do not add any value. I can delete these zeros and it would be the same as 0.005. These two would be the same value whether I put the zeros on it or not, right? After your last non-zero digit, you can put as many zeros after it as you want. You're not changing the value of the number. So with that being said, let's compare our two decimals. So we have 0.005351 and 0. Again, lining up the decimal points, 0.05000. So everything is the same until we get to this right here. We have a 3 here and a 0 here. The digit that's larger, 3 is greater than 0. So that tells me that this number right here is going to be the larger number. So we can go ahead and say that 0.0053051 is larger than 0.00, and I can just put 5 here. I don't need to add these zeros at the end. You can do it if it makes you feel more comfortable, but it's the exact same number. All right, let's take a look at one final one. We have 15.489146, question mark, 15.489276. So again, I'm just going to stack the numbers on top of each other. 15.489146, 15.489276. And at this point, you can kind of just start eyeballing things. I can see that everything is the same going down until I get right here. And let me highlight that in light blue. So I have a 1 and I have a 2. 2 is larger, right? 2 is greater than 1. So that tells me that this number right here is going to be bigger. Let me just kind of erase that. This is going to be the bigger number. And so that number is over here. So I would put that 15.489146 is less than 15.489276. And the reason for that is my digit in the 10,000ths place, and this number is a 1. My digit in the 10,000ths place, and this number is a 2. 2 is greater than 1, so that means this number is the larger number. So the last thing we're going to talk about is rounding decimals. And basically, it's the exact same procedure as you used for rounding whole numbers. There's one slight difference, though. And as we're working through the problem, I'm going to explain that to you and why it makes sense. So we want to round 26.13 to the nearest tenth. So the procedure, again, starts out the same. So you have 26.13. So find the digit in the round-off place. So where's the tenths place? That's right here. So this is my digit in the round-off place. That's a 1. Then I look one digit to the right. That's this 3. And you look for the rule, right? The rule is if it's 4 or less, okay, 4 or less, you leave the digit in the round-off place unchanged. If it's 5 or greater, you add 1 to the digit in the round-off place. Now, this falls in the category of 4 or less, so I'm going to leave 1 unchanged. Now, when we round whole numbers, we're told that we replace everything after the round-off place digit with a 0. When you're working with decimals, they're just going to tell you to cut everything off after the round-off place digit. And why does that make sense? Well, if I had followed my procedure for whole numbers, I would have put a 0 here, and that 0 doesn't add any value to the number, so I can just get rid of it. It's different than if I was rounding 2,613. Let's say I wanted to round this number to the nearest 10. Well, this is the round-off place. I would look at 3. 3 falls in the category of 4 or less. So I would keep 1 unchanged, and I would change 3 into a 0. In this case, the 0 adds value to the number, right? The number 0 at the end makes it 2,610. If I just erased it, I'd only have 261. Well, it's not the same when you're working with decimals. If I have 26.10 or if I have 26.1, it's the exact same number. All right, let's take a look at another one. We want to round 572.91557 to the nearest hundredth. So 572.91557, again, to the nearest hundredth. So where's the hundredths place? This is the tenths place. Here's your hundredths place. And again, if you forget where your places are, either kind of work with a place value chart, or, again, knowing that this is the tenths, or 1 over 10, I can then move to the right by multiplying by 1 over 10. And 10 times 10 is 100, so I know I would get to 1 over 100, or I'm in the hundredths place. All right, so now that we're in the hundredths place, we look at the digit immediately to the right. That's a 5, so that falls in the category of 5 or greater. So that means I'm adding 1 to the digit in the round-off place. So I'm going to have 572.9, 1 plus 1 is 2. And then again, I would replace all of these with zeros, but they don't add any value to the number, so I just leave them off. Right? I can just not put anything else after that too. So my final answer here would be 572.92. Okay, let's take a look at one final problem. We want to round 0.8579135612 to the nearest millionth. So let's rewrite this long number, 0.8579135612. So where's the millionths place? Again, we have the tenths. Once we know that spot, you can kind of just go in a familiar way. Tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths. So here's your millionths place. This is the millionths place. All right, so once we find the digit in the round off place, we look at the digit to the right of it. In this case, it's a 5. 5 is in the category of 5 or greater. So I'm going to add 1 to that 3. It's going to become a 4. So I would have 0.857914. And again, when we round whole numbers, at this point, everything after it becomes a 0. The zeros here, if I change everything to a 0, I'm not changing the value of the number. So I can just delete them, right? I don't need to write that step because, again, 0.857914 is the same as 0.857914, 0, 0, 0, 0, 0. Right? I don't need to put those 5 zeros there. They add no value to the number. Hello and welcome to Pre-Algebra Lesson 41. In this video, we're going to learn about adding and subtracting decimals. All right, for the lesson objective for today, we want to learn how to add and subtract decimals. And this is something where we can kind of just jump right in. It's really easy to add and subtract decimals, especially if you've already mastered vertical addition and vertical subtraction. So to add or subtract decimals, basically all we want to do is write the numbers vertically and line up the decimal points. So you recall when we did multi-digit addition or multi-digit subtraction, meaning vertical addition or vertical subtraction with whole numbers, we stacked the numbers on top of each other and we line them up by place value. Well, it's no different here. We just need to make sure that we line up the decimal points when we stack our numbers on top of each other. The next thing we want to do is bring the decimal point directly down into the answer. So just go straight down, don't deviate. Then lastly, we're going to add or subtract starting with the rightmost column and working your way to the left. So just like we did, again, with vertical addition or vertical subtraction. So for the first problem, we have 0.17, which is basically 0.17, plus 0.3, which is 0.3. Remember, these zeros here don't add any value to the number. We just kind of write them to make it clear that we have some decimal points. So I can just write 0.17 on top of 0.3 and put my addition sign out here and my horizontal line, and I am ready to add. Now, for some people, it makes them more comfortable to have the same number of digits when they're adding. So remember that if you have something like 0.3 or 0.30, it still has a value of 0.3, right? After a decimal point, when I have a non-zero number, like 3, after that number, I can put as many zeros as I want, and I won't change the value. So I could keep putting zeros if I want. It's still going to be 0.3. So with that being said, I can write a 0 in here, and then I can start my addition. Remember, we always start at the rightmost column, and we work to the left. So I would do 7 plus 0, that's 7. Then move to the left, 1 plus 3 is 4. And then I told you in the lesson to bring this down to start. It really doesn't matter when you do it. It's just a matter of remembering to do it. And when you first kind of start working with decimals, sometimes people will forget. They'll just go, okay, the answer is 47. Just make sure that at some point in this procedure, you bring that decimal point straight down into your answer. And so we're going to end up with 0.47. Or again, for clarity, if we want to, we can write 0.47, right? There's no change in the value of that number. All right, for the next one, we have 72.65 minus 31.521. So again, you're just going to stack these numbers on top of each other. So 72.65, that has to go on top because remember, with subtraction, it's not commutative. And then on the bottom, you're going to have 31 point, notice how I'm lining up the decimal points, 521. Okay, so I'm going to write a horizontal line and then my subtraction symbol, and now I'm ready to go. Well, let me go ahead and put the decimal point down. And again, you can do this at any time. I know in the procedure I put that you do it before you start your operation. Really, it doesn't matter. Just remember to do it. Now, when we start in our rightmost column, you're going to find that you have a problem. If I was doing addition here, if I change this to addition, I can just go ahead and bring down the 1. Say, okay, I have a 1 there, and keep going. With subtraction, I need to have something that I can take 1 away from, right? So I need something minus 1. Well, remember, I can put a 0 at the end here and not change the value of the number. And I can't do 0 minus 1 without getting a negative. So what I would do is I would just borrow. So I'd borrow from this 5. This would become 4. This would become 10. And now I can do 10 minus 1. That's going to give me 9. 4 minus 2 would give me 2. 6 minus 5 would give me 1. 2 minus 1 would give me 1. And then 7 minus 3 would give me 4. Now, since I already put my decimal point down there, I really don't need to think about it again. I can just write this number as my answer. It's 41.129. All right, now we're going to look at some addition with 3 numbers involved. So we have 0.8274 plus 3.6 plus 12.007. Again, just stack the numbers on top of each other. Just make sure you line up the decimal points. So I'm going to put 0.8274. I'm going to put 3.6. And then I'm going to have 12.007. Now, this is one of the situations where you might want to put some zeros in so that you have the same number of digits for everything after the decimal point. So I can put 3 zeros in here and a 0 here. Again, I'm not changing the value of the number. So when I start my addition problem, again, I'm going to put this down here now to start so I don't forget. I have 4 plus 0, that's 4. I have 7 plus 0 plus 7, that's 14. So put a 4 down and carry the 1. Again, just like you would if you were adding some whole numbers. Then I have 1 plus 2, that's 3. Plus 0, that's still 3. Then I have 8 plus 6, that's 14. Plus 0 is still 14. So put a 4 down, carry the 1. 1 plus 3 is 4. 4 plus 2 is 6. And I can just bring down that 1. So I get 16.4344. So let's write this up here. 16.4344. So what if we have some negatives involved? Well, really, we just kind of use the rules that we used when we added integers together. Just figure out what the sign's going to be first. So we have a negative plus another negative. That's going to give me a negative. And then we can kind of just work with the absolute values. So I can think about 6.13 plus 7.85. So now I would just start in the rightmost column and work my way to the left. 3 plus 5 is 8. 1 plus 8 is 9. And 6 plus 7 is 13. And again, notice how I forgot to bring my decimal point down. So if I wrote 1,398, obviously I would get the wrong answer. So you got to make sure that you bring this down at some point and put it there to where we know we have 13.98 as the answer. Now drag this back up here and put it next to that negative to say we have negative 13.98 as our answer. All right, for the next one I have negative 7.21 plus 3.64. So just think about the fact that if I was adding negative 7 and 3, what would I do here? Well, again, I would use the sign from the number with the larger absolute value. If I kind of get rid of this negative here and think about both numbers as if they were positive, 7.21 would be larger. So we're going to use its sign, right? Its sign is negative. And now we're going to do a subtraction. We're going to take 7.21 and we're going to subtract away 3.64. And let me go ahead and just write this down here before I start so I don't forget like I did in the last problem. So we'll borrow from the 2. It will become a 1. This will become 11. 11 minus 4 is 7. Then I'd have 1 minus 6. I need to borrow again. So borrow from the 7. This becomes 6. This becomes 11. 11 minus 6 is now 5. And then 6 minus 3 is 3. So we get 3.57. Drag that up there and attach the negative to it. And my answer is going to be negative 3.57. Okay, for the next one we have 128.209 minus 34.55813. So again, just stack the numbers on top of each other. Because it's subtraction, this 128.209 has to go on top, and then 34.55813 is going to go on the bottom. Put my minus sign out here and my horizontal line, and I'm going to bring down my decimal point. Now again, we have a problem because when we go to start subtracting in the rightmost column, I don't have anything to subtract 3 away from. Again, when you have this situation Remember, you can put zeros here to kind of fill in these spaces. You're not adding any value to the number, right? It's the same number as it was. And now I can go through and borrow. But I have to go and borrow from the 9. 9 becomes 8. This is going to become 10. Then I'll borrow from the 10. 10 becomes 9. And this 0 becomes 10. So now I can start cranking this out. 10 minus 3 is going to give me 7. 9 minus 1 is going to give me 8. 8 minus 8 is going to give me 0. Now I have 0 minus 5, so I need to borrow. So I'm going to cross this 2 out and put a 1. This 0 will become 10. 10 minus 5 will give me 5. And now I have a 1 over here, so I need to borrow again. This 8 will become 7. This 1 will become 11. 11 minus 5 is 6. Then I'll have 7 minus 4, that's 3. I need to borrow 1 last time. So I'll borrow from the 1, it will become 0. This will become 12. 12 minus 3 is 9. So we end up with 93.65087. So 93.65087. All right, now we have addition and subtraction mixed. So I have 0.685 plus 0.312 minus 5.24 minus a negative 7.035. So the first thing I want you to do is just rewrite this. We have 0.685 plus 0.312 minus 5.24. Minus a negative is plus a positive. So I'm going to put plus positive 7.035. So even though we're not working with integers anymore, we have some decimals involved, the same rules are going to apply. If I'm subtracting away a negative, I'm adding a positive. So I'm just going to work left to right here. And I'm going to start out with 0.685 plus 0.312. Bring down the decimal point. 5 plus 2 is 7. 8 plus 1 is 9. 6 plus 3 is 9. So we get 0.997. So I'm going to put equals 0.997. Let me just put a 0 out here just for clarity. So that took care of those two. And then I'm subtracting away 5.24, and I'm adding 7.035. So the next thing I'm going to do is 0.997 minus 5.24. So let me write this over here. 5.24. So because this is going to result in a negative when I do this subtraction, kind of the easy way to do this would be to reorder everything. Just think about having 0.997 plus a negative 5.24. What would we do in this situation? Well, we know that the answer would be negative. And then what we do is we would just think about the absolute values for a second. Then we would subtract 5.24 minus 0.997. So I'm going to put a 0 here to start. Again, that doesn't add any value to the number. And I'm going to borrow from this 4. This will become 3. And then this is going to become 10. 10 minus 7 is 3. I have a 3 minus 9, so I need to borrow again. So I'm going to borrow from the 2. It becomes 1. This becomes 13. 13 minus 9 is 4. Then I have 1 minus 9. I need to borrow again. This becomes 11. 11 minus 9 is 2. Again, I forgot to bring down my decimal point when I started. But again, as long as you remember to do it, at some point, you'll be okay. Then lastly, I have the 4. Nothing to subtract away, so I just bring it down. And I've got 4.243. Now remember, this is negative. I already wrote my negative sign out here. So I'm going to have a negative 4.243. Okay, so there's one more operation to carry out here. And I'm just going to be adding to this 7.035. So negative plus positive, again, we think about what the sign's going to be. And 7.035 is bigger in terms of its absolute value than this negative 4.243. So our answer is going to be positive. And now we just need to subtract. So I'm going to do 7.035 minus 4.243. So 5 minus 3 is 2. So now I want to do 3 minus 4, and I need to borrow. I can't borrow from the 0, so I got to go to this 7. 7 becomes 6. The 0 becomes 10. Then 9. Then finally this 3 becomes 13. 13 minus 4 is 9. Then I'm going to have 9 minus 2, that's 7. And again, I forgot to bring down my decimal point when I started. And so I bring it down now. And then I'll have 6 minus 4, that's 2. So I'm going to get a positive 2.792. So again, when you're adding and subtracting decimals, it's not really any more difficult than when you were just performing vertical addition or vertical subtraction with whole numbers. A couple of things we sprinkled in here, some negatives and some situations where we had to, write some zeros in, but nothing that's really too complicated. Hello and welcome to Pre-Algebra Lesson 42. In this video, we're going to learn about multiplying decimals. So our lesson objective for today is just to learn how to multiply decimals. So before we get started, I just want to mention that multiplying decimals is no more difficult than multiplying whole numbers. If you've already mastered multi-digit multiplication, meaning vertical multiplication, then basically at this point you can already multiply decimals. There's just one additional step that you're going to have to deal with, and that's going to be where you're going to put your decimal point at. So here we go, multiplying decimals. The first thing we want to do, we want to ignore any decimal points and multiply the resulting numbers. So essentially what I'm saying here is that you're going to pretend like your numbers are whole numbers. So if I had something like 5.5 times 3.7, I would start out by pretending I had 55 times 37. Right? I would find the answer for that. Now in the next step, I want to move the decimal point in the answer. And when I say the answer, I mean the answer to the multiplication I just got where I was using whole numbers. So I want to move this to the left by the number of decimal places between all factors. Okay, so between all factors. So let's jump in and look at an example. So we're going to begin today with 5.15 times 0.32. So I'm going to start out, I'm going to ignore any decimal points that I have. And so this number here will be 515. Just going to treat it like it's a whole number. And this number here will be 32. And I just find this product first, and then I'll figure out where to put the decimal point. So 2 times 5 is 10. 0 down, carry the 1. 2 times 1 is 2, plus 1 is 3. 2 times 5 is 10. Okay, I'm going to erase this. And remember, we're moving to the left here, because we're starting over here in the tens place now. 3 times 5 is 15. 5 down, carry a 1. 3 times 1 is 3, plus 1 is 4. And then 3 times 5 is 15. And so now we're going to add. Go ahead and bring down this 0. 3 plus 5 is 8. 0 plus 4 is 4. 1 plus 5 is 6. And then bring down that 1. So what I get is 16,480. But that's obviously not my answer because I haven't figured out where to put the decimal point yet. So just go ahead and come up here, drag this up, 16480. And now we're going to figure out where to put the decimal point at. Now what I told you is that we're going to move the decimal point to the left by the number of decimal places we have between all the factors. So if I look at these two factors here, in 5.15, I have 2 decimal places, 2 decimal places. And in 0.32, I also have 2 decimal places. Okay, we're talking about what's after that decimal point, right? Here I have 2, and here I have 2. So if I combine those two, 2 plus 2 is 4. So between all of the factors here, we have 4 decimal places. So that tells me we're going to have to move our decimal point 4 places to the left. Now, when we don't have a visible decimal point, like in a whole number like we have here, we can always write one at the very end of the number, so at the very right part of the number. And now I'm free to move my decimal point 4 places to the left. So I'm going to go 1, 2, 3, 4 places to the left. So my decimal point is going to go right there. And we have an answer that's 1.6480. But remember, I don't need this 0 here. I can erase it because that 0 does not add any value to the number. After your decimal point, or to the right of the decimal point, after your final non-zero digit, you can add as many zeros as you want. So I could put 0, 0, 0, 0, 0. It's still 1.648, right? These zeros do not change the value of the number at all. All right, so again, our final answer here will be 1.648. Okay, for the next one, we have 0.00153
times 2.71. So again, I'm going to ignore the decimal points, and I'm going to pretend like I had 153 times 271. And I just multiply. So 1 times 3 is 3, 1 times 5 is 5, and 1 times 1 is 1. Now I'm going to the tens place, so I need to move to the left in my answer. 7 times 3 is 21. Put a 1 down, carry the 2. 7 times 5 is 35, plus 2 is 37. 7 down, carry the 3. 7 times 1 is 7, plus 3 is 10. And move over one more time. We're going to the hundreds place. 2 times 3 is 6. 2 times 5 is 10. 0 down, carry the 1. 2 times 1 is 2, plus 1 is 3. All right, so let's add now. Get rid of these arrows, bring down the 3. 5 plus 1 is 6. 1 plus 7 is 8, plus 6 is 14. 4 down, carry the 1. 1 plus 0 is 1. And then 1 plus 3 is 4. So we end up with 41,463. But again, that's not our answer, right? We can just drag this up to the top here. And just to get a little room going, I'm just going to erase this. So again, it was 41,463. My next step is to figure out where I'm going to put the decimal point in this number. If I look between the two factors here, I need to count how many decimal places I have. In this number, I have 1, 2, 3, 4, 5 decimal places, right? 5 decimal places. In this number over here, I have 2. 1, 2 decimal places. So between all the factors, or between both factors, I have 5 plus 2, or 7 decimal places. So that tells me I need to move my decimal point 7 places to the left. Let me erase this real quick. And we'll put a visible decimal point to the right of that 3. Remember, if you have a whole number, you can just put it at the end of the whole number. And we're going to move the decimal point 7 places to the left. So 1, 2, 3, 4, 5. And do I stop now? No, I put some zeros in, right? So I put a 0 in here so that I can do 6. And then one more 0 so that I can do 7. And so I put my decimal point there. I can erase all this at this point and say that my answer is 0.0041463. All right, let's take a look at one with a negative involved. So we have negative 3.01 times 1.8. So remember, when we worked with integers, we learned that a negative times a positive is a negative. The rules are the same for all real numbers. So when you come across a negative times a positive, you're always going to get a negative. Doesn't matter if you're multiplying fractions or decimals or whole numbers or integers. Whatever you're doing, negative times positive is negative. Now, once we figure out the sign, remember, we can just work with the absolute value. So I could just pretend like I had positive 3.01 times positive 1.8. And when we multiply decimals, remember, the first step is just to ignore the decimal point and pretend like we had whole numbers. So 301 times 18. So 8 times 1 is 8. 8 times 0 is 0. 8 times 3 is 24. Now we're moving to the left because we're going to the tens place. We're doing 1 times 301. That's 301. So I'm going to write a 1, a 0, and a 3. And now we're going to add. So just bring down this 8. 0 plus 1 is 1. 4 plus 0 is 4. 2 plus 3 is 5. So I get 5,418. And again, this is not my answer. I'll write this up here next to this negative, 5,418. And I can go ahead and erase this now. And let's just figure out where we're going to put our decimal point at. Again, I'm looking for how many decimal places I have between the factors. So here I have 2 decimal places. 2 decimal places. Here I have 1 decimal place. So what that means is that between all the factors, or between both factors here, I have 3 decimal places. So my decimal point is going to go 3 places to the left. So I'm going to put it right there to start. And then I'm going 1, 2, 3 places to the left. So I'm going to end up with negative, okay, don't forget the negative out here, 5.418 as my answer. Okay, let's take a look at one final problem, and then we'll kind of jump into a section where we'll talk about multiplying by 10 or power of 10. something that's going to help you speed up your multiplication. All right, so we have negative 19.06 times 0.0051 times negative 2.02. Now, what we're looking at here is we have a negative times a positive times a negative. Now, we know from working with integers that if we multiply more than two numbers and we have an even number of negatives, we're going to get a positive result, right? Each pair of negatives makes a positive. So I'm just going to go ahead and write that the answer is going to be positive. And now we can just think about these numbers as if they were all positive, right? We just think about the absolute values. Now, the next thing we want to do is multiply any of the two numbers together. And so I'm going to start out with 19.06 times 0.0051. So to do that, I'm going to pretend this is 1,906 times 51. So 1 times 1,906 is 1,906. Then I'm moving to the left here, so I move to the left when I put my answer down. 5 times 6 is 30. 0 down, carry the 3. 5 times 0 is 0, plus 3 is 3. 5 times 9 is 45. Put a 5 down, carry the 4. 5 times 1 is 5, plus 4 is 9. So now let's add. Bring down the 6. 0 plus 0 is 0. 9 plus 3 is 12. 2 down, carry the 1. 1 plus 1 is 2, plus 5 is 7. Bring down the 9. So I get 97,206. So let me write that here, 97,206. Now, at this point, you can figure out where the decimal point would be based on these two right here, or you can keep going and multiply this number times this number here as if it was 202. Now, both ways will work. I think it's a little faster if we just figure out where the decimal point is going to be in the end. So let's go ahead and do that. So I'm going to think that I have 97,206 times 202 for right now. Okay, so 97,206 times 202. And once we figure this out, we're going to put our answer here. We're going to go back and figure out where the decimal point should be. So 2 times 6 is 12. Put a 2 down, carry the 1. 2 times 0 is 0, plus 1 is 1. 2 times 2 is 4. 2 times 7 is 14. 4 down, carry the 1. 2 times 9 is 18, plus 1 is 19. Now I know 0 times anything is 0, so that would have started here. I'll just put 1 0 there. Then we're going to the 2. 2's in the hundreds place, so I'm moving over one more time. My answer is going to start there. 2 times 6 is 12. 2 down, carry the 1. 2 times 0 is 0, plus 1 is 1. 2 times 2 is 4. 2 times 7 is 14. Put a 4 down, carry the 1. Then lastly, 2 times 9 is 18, plus 1 is 19. So now we're going to add. Go ahead and bring down the 2. 1 plus 0 is 1. 4 plus 2 is 6. 4 plus 1 is 5. 9 plus 4 is 13. Put a 3 down, carry the 1. 1 plus 1 is 2, plus 4 is 6. Bring down the 9, bring down the 1. So we end up with 19,635,612. So let's erase this, and we're going to write that up top. So now we want to just figure out where our decimal point should be in this answer. So to do that, we count the total number of decimal places between all of the factors. So if I come here, I have 2 decimal places. So 2 decimal places. Here I have 1, 2, 3, 4. So 4 decimal places. And here again I have 2 decimal places. So 2 plus 4 is 6. 6 plus 2 is 8. So that means I need to move my decimal point 8 places to the left. So I'm going to start it right here. And let me kind of make this number a little bit straighter. So again, put the decimal point here. And we're going 8 places to the left. So 1, 2, 3, 4, 5, 6, 7, and finally 8. So that decimal point is going to go out in front. And we have 0.19635612 as our final answer. So for this next section, I want to talk a little bit about multiplying by 10 or a power of 10. And when I say power of 10, let me just explain that I'm talking about an exponent on 10 that's going to be a whole number that's 1 or larger. So for example, you'd have something like 10
to the first power, which is just 10. 10 squared, which is 100. 10 cubed, which is 1,000. 10 to the fourth power, which is 10,000. 10 to the fifth power, so on and so forth, right? I'm not talking about raising it to 10 to the power of -4, right? I'm only including these values here. So for the trick, essentially what you're going to do is you're going to move your decimal point one place to the right for every 0 in the power of 10. So let me give you something to start with that you're already familiar with. Let's say you had the number 5 and you multiply it by 10. Well, we already know that this is 50. But one of the ways you can figure this out is you can put a decimal point behind 5, right? You can do that with a whole number. And I can put a 0 behind that decimal point, perfectly legal. If I'm multiplying by 10, really all I need to do is take that decimal point and move it to the right one place, because there's 1 0 here. So that tells me that the answer is 50. If I took 5.0 and multiplied it by 100, okay, by 100, there's 2 zeros in 100, so 5.0, move this 1, put another 0 in, 2 places to the right, and I'd get 500. I could do the same thing with 1,000 or 10,000, so on and so forth. Now, really 100 is just 10 squared. So I could replace this 100 with 10 squared if I want. And I know that if the exponent is a 2, I'm going to have a 1 followed by 2 zeros, right? So it's 1 followed by 2 zeros. This tells me how many zeros I'll have. So without even converting 10 squared to 100, I know I just take 5.0 and move that decimal point 2 places to the right to get 500. And so if I ran across something like 5.0 times 10 to the 9th power, I know I would do 5 point, and then I would basically just move this 9 places to the right. So let's do that. Go 1, 2, 3, 4, 5, 6, 7, 8, 9. So because this is all the way out there, I'm going to use some commas now. And we'd end up with the number 5 billion. All right, so let's try some basic ones here. We have 0.015 times 10. So I'm going to take this decimal point and move it one place to the right. And so I'd end up with what? I would end up with 0.15, or I could put a 0 out in front. I have 0.15 in that case. What about in the case of 0.015, same number as above, times 10 squared? Well, really all I need to do is move this one place to the right from here because I have one additional 0. Here I have 1 0, here I have 2, right? I can just look at the exponent. So I can take this number, 0.15 basically, move it one place to the right, and I'd have 1.5. Or you can do it from here and just say, okay, I have 2 places to move my decimal. And again, I get 1.5. In this case, I'm moving the decimal 4 places to the right. Right? I'm multiplying by 10 to the 4th power. There's going to be 4 zeros in that power of 10. So what I want to do is go 1, 2, 3, add a 0, and then finally 4. So that's going to give me 150 or 150, right? Because if I kept this 0 out in front, it would add no value to the number. 0150 is the same thing as 150, right? So that's how we would read that number. Here's an example where this would really come in handy. Let's say you get this on a test. Negative 23.2815 times 0.001 times 10 squared. If you do this without using any technique, it might take you a little while. But the first thing I do is I kind of eyeball it and I see that, okay, 10 squared times 0.001, I can just move this 2 places to the right and have 0.1. So essentially this problem just becomes negative 23.2815 times 0.1, or for clarity we can do 0.1. Now I know that negative times positive is negative, so I know the answer is negative. So if I were to pretend these are whole numbers, I would do 232,815 times 1. Well, that's just going to give me 232,815. At that point I just have to figure out where to put my decimal point. And I'd say, okay, well I have 1, 2, 3, 4, 5 decimal places between both factors here. So the decimal point's going to go 1, 2, 3, 4, 5 places to the left, and I'd end up with negative 2.32815. All right, for the final problem, we have 0.012456 times 100 times 1,000. So 100, most of you should know at this point, is 10 squared. Right? That's a power of 10, and the exponent is a whole number that's 1 or larger. 1,000 is also a power of 10. It's 10 cubed. Right? So same scenario. So we can use our trick here. And you basically can count the number of zeros between both of these. You have 1, 2, 3, 4, 5, because if I was to multiply these two numbers together, let's say I started out by saying, what is 100 times 1,000? Well, using my trick for trailing zeros, I know that I would do 1 times 1, that's 1, and then I would attach 5 trailing zeros, right? So 1, 2, 3, 4, 5. I'd get the number 100,000, or we could write that as 10 to the 5th power. So let me put this over here, 0.012456. And now to do this multiplication, all we need to do is move our decimal point 5 places to the right, right? Because we have 1, 2, 3, 4, 5 zeros in this power of 10. So let me copy this number. We're going 1, 2, 3, 4, 5 places to the right. And I can delete this 0 and this 0. I don't need them anymore. They're not going to add value to the number. And so we would have 1,245.6. Hello and welcome to Pre-Algebra Lesson 43. In this video, we're going to learn about dividing decimals. So our lesson objectives for today, we want to learn how to divide a decimal by a whole number. And also we want to learn how to divide a decimal or whole number by a decimal. So before I started talking about multiplying decimals, I told you that it was really no more difficult than multiplying whole numbers. You just have an extra step involved. Well, it's really the same thing here. Some cases you're going to have 1 extra step, in some cases you'll have 2 extra steps, just depending on what the situation is. But if you can divide whole numbers using long division, you can divide decimals. It's no more difficult. So let's start out by saying to divide a decimal by a whole number, which is the easier scenario, we just want to set up the long division normally and place the decimal point in the answer directly above the decimal point in the dividend. Now, I know we haven't talked about division in a while, so just remember if you have something like 6 divided by 3 equals 2, the 6, the amount you start with is the dividend. 3, the amount you're dividing by is the divisor. And 2, the answer that you get, or the result, is the quotient. So once you've performed this step, where we place the decimal point in the answer directly above the decimal point in the dividend, you just divide normally. Right? You can just ignore the decimal point, pretend like it's not there, because you already know where it's going to be in your answer. All right, let's start out with 1.5 divided by 3. So we set up our long division normally. So I take my dividend, which is 1.5, and that goes underneath. I take my divisor, which is 3, and I put it off to the left. Now, the first step we're going to do is we're going to take this decimal point, and we're going to bring it straight up into the answer. Make sure it lines up properly, otherwise you won't get the right answer. Now, once I've done that, I know where the decimal point's going to be, and I can just pretend I have 15 divided by 3, right? So I would say, what is 3 going into 1? Well, we can't do that. So how many times would 3 go into 15? Well, that would go in 5 times. So I put a 5 here, and then I multiply. 5 times 3 is 15, and I subtract, and I get 0. So my answer for this is going to be 0.5, or I could put 0.5. Now remember, we can check division with multiplication. So we already know how to multiply with decimals. I could do 0.5 times 3, right? I could go backwards, and I should get 1.5. So what is 0.5 times 3? Well, we already know that we do 5 times 3. That would give us 15. And I would look to see how many decimal places I have between the factors. Well, this has 1 decimal place. This really doesn't have any. So I would move my decimal point 1 place to the left, and I would end up with 1.5, which is exactly what I started with as my dividend. Right? So we know that this answer is correct. 1.5 divided by 3 is 0.5. Let's take a look at the next one. We have negative 2.17 divided by 7. Now, again, if you're multiplying or dividing with negatives, the same rules that we learned with integers are going to apply.
Negative divided by positive is negative. Once you find out the sign, you can just pretend like all the numbers are positive. You don't need to think about it anymore. So I'm just going to set up my long division as 2.17, and we're dividing by 7. Now, bring your decimal point straight up into the answer, and then you're done with it. You don't have to think about it anymore. You can just divide like if you had 217 divided by 7. So 7 is not going to go into 2, but 7 will go into 21. It goes in exactly 3 times. 3 times 7 is 21. Subtracting gets 0. Bring down the 7. 7 will go into 7 one time. 1 times 7 is 7. Subtracting gets 0. So we have 0.31 as our answer. But remember, we have this negative up here. So let's attach that. And we'll say that we have negative 0.31 as our answer. And again, when you first start doing this, it's good for you to check, right? Take your quotient, your answer, multiply it by the divisor, you should get the dividend. So let's do one more where we check it. And then in the future, I'll leave it up to you to check your work. But it's good practice to check because you just learned how to multiply decimals. And so it can kind of reinforce what you learned. So you can take negative 0.31, and we're multiplying this by 7. So what is 7 times 31? So 31 times 7. 7 times 1 is 7. 7 times 3 is 21. So we would have 217 there. Remember, it's a negative times a positive, so that gives us a negative. And then we just need to figure out how many decimal places we have between the factors. Well, we have 1, 2, right? None over here. So this would go 1, 2 places to the left. You'd have negative 2.17, which is exactly what you have here as your dividend. So again, you know your answer is correct, right? Our answer here is negative 0.31. Okay, for our next one, we have 44.95 divided by 31. So again, let's set this up. 44.95 divided by 31. Bring this up into the answer so you can forget about it. And now you just divide normally. So 31 will not go into 4, but it will go into 44. It'll go in once. 1 times 31 is 31. Subtract here and you would get 13, right? 4 minus 1 is 3. 4 minus 3 is 1. Now bring down the next number. How many times will 31 go into 139? Well, let's see. I know that 31 times 10 is 310. 310. Let's say I was to mentally cut that in half. Think about 310 as 300 plus 10. Cut 300 in half, you'd have 150. Cut 10 in half, you'd have 5. So half of this would be 155. That's too big. So my guess is going to be for 4. So what is 31 times 4? 4 times 1 is 4. 4 times 3 is 12. That's 124. So that's as close as we can get without going over. So we're going to put a 4 here, and we're going to multiply. 4 times 31 again is 124. Now we're going to subtract. 9 minus 4 is 5. 3 minus 2 is 1. So we'd have 15 there. And then we're going to bring down the 5. Now, we figured out earlier that 31 times 5 was 155, right? We just saw that. So I know that 31 will go into 155 5 times exactly. So this is going to be a 5. 5 times 31 again is 155. Subtracting, we get 0. So we get 1.45 as the answer. And let me just scroll back up here and write this next to this. So equals 1.45. So now we're going to kind of use this information to kind of tackle something that might have been confusing you for a while. I know that a lot of you will do division on a calculator. Let's say you have something like 17 divided by 5. So if you perform this operation using long division, 5 doesn't go into 1. 5 goes into 17 3 times. 3 times 5 is 15. You subtract and you get 2. So kind of up to this point, we've written 3 with a remainder of 2 as our answer. Now, your calculator won't give you 3 with a remainder of 2. It's going to tell you that the answer is 3.4. So how do we go from this format to the 3.4 format? Well, that's what we're going to get to right now. So let me erase this real quick and kind of give you the backstory. So I want you to recall that after a decimal point, a 0 does not add value unless it precedes a non-zero number. So something like 5.000000 is still 5.
right? Where you run into problems if you had something like 5.000001, well, these zeros do matter now, right? Because they come before a non-zero digit. They precede a non-zero number, okay? But if you don't have anything that's out there other than 0, you can put as many as you want. It doesn't matter. You're not adding value to the number. So knowing that, let's explore that 17 divided by 5 again and see if we can get 3.4 as our answer. So 17 divided by 5. So the first thing I'm going to do is I'm going to write 17 as 17 point, and I'm going to put 1 0 behind it. I'm going to put this decimal point up here in the answer, and now I'm going to divide like I normally would. 5 won't go into 1, so we say 5 goes into 17 3 times. 3 times 5 is 15. Subtract and get 2. Now instead of stopping and saying that's my remainder, I can bring down this 0. 5 goes into 24 times. 4 times 5 is 20. Subtract and get 0. So now you see what your calculator is doing. It's just continuing the division, right? So our answer here is 3.4. It doesn't make it wrong if you say you have 3 with a remainder of 2. It's just a little bit more precise to use this method and say, okay, well, our answer is 3.4. Let's try another one. So let's say we had 6.2 divided by 5. So 6.2 divided by 5. So we already have a decimal point here. Let's bring that up into the answer. And let's divide. 5 goes into 6 once. 1 times 5 is 5. Subtracting, you get 1. Bring down the 2. 5 goes into 12 twice. 2 times 5 is 10. Subtracting, get 2. So we're not going to say that we have 1.2 with a remainder of 2. We're going to continue the division. So remember, if I have 6.2, I can legally add as many zeros after that 2 as I want, not changing the value of the number. So let's continue our division. Let's put a 0 here, and then let's bring it down. So 5 will now go into 20 exactly 4 times. 4 times 5 is 20. Subtract and get 0. So our answer here is going to be 1.24. So we're going to get 1.24. And this is basically what we're going to do from here on out. We're going to continue the division until we get an answer, or sometimes we're going to get a digit that repeats or a pattern of digits that repeat. And we'll get to an example of that in a minute. All right, let's take a look at another one. We have 65.98 divided by 50. So 65.98 divided by 50. So bring your decimal point up into the answer. 50 is not going to go into 6, but it will go into 65. It'll go in once. 1 times 50 is 50. Subtract, 5 minus 0 is 5. 6 minus 5 is 1. And go ahead and bring down the 9. So now how many times will 50 go into 159? Well, 50 times 3 is 150. And that's about as good as we can do. So let's put a 3 here. 3 times 50, as I just said, is 150. Subtract 2, we get 9. Bring down the 8. Now let me scroll down and get a little room going here. So I know that 50 is going to go into 98 once. Only once. 1 times 50 is 50. Subtract, and we'd have 48, right? 8 minus 0 is 8. 9 minus 5 is 4. So we continue, right? We put a 0 after the 8, and we bring that down. So now we're going to ask, how many times will 50 go into 480? Well, I know 50 times 10 is 500, so I'd have to do 50 times 9. So 9 times 5 is 45. Attach a 0, it's 450. Let me kind of go back and forth here because we're not going to be able to fit all this on the screen. So 450, subtracting, you'd have 30. So I can keep adding zeros until I have something. So I'm going to add another 0 here and drag that down. I'm going to drag that down. So now I have 300. Now let me scroll up. So 50 goes into 300 exactly 6 times. So put a 6 here. And 6 times 50 again is 300. And when we subtract, we're going to have 0. So there's no remainder. So go up here, and our answer is going to be 1.3196. So let's take a look at this other scenario that you're going to run into. Occasionally, we're going to get a digit or series of digits that repeat forever. So when this occurs, we place kind of a bar over the part that repeats. So if I got an answer that was 4.33333, and that 3 just kept continuing forever, what I do is I just put a bar over the 3. Or if I had 3 digits like 367, 367, 367, I would just erase these and put a bar over the 3, 6, and 7, right? The part that repeats. Let's look at 1.3 divided by 6. So 1.3 divided by 6. So bring this up into the answer. 6 doesn't go into 1. It goes into 13 twice. 2 times 6 is 12. Subtract and get 1. Put a 0 here to continue the division. Bring that down. 6 is going to go into 10 once. 1 times 6 is 6. Subtract and get 4. Put a 0 to continue the division. Bring that down. 6 is going to go into 46 times. 6 times 6 is 36. Subtract and get 4. Put a 0 to continue the division. Bring that down. 6 goes into 46 times. 6 times 6 is 36. Subtract and get 4. Now, a lot of you at this point can already see there's an issue. Every time you continue this, if I put another 0 here and bring it down, I'm going to have 40 again. I had 40 here, then here, then here. It's just going to keep going because every time you're going to ask, how many times will 6 go into 40? Well, it's going to go in 6 times. So I'm going to have another 6 up there. I'll multiply. 6 times 6 is 36. I'm going to subtract 40 minus 36, and I'm going to get a 4. Bring down another 0. I'll have 40 again. This will continue forever and ever and ever. So once you recognize that there's a pattern going on, you just stop. And you say, okay, the 6 will repeat forever. So my answer is 0.216 with a bar on top of the 6. Okay, a bar on top of the 6. That way we know that that 6 continues forever. All right, let's take a look at another one where you'll have a pattern that continues forever. So you have 51.2, and we're dividing this by 11. So bring that up into the answer, and 11 will not go into 5. It's going to go into 51 4 times. 4 times 11 is 44. Subtract here. I would need to borrow. This would become 4. This would become 11. 11 minus 4 is 7. 4 minus 4 is 0. So I'll go ahead and bring down this 2 here. 11 will go into 72 6 times. 6 times 11 is 66. Subtract. I need to borrow. 12 minus 6 is 6. So I'm going to put a 0 here so I can continue. And I have 60. 11 goes into 65 times. 5 times 11 is 55. Subtract and I get 5. Go ahead and put a 0 here and bring that down. 11 goes into 54 times. 4 times 11 is 44. Subtract and you're going to get 6. So we're going to bring down another 0. And we're going to have 60. And remember, the divisor is 11. I don't want to scroll back and forth. The divisor is 11. So you'd say, how many times does 11 go into 60? Well, it's going to go in 5 times. It's going to go in 5 times. So this will be a 5. 5 times 11 is 55. 55. And subtract. You can already kind of see what pattern is going to emerge, right? You have 60 minus 55 here, and then you have it here again. So you know the result is going to be this next, right? Underneath it, I could basically just write 50 and 44 and minus and keep going, right? That's the pattern. But let me erase this real quick and say that, okay, this will be 5. This will be 10. 10 minus 5 is 5. And again, I'd bring down a 0 from all the way up top. Let me do that. And we'd have 50 again. 11 will go into 50 only 4 times. Only 4 times. So you can really see that it's 5, 4, 5, 4, 5, 4. That's the pattern that's going to continue forever. So 4 times 11 is 44. Subtract and you get 6. So again, you're going to start out with 60 again, right? You have 60 here, and then you go to 50, then 60, then 50, and then that's exactly what's happening again. You'd have 60, you go through that again, you'd have 50, so on and so forth. It would just continue forever and ever and ever. So when you notice your pattern, you can go ahead and just stop and say, okay, I have 4.654. Now, the 5, 4 is what's repeating forever. So I'm going to put that bar over the 5 and the 4 only. But make sure you cover both digits, whatever's repeating. So I'm basically demonstrating that the 5 and the 4 will continue forever. So in other words, 4.654, 54, 54, 54, you know, so on and so forth. All right, so now another important fact. Now, when we talked about multiplying decimals, I kind of work into the situation when we multiply by 10 or a power of 10. And when I say a power of 10, I mean a whole number that is 1 or larger. So we're talking about 10 to the first power, 10 squared, 10 cubed, 10 to the fourth, so on and so forth. We saw that we'd move the decimal point 1 place to the right for every 0 in the power of 10. So if I did, 96 times 10 cubed, well, 10 cubed is a power of 10 with 3 zeros, right? It's 1,000. This is basically 96 times 1,000, right? So I have 1, 2, 3 zeros there. So I'm going to move the decimal point 3 places to the right. I'd go 1, 2, 3, and I'd end up with 96,000 as an answer. When we divide by 10 or power of 10, when I say power of 10 again, I'm saying a whole number that's 1 or larger, we're going to kind of do the reverse. We're going to move the decimal point 1 place to the left for every 0 in the power of 10. So multiplying, it's going to the right. Dividing, it's going to the left. So if I have 96.12 divided by 10, the shortcut is just to say, okay, I have 1 0 going to the left by 1. That would be 9.612. If I have 96.12 divided by 100, the shortcut is to say, okay, I have 2 zeros, so I'm going to go 1, 2 places to the left, so I'd have 0.9612. If I have 96.12 divided by 10,000, I have 1, 2, 3, 4 zeros in this power of 10. So I'm going to have 96.12. I need to put 2 zeros over here. I'm going to go 1, 2, 3, 4 places to the left, and I'll end up with 0.009612 as my answer. Okay, let's talk about the other scenario now. So our other scenario involves dividing by a decimal. And basically what we're going to do here, we're going to move the decimal point in the divisor by enough places right to make it into a whole number. Now, once we've done that, our kind of next step is to match that movement with the decimal point in the dividend. So as a quick example, let's say I'm dividing 6.3 by, I don't know, 3.27. What I want to do is I want to start out with my divisor. Remember, that's the number you're dividing by. And I want to make it into a whole number. So I'm basically going to move this decimal point 1, 2 places to the right. I just have to match that movement in my dividend. So for 6.3, I'm going to put a 0 behind the 3, and I'm going to move this 1, 2 places to the right as well. So I'm basically turning this into the division problem, 630 divided by 327. Now you might stop for a minute and try to figure out how that's legal. The best way I can explain it to you is if you put it in fractional form, you can kind of think about having 6.3 in the numerator over 3.27 in the denominator. And let's say I just multiply the numerator and denominator by 100. Remember, that's just like multiplying by 1. So we would end up with, again, 630 over 327. So let's take a look at a few examples. So if I have 91.35 divided by 6.09, this is the divisor. This is the divisor. And essentially what I'm doing is I'm saying, okay, I need to move this 1, 2 places to the right to make it a whole number, to make it the number 609. I just need to match that over here, move this 2 places to the right. Basically, I'm just multiplying each by 100, right? We learned earlier if you multiply by 10, you go 1 place to the right. If you multiply by 10 squared or 100, there's 2 zeros there, so you go 2 places to the right. And that's all we're doing. In fractional form, you can kind of think about this set up this way. If I just multiply the numerator and denominator here by 100, what I'm going to end up with is what? I'm going to end up with 9,135 over 609. Right? That's all I'm basically doing. I'm matching the movement that was made in the divisor that made it into a whole number in my dividend. Right? So that's the first thing we want to do. So once we have that, I'll just rewrite this problem. I'll just say it's 9,135 divided by 609. And we'll just crank that out real quick. So 609 will go over here. 9,135 will go here. Let me scroll down and get some room going. And so 609 will go into 913, right? It's not going to go into 9 or 91, but 913 once. 1 times 609 is 609. We would subtract here, and I'll borrow here. 13 minus 9 is 4. 0 minus 0 is 0. 9 minus 6 is 3. So that's 304. Bring down the 5. So we have 609. How many times is that going to go into 3,045? Well, you can eyeball this and see that it's going to work out perfectly, right? Think about 609 as 600 plus 9. If I multiply 600 times 5, I get 3,000. If I multiply 9 times 5, I get 45. So that tells me that what I'm looking for here is a 5. Right? 5 times 609 is going to give me 3,045. 5 times 9 is 45. 5 down, carry the 4. 5 times 0 is 0 plus 4 is 4. 5 times 6 is 30. So again, 3,045. So again, 5 times 609 is 3,045. Subtracting gets 0. So our answer here is just 15. So let me erase this and we'll scroll up and write that down. That our answer is going to be 15. Now let's take a look at one more. All right, so we have 183.4272, and we're going to divide this by 21.23. So again, I'm looking at my divisor, and I want to make it into a whole number. So I need to move this 2 places to the right. Basically, I'm multiplying it by 100. I need to match that movement over here in the dividend. So I'm going to move this 2 places to the right. A lot of students get confused at first. They can't remember what they need to move. Remember, it's always the divisor, what you're dividing by, that you need to change into a whole number. So I'm going to write this problem now as 18,342.72 divided by 2,123. So now let's crank this out. I have 18,342.72. Again, I'm dividing this by 2,123. And when you work with really big numbers like this, it can be very, very tedious. And I doubt you get something like this on a test. If you did, it would probably be like your final question or something like that. I just like to do some examples that are a little bit challenging so that you get experience working with something that's very tedious. So 2,123, it's not going to go into 1. It's not going to go into 18. It's not going to go into 183. It's not going to go into 1,834. The first thing we could check is 18,342. So we got to make some guesses. I would guess with a 9, that's probably going to be too big. So 2,123 times 9. 9 times 3 is 27. 9 times 2 is 18, plus 2 is 20. 9 times 1 is 9, plus 2 is 11. 9 times 2 is 18, plus 1 is 19. So that's 19,107. That's too big. So we're going to go with 8. So I'll put an 8 here. And let's do that multiplication real quick so we can get our product going. 8 times 3 is 24. 8 times 2 is 16, plus 2 is 18. 8 times 1 is 8, plus 1 is 9. 8 times 2 is 16. So I'm going to get 16,984 as my answer there. 16,984. We're going to subtract. And I'll need to borrow here. This will become 3, then 12. 12 minus 4 is 8. We'll borrow again. This will become 2. This is 13. 13 minus 8 is 5. We'll borrow again. This will become 7. This will become 12. 12 minus 9 is 3. 7 minus 6 is going to give me 1. And then 1 minus 1 is 0. So I get 1,358. 1,358. And I'm going to bring down my 7. So now I'm working with 13,587. So again, I'm going to make a little guess. So what I do is I think about, okay, 2,000 times 6 would give me 12,000. Let's just try that out first. So 2,123 times 6. Let me scroll down. Get a little room going. 6 times 3 is 18. 6 times 2 is 12, plus 1 is 13. 6 times 1 is 6, plus 1 is 7. 6 times 2 is 12. So 12,738, that's as close as we're going to get. 12,738 is as close as we can get. So 2,123 will go into 13,587 6 times. 6 times 2,123, again, is 12,738. So now we want to subtract. And let me just move this over a little bit. So I'm going to borrow here to start. This will become 7. This will become 17. 17 minus 8 is 9. 7 minus 3 is 4. Borrow again. 15 minus 7 is 8. 2 minus 2 is 0. 1 minus 1 is 0. So basically I have 849. And I'm going to bring down this 2 here. So I get 8,492. So how many times will 2,123 go into 8,492? Well, I'm going to guess 4, right? Because 2,000 times 4 will be 8,000. So let's check that out. What would 2,123 times 4 give me? 4 times 3 is 12.
4 times 2 is 8, plus 1 is 9, 4 times 1 is 4, 4 times 2 is 8. So 2,123 will go in 8,492 exactly 4 times. 4 times 2,123 is 8,492. Subtract and we will get 0, and we are done. Our answer here is going to be 8.64. Let's go back up to the top and write that in. So this is going to be 8.64 as our final answer. Hello and welcome to Pre-Algebra Lesson 44. In this video, we're going to learn about changing fractions to decimals. So our lesson objective for today is just to learn how to change a non-decimal fraction into a decimal. And the procedure for this is very simple. To convert a non-decimal fraction, remember a decimal fraction is a fraction whose denominator is 10 or a power of 10. So again, to convert a non-decimal fraction into a decimal, we divide the numerator by the denominator. Very easy to do. So let's start out with something like 1/4. So all we need to do is take the numerator, which is 1, and divide it by the denominator, which is 4. Now, in the case of a proper fraction, like you have here, your numerator is smaller than your denominator. So what you're going to have to do is put a decimal point at the end of your dividend, bring it up into the answer, and then put a 0 after that decimal point. Now we can do our division. So we would ask, how many times will 4 go into 10? Well, it will go in twice. Multiply 2 times 4, you're going to get 8. Subtract here, you will get 2. And I could put another 0 so I can continue my division. Go ahead and bring that down. 4 goes into 25 times. 5 times 4 is 20. Subtract and you would get 0. So 1/4 is the same as 0.25, or you could write 0.25. All right, let's take a look at another one. We have 2/3. So again, I'm going to divide the numerator by the denominator. So 2 is going to be divided by 3. Now 2 is smaller than 3, so I know that I have to put my decimal point after 2. Bring that up into the answer, put a 0 behind it, and now I can start my division. 3 will go into 26 times. 6 times 3 is 18. Subtracting, you would get 2. I could put another 0 and bring that down. 3 goes into 20, again 6 times. 6 times 3 is 18. Subtracting, you would get 2. And I could keep doing this, but obviously at this point, most of you have recognized that you're going to have an infinitely repeating digit, right? Every time I'm going to bring down a 0 and get 20, and I'm going to ask that same question. How many times does 3 go into 20? You're going to keep getting 6. You're going to multiply 6 times 3, you're going to get 18. You're going to subtract, you're going to get 2 again. So it's kind of an infinite loop, right? It will never stop. So as I taught you in the last lesson where we covered dividing decimals, basically what you're going to do is you're going to put 0.6, or you could do 0.6, and you're going to put a bar, a horizontal bar, on top of that 6 to denote that that 6 is a repeating digit, right? It will repeat forever. Okay, for the next one, let's look at 2/11, or 2/11. So again, I want to divide the numerator by the denominator. So 2 is going to be divided by 11. And again, 2 is smaller than 11, so I'm going to put a decimal point after 2, bring that up into the answer, and put a 0 after that decimal point. And now I can just ask, how many times will 11 go into 20? It's going to go in once. 1 times 11 is 11. Subtract here and you get 9. So I can put another 0 so I can continue my division. Go ahead and bring that guy down, and you'll have 90. 11 goes into 98 times. 8 times 11 is 88. Subtracting, you get 2. Now to continue the division, I put a 0 here and bring that guy down. Now notice how I started out with the question, 11 goes into 20, and I got 1. Again, I'm asking that question. 11 is going to go into 20 once. So you can already see that you're going to have a pattern that's going to repeat. It's going to be 1, 8, 1, 8, 1, 8, so on and so forth. Because 11 is going to go into 20. Again, we put 1 there. We multiply 1 times 11 is 11. When we subtract, we're going to get 9. We're going to put another 0 here and bring this down. And again, we're going to ask, how many times does 11 go into 90? That's going to be 8. 8 times 11 is 88. Subtracting, we're going to get 2. Right? So it's the same pattern over and over again, where I have basically 20, then 90. Then this would be 20 again, then you'd have 90 again. You know, so on and so forth. So we can stop at this point and go ahead and give an answer. It's going to be 0.18, where the 1 and the 8 repeat forever. So we'll put a horizontal bar on top of the 1 and the 8. Very important. And if you want, you can put a 0 out here just for clarity. So our answer is going to be 0.18, where the 1 and the 8 repeat forever. All right, let's take a look at another one. We have 25 over 44. So I'm going to take 25, my number in the numerator, and divide that by 44, my number in the denominator. And again, 25 is smaller than 44, so I'm going to begin by putting a decimal point there, bringing that up into the answer, and then putting a 0 behind that decimal point. So now, how many times will 44 go into 250? A lot of us don't really work with 44 that often, but just think about 44 times 10. 44 times 10, that's 440. Obviously, that's too big. But if you cut it in half, you're going to get a number that's just right. Cut 400 in half, you get 200. And then cut 40 in half, you get 20. So 44 times 5 would be 220. That's going to be perfect for us because if I go up one more to 6, I'm going to go over 250, right? So this is the perfect amount that we need. So we're going to write here that the answer is 5. Multiply 5 times 44. Again, that's 220. Subtract 250 minus 220 is 30. And then we'll put a 0 here so we can bring that down and continue our division. So 44 is going to go into 300 how many times? Well, 220 plus 44 is going to be 264. That is as close as I'm going to get to 300 without going over. So that's going to mean that we're going to have an answer of 6 there. 6 times 44, as I just said, is going to be 264. Now we're going to subtract. I'm going to borrow all the way from this 3 here. This will be 2. This will be 10, then 9. Then this will be 10. 10 minus 4 is 6. 9 minus 6 is 3. And then 2 minus 2 is 0. So now I'm going to put another 0 here and bring this down. And I'm going to have 360. So when I did 44 times 10, we saw that that was 440. So then times 9, I could just subtract 44. I'd be at 396. That's still too big because I'm trying to get to 360. If I take 44 more away, then I'm going to be just right. 9 is too big, but 8 is going to be just right. So I'll use 8. And then what is 8 times 44? Let's do that real quick. 44 times 8. 8 times 4 is 32. 2 down, carry the 3. 8 times 4 is 32. Plus 3 is 35. So 352. So we're going to write 352 here. And we're going to subtract. 360 minus 352 is 8. And we'll put a 0 here and bring that guy down. So what is 44 into 80? Well, it's only going to go in once. Right? It's only going to go in once. 1 times 44 is 44. 44. And we're going to subtract. So I'll borrow here. This is 7. This is 10. 10 minus 4 is 6. 7 minus 4 is 3. So I got 36. And when I bring down my 0, I'm going to have 360. So I can already see that there's a pattern forming. I had 360 already here. If I have it again here, it's just basically going to repeat. So in other words, the result there was 8. I know I'd get 8 again. Then I get 1, then 8, then 1, so on and so forth, right? 8 times 44 would give me 352 again. I'm basically repeating this part right here, right? If I subtract, I'm going to get 8. If I brought down another 0, I'd have 80, and I'd be at this step right here. Right, I'd be at that step right there. So at this point, we can go ahead and just answer, right? We know that the answer would be 0.5681, where the 8-1 would repeat forever. So I'm going to put a horizontal bar over the 8 and the 1, again, to show that those two digits are going to repeat forever. Okay, for the next one, we have a mixed number. And when you have a mixed number, basically what you're going to do is you're going to take your whole number part and just write that. So that's going to be the part that comes to the left of your decimal point. You can basically just write a decimal point after that, because after that decimal point, you're going to put what the fraction is converted into a decimal. Right, so you just kind of treat them as two different things for right now, and then you merge them together in the end. So what is 3/8, right, in decimal form? We're going to do 3 divided by 8. Put your decimal point down and bring it up into the answer. And I'll put a 0 after that decimal point. 8 goes into 30 3 times. 3 times 8 is 24. Subtracting, you would get 6. Put another 0 and bring that down. 8 goes into 60 7 times. 7 times 8 is 56. Subtracting, you would get 4. Put another 0 and bring that down. 8 will go into 40 exactly 5 times. 5 times 8 is 40. Subtracting gets 0. So we get 0.375. 0.375. And basically you just merge these two parts together. If I have 5 and 3/8, I basically have 5 point and then 375. So 5.375, right? This part right here is your part of a whole amount. And it's the same over here. After the decimal point, we're working with part of a whole amount, right? As a decimal fraction, that would be 375 over 1,000, right? 375 thousandths. All right, let's take a look at another mixed number. We have 1 and 2/9. So again, I'm just going to write this whole number part here, this 1. I'm going to put my decimal point down. And basically, after the decimal point, I'm going to have this part of a whole, right? This 2/9 expressed as a decimal, right? So 2 divided by 9. I'm going to put my decimal point here after the 2 and bring it up into the answer. Put a 0, and now we can start our division. 9 is going to go into 20 twice. 2 times 9 is 18. Subtracting, we get 2. Put another 0, bring that down. You can already see that this is going to be an infinitely repeating pattern, right? 9 goes into 20 twice. 2 times 9 is 18. Subtracting, you get 2, right? You'll keep getting this over and over, so you'll have this 2 repeating forever. So we can go ahead and stop and say that the part that comes after the decimal point here is just going to be a 2 with a horizontal bar over the 2 to say that it's going to repeat forever. So 1 and 2/9 is equal to 1.2, again, where the 2 repeats forever. All right, now let's take a look at an improper fraction. So with an improper fraction, again, I'm just going to divide the numerator by the denominator. So 31 divided by 20. The only difference is I don't need to put a decimal point out to start, right? I'm going to have to do it at some point in this problem, but I don't have to do it right away because my numerator is bigger now than my denominator. So 20 will not go into 3, but it will go into 31 once. 1 times 20 is 20. If I subtract, I'll get 11. Now I can put a decimal point there and bring it up into the answer. Put a 0 behind it and bring it down. 20 will go into 110 5 times. 5 times 20 is 100. Is, again, 100. Subtracting, we have 10. Go ahead and put another 0 and bring that down. 20 goes into 100 exactly 5 times. 5 times 20 is 100. Subtracting gets 0. This is 1.55. And if we were to write this as a mixed number, remember what we would do is just not continue the division, right? We would have had 31 divided by 20. This would go in once here. 1 times 20 is 20. We'd subtract and get 11. So really, we could also say that this is equal to 1 and 11/20, right? All of these forms are the same. We have this as an improper fraction. We have this using a decimal. And then we also have it as a mixed number. All right, let's take a look at one final problem. We have 17/8. So again, all I'm going to do is I'm going to take 17 and I'm going to divide it by 8. So 8's not going to go into 1, but it will go into 17 twice. 2 times 8 is 16. Subtract and get 1. And in the past, we'd stop and say, okay, our mixed number is 2 and 1/8. But here we can continue. We can get a result using a decimal. So I'm going to take that decimal point and bring it up into the answer. Put a 0 here and bring this down. So 8 is going to go into 10 only once. 1 times 8 is 8. Subtract and get 2. We'll put a 0 here and bring this down. So 8 is going to go into 20 twice. 2 times 8 is 16. Subtract and get 4. Put a 0 here and bring this down. 8 is going to go into 40 exactly 5 times. 5 times 8 is 40. Subtract and get 0. So 2.125. 2.125. 17/8 is 2.125. Or again, we could have also written this as a mixed number as 2 and 1/8, right? All of these are the same. We have our improper fraction, we have it as a decimal, and then we have it as a mixed number. Hello and welcome to Pre-Algebra Lesson 45. In this video, we're going to learn about percents. So our lesson objectives for today, we just want to learn how to convert a decimal to a percent and vice versa, meaning we also want to learn how to take a percent and convert it into a decimal. And then we want to learn how to convert a fraction to a percent as well. So a percent is just another method used to describe a part of a whole amount. Basically, it's just another fraction. So a percent is a fraction whose denominator is 100. Okay? So if you see a fraction and the denominator is 100, you're dealing with a percent. So as a more convenient way to write a fraction with the denominator of 100, we can use this percentage symbol to denote a percent. And I'll show you how to do that in a second. But one thing you need to understand is that the literal meaning is parts per 100. All right, so let's start out by looking at kind of the easier scenario. So let's say you start off on your test, you're having a percent test, and you have this 17 over 100. And your teacher says, write this using a percentage symbol. Well, the first thing you'd want to do is take your numerator, which is 17, and just write it. And then all you have to do is follow it with that percentage symbol. So 17 over 100 is equal to 17%. And that's all you need to do when your denominator is 100. It's nice and clean and simple. You have 17 parts out of 100 parts. Kind of something you can relate this to. Let's say that you take a test and you fail the test badly, right? You just completely bomb it. So you have 100 questions on this test and you only get 17 of them correct. So out of 100 questions, I got 17 correct. So my score on the test is going to be 17 out of 100 or 17%. Let's take a look at 3 over 100. So again, if the denominator is 100, to write this using a percentage symbol, I'll just take that numerator, which is 3, and I'll follow it with a percentage symbol. So 3 over 100 is equal to 3%. As another example, I have 96 over 100. Again, as long as the denominator is 100, I just write the numerator, whatever it is. In this case, it's 96, and I follow it with a percentage symbol. So 96 over 100 is equal to 96%. Now we're looking at 512 over 100. And it's okay that this number is greater than 100. It doesn't matter. We're still just going to take the numerator, which in this case is 512, and we're going to follow it up with a percentage symbol. So 512 over 100 is equal to 512%. Okay, what about 0.01 over 100? Again, it's the same thing. I take my numerator, which in this case is 0.01, and I just follow it up with a percentage symbol. So 0.01 over 100, again, the denominator is 100, is equal to 0.01%. All right, let's take a look at something a little bit more challenging. Still going to be pretty easy, though. So we're looking at decimal to percent, right? So I'm taking a decimal, and I'm going to change it to a percentage. So to write a decimal as a percent, we just move our decimal point 2 places to the right and place the percentage symbol at the end. Let's look at this quick exercise. Change each decimal to a percent. So as I said, we're just going to move our decimal point 2 places to the right, and then we're going to put a percentage symbol at the end. So we're going to start out with 0.032. So I'm going to say this is equal to, I'm going to move this guy 2 places to the right. So that would give me 3.2, and I'm going to put that percentage symbol after it. So 0.032 is equal to 3.2%. Now, some of you might be saying, where did those zeros to the left of the 3 go? Remember, if I have 2 zeros to the left of the 3, that does not add value to the number, so we can just get rid of them. All right, for the next one, we have 0.115. And again, all I want to do is take this decimal point and move it 2 places to the right. So I ended up with 11.5, and then I put my percentage symbol after it. So 0.115 is equal to 11.5%. Next, we're looking at 6.23. Again, move the decimal point 2 places to the right. So that's going to be 623. And then put a percentage symbol at the end. So 6.23 is equal to 623%. All right, now we're looking at 0.85. Again, take your decimal point and go 2 places to the right. So I'd have 85, and then put the percentage at the end. So 85%. 0.85 is equal to 85%. All right, now we're looking at 0.00037. Again, this goes 2 places to the right. So this will be equal to 0.037 and then percent. And you can put it at 0 out in front if you want, just for clarity. Doesn't really matter. 0.00037 is equal to 0.037%. Okay, let's look at 2 more. We have 0.014. Again, this decimal point's going 2 places to the right. So that's going to be 1.4. And then just throw your percentage symbol at the end. So 0.014 is equal to 1.4%. And then for the final one, we have 312.25. Again, this decimal point goes 1, 2 places to the right. So that's going to be 31,225, and then put your percentage symbol. So 312.25 is equal to 31,225%. Okay, so let's say we want to reverse this process and take a percent and go to a decimal. So essentially, you just reverse what you just did. So to write a percent as a decimal, we move our decimal point 2 places to the left. Remember, we're going 2 places to the right. Now we're just reversing that and going 2 places to the left. And then we're just going to delete the percentage symbol, right? We're just reversing what we just did. So we're going to change each percent to a decimal. And I'm going to start out with 4.27%. So let me rewrite this over here. I'm going to delete this thing. I don't need it. And I'm just going to write the number 4.27. Now I'm going to need to add 1 0 in here to make this work. And this is going to go 1, 2 places to the left. So I'm going to have 0.0427, right? So 4.27% is equal to 0.0427, or I can put a 0 out in front for clarity. Again, 4.27% is equal to 0.0427. All right, for the next one, we have 39.867%. I'm just going to rewrite this number, 39.867. And again, I don't need this percentage symbol, so I can just leave it off. Now I'm going to move this decimal point 1, 2 places to the left. And so I'm going to end up with a decimal point there. Let me put a 0 out in front for clarity. And we'll say that 39.867% is equal to 0.39867. All right, for the next one, we have 215.37%. Again, I'm just going to rewrite this number, 215.37. I'm not going to write the percentage symbol. We don't need it. And I'm just going to move this decimal point again, 2 places to the left, 2 places to the left, and that'll go right there. So 215.37% is equal to 2.1537. Okay, for the last one we're going to look at, we have 0.003591%. And of course, I'm just going to rewrite the number. Leave the percentage symbol off. I don't need that anymore. And the decimal point is just going to go 2 places to the left. So 1 and then 2 places to the left. So that would be right there. And if I want to, I can put a 0. Let me kind of scoot this over a little bit. I can put a 0 out in front for clarity. So 0.003591% is equal to 0.00003591. All right, so now let's talk about the most tedious scenario you're going to come across. And basically, a more tedious situation comes up when we're asked to convert a fraction to a percent. There's kind of 2 ways you can think about doing this. The first way, let's say you have something like 4/5. Well, you could divide the numerator by the denominator, basically take the fraction and put it into a decimal, then take that decimal and convert it into a percentage. Now, the faster way would be to transform the fraction into an equivalent fraction with 100 as its denominator. But you're going to see that that's not always so simple. So for 4/5, let's do it both ways. The long way would be to say, okay, 4, divided by 5. Put my decimal point here and bring it up. And put a 0 here. 5 is not going to go into 4, but we'll go into 48 times. 8 times 5 is 40. Subtracting gets 0. So we know that 4/5 is equal to 0.8. And then to convert this to a percentage, we'd move this 2 places to the right. So 1, put a 0 there, 2. So the decimal point would go there. And then I would add a percentage symbol to the end. So 4/5 is equal to 0.8, and it's also equal to 80%. The other way you could have done this, which is much faster in this case, is to take 4/5 and just realize that if I multiply 5 times 20, I get to 100, right? And if you didn't know that, you could take 100 and just say, okay, if I divide 100 by 5, I get 20, so that means if I multiply 5 by 20, I get 100. It's whatever I need to multiply this by to get to 100. So if I multiply this by 20, my denominator is 100, and I know I have a percent. If I multiply the denominator by 20, I also have to multiply the numerator by 20 so that I have an equivalent fraction. So 4 times 20 is 80 over, again, 5 times 20, that's 100. So now I have a percent, a fraction whose denominator is 100. And when this occurs, we just simply take the numerator, which in this case is 80, and we follow it up with a percentage symbol. So we get the same answer either way, 80%. It's just a different kind of way to do it. And in most cases, this is going to be a lot quicker. But sometimes you're going to run into problems using this method. And I'll show you an example of that in a minute. All right, so what about 3/4? Again, there's two ways we can kind of do this. We can take 3 and we can divide it by 4. Put my decimal point here and bring it up into the answer. 4 is not going to go into 3, but we'll go into 37 times. 7 times 4 is 28. Subtract and get 2. Bring down a 0. 4 goes into 20 exactly 5 times. 5 times 4 is 20. Subtract and get 0. So 3/4 is 0.75. 0.75. Now, again, to turn this into a percentage, I just move that decimal point 2 places to the right. So it's going to go 1, 2 places to the right. That gives me 75. And then I just add my percentage symbol in. So 3/4 is equal to 0.75, and it's equal to 75%. Now, kind of, again, the quicker way to do this would have been to say, okay, I have 3/4, and I can multiply 4 times what to get to 100? Well, if you don't know the answer to that is 25, again, take 100 and divide by 4. 100 divided by 4 is 25. So therefore, 4 times 25 is 100. You can always use little tricks like that to get what you're looking for. So we would multiply by 25 over 25, since that would give me a denominator of 100. And 3 times 25 is 75. So now I have a percent, right? I have a fraction whose denominator is 100. And essentially all I need to do is take that numerator and rewrite it, follow it up with a percentage symbol. So 3/4 is going to be equal to 75 over 100, and that's equal to 75%. Okay, what if we had 11 over 20? So again, we can take 11 and we can divide it by 20. So I'll need to put a decimal point here and bring it up into the answer. So 20 is not going to go into 1. It's not going to go into 11. It will go into 110 5 times. 5 times 20 is 100. Subtract and we'd have 10. Go ahead and put a 0 there and bring it down. 20 goes into 100 5 times. 5 times 20 is 100. Subtract and get 0. So 11 over 20, or 11/20ths, is going to be equal to 0.55 as a decimal. And then as a percentage, we just move this 2 places to the right. So that would be 55, put our percentage symbol, so 55%, right? So 11/20ths is equal to 0.55, which is equal to 55%. Now, again, kind of the quicker way to do this, I think everybody at this point knows that I can take 20, multiply it by 5 to get to 100. So I could have said, okay, 11 over 20. I can multiply this by 5 over 5. Again, I just need to figure out what I need to multiply the denominator by to get to 100. Right? And once I figure that out, I just do it to the numerator and denominator so that it's legal. 11 times 5 is 55. Over 20 times 5, that's 100. Again, now I have a percent. Right? I have a fraction whose denominator is 100. So to write this as a percentage, just take the numerator, which is 55, follow it up with a percentage symbol. 11/20ths is equal to 55 over 100, which is 55%. Okay, let's look at one that's a little bit more challenging. So I have 23 over 46. Now, let's say I started out and I said, okay, what number can I multiply 46 by to get to 100? Well, it's not going to be a whole number. So that's where it kind of gets a little challenging, right? That's where you might want to save some time by just doing the division, right? You might want to say in this case, okay, well, 23 divided by 46. And a lot of you already know this is going to be 0.5, right? Because 23 is half of 46. But I'll put my decimal point here and bring it up into the answer. Put a 0 here. 46 is not going to go into 2. It's not going to go into 23. But it will go into 230 exactly 5 times. 5 times 46 is 230. Subtract and we get 0. So as a decimal, we would write this as 0.5. Now, to convert it to a percentage, again, we just take that decimal point and move it 1, 2 places to the right. So it's going to be right there, and I can just get rid of it, right? 50 has a decimal point after the 0, but we don't need to write it. And then put a percentage symbol after the 0, so it's 50%, right? 23 over 46 is equal to 0.5. That's also equal to 50%. Now let's say that we wanted to go through and try to do it using the other method. So 23 over 46 times what over what will give me something over 100. So we know from basic rules that 46 times some number equals 100. 100 divided by some number will give me 46, or 100 divided by 46 would give me this number. So let me just go down to a scratch sheet here. So 100 divided by 46. What is that? Well, we can divide it out and kind of get a decimal, or we can keep it as a fraction. If we actually go through and get the division, we're going to get a number that we don't want to mess with, right? It's very, very messy. So let's just keep this as 100 over 46, and I'll show you how you can kind of use it this way. So let's go back up to the top and say that 46 times 100 over 46 would give me 100. And you can go ahead and check that. If we were to multiply these two together, this would cancel with this and just leave me with 100. So that does work. Now, if I do it to the denominator, I've also got to do it to the numerator. Now you see how complicated this has become. So I know that if I multiply 23 times 100 over 46, let's just do that problem down here. So 23 times 100 over 46. So I know that 46 divided by 23 is 2. So if I cancel this with this, I'm going to have a 2 here, and I have 100 up here. What is 100 divided by 2? That's going to be 50. So I can just cancel this with this and put a 50. So my numerator is going to be 50. Now in the denominator, as I just explained, this would cancel with this, right? 46 over 46 is 1, and I'd just be left with 100. So that's where I get that there. So I end up with 50 over 100, which again, as a percentage, is just 50%, right? I just take what's in the numerator and write it, follow it with my percentage symbol. So you can see in this case, it's probably not quicker to go through and deal with all this. I probably could have just did the division faster, but it just kind of depends. I mean, it's fun to know both methods because in some cases it's quicker to do it this way, and in other cases it's quicker to do, the division and then convert that decimal into a percent, right? You just have to kind of know the situation. Hello and welcome to Pre-Algebra Lesson 46. In this video, we're going to learn how to find the mean, median, and mode for a group of numbers. All right, so again, the lesson objective for today is just to learn how to find the mean, median, and mode for a group of numbers. All right, so let's start out with one that you're probably already familiar with, even if you've never heard it called the mean. So the mean, otherwise known as the average, and that's probably what you've heard it as, of a group of numbers is found by adding all of the numbers for the group, then dividing by the number of numbers in the group. So it's very, very simple to find an average. All right, so find the mean. And again, you could say find the average if you want. Those two words are interchangeable. So we have our numbers here. We have 6, 12, 13, 5, and 9. So all I need to do is find the sum to start. So let's just do this using a vertical addition. I'm going to put the 2-digit numbers on top. So I'm going to put 13, then 12, then we could do 9, then 6, then 5. So again, you can add in any order. I just did this because it's kind of a way for me to organize it in my head. All right, so put my addition operator out there, and let's start adding. 3 plus 2 is 5, 5 plus 9 is 14, 14 plus 6 is 20, 20 plus 5 is 25. I'm going to put a 5 down, carry a 2, 2 plus 1 is 3, plus 1 is 4. So I've got 45 as my sum. Okay, so let's erase this real quick. And I'm just going to write here that the sum is 45. Now the next piece of information is we need to know how many numbers are in the group. So I can just go through and count. That's pretty easy. I just go 1, 2, 3, 4, 5. There are 5 numbers in the group. 5 numbers in our group. So to get the average, I just take the sum of the numbers in the group, which is 45, and I divide by the number of numbers in the group, which in this case is 5. Now, I don't need to do a long division for this. I know 45 divided by 5 is 9. So the average here, or the mean, is going to be 9. Okay, let's take a look at another one. Let's say we have 28, 34, 115, 7, 2, and then 6. All right, so let's find the sum first. And again, I'm going to take the numbers with more digits and put them on top. And again, just to keep this organized, I'm going to take and just list them in descending order, right? Starting at the top with 115 and then just moving down. So to 34, then 28, then 7, then 6, then 2. Okay, so let's start our addition. I'm going to scroll down a little bit. So 5 plus 4 is 9, plus 8 is 17, plus 7 is 24, plus 6 is 30, plus 2 is 32. So let me put a 2 down and carry a 3. And let me scroll up a little bit so I can put this 3 up here. And 3 plus 1 is 4, plus 3 is 7, plus 2 is 9. Then I can just bring this 1 all the way down, and I have 192 for my sum. So the sum is 192. Now, how many numbers do we have in our group? Well, we have 1, 2, 3, 4, 5, 6. We have 6 numbers in the group. So I just take the sum for the numbers in the group divided by the number of numbers in the group, and then I have my average, or again, the mean. So what is 192 divided by 6? Well, I don't really work with those numbers very often, so I don't know that off the top of my head. I would need to crank out a long division. So let's do that real quick. So what is 192 divided by 6? 6 will not go into 1. It will go into 19 3 times. 3 times 6 is 18. Subtract them, we'll get 1. Bring down the 2. 6 goes into 12 twice. 2 times 6 is 12. Subtract and get 0. So 192 divided by 6 is 32. And again, 192 divided by 6 is 32. And so this is our answer, right? Our average, or our mean, is going to be 32. All right, let's take a look at one final problem for finding the mean, or again, the average. I have 125, 17, 22, and negative 7. So let's add all these numbers together. And what I'm going to do, since we have a negative involved, let's add the positive numbers together first, and then let's do a final operation where we add the result to that negative. So what is 125 plus 22 plus 17? 5 plus 2 is 7, plus 7 is 14. 4 down, carry the 1. 1 plus 2 is 3, plus 2 is 5, plus 1 is 6. Bring down the 1. So I've got 164. I'm going to have 164 plus a negative 7. So obviously 164 is larger in terms of its absolute value, so the answer is going to be positive. Essentially, I just have a subtraction problem here. 164 plus negative 7 is the same thing as 164 minus 7. So we do 164 minus 7. Borrow here, this will be 5, this will be 14. 14 minus 7 is 7. Bring down the 5, bring down the 1. So I get positive 157 as my answer. So let's write that the sum is 157. And then the number of numbers is 4, right? I have 1, 2, 3, 4. So the number of numbers in the group is 4. So now I would just want to take that sum, which is 157, and divide by 4, right? The number of numbers. Again, something I don't work with a lot, so I have to do a long division. And so 157 divided by 4. 4 will not go into 1. It'll go into 15 3 times. 3 times 4 is 12. Subtract, we get 3. Bring down the 7. So 4 is going to go into 37 9 times. 9 times 4 is 36. Subtract, and we get 1. So to continue this, I can put a decimal point and bring it up into the answer. Put a 0 here and bring that down. 4 goes into 10 twice. 2 times 4 is going to give me 8. Subtract, and we'd have 2. Put another 0 and bring that down. 4 goes into 20 exactly 5 times. 5 times 4 is exactly 20. Subtract, and we get 0. So we get 39.25. So we get 39.25 as our answer. Again, this is the mean, or what we call the average. All right, so another way to think about the middle value for a group of numbers is to use the median. Now, a lot of times when you hear data on people's salaries or on house prices or things like that, things that are affected by very high and very low values, you'll hear people talk about the median. So the median is not affected by these kind of outliers, these large values that kind of pull your average up, or these low values that kind of pull your average down. For example, if you thought about salaries, let's say you had 5 salaries and it was like 52,000. You know, let's say another one would be like 58,000. Let's say you had one that was 64,000. Let's say another one was, 60,000.
So these are all relatively close together. So your average should be somewhat representative of, what these values are. It would be close. But let's say for my fifth one, I throw in something like $18 million. Well, what happens is when I take the average here, I'm going to get a number that doesn't really accurately represent what the salaries are, right? It's inflated. From this kind of outlier here, this was way above what everything else was, and it pulled my average up. When we look at the median, we're going to correct for that. So we're not going to be affected by these very large or very small values. And essentially, to find the median for a group of numbers, we just arrange the numbers from smallest to largest. So the smallest goes to the left, and then we just keep going to the largest. The median is going to be the middle number when the number of numbers in the group is odd, or the average of the two middle numbers if the number of numbers in the group is even. Okay? And that's a lot to sink in. You might want to write that down as a note and just use it as you're practicing. But once you do a few examples of this, you'll kind of have it down. It's not very, very hard. All right, so we want to find the median in these examples. And we're going to start off with a pretty easy one. We have the numbers 3, 9, 8, 1, and 12. So again, the first thing you would do is arrange the numbers from smallest to largest. So I'd start out with 1, then 3, then 8, then 9, and then 12. Okay, so smallest number goes all the way to the left, and then we just, the next smallest, the next smallest, the next smallest, and then finally get to the largest value. Now, we have an odd number of numbers here. We have 1, 2, 3, 4, 5 numbers, and so the median is simply the middle number. In this case, that's going to be 8, right? It's going to be 8. And you can tell that's the middle number because I have the same number of numbers that come before it, right? I have 1, 2 numbers that come before it, as that come after it. I have 1, 2 numbers that come after it. So 8 is the middle number and therefore the median. All right, so for the next one, we have 150, 25, -2, 14, 18, 3, and then 9. So we're going to start out with the smallest number, which is -2 all the way to the left. Then we'll go to the next smallest. That's going to be +3. And then we're going to have 9, then 14, then 18, then 25, then 150. Now, how many numbers do we have in this group? We have 1, 2, 3, 4, 5, 6, 7. So again, 7's an odd number. So we know that it's just going to be the middle number here. So that's going to be right here where this 14 is. I have 1, 2, 3 numbers that come before it, and 1, 2, 3 numbers that come after it. So 14 is your middle number or your median. And when you get to your statistics class, or if you're reading a statistics book, you might see a formula in there that tells you that if you have an odd number of numbers, the median position is at n plus 1 divided by 2. N is just the number of numbers in your group. So you have 1, 2, 3, 4, 5, 6, 7 numbers in the group. So you'd replace that with a 7. 7 plus 1 is 8. 8 divided by 2 is 4. So essentially, you would be looking for the number that occurs in the fourth position. Well, this is the first, the second, the third, this is the fourth, and there's your median. All right, and that works when you have an odd number of numbers. All right, let's look at some scenarios where you have an even number of numbers, and you're going to see it's a little bit more tedious. So we have -2, 4, 6, and 5. So to arrange the numbers from smallest to largest, I need to flip the order here. I'd have -2, 4, 5, and then 6. Now, there is no middle value here, right? If you kind of look, okay, 4 looks like it's kind of in the middle. It has 1 that comes before it, but 2 that comes after it. Then if you look at 5, okay, that kind of looks like it's in the middle. 2 that come before it, 1 that comes after it. So neither of those is going to work. And essentially what you need to do is just treat these two numbers here, 4 and 5, as if they're in the middle. Okay, 4 and 5 as if they're in the middle. And you can see you have one number that comes before and one number that comes after. Now, because it's two different numbers here, what they want you to do is find the average of those two numbers, right? Kind of the average of the two middle numbers. So if I average those numbers, I would just sum 4 and 5. 4 plus 5 is 9, and then I would divide by 2. What is 9 divided by 2? 2 goes into 9 4 times. 4 times 2 is 8. Subtract and get 1. Put the decimal point there and bring it up. Put a 0 and bring it down. 2 goes into 10 5 times. 5 times 2 is 10. Subtract and get 0. So the average of these two numbers, 4 and 5, is 4.5, and that's your median. Your median is 4.5. Again, the average of the two middle numbers. All right, let's look at one more here. We have negative 8, 14, 2, 155, 30, 7, 5, and negative 2. So again, I'm going to arrange the numbers from smallest to largest. So negative 8 is the smallest, then negative 2, then positive 2, then we'd have 5, then 7, then 14, then 30, then 155. And if you count the number of numbers here, again, we have 1, 2, 3, 4, 5, 6, 7, 8. So again, it's an even number of numbers. There is no true middle number. If you kind of think about it, okay, well, if I have 8 numbers, that means that kind of these two numbers here that occupy the 4th and the 5th position. So this is the 1st, the 2nd, the 3rd, and I'm kind of messing up the writing on this, so let me kind of make that clear. So the 2nd, the 3rd, the 4th, and the 5th. If you look at these two numbers, you have 3 numbers that come before and 3 numbers that come after, if you just kind of block those two off. So those are your two middle numbers. They're your two middle values here, and you just want to average them to find your median. So you would add 5 plus 7, you get 12, divide that by 2, and you get 6. So the median here, again, is the average of the two middle numbers, and that's going to be 6. All right, let's talk about probably the easiest one to find, and this is called the mode. So the mode for a group of numbers is the number that occurs most often. That's it. You just have to find the number that occurs most often in your group of numbers. And it's important to note here, let me highlight this, that we can have more than one mode. So if you had a group of 6 numbers and each number appeared 3 times, let's say you had something like, I don't know, 3, 3, 3, 7, 7, 7. The mode here is both 3 and 7. Right? You have 2 modes because each number, 3 and 7, both appear the same number of times. And so you would have 2 modes. It's different than if you had something like 3, 3, 4, 6, 8, 2. Here, the number that occurs most often is 3, and so you have one mode, just 3. Right? 3 occurs twice. Every other number occurs just once. All right, so we're going to find the mode for each group of numbers. And basically, you just look through the numbers and see what occurs most often. So you have 82 and 86, 104, 82 again, 75, and then 30. So your mode is 82. The mode is 82. And why is that the case? Because 82 occurs twice in this group of numbers, and each other number occurs only once. So again, the mode is the number that occurs most frequently, and 82 occurs twice, whereas every other number occurs only once. So that's why our mode is 82. All right, here we have 103, 27, negative 4, 2, 27, 3, 2, 27, and 104. So I know 103 only occurs once, so I'm just going to kind of cross that out. That's not the mode. 27 occurs once, twice, 3 times. And let me use a different color here. Negative 4 only occurs once. 2 occurs once, twice. 3 only occurs once. 104 only occurs once. So the mode here is going to be 27. You have 1, 2, 3 occurrences. 2 came close. It had 2 occurrences, but 3 has the most, and so that's the mode. So your mode is 27. Okay, for the last one, we have 333, 75, 81, 75, 621, 79, and 333. So you can see here, just by eyeballing this, that you have 333 and 333. You have 75 and 75. So you have 2 modes here. 333 and 75 each occur twice. Everything else occurs only once. So we'll say that there are 2 modes. And those are 75 and 333. Hello and welcome to Pre-Algebra Lesson 47. In this video, we're going to be converting between US units of measurement. So our lesson objective for today, we want to learn how to change between US units of measurement. All right, so we're just going to start by looking at the relationship between a few common units of measurement. We're not going to cover all the possibilities here, but just a few of the basics so that we can kind of get our brain thinking about converting units. All right, so we have here length. So here are 3 common ones. We have that 12 inches equals 1 foot. We have that 3 feet equals 1 yard. And we have that 5,280 feet equals 1 mile. All right, let's look at weight. We have that 16 ounces equals 1 pound.
And we have that 2,000 pounds equals 1 ton. For volume, we have that 2 cups equals 1 pint, 2 pints equals 1 quart, and 4 quarts equals 1 gallon. And then lastly, for time, we have 60 seconds equals 1 minute, 60 minutes equals 1 hour, 24 hours equals 1 day, and 7 days equals 1 week. Now, based on the circumstances of your life, you may know all of these, you may know none of them. So try not to stress out too badly about memorizing these right away. As you work a lot of practice problems, you will memorize these relationships very, very quickly. And a lot of them you probably already know. For example, 60 seconds equals 1 minute. I think everybody knows that. Or 60 minutes equals 1 hour. 24 hours equals 1 day. You know, so on and so forth. So the ones that you don't know, as you work through the practice problems, you'll pick it up very quickly. So let's start out our lesson by just asking a simple question. If we are asked to convert 5,280 feet into miles, it's pretty simple. So we know that 5,280 feet is equal to 1 mile. And we saw that earlier when we were looking at the provided relationship between units. But what happens when we want to convert 6,600 feet into miles? So if I said 6,600 feet equals how many miles? Well, let's go through the process so that we can get the answer here. So our first step is just to set up something called a unit fraction. And let me highlight this because this is going to be important for you to know. A unit fraction shows the relationship between units and has a value of 1. So that part is very, very important. The fact that it has a value of 1, because remember, when we multiply by 1, even if it's a complicated form of 1, like we saw with fractions, it does not change the value of the number, right? If I take the number 4 and I multiply by 3 over 3, right? This is a complicated form of 1. So 4 times 3 is 12 over 3. 12 over 3 is the same thing as 4, right? If I do the division, 12 divided by 3, I get 4 back. So it's going to be the same thing here. We're going to be multiplying by a complicated form of 1. For example, if I have 5,280 feet, and that's equal to 1 mile, well, if I write 5,280 feet over 1 mile, this is going to have a value of 1, right? It's the same thing over itself, right? It's the same distance. It just looks different because it has different units involved, right? This has feet, and this is based on miles. So now that we understand what a unit fraction is, to actually perform the conversion, again, you identify the relationship between the units. So in our case, again, 5,280 feet is equal to 1 mile. If you didn't know that from memory, you'd have to look that up and then gain that relationship. Now, the next thing you want is to write the unit fraction with the unit of measure you want to end up with in the numerator. So recall that we had 6,600 feet, and we wanted to know how many miles. How many miles? So the unit I want to end up with is miles. This is what I'm trying to get to. So I'm going to write the unit fraction, again, with the unit measure you want to end up with in the numerator. So because I want miles in the numerator, I'm going to have 1 mile over 5,280 feet. This is my unit fraction. Remember, this has a value of 1. And it's just about taking the relationship between the units and putting, again, the units that you want to end up with in the numerator. I want to end up with miles in the numerator, so that's why I wrote it this way. If I was doing something where I was converting to feet and I wanted to end up with feet, I would just flip this. I would have 5,280 feet on top. I would have 1 mile on the bottom. All right, then we want to multiply what you're trying to convert by the unit fraction. So let's go ahead and do that real quick and see what we come up with. So we had 6,600 feet, and we're going to multiply this by the unit fraction. Again, it was 1 mile on top over 5,280 feet on the bottom. Now, the reason we want the units that we want to end up with on top is because this is what we're going to end up with. The units that we're trying to get rid of are going to cancel out when we write it this way. Feet over feet will just cancel, so we don't have to worry about them. Basically, what I have here is, forget about this unit for a second. That's going to just carry itself over. So we'll put miles over here. And we're just going to think about, okay, what is 6,600 times 1 over 5,280? Well, basically, that's just a division problem, right? It's 6,600 divided by 5,280. And we would just divide this. We know that this will only go into 6,600 once. And multiply 5,280. And we're going to subtract. 0 minus 0 is 0. I need to borrow here. So this will become 5, and then this will become 10. So now we can do 10 minus 8, that's 2. 5 minus 2 is 3. 6 minus 5 is 1. Now we're going to continue the division. So let me scroll down here so we have room to do this. I'm going to put my decimal point here and bring it up into the answer. Put a 0 here and bring it down. So for 5,280, how many times can I go into 13,200? Well, if you just eyeball this, if you just approximate this number to 5,000, 5,000 times 3 would be 15,000. That's too big. So the best we can do here is 2. I'm going to put a 2 here, and I'm going to multiply. 2 times 5,280. Let's do that down here. So 5,280 times 2. 2 times 0 is 0. 2 times 8 is 16. 6 down, carry the 1. 2 times 2 is 4, plus 1 is 5. 2 times 5 is 10. So 10,560. So 10,560. So again, let's subtract. 0 minus 0 is 0. And we need to borrow again over here. So I'm going to borrow from this 2. This will become 1. This will become 10. 10 minus 6 is 4. And then we need to borrow again. This will become 2. This will become 11. 11 minus 5 is 6. And then 2 minus 0 is 2. 1 minus 1 is 0. So I have 2,640. Let's put another 0 so we can continue the division and bring that down. And so we'll have 26,400 now. So if I kind of eyeball this again, I know 5,000 would go into 25,000 5 times. So I know it's at least a 5. Let's think about this 280 part. So let me go down here again. So 5,280 times 5. What would that give us? 5 times 0 is 0. 5 times 8 is 40. So 0 down, carry the 4. 5 times 2 is 10. Plus 4 is 14. 4 down, carry the 1. 5 times 5 is 25. Plus 1 is 26. So this is exactly what we're looking for. 26,400. So we know that the answer here for 5,280 goes into 26,400. That's going to be 5. So 5 times 5,280, again, is 26,400. Subtracting gets 0. So I just need this part, this 1.25. I can erase everything else. And basically at this point, I can just answer this by putting 1.25 here. And our unit conversion is done, right? It's actually that simple. Probably the harder part is just memorizing the units if you're required to do that. If your teacher gives you like a little cheat sheet, this is actually a piece of cake, right? You're just multiplying with fractions basically. So 6,600 feet is equal to 1.25 miles. And again, all you do is you multiply what you start out with by a unit fraction where the relationship you want to end up with, in this case it was miles, so we have mile up here, is in the numerator. If you can just remember that, this is no harder than just multiplying with fractions. All right, let's take a look at another one. So we have 360 seconds to minutes. So what's the relationship between seconds and minutes? Well, I know that 60 seconds equals 1 minute. So again, this is always your first step. Just show the relationship between the units. How much of one is equal to how much of another? Now I'm going to set up a unit fraction. So I'm going from seconds to minutes. All right, so I want to end up with minutes. So that means I'm going to write this where I have minutes in the numerator, or in this case, because it's singular, I'm going to have 1 minute in the numerator. So I'm going to write 360 seconds times, again, 1 minute's going to be in the numerator, over 60 seconds, that's going to be in my denominator. Let's scroll down a little bit and get some room going. Now, once you've set this up, you've basically done all the hard work, because seconds over seconds is going to cancel. I don't need to worry about the units anymore because I know this is what's going to be left over. And that's what I was trying to get, right? I wanted this in terms of minutes. So I'm just going to write minutes over here. And I'm done with that part. Now I can just think about, what is 360 times 1 over 60? Well, it's basically the same thing as 360 divided by 60. And a lot of us can do that in our head by this point, right? 36 divided by 6 is 6. And basically we have a trailing 0 on each one, right? So you can just think about this as 36 times 10 up here over 6 times 10, right? Kind of break that down in your head. This over this is 6. This over this is 1. So basically we're going to have 6 minutes. But again, if you can't do that at this point, I don't want to lose anybody, we can just do our basic division, right? 360 divided by 60. 60 doesn't go into 3. It doesn't go into 36. It goes into 360, again, 6 times. 6 times 60, you can do 6 times 6, that's 36. And then put a 0 at the end, that's 360. Subtract and get 0. So again, we're going to get 6 minutes for our answer here, right? 360 seconds is going to be equal to 6 minutes. All right, let's take a look at another one. We have 15 quarts, 2 gallons. So what's the relationship between quarts and gallons? Well, this is one that a lot of us know because we buy milk, right? 4 quarts is equal to 1 gallon. So 4 quarts is equal to 1 gallon. So now that I know the relationship between the units, I want to end up with gallons, right? So because I'm going from quarts to gallons. So when I write my unit fraction, I'm going to put gallons, or in this case, 1 single gallon, in the numerator. So I'm going to have 1 gallon in my numerator, and I'm going to have 4 quarts in the denominator. And that's the trick, right? Just remembering, hey, the units I want to end up with, that's always going to go in the numerator. If you can remember that, again, you're going to be good to go. And we're multiplying this by 15 quarts. 15 quarts, what we're starting with. And again, the units here are going to cancel. This cancels with this, and we're just going to be left with this. And again, that's what we want, right? We're going 2 gallons. So now I basically have 15 times 1/4, which is the same thing as saying, what is 15 divided by 4? So let's do that down here. What is 15 divided by 4? 4 doesn't go into 1, but it will go into 15 3 times. 3 times 4 is 12. Subtract and get 3. Let's put a decimal point here and bring it up into the answer. Put a 0 here and bring that down. 4 goes into 37 times. 7 times 4 is 28. Subtract and get 2. Put another 0 and bring that down. 4 goes into 25 times. 5 times 4 is 20. Subtract and get 0. So 3.75 is our answer. So 3.75. And of course we have gallons. And you can kind of think your way through that one. If 4 quarts gives you 1 gallon, well, yeah, if I had 12 quarts, that's 3 gallons. That's this part right here. And then I have 3 additional quarts, right? 15 minus 12 is 3. That's not quite enough to make another gallon because I need 4 quarts to make another gallon. So I just have 0.75 or 3/4 of a gallon remaining, right? So that's how I end up with this 3.75 gallons when we convert over from 15 quarts. So another thing you need to know is how to do multiple conversions in one shot. So I have here that you can also carry out multiple conversions in one shot. Let's suppose that you don't know the relationship between cups and gallons. So let's say that you're told to convert 25 cups to gallons. So what you know is that 2 cups equals 1 pint, 2 pints equals 1 quart, and 4 quarts equals 1 gallon. So using this information, we're going to go from cups to gallons. Okay, we're going to go this way. So let me just write these out real quick. 2 cups is going to be equal to 1 pint. 1 pint. And then 2 pints is going to be equal to 1 quart. 1 quart. And then lastly, 4 quarts. 4 quarts is going to be equal to 1 gallon. 1 gallon. So if I'm starting out with cups, which is right here, and I want to go to gallons, which is right here, I would first just think about converting cups to pints. So let's start out here. We have 25 cups, and I'm going to multiply this by 1 pint over 2 cups. 2 cups. Now, why did I do that? Well, again, I want to convert to pints to start. If I want to convert to pints, it's 2 cups equals 1 pint, so 1 pint is in the numerator, right? Because I want to go 2 pints, and 2 cups is going to be in the denominator. Now, this right here now would be in terms of pints.
after I do this multiplication, be in terms of pints. So I'm going to multiply again. Now I'm going to go to quarts. So I have the relationship between pints and quarts. I want to go to quarts, so 1 quart's going to be in the numerator. It's going to be in the numerator. And 2 pints is going to be in the denominator. Again, just put the units you want to end up with in the numerator. So this is going to put it in terms of quarts now. Now the last step is to put it in terms of gallons. So I have 4 quarts equals 1 gallon. So I'm going to multiply one more time. Again, gallons will be in the numerator, so 1 gallon will be up top. And 4 quarts will be on the bottom in our denominator. Okay, so this will put it in terms of gallons. And that's all it is. You're just doing multiple conversions at once. And if you're not comfortable with this, just do it individually first. Just do a part where you go, okay, 25 cups, I'm going to convert that to pints, stop. Then convert it into quarts, stop. Then convert it into gallons. But once you get good, you want to just do it all in one shot like this. Okay, so let's go through, and you can cancel out all the units. You're going to see that cups will cancel with cups, pint will cancel with pints, quart will cancel with quarts. All you're going to be left with is gallon right there. And let me kind of make that a little better. I cover up that 1. So you're just going to be left with this in terms of gallons. So now all we need to really think about is what numbers are involved. Because I know my units, I'm going to end up with gallons. And so I would just think about 25 times 1/2 times 1/2 again times 1/4. What's that equal to? Well, I know that I could just write this over 1. Just think about multiplying the numerators. 25 times 1 times 1 times 1 is just 25. And for the denominators, 1 times 2 times 2 times 4 is the same thing as 4 times 4. That's 16. So we have 25 over 16. That's just a simple long division. So 25 divided by 16. 16 will go into 25 only once. 1 times 16 is 16. Subtract here, we would get 9. Right? If I borrow from the 2, I put a 1 there and a 15 here. 15 minus 6 again is 9. Put my decimal point here and bring it up into the answer. Let's put a 0 here and bring it down. How many times will 16 go into 90? Well, 5 times 16 is 80. That's as close as we can get. So let's put a 5 here. Again, 5 times 16 is 80. If we subtract, we get 10. Put another 0 and bring that down. 16 goes into 100. I know 16 times 5 is 80. So 16 times 6 would be 16 more, or 96. Again, that's as good as we could do. So we'll put a 6 here. 6 times 16 again is 96. Subtract, we would get 4. Right? If I go through and do the official procedure, borrow here, this will be 10, and then it'll be 9, and this will be 10. 10 minus 6 is 4. 9 minus 9 is 0, and bring down that 0, I would just have 4. So I'm going to put another 0 here and bring that down to give me 40. So how many times will 16 go into 40? Well, only twice. Only twice. 2 times 16 is 32. Subtract and we're going to get 8. Right? Borrow from the 4, this will be 3. This will be 10. 10 minus 2 is 8. Put a 0 here and bring that guy down. Now I have 80. And we know that 16 goes into 80 exactly 5 times. 5 times 16 is 80. Is 80. Subtract and get 0. So we have our answer of 1.5625. So 1.5, let me scroll over a little bit so I can get some room going. 625, and then gallons. And it really is just that simple. We started out with, let me see if I can fit all this on the screen. We started out with 25 cups way over here. And then we went through and we converted basically one at a time, but in one shot, right? We converted to pints. Then we took pints and we converted to quarts. Then we took quarts and we converted to gallons. And then we ended up with our answer, which was, again, 1.5625 gallons. All right, let's take a look at one final problem. And we want to convert 4.5 days to minutes. So let's start out by looking at the relationship between minutes and hours. How many minutes are in an hour? Well, we know that 60 minutes equals 1 hour. And then how many hours are in a day? Well, 24 hours are in one day. So then now 24 hours equals 1 day. So we're going to go from minutes to days. So not really that complicated here.
If we start out with 4.5 days, we're going to multiply by a unit fraction where hours is going to be in the numerator, because our first step is to convert from days to hours, right? We're trying to get to minutes. So I'm going to put 24 hours in my numerator, and I'm going to put 1 day in the denominator. Again, always what you want to end up with in the numerator. So this will put this in terms of hours. Now I'm going to multiply one more time to get it in terms of minutes. Right now I need to go from hours to minutes. So I want to end up with minutes, so minutes will go in the numerator. So 60 minutes in the numerator. And this will be over 1 hour. That will be in the denominator. And now this will be in terms of minutes, which is what we want. Right? We want to end up with minutes. Let's scroll down here. And you can see everything's going to cancel except for minutes. This will cancel with this. This will cancel with this. And this is what I'm left with for my units. And basically I just have 4.5 times 24 times 60. Right? It's just a multiplication problem at this point. So let's go down to a scratch sheet. What is 24 times 4.5? So 24 times 45. Forget about the decimal point for now. 5 times 4 is 20. Put a 0 down, carry the 2. 5 times 2 is 10, plus 2 is 12. So erase this. 4 times 4 is 16. 6 down, carry the 1. 4 times 2 is 8, plus 1 is 9. We'll add here, bring down the 0. 2 plus 6 is 8. 1 plus 9 is 10. So that's 1,080. Let me go back up here real quick. 1,080. So I'll put 1,080. And I have one decimal place between these two factors that I did. So that means I'm going to move the decimal point one place to the left. So basically that's going to give me the number 108. Now I still need to multiply by 60. But to save myself a little bit of time, remember I have a trailing 0 here. So I can just basically do 108 times 6 and then attach a trailing 0 to the end of that. So 108 times 6. 6 times 8 is 48. 8 down, carry the 4. 6 times 0 is 0. Plus 4 is 4. 6 times 1 is 6. So that's 648. And then we're going to put a trailing 0 at the end. 648. Put a 0 at the end. It's 6,480. So let me erase this. And we'll put that this is equal to 6,480. And then the units again will be minutes. Hello and welcome to Pre-Algebra Lesson 48. In this video, we're going to learn about converting between metric units. So again, the lesson objective for today would be to learn how to convert between metric units. And for most of you watching this video, you're going to live in the United States like I do. We don't really deal with the metric system that often, but it is important for us to get a general understanding of the metric system and how to convert between the units because at minimum, it's going to come up on one of your tests in the future. All right, so let's start out by looking at the commonly used metric units. So we have three that we're going to cover today. We have the gram, that's for weight. We have the liter, that's for volume. And we have the meter, that's for length. Now, one of these I know that all of you have seen. The liter is used when you buy a 2 liter of Coke or Sprite or Pepsi or whatever soda you'd like to consume. Now, one thing that's different about the metric system, when we have values that are larger or smaller than the basic unit, we use a prefix. So when we talk about prefix, that's a word that's going to come before the basic unit, right? So we put a word before we say gram. And here are our prefixes. So the first few we're going to look at represent larger values than the basic unit. So we have kilo, which stands for 1,000. We have hecto, that stands for 100. We have deca, that stands for 10. Now, when we start talking about values that are smaller than the basic unit, we have deci, that stands for 0.1 or 1/10. 1/10. We have centi, which stands for 0.01 or 1/100th. And we have milli, which stands for 0.001 or 1,000th. Now, let's see an example real quick of how we could kind of use this prefix. If we know that kilo stands for 1,000, if I had 1,000 meters, instead of writing 1,000 meters, I could just say I have a kilometer. So we could say that 1,000 meters is equal to or is the same as 1 kilometer. And that's all you're doing. You're just taking this prefix and putting it before the basic unit meter. If you had 100 meters, you could say that you had a hectometer. So you had 1 hecto. I'm just putting that word hecto before I put meter. And let's skip a few. We'll come down here to, let's say, milli. So if I had 1,000th of a liter, let's say, I could say I have a milliliter. So 1,000th of a liter, or in decimal form, you could put 0.001 of a liter, is going to be equal to 1 milliliter. So I'm going to write M-I-L-L-I and then follow that with liter. So the prefix is not too difficult to understand. You just take that part and put it before your basic unit. All right, so let's look at a basic conversion. So we want to convert 5 kilograms to grams. Now I'm going to kind of show you the slow way to do this, and then I'm going to kind of show you the trick, which makes metric conversion an absolute joke. Right? Once you see this trick, you're going to be like, wow, this is easy. So to go from 5 kilograms to grams, let's use our knowledge of what we did in the previous section when we converted between US units of measurement. Let's identify the relationship between kilograms and grams. I know that kilo stands for 1,000. So what this is saying is that I have a relationship that is 1 kilogram is equal to 1,000 grams. So if that's the relationship, and I'm trying to go from 5 kilograms to grams, remember we write a unit fraction with the units that we want to end up with in the numerator. So I want to end up with grams, so I'd put 1,000 grams in the numerator, 1,000 grams, and I'd put 1 kilogram in the denominator. And I just multiply by what I'm trying to convert. So I have 5 kilograms here, 5 kilograms. And the units I no longer want are going to cancel, kilograms and kilogram. And basically all I need to do is multiply 5 times 1,000, and then my units will be grams. So 5 times 1,000 is, of course, 5,000. 5,000, and then grams. So that's pretty easy to do. Again, when I show you the simplified method, it's going to be even easier. But one thing you can kind of look at and rationalize here, if each kilogram is 1,000 grams, and I have 5 of those, well, yeah, then of course I have 5 times 1,000, right? 5,000 grams. So an easier method is to look at a prefix chart. So a prefix chart is a chart that has everything in order based on the number 10. And let me explain that. So we started out at the unit. If I start out at the unit and I just put the number 1, as I go to the right, I'm looking at smaller values, and so I'm dividing by 10. So to go from the unit to deci, I take 1 and I divide by 10, and I end up at 1/10. Or you could write 0.1. Then to go to the right one more time, to go from deci to centi, I divide by 10 again. If you think about 1/10 divided by 10, or 1/10 times 1/10, that's going to give you 1 over 100. Right? Or again, in decimal form, 0.01. And then if I go to the right one more time and end up at milli, I would divide by 10 again, or multiply by 1/10, and I'd end up with 1,000th. Or again, I could put 0.001. Now, as I go to the left, notice I'm just multiplying by 10. So this times 10 will give me this. This times 10 will give me this. This times 10 will give me this. And once I start going to the left over here and working with whole numbers, it's really simple. 1 times 10 is 10. So deca, remember that means 10. Multiply by 10 again to get to hecto. Remember, hecto means 100. Multiply by 10 one more time to get to kilo. Remember, kilo means 1,000. So now we can see that this is based on the number 10. Right? If I'm moving to the right, I'm dividing by 10. If I'm moving to the left, I am multiplying by 10. And that should be familiar to you from working with place value, right? If I come out and put, okay, the 1s, the 10s, the 100s, as you go to the left, you're multiplying by 10. As you go to the right, you're dividing by 10. Same thing here. Now, when we encounter a problem, like let's say what we just worked with here, convert 5 kilograms to grams, you're going to look at your prefix chart, and you're going to identify the starting prefix. So in this case, if we're going from 5 kilograms to grams, I'm starting out right here at kilo. And I want to end up at grams, which is the unit, right? The basic unit. So what I want to do is match the movement and the direction on the prefix chart with my decimal point in what I'm trying to convert. So for example, if I'm going from kilo to the basic unit, right, for grams, I'm going to go 1, 2, 3 places to the right. So with 5 kilograms, I'm going to put 5, I'm going to put my decimal point, and then I'm going to go 1, I'm going to put a 0 in, 2, I'm going to put another 0 in, 3 places to the right, and put a final 0 in there. And I can put a decimal point at the end, or I can leave it off. The number is 5,000. And then I would just write my new units that I'm going to, right, which would be grams in this case. So no complicated unit fraction involved, no multiplication involved. I'm simply looking at a prefix chart and matching the movement and the direction with my decimal point for what I'm trying to convert. It's that simple when you work with the metric system. The only thing you might struggle with is memorizing this part right here. And a lot of students will remember king for kilo, Henry for hecto, died for deca, unexpectedly for unit, drinking for deci, chocolate for centi, and milk for milli. So King Henry died unexpectedly, drinking chocolate milk. So hopefully you can remember that. If not, again, if you just kind of write out the prefix chart a few times while you're doing some examples, you will memorize it. Okay, for the next one, we want to convert 4 millimeters to decameters. Now, all I need to do is write this number 4 down, write the number 4 down, and I'm going from millimeters, so this is where milli is, that's your prefix, to decameters. So deca is right here. Now I'm going to match the movement and the direction on the prefix chart with my decimal point. So I'm starting here at milli, and I'm going 1, 2, 3, 4 places to the left. So I just need to match that over here. Let me just kind of back this up. So let me put 3 zeros to the left of this 4. So 1, 2, 3 zeros. My decimal point for the number 4 starts here. And then again, I'm just going to move it 4 places to the left. So 1, 2, 3, 4 places to the left, so it would go right there. And then once you're done with that, just write in your new unit. So we're converting to decameters, so that's what I'm going to write. Decameters. So 4 millimeters is going to be equal to 0.0004 decameters. Okay, let's take a look at another one. We have 3.8 kilometers, and we want to convert that to millimeters. So look at your prefixes. Again, you're starting out with kilo, and you're going to milli. So here's kilo, here's milli. So you're going all the way across the map. So let's write that number 3.8. And we're going to move our decimal point 1, 2, 3, 4, 5, 6 places to the right. So that means I'm going to need to place 5 zeros behind the 8. 1, 2, 3, 4, 5. So this is going to go 1, 2, 3, 4, 5, 6 places to the right. And let's just erase all that. Put some commas in. And we'll get 3,800,000. And then we convert it to millimeters. So we'll put millimeters behind that. All right, let's take a look at another one. We want to convert 3 milligrams to hectograms. So again, look at your prefixes. You have milli here, you have hecto here. So here's milli, here's hecto. So let me go ahead and write this number here. We have 3. And we're going to be going to the left. Let me kind of write that a little further over here so that I have some room. And we're just going to match the movement and the direction on our prefix chart. That's all we need to do. So we're going to go 1, 2, 3, 4, 5 places to the left. So I would need to go and add in 4 zeros here to the left of the 3. 1, 2, 3, 4.
So I can move this 1, 2, 3, 4, 5 places to the left. And I'll end up with 0.00003 and then hectograms. So hectograms. All right, for the final problem we're going to look at, we have 5.42 centiliters to decaliters. So you look at your prefixes, you have centi and you have deca. So here's centi and here's deca. So let's write down our number. It's 5.42. And I'm starting at centi and I'm going to deca. So I'm going 1, 2, 3 places to the left. Let me kind of move this over to the right a little bit. And I'm going to put in 2 zeros to the left of the 5. And so this is going to go 1, 2, 3 places to the left. And I'm going to end up with 0.00542 and then decaliters. Decaliters.